Welcome to this masterclass from the System Engineering series on Distributed Architecture Foundations. Instead of looking at these ideas as isolated short lessons, this video brings them together into one structured learning journey. We'll move from first principles like scalability, reliability, and consistency into service architecture, resilience patterns, coordination mechanisms, performance optimization, and the operational trade-offs that define real distributed systems. The goal here is not just recall, but architecture judgment, how to connect these ideas, how to reason through trade-offs, and how to build stronger mental models for interviews and real engineering work. Because this masterclass pulls together nearly 40 lessons, the agenda is organized as learning tracks rather than as a long list of episode names. We begin with the core foundations: scalability, availability, consistency, fault tolerance, replication, timing assumptions, and service-level thinking. From there, we move into service architecture with monoliths, microservices, decomposition, API composition, backend for frontend, sidecars, and service mesh. The next layer is resilience and traffic protection: circuit breakers, bulkheads, retries, idempotency, sagas, load shedding, and graceful degradation. Then we cover distributed coordination through leader election and locking. After that, we move into elasticity and performance engineering with auto-scaling, bottleneck analysis, throughput, edge distribution, compression, and large result handling. We close the data processing choices and the hard distributed realities of partitions, split brain, and clock synchronization. This way, the full journey stays understandable without turning the agenda into a wall of text. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 1 of the System Engineering series, and today we will explore scalability, vertical versus horizontal, in a way that helps you prepare for system engineering interviews on this topic. Knowing how to grow a system without hitting a hard ceiling is a massive part of a designer's job. Interviewers want to see that you can navigate those tricky trade-offs between cost and complexity. So, we'll give you the logic you need to justify those high-level architectural decisions, well, when the pressure's on. We'll start by breaking down what scalability actually means in a production environment, specifically looking at the fundamental choice between scaling up and scaling out. First, we are going to examine vertical scaling, where we'll look at the hardware limits and the dangerous single point of failure that often makes this a non-starter for massive systems. From there, we'll dive into horizontal scaling. You will see how adding commodity nodes changes the game, but it also introduces the need for smart state management. So we'll compare stateless designs against session-heavy architectures. Now, this transition isn't free, so we'll spend some time on the complexity tax, covering load balancing strategies and the trade-offs in data consistency. We'll wrap things up by tackling the biggest hurdle of all, the database. We look at how read replicas and sharding can solve bottlenecks when your storage layer starts to crawl. By the time we are finished, you'll have a clear framework for justifying these architectural decisions and identifying the exact moment a system needs to evolve. So, when we talk about scaling, we are really looking at two fundamentally different philosophies for keeping a system alive as its user base explodes. You've got vertical scaling, where you're essentially beefing up a single machine, and horizontal scaling, where you're just adding more machines to the party. What matters here is that in an interview, you'll often be asked to justify why you chose one over the other for a specific use case. Vertical scaling is basically the easy path. You don't have to change your code much, but you're going to hit a wall pretty fast. On the flip side, horizontal scaling is what lets companies like Netflix or Google handle millions of concurrent users, but it introduces a ton of architectural complexity. If you don't understand how these two interact, you'll likely over-engineer a small internal tool, or even worse, build a massive consumer app that can't grow past its first 1,000 users. We're going to dive into the mechanics of both so you can actually defend these design choices when a lead engineer starts drilling you on cost versus reliability. Let's get a precise definition down. Scalability is the ability of your system to handle increased load by adding resources without having to completely redesign the core architecture. It sounds simple, but it's actually a huge test of how well you've built your software. In an interview, the interviewer is looking to see if you understand that scalability isn't just about getting bigger, it's about the efficiency of that growth. If adding double the servers only gives you a 20% boost in performance, your system isn't scaling well. That's a failure of architectural efficiency. Why does this matter? Well, if you build a brittle system that requires a total rewrite every time you hit a new traffic milestone, you're going to burn through your budget and lose your users. A truly scalable system can absorb a 10 times spike in traffic gracefully. The failure mode here is usually hidden until it's too late. You might think you are scalable until a database lock or a synchronous bottleneck suddenly brings everything to a grinding halt under pressure. You've got to design for that growth upfront. Now, let's break down the two main players, scale up and scale out. Scaling up, or vertical scaling, is when you take your existing server and give it more juice. Think more RAM, faster CPUs, or better storage. It's the go-to for many startups because it's easy to manage. It's still just one box. But scaling out, or horizontal scaling, is about adding more independent machines to your cluster. This is where the magic happens for massive systems. In an interview, you'll want to highlight that scaling up is great for simplicity, but scaling out is necessary for high availability. The trade-off is often between administrative ease and system resilience. If you only scale up, you're eventually going to hit the biggest box limit, and your costs will grow exponentially. If you scale out, you have to deal with the overhead of networking and data consistency between all those nodes. Knowing when to switch from one to the other is a key signal of senior engineering experience. You don't want to overcomplicate things too early, but you also can't afford to be stuck on a single machine when the traffic surge hits. When we talk about the mechanics of vertical scaling, we're really talking about hardware upgrades. You're increasing the horsepower of a single unit by swapping out components or moving to a more powerful instance in the cloud. We are talking about adding more CPU cores to handle parallel tasks, cranking up the RAM so your database can keep more data in memory, or switching to NVMe SSDs to kill those I/O bottlenecks. It works because it's transparent to your application. Your code doesn't care if it's running on a 4-core machine or a 64-core machine. It just sees more resources. What matters here is that it's the fastest way to solve a performance crisis in the short term. However, the failure mode here is that you're just delaying the inevitable. Eventually, your application logic might not even be able to utilize all those cores effectively due to software limitations like global interpreter locks or single-threaded bottlenecks. It's also incredibly expensive because the price of top-tier hardware isn't linear. It's exponential. You end up paying a massive premium for the last 10% of performance, which just isn't sustainable for most growing businesses. So here's the reality check. Vertical scaling has a hard ceiling. You can only buy so much RAM or so many CPU cores before you simply run out of options on the market. Even the most powerful instances on AWS or Azure have a limit. This is the hardware wall, and hitting it is a nightmare. Why does this matter for your design? Because if you've built an architecture that can only run on a single machine, once you hit that ceiling, you're stuck. You can't just buy a bigger server anymore. You have to re-architect your entire codebase while your system is likely already struggling. That's a recipe for a massive outage. The failure mode here is a lack of foresight. Interviewers love to ask, what happens when we outgrow our largest available instance? If your answer is, we rewrite everything, you've already lost. You need to be thinking about how to distribute that load long before you reach the top of the hardware curve. It's about recognizing that vertical scaling is a temporary bridge, not a permanent destination for any system that expects serious growth. One of the biggest risks with a vertical model is the single point of failure, or SPOF. If you have one super server doing everything and that server goes down because of a hardware glitch, a power failure, or even just a bad OS update, your entire application goes offline. It doesn't matter how powerful the machine is if it's not reachable. This is why resilience is so hard to achieve with vertical scaling. In an interview, you should talk about blast radius, the idea that a single failure shouldn't take down the whole system. With vertical scaling, the blast radius is 100%. Everything stops. What matters here is that high availability is usually a non-negotiable requirement for modern services. The failure mode here is obvious, total downtime. Even with high-end hardware, things break. If you haven't distributed your workload across multiple nodes, you're essentially gambling that your one big box stays healthy forever. Shifting to a horizontal model reduces that risk because even if one or two nodes fail, the rest of the cluster can keep the lights on and the users happy. When you move toward horizontal scaling, the biggest architectural hurdle you'll face is the choice between stateless and stateful designs. In a stateless system, any server in your cluster can handle any request because no data about the user is stored locally on that specific machine. This is the holy grail for scaling because you can just spin up 10 more servers and the load balancer can start sending them traffic immediately. Stateful systems are the opposite. They remember things like login sessions or temporary data on the local disk. If a user starts a session on server A, they have have to stay on server A. What matters here is that it makes scaling incredibly difficult. If server A gets overloaded, you can't just move that user to server B without losing their progress. The failure mode here is session stickiness, causing unbalanced loads where one server is dying while others are idle. In an interview, you want to show how to move state out of the application layer and into a centralized store like Redis. That's how you turn a clunky stateful app into a sleek, horizontally scalable machine. Let's look at the trade-offs through a decision matrix. Vertical scaling is simple and has low administrative overhead, but it's expensive and has a hard limit. Horizontal scaling is practically infinite and very resilient, but it's complex and requires much more sophisticated networking and monitoring. Why does this matter? Well, as a system designer, you have to balance cost against reliability. If you're building an internal tool for 20 people, horizontal scaling is probably massive overkill. But if you're building a public API, going vertical is a death wish. The failure mode for choosing horizontal too early is premature optimization. You spend all your time managing Kubernetes instead of building features. The failure mode for staying vertical too long is a scaling cliff where you can't handle the next surge of users. In an interview, demonstrating that you can weigh these pros and cons based on the specific constraints of the project is exactly what they're looking for. It's not about finding the best way, it's about finding the right way for the current business stage and the projected growth curve. As soon as you add that second server, you need a load balancer. Think of it as the traffic cop sitting in front of your cluster. Its job is to take incoming requests and distribute them across all your available healthy nodes. It's the gateway that makes horizontal scaling actually work. Without it, your users wouldn't know which IP address to hit. What matters here is that the load balancer is also your first line of defense. It can perform health checks to make sure it's not sending traffic to a server that just crashed. If a node fails, the load balancer simply routes around it. However, the failure mode here is that the load balancer itself can become a single point of failure or a bottleneck if it's not configured for high availability. In an interview, you should mention things like round-robin or least connections algorithms to show you understand how traffic is actually split. If you don't have a strategy for balancing the load, you'll end up with hot nodes that take all the hits while other servers sit around doing nothing, which totally defeats the purpose of scaling out. Now, if you're dealing with a legacy app that's stateful, you might have to use sticky sessions as a temporary fix. This is where the load balancer remembers which server a user was assigned to and keeps sending them there for the duration of their session. It's basically a band-aid. It allows you to scale horizontally without rewriting your whole session management logic. But why does this matter? Well, it's a quick fix that comes with a lot of baggage. The failure mode here is that it leads to very uneven traffic distribution. If you have a few power users who are making heavy requests and they all happen to be stuck to the same server, that node is going to crash while the rest of your cluster is perfectly fine. Plus, if that specific server goes down, those users lose all their session data anyway. In an interview, you should acknowledge sticky sessions as a migration strategy, but always point towards a truly stateless design as the final goal. It's about showing you recognize technical debt when you see it and that you have a plan to move past it. To truly unlock horizontal scaling, you've got to move to a stateless design. This means offloading all that session data or temporary state to an external centralized cache like Redis or Memcached. This way, the application servers themselves become completely interchangeable. It doesn't matter if a user hits server 1 for their first request and server 50 for their second. The data is fetched from the shared cache either way. What matters here is that it makes your system incredibly elastic. You can add or remove servers at will based on demand without ever worrying about kicking users off or losing data. The failure mode here shifts from the web server to the cache itself. If your Redis cluster goes down, your whole application might lose the ability to track who is logged in. So, in an interview, you'd want to talk about making that state layer highly available too. By separating the brains of the app from its memory, you create a much more robust architecture that can grow and shrink without any drama, which is exactly what modern cloud-native systems are all about. Scaling the database is where things get really tricky. One of the first moves you'll make is implementing read replicas. In this setup, you have one primary or master database that handles all the writes, like creating a new user or posting a comment. And then you have multiple replica or secondary databases that handle all the read traffic. What matters here is that most applications are read-heavy. People browse much more than they post. By offloading those reads, you free up the primary node to focus on data integrity and updates. However, the failure mode you have to watch out for is replication lag. If a user writes data to the primary and then immediately tries to read it from a replica that hasn't synced yet, they'll see old data. This eventual consistency can be a real headache for developers. In an interview, if you mention read replicas, you've got to be ready to discuss how you'll handle that lag and which parts of your app actually need strong consistency versus those that can wait a few hundred milliseconds for the update to arrive. When read replicas aren't enough because your write volume is too high or your dataset is just too massive for one machine, you have to look at sharding. This is horizontal scaling for your data. You're basically breaking a huge database into smaller manageable chunks called shards and spreading them across different physical servers. You might shard by user ID, geography, or some other partition key. What matters here is that it's the only way to scale a database to petabyte levels. But man, the failure modes here are intense. If you pick the wrong shard key, you'll end up with hot shards where one server is doing all the work while the others are idle. Plus, you lose the ability to do easy joins across all your data. In an interview, sharding is a high-level topic. You need to explain how you'll route queries to the right shard and what you'll do if a shard gets too big and needs to be split again. It adds a massive amount of complexity to your application logic, so it's usually the last resort after you've exhausted every other scaling option available. Let's look at a real-world example, a web server cluster during a viral event. Imagine you're running a new site and a huge story breaks. Your CPU usage spikes across your 3 existing servers. If you've set up an auto-scaling group, the system detects this spike and automatically spins up, say, 50 new nodes to handle the surge. This is horizontal scaling in action. It works because the load balancer sees the new healthy nodes and starts spreading the traffic. What matters here is that it saves you from a total crash and also saves you money. When the traffic dies down, those 50 nodes are terminated, so you're not paying for idle hardware. The failure mode to watch out for here is cold starts or slow scaling. If your servers take 5 minutes to boot up and install dependencies, the traffic might have already overwhelmed your system before the help arrives. In an interview, you should mention the importance of pre-baked machine images or containers to make sure your scaling is fast enough to actually be useful when that sudden spike hits. It's about being responsive, not just being big. Ultimately, you'll often find that scaling web servers is the easy part. They're stateless, they're cheap, and they're fast to spin up. The real bottleneck is almost always the database. Databases are stateful, they're heavy, and they're hard to move around. As you add more web servers, you're also adding more database connections. Eventually, your database will run out of available connections and start rejecting requests, even if the CPU is fine. What matters here is that a single slow query can back up the entire system. To fix this, we use things like connection pooling to reuse database connections or caching layers to keep traffic away from the DB entirely. In an interview, being able to identify the database as the most likely bottleneck shows you've actually worked on real systems. You should talk about how you'd use tools like PG Bouncer for Postgres or how you'd implement a tiered caching strategy. Scaling is a game of finding the narrowest part of the funnel and widening it until the next bottleneck appears. It's an ongoing process, not a one-time fix, and the database is usually where that battle is won or lost. Alright, we've covered the core pillars of scaling. Now the big takeaway is that scaling involves choosing exactly where you're willing to take on complexity. We walk through vertical scaling, pumping up a single machine specs, which is straightforward but eventually hits a hard hardware ceiling and creates a risky single point of failure. Well, then we looked at horizontal scaling, which is the standard for high availability because it spreads the load across many nodes. In an interview, this is where you've got to shine. Don't just blindly pick horizontal, explain the reasoning. You're weighing the simplicity of one big box against the resilience and management overhead of a distributed cluster. It's that ability to justify the trade-offs between hardware limits and architectural complexity that shows you really understand system design. You're now ready to articulate why a system should grow one way or the other depending on the specific bottleneck. So that wraps up our look at scaling strategies. When you're in a system design interview, remember, it's rarely just about picking horizontal scaling and calling it a day. You've got to justify the trade-offs, right? Explain how sharding adds complexity or why stateless designs are your best friend for auto-scaling. Show the interviewer you see the bottlenecks before they even happen. If you found this helpful, subscribe for more. In the next episode, we will discuss latency versus throughput, where we'll discuss core understanding, latency, throughput. Happy designing, and I'll see you there.
Welcome to Systemic Stack. My name is Kabir Anand. This is episode 2 of the System Engineering series, and today we will explore latency versus throughput in a way that helps you prepare for system engineering interviews on this topic. It's essential because these pillars often pull in opposite directions, and you'll need to defend which one you're prioritizing during a design loop. We'll look at how to articulate these trade-offs clearly so you can show an interviewer you know how to balance snappy user experiences with massive system seal. It's all about proving that technical maturity.
We'll begin by defining the two pillars of performance, separating the speed of a single request from the total volume a system can handle. It's a fundamental distinction that often trips people up, so we'll use a toll booth analogy to make it stick. Then we are moving into measurement, looking past simple averages to focus on P95 and P99 tail latency. Understanding those outliers is a major signal interviewers look for when testing your ability to build reliable high-scale systems. Next, we'll investigate what happens when things go south, specifically how CPU constraints and I/O bottlenecks force throughput to plateau while latency spikes. We'll then look at the architectural tools we have to fight back, like caching, batching, and async processing. While each of these involves a trade-off, and knowing which one to pick is key. We'll wrap up by applying these principles to real-world scenarios, contrasting low-latency microservices with high-throughput data pipelines. By the end, you'll have a clear framework for identifying bottlenecks and choosing the right optimization strategy for any architecture.
Mastering the fundamental pillars of system performance is all about understanding the balance between response speed and overall system capacity. In any architecture, these two forces are often in tension. Latency focuses on the time it takes for a single operation to complete, while throughput measures how much total work the system can handle in a given window. This distinction matters because a system can be incredibly fast for one user but completely fail when 1,000 users arrive at once. Conversely, a system might handle millions of tasks but take 5 seconds to finish each one, making it useless for an interactive web app. Failure to distinguish between these two often leads to expensive architectural mistakes where teams scale up hardware to fix speed issues only to find the bottleneck was actually a serialized process. By treating these as separate but related goals, you can design systems that meet both the immediate needs of the user and the long-term demands of the business. We are moving from just making things work to making them work efficiently under real-world conditions. Let us get really precise with these definitions because being vague here is a recipe for bad architecture. Latency is essentially the duration of a single round trip for one specific request. It is the time that elapses between a client sending a signal and receiving the expected response. On the other side, throughput represents the volume of successful operations performed over a specific time window, like a second or a minute. This is how the system handles work in aggregate. These definitions matter because they represent different dimensions of success. If your latency is high, users feel a lag. If your throughput is low, the system cannot scale to meet demand. A common failure mode is assuming that lowering latency will automatically increase throughput. In reality, you could optimize a single function to be lightning fast, but if it requires a global lock on the database, your throughput will remain abysmal because only one request can happen at a time. Understanding these definitions helps us identify whether we have a speed problem or a capacity problem. When we talk about latency, we are really talking about the individual user experience. We measure this in milliseconds or seconds, and it is the primary factor in how snappy an application feels. Low latency is absolutely critical for interactive applications where a human is waiting for feedback, like typing in a search bar or loading a profile. What matters here is that human perception is finely tuned. Delays as small as 100 milliseconds can start to feel sluggish. The failure mode here is a poor user experience that leads to frustration and high bounce rates. If the system takes too long to respond, users do not care how many other people are using the site successfully. They only care that their own request is lagging. From a technical standpoint, latency is affected by things like geographical distance, network hops, and efficient code execution. If you ignore latency, you risk building a technically capable system that no one wants to use because it feels broken. Keeping latency low ensures that the technology fades into the background of the user experience.
Throughput shifts our focus from the individual to the entire system capacity. Usually measured in requests per second or queries per second, it tells us how much total work our infrastructure can process simultaneously. This is the metric that matters most for scalability and capacity planning. If you expect a million users to log in during a sale, throughput is what stands between a successful day and a total system outage. The common failure mode for throughput is the bottleneck, where one component, like a database or a network switch, reaches its limit and causes every subsequent request to queue up. When this happens, even if your code is fast, the system as a whole stops performing because it simply cannot ingest more data. Understanding throughput allows you to determine where to add replicas or where to split services into smaller pieces. It is about building a pipe wide enough to handle the flow rather than just making the water travel faster. Without a clear handle on throughput, your system will eventually hit a hard ceiling that prevents any further growth.
To make these concepts concrete, let us use the toll booth metaphor. Imagine a highway with a toll plaza. Latency is the amount of time it takes for one single car to stop, pay the toll, and pull away. If that takes 5 seconds, your latency is 5 seconds. Throughput, however, is the total number of cars that pass through the entire plaza in an hour. This distinction is crucial because you can improve throughput by adding more toll booths, even if each car still takes 5 seconds to pay. In this scenario, the latency for an individual driver has not changed, but the system capacity has increased significantly. Conversely, you could make the payment process faster, lowering latency. But if you only have one booth, you will still have a massive traffic jam when the volume increases. A failure occurs when you try to solve a traffic jam by just speeding up the payment process, when what you really needed was more lanes. This metaphor helps us remember that system performance requires balancing the speed of the individual transaction with the collective capacity of the infrastructure.
When we measure performance, we cannot just look at averages because they hide the truth. Instead, we use percentiles like P50, P95, and P99. P50 is the median, representing the typical experience where half of the users see a faster response and half see a slower one. P95 shows the performance for the bottom 5%, giving you a glimpse into where things are starting to degrade. P99 is the critical long tail, representing the slowest 1% of all requests. What matters here is that in a distributed system, a single user session might trigger dozens of internal requests. If any one of those hits the P99 latency, the entire user experience is ruined. A common failure mode is ignoring the P99 because it seems like an outlier. However, if you have millions of requests, that 1% represents thousands of unhappy users. By tracking these percentiles, you gain a clear picture of how your system behaves under stress and where the most significant delays are occurring, allowing you to target optimizations where they will actually improve the overall reliability.
The impact of latency on user experience follows a few well-established psychological rules. The 100 millisecond rule states that any response within this window feels instantaneous to the user, creating a sense of direct manipulation. Once you hit the 1 second mark, users notice the delay. Their flow is interrupted, but they generally stay focused on the task. However, the 10-second rule is where the real danger lies. At this point, users lose focus, feel the system has failed, and are likely to abandon the task or refresh the page, which often just adds more load to your system. What matters here is that these thresholds should dictate your performance targets. If you're building a search as you type feature, you must stay under 100 milliseconds. If you're generating a complex report, you might have more leeway, but you need to provide feedback. A failure to respect these limits results in a product that feels broken or untrustworthy. Understanding the human element of latency allows you to prioritize optimizations that have the biggest impact on how people actually use your software. To optimize for speed, one of our most powerful tools is caching. Caching works by storing the results of expensive or frequent operations in a high-speed storage layer, like RAM, so that subsequent requests do not have to repeat the work. This dramatically reduces latency by bypassing slower components like databases or external APIs. It matters because moving data closer to the user, whether in a local memory cache or a content delivery network at the edge, removes the biggest bottlenecks in the request path. However, there is a significant failure mode, cache invalidation. If the data in the cache becomes stale and does not reflect the current state of the system, users may see incorrect information, leading to data integrity issues. Furthermore, if your cache goes down and all traffic suddenly hits your database at once, it can cause a thundering herd effect that crashes your infrastructure. Used correctly, caching is the key to achieving sub-millisecond response times, but it requires careful management of data freshness and fallback strategies to ensure the system remains both fast
fast and accurate.
While caching targets speed, batching is our primary strategy for increasing throughput. Batching works by grouping multiple individual requests together and processing them as a single unit. For example, instead of writing 10 separate rows to a database one by one, you send them all in a single transaction. What matters here is that it significantly reduces the overhead associated with each operation, such as network handshakes or disk seek times, allowing the system to handle a much higher total volume. The trade-off here is that you often sacrifice individual latency. A request might have to wait a few milliseconds while the system gathers enough other requests to form a batch. The failure mode occurs when the batch size is too large or the wait time is too long, causing latency to spike to unacceptable levels for the end user. If you find your system is overwhelmed by a high frequency of small tasks, batching is often the answer, provided you balance the efficiency gains with the need for timely responses. It is a deliberate choice to favor system-wide capacity over individual speed.
Asynchronous processing is a technique used to decouple the initial request from the final response. Instead of making a user wait while a complex task like processing an image or sending an email completes, the system acknowledges the request immediately and handles the work in the background. This improves the perceived latency because the user gets a response right away, even if the actual work takes longer. What matters here is that it prevents slow tasks from tying up your web servers, which in turn keeps your throughput high for other incoming requests. However, this approach introduces its own failure modes. Without proper visibility and monitoring, background tasks can fail silently, or the message queue can grow so large that the eventual part of eventual consistency takes hours instead of seconds. You also have to handle the complexity of notifying the user when the work is finally done. When implemented well, async processing allows you to manage massive spikes in traffic without slowing down the core user experience, providing a resilient bridge between high-demand interactions and heavy-duty processing.
In the real world, the priorities for performance shift depending on the context. Take API microservices as an example. Here, the priority is always low latency because these services directly power user interactions. The goal is to make every click feel instantaneous. To achieve this, we use tools like in-memory caches, CDN edge locations to bring data closer to the user, and lightweight communication protocols. What matters here is that in a microservice environment, latencies are additive. If 5 services each take 50 milliseconds, the user is already waiting a quarter of a second. The failure mode in this space is microservice sprawl, where too many network hops between services create a death by 1,000 cuts for performance. If you do not keep a tight rein on service-to-service latency, the aggregate response time will quickly exceed the limits of a good user experience. By focusing on fast, predictable response times for each service, you build a foundation for a responsive and scalable application that users will find a joy to navigate. Now let us look at the opposite end of the spectrum, data pipelines. In this world, the primary goal is high throughput. You might be processing millions of events per hour, such as logs, sensor data, or financial transactions. Individual latency, meaning how long a single log entry takes to reach the database, is often secondary to the total volume the system can ingest. To handle this, we use tools like message queues, parallel processing clusters, and bulk database inserts. What matters here is that if your pipeline cannot keep up with the data being generated, you will start losing information or creating massive backlogs that are impossible to clear. The failure mode here is a bottleneck in the ingestion layer that causes data loss or system-wide delays in reporting. If your database can only handle 1,000 writes a second, but your sensors are sending 10,000, your system is fundamentally broken regardless of how fast each write is. By prioritizing throughput and using techniques like partitioning and batching, you ensure that your data infrastructure can scale alongside your business growth.
Now that we have explored these concepts, it is time to put these performance principles into action. You should now have a solid understanding of the fundamental trade-offs between speed and capacity. The next step is to start measuring your own systems properly. Do not just look at the averages. Start identifying your P99s and look for the outliers that are hiding in your logs. What matters here is that you cannot improve what you do not measure accurately. Look for your system's primary bottlenecks. Is it the CPU, the disk, or the network? Use the tools and techniques we discussed, like caching for speed or batching for volume, to address the specific needs of your application. The failure mode to avoid is premature optimization, where you try to fix everything at once without knowing where the real problems lie. By applying a structured approach to performance, you can build systems that are not only fast and scalable, but also predictable and resilient. Start small, measure the impact of your changes, and continue to refine your architecture based on real data. So, we've just nailed down the two fundamental pillars of system performance. You now see that latency is about the individual user's clock, while throughput is about the system's total capacity. In an interview, don't just talk about averages, show you understand the impact of P99 tail latency and how those outliers can stall an entire distributed system. We looked at how bottlenecks like CPU saturation can make latency spike exponentially, while throughput hits a hard ceiling. It's really all about that balancing act, right? Whether you're batching requests to maximize throughput or using caching to slash response times, you're making intentional trade-offs. Mastering this mental model means you're no longer just guessing at performance, you're strategically designing for it. You've now got the tools to identify exactly where a system is actually hurting, and more importantly, how to justify the architectural choices to fix it.
So that wraps up our deep dive into the pillars of performance. Now, when you're in an interview, remember that a strong answer isn't just about definitions. It's about how you balance the trade-offs between them. You'll want to demonstrate that you can identify where a P99 tail latency might be hiding a bottleneck, or exactly when batching is the right call to maximize throughput, even if it costs some speed. Being able to justify these design choices shows you're thinking about real-world failure modes and system reliability. If you found this helpful, hit subscribe for more system design breakdowns. Good luck with your preparation.
Welcome to Systemic Stack. This is episode 3 of the System Engineering series. And today, we will explore availability versus reliability in a way that helps you prepare for system engineering interviews on this topic. Well, it's easy to treat these as identical, but interviewers really look for that specific distinction between staying reachable and staying stable over time. We look at how metrics like MTBF and MTTR drive your design choices, so you can walk into your next interview ready to justify your architectural trade-offs with total precision. We'll begin by untangling the fundamental difference between availability and reliability. It's a classic interview pitfall to treat these as identical, so we're going to break down why uptime percentages don't tell the whole story. From there, we'll dive into the math, looking at metrics like MTBF and MTTR. You will see how these numbers actually dictate your system's nines and, well, how a fast recovery can sometimes mask a shaky architecture. Then we'll shift gears into the design side. We're going to examine redundancy and failover mechanisms, but we'll also tackle the messier side of things, like partial failures and those dreaded cascading outages where one small blip brings down the whole house. Finally, we'll weigh the actual costs of chasing perfection and compare how a high-stakes banking system approaches these trade-offs differently than a global social platform. By the end, you'll have a clear framework for deciding when to prioritize raw uptime and when to focus on bulletproof consistency. Now, let's get the definition straight, because your interviewer will definitely be listening for this nuance. Availability is the probability that your system is functional at any random point in time. It's often expressed as those famous nines. Reliability, on the other hand, is the probability that the system will work without failing for a specific period under certain conditions. So think of it this way. A system could be highly available because it recovers in milliseconds, but it could be incredibly unreliable if it crashes every hour. This distinction matters because it dictates your recovery strategy. If you focus solely on availability, you might ignore the root causes of crashes and just build faster reboot scripts. The failure mode here is flapping, where a service oscillates between up and down. To a user, that's just as bad as being totally dead. In an interview, you want to show you're thinking about the quality of the uptime, not just a raw percentage. You need to account for both the frequency of failures and the speed of the fix. Let's talk about availability, which is basically the metric of uptime. We usually measure this in nines. For example, 99.9% or 3 nines means your system can be down for about 9 hours a year. If you push that to 5 nines, you're looking at only 5 minutes of downtime per year. This works by measuring the total time a system is responding to requests versus the total time it should be working. It's a high-level view that matters because it's usually what you're legally committed to in a service-level agreement. However, a major failure mode here is measuring shallow availability. If your load balancer returns a 200 OK, but the database behind it is dead, your monitoring might say you're up while your users are seeing nothing but errors. In an interview, you should mention that availability isn't just about the network being reachable. It's about the system actually providing value. If you don't define uptime correctly, your metrics become a vanity project that masks a broken user experience. You need to look at success rates, not just heartbeats. Reliability is all about consistency. While availability asks, are you up right now? Reliability asks, can I trust you to finish this job? It works by looking at the probability of a system performing its function over a specific interval. If you're running a long-running data processing job that takes 12 hours, you need the system to be reliable for that entire window. Why? What matters here is that a system can have great availability but terrible reliability. Imagine a server that crashes every 5 minutes but reboots in 1 second. Technically, it's up 99% of the time, but it can't finish any task that takes longer than 5 minutes. That's a massive failure mode for mission-critical software. In your interview, highlight that for certain workloads, a system that stays up for a solid week is much better than one that's technically available but constantly stuttering. It's about matching your reliability targets to the actual needs of the work being done. You're building for consistency and long-term stability, ensuring the process completes without interruption. Mean time between failures, or MTBF, is our primary metric for how reliable a system really is. It works by taking the total operating time and dividing it by the number of failures. If your server runs for 1000 hours and fails twice, your MTBF is 500 hours. What matters here is that it gives you a predictable window of success, which helps with capacity planning and preventive maintenance. If you know a component usually fails after a year, you can replace it at month 11. A common failure mode, though, is misapplying MTBF to things that aren't repairable, like a light bulb or a specific type of hard drive, where mean time to failure is more accurate. Also, MTBF assumes a constant failure rate, but real systems often follow a bathtub curve, where they fail early or very late. In an interview, using MTBF correctly shows you're thinking about the long-term life cycle of your infrastructure, not just the next 5 minutes. It's about building a sustainable, predictable environment for your software to live in by prioritizing component longevity. While MTBF is about how often things break, mean time to repair, or MTTR, is about how fast you can get them back up. It covers the whole cycle: detection, diagnosis, and the actual fix. What matters here is that lowering MTTR is often the most cost-effective way to hit your availability targets. You might not be able to prevent every hardware glitch, but if you can automate the recovery to happen in seconds, your availability stays incredibly high. The big failure mode here is speed over quality. If your automated fix just clears a cache without investigating why it filled up, the system will just crash again in 10 minutes. You're essentially lowering MTTR while also trashing your MTBF. In an interview, emphasize that a mature MTTR strategy includes robust monitoring and automated rollbacks, but also leaves a trail for post-mortem analysis. You want to show that you're patching holes and, more specifically, actually learning from every incident to make the system more resilient. It's about making the restoration process as invisible to the user as possible. One of the most direct ways to boost availability is through redundancy, which means having backup components ready to take over. You likely heard of active-active or active-passive setups. In an active-active configuration, all your nodes are handling traffic, so if one dies, the others just pick up the slack. In active-passive, you have a standby waiting in the wings. What matters here is that it removes single points of failure from your architecture. If your only database goes down, your availability drops to zero immediately. But redundancy isn't a silver bullet. A common failure mode is correlated failure. This happens when a bad configuration change or a specific bug hits all your redundant nodes at the exact same time. Now, instead of one node failing, your entire fleet is toast. When you're explaining this in an interview, show that you're thinking about diversity in your redundancy, like spreading nodes across different power grades or cloud regions. It's about ensuring that whatever kills the primary node doesn't also have the reach to take out the backup. Failover is the automated process that kicks in when a failure is detected, switching your traffic from a broken component to a healthy one. It works through health checks, basically heartbeats that say, "I'm still alive." If the heartbeat stops, the load balancer or orchestrator reroutes traffic immediately. What matters here is that it slashes your MTTR. If a human has to wake up at 3 a.m. to flip a switch, your availability is going to tank. Automation keeps the system running while you're still sleeping. But there's a dangerous failure mode called split brain. This happens when two parts of a cluster both think they are the primary because the network between them died, not the nodes themselves. They start writing conflicting data and you've got a massive mess to clean up. In an interview, don't just say you'll use failover. Talk about how you'll handle consensus and avoid split brain using tools like Zookeeper or etcd. It shows you understand the complex risks of the automation you're proposing. Reliability engineering is the proactive side of the house. Instead of just trying to recover faster, we work on making sure the system doesn't break in the first place. This works through deep root cause analysis, rigorous unit and integration testing, and component hardening. You're basically building a system that can withstand the expected chaos of the real world. Why? What matters here is simple. A highly reliable system is much cheaper to operate in the long run because you aren't constantly fighting fires or paying engineers for on-call emergencies. However, a major failure mode here is diminishing returns. You can spend months hardening a piece of code against a hardware failure that only happens once every decade. In a system design interview, you want to show that you're prioritizing your hardening efforts on the most likely or most damaging failure points. It's about being smart with your engineering hours. You're looking for high-impact improvements that prevent the most common crashes rather than chasing every possible edge case that might never actually happen. In the real world, failures aren't always all or nothing. We distinguish between total failures, where the whole site is down, and partial failures, where maybe only the search feature is broken. This works by decoupling your services so they don't have a hard dependency on each other. What matters here for your design is that it allows for graceful degradation. Users can still browse and add items to a cart even if the recommendation engine is offline. The failure mode to watch out for here is a cascading failure. That's when one small service fails and the resulting error messages or retries overwhelm another service, eventually bringing down the entire system. In an interview, this is where you talk about circuit breakers and rate limiting. You want to demonstrate that you've designed a system that's available enough by keeping the core features running while isolating the buggy parts. It's a sophisticated way to maintain high perceived availability even when individual components slip. It shows you're thinking about the user's journey. When you're designing for high availability, you'll eventually hit a wall where the cost of adding another 9 becomes astronomical. This is a favorite topic for interviewers because it tests your business sense. Moving from 3 nines to 4 nines means your allowed downtime drops from nearly 9 hours a year to less than an hour. To achieve that, you're usually moving from basic redundancy to global multi-legion deployments with automated failover and sophisticated health checks. What matters here is that you have to justify that 10x increase in infrastructure cost. If you're building a cat photo sharing app, the cost of that extra 9 might be way higher than the revenue loss during a brief outage. A common failure mode for junior architects is over-engineering for 99.999% uptime when the business only needs 99.9%. You've got to be able to explain the ROI. In the interview, point out that every additional 9 requires more complex coordination, which can introduce new failure points like configuration drifts or synchronization issues between regions. Let's look at a domain where reliability is the absolute king: banking and financial services. In these systems, data integrity is everything. You cannot have a transaction partially complete or a database record get corrupted during a crash. How this works in practice is through heavy emphasis on asset compliance and rigorous testing of every state transaction. It matters more that the system is correct than it is up during a massive hardware failure. If there's a risk of data corruption, it's often better for the system to stop entirely, essentially sacrificing availability to preserve the reliability of the data itself. A failure mode here would be a ghost transaction, where a user's balance is updated but the logs didn't clear, leading to financial loss. When you're discussing this in an interview, emphasize that you're prioritizing consistency and correctness over immediate response times. You're signaling that you understand the stakes of the specific industry you're designing for. It's about choosing the right tool for the job rather than just chasing the highest uptime number. Social media platforms often take the opposite approach of banks, prioritizing availability over perfect reliability or consistency. If you post a comment and it doesn't show up for your friends for a few seconds, it's not a disaster. This works through eventual consistency models, where the system stays available for writes even if the data hasn't propagated everywhere yet. What matters here is that users would much rather have a site that's mostly working than an error screen. If a social app went down every time a database node lagged, nobody would use it. The failure mode here is user confusion. If someone sees their post disappear and then reappear, it feels buggy and untrustworthy. When you're explaining this in an interview, talk about the trade-offs in the CAP theorem. You're consciously choosing availability and partition tolerance over immediate consistency because the cost of an outage is higher than the cost of a minor data lag. It's a pragmatic design choice that keeps the user engaged even when the underlying infrastructure is having a bad day. Finally, let's look at how these requirements change across different industries. A cloud provider might promise 99.99% for its core storage service because thousands of other businesses rely on it. In healthcare or emergency services, the reliability requirements are even more intense because a system failure could have life or death consequences. This table shows that there's no single correct number for availability or reliability. It's always a business decision driven by the cost of failure. Why? What matters here for you as an architect is that it helps you set realistic goals. A failure mode here is trying to apply a one-size-fits-all approach. If you build a simple internal tool with the same redundancy as a global payment processor, you're wasting massive amounts of time and money. In an interview, use these industry standards to anchor your answers. If you're asked how much uptime a system needs, start by asking what the business impact of an hour of downtime looks like. It shows you're an engineer, and more specifically, a strategic thinker who understands that every architectural choice has a price tag attached. So, we've broken down the fundamental tug-of-war between availability and reliability. In a system design interview, you've got to be razor sharp here. Availability is your uptime percentage, while reliability is the consistency of that operation over time. We saw how the math ties them together through MTBF and MTTR. You know, a common trap is thinking they're the same, but a system that crashes every 10 minutes can still be highly available if you're fast enough at rebooting it. That's why understanding the MTBF divided by MTBF plus MTTR equation is so vital for your toolkit. It lets you explain exactly why you're choosing redundancy to mask failures or hardening components to prevent them entirely. Being able to articulate that trade-off shows you're looking past the dashboard and actually managing the life cycle of the system, right? So that brings us to the end of our look at availability versus reliability. In a high-stakes interview, the real signal is how you justify your design choices. Try to explain how you'd handle a partial failure or why you'd prioritize availability over consistency for a social feed. Showing that you understand the infrastructure costs and the risk of over-engineering proves you can think like a senior architect. Subscribe to the channel for more topics. In the next episode, we will discuss CAP theorem, practical application, where we'll discuss core understanding, consistency, availability. Good luck with your prep. Welcome to Systemic Stack. This is episode 4 of the System Engineering series, and today we will explore CAP theorem practical application in a way that helps you to prepare for system engineering interviews on this topic. See, when a network split hits, you've got to make a choice, right? Your ability to justify that trade-off is exactly what an interviewer wants to hear. We'll go beyond basic definitions so you can confidently defend architectural decisions for real-world systems like Cassandra or MongoDB. We'll begin by breaking down the 3 pillars of the CAP theorem to see how they actually function in a distributed environment. You're going to see why consistency and availability often pull in opposite directions when a network partition happens, which is, the inevitable reality we face in production. We'll spend some time debunking the common pick 2 myth, because in actual system design, you don't just pick 2 and walk away. You make a deliberate choice about how your system behaves when things break. This is a critical area for interviews, so we look at how to justify choosing a CP or AP architecture based on real business needs, like comparing a high-stakes banking ledger to a high-volume social media feed. Finally, we'll see how databases like Cassandra and MongoDB handle these trade-offs through quorum tuning. And we'll even look beyond CAP to the PACELC Theorem to understand performance during normal operations. By the end, you'll have the framework to justify architectural decisions that balance data integrity with system uptime. The CAP triangle is basically the fundamental law of the distributed world, and it's the first thing an interviewer will look for when you're discussing scaling. It works by mapping out 3 competing goals: consistency, availability, and partition tolerance. Now here's the thing. While we want all 3, the theorem proves that in the presence of a network partition, you have to trade one off. What matters here is that your choice defines how the system handles pressure. If you try to force all 3, you'll end up with a system that deadlocks or produces conflicting data when the network gets flaky. The failure mode here is a total lack of predictability. Without a clear strategy on this triangle, you can't guarantee what a user will see after they hit save. In an interview, you need to show you understand that this isn't about picking your favorite 2 features. It's about deciding which failure you're willing to tolerate to keep the business running. Consistency in the CAP sense is all about ensuring that every node in your cluster sees the same data at the same time. When you perform a write, the system works by broadcasting that update and waiting for confirmation before it tells the user the job is done. What matters here is that it prevents what we call dirty reads, where one user sees a bank balance of $100 while another sees zero. If consistency isn't handled correctly, the failure mode is a fractured state where different parts of your application are making decisions based on conflicting information. In an interview, when you're asked about consistency, it's a great chance to mention that this isn't just about being right. It's about the performance bottleneck that occurs because nodes have to talk to each other before finishing a task. If the network is slow, your consistency guarantees will make the entire system feel sluggish or even time out for the end user. Now, it's important to realize that consistency isn't just a binary on-off switch, it's actually a spectrum. On one end, you've got strong consistency or linearizability, where every single node is updated immediately. This is great for accuracy but can be a huge performance killer. On the other end, we have eventual consistency, which lets the system respond quickly while syncing nodes in the background. What matters here is that choosing the wrong spot on this spectrum can lead to massive latency issues. If you demand strong consistency across the globe, your system's failure mode is extreme slowness, as every request waits on a slow transoceanic cable. In an interview, you'll want to discuss this as a trade-off between user experience and data correctness. If you can tolerate a user seeing a slightly older comment for a few seconds, eventual consistency might be the way to go. But for things like inventory levels, you probably need to stay on the stronger side. Partition tolerance is often the most misunderstood part of CAP. It works by ensuring the system keeps running even if the network between nodes goes down or starts dropping messages. We call these network partitions. What matters here is that in the real world, networks aren't perfect. Cables get cut, routers fail, and packets just disappear. If your system doesn't have partition tolerance, the failure mode is a complete cluster collapse the moment a single network link gets shaky. In an interview, you should emphasize that P is essentially a cost of doing business in a distributed system. You can't just wish away network failures. If you're designing something that lives on more than one machine, you're effectively forced to deal with partitions. The real question isn't whether you want partition tolerance, but how your system behaves when the partition inevitably happens. Do you stop all traffic to stay consistent, or do you keep serving users and sort out the data mess later? So, why do we say P is non-negotiable? Well, if you're building a distributed system, you're inherently using a network, and networks are statistically guaranteed to fail at some point. This is why you can't actually choose a CA system for a distributed environment. What matters here is that if you try to ignore P, you're designing for a fantasy world. When a real-world partition hits a system that hasn't planned for it, the failure mode is often a split-brain scenario where two different parts of your system think they're the master and start writing conflicting data. Interviewers love to see if you recognize this reality. If you suggest a CA architecture for a multi-region app, it shows a lack of understanding of physical constraints. The choice isn't C, A, and P, it's how you handle C and A when P occurs. You're either deciding to favor consistency and shut down temporarily, or you're favoring availability and accepting that some data might be out of sync. One of the biggest misconceptions people have is the pick two trap. It sounds simple, but it's actually a bit misleading. In reality, when the network is behaving perfectly, you can have both consistency and availability. The trade-off only kicks in the moment the network breaks. What matters here is that it changes how you think about system health. Most of the time, your system will look like it's doing everything right, but the failure mode appears when that one critical network link drops. That's when your predefined CAP strategy takes over. If you haven't planned for this, the system might flip-flop between states or crash under the pressure of trying to resolve conflicts it wasn't built to handle. In an interview setting, make sure you clarify that CAP is a design for the worst-case scenario. It's about what happens during the partition, not what happens during normal operation. Demonstrating that you know the difference between steady state and partition state is a huge signal for seniority. When a network partition actually hits, you're forced into a fork in the road. You can either cancel the operation to maintain consistency, which we call a CP system, or you can proceed with the operation to maintain availability, which is an AP system. This works by setting a strict protocol for how nodes respond when they can't talk to their peers. What matters here is that it directly impacts your user's experience during a crisis. If you go the CP route, a user might see an error message saying service unavailable. If you go AP, they might see a version of their profile that's 5 minutes old. The failure mode of making the wrong choice here can be devastating. For example, if you choose AP for a money transfer, you could end up with double spending. If you choose CP for a social media feed, your site goes dark just because one data center is having trouble. You have to match the trade-off to the specific business risk. Let's talk about CP systems, which prioritize consistency and partition tolerance. These systems work by ensuring that if a node can't confirm a write with the rest of the cluster, it simply refuses to perform the operation. What matters here is that it guarantees that your data is always accurate and synchronized across all points. You'll see this in systems like Zookeeper or many traditional relational databases. However, the trade-off is clear. The failure mode here is downtime. If the network splits, the minority side of the cluster will stop accepting requests to prevent data divergence. In an interview, you justify a CP choice by explaining that data integrity is your absolute top priority and that providing stale data is worse than providing no data at all. Just keep in mind that the bottleneck here is the consensus mechanism. Every write needs a majority of nodes to agree. So if your network has high latency, your write performance is going to take a significant hit. On the other side of the coin, we have AP systems, which favor availability and partition tolerance. These systems work by allowing every node to keep responding to reads and writes, even if they can't talk to the rest of the cluster. What matters here for high-scale applications, where being offline is the ultimate failure. Think about a shopping cart or a social media feed. You want the user to keep interacting, even if the backend is struggling to sync up. But there's a catch. The failure mode here is inconsistency. You might end up with conflicting updates that have to be resolved later, often using complex logic like last write wins or vector clocks. When discussing this in an interview, you should mention that while the system stays online, the complexity shifts to the application layer to handle those data conflicts. The bottleneck isn't the consensus anymore. It's the eventual synchronization process that has to merge all those divergent states back into a single truth. We often hear about CA systems where you supposedly have both consistency and availability. In theory, this works perfectly as long as the network is flawless. But in any distributed environment, the network is never flawless. This is why a CA system is essentially a myth for anything spanning multiple nodes. If you claim a system is CA in an interview, you're basically assuming messages are never dropped or delayed, which is a massive red flag. Why does this matter? Because if you build a CA system and a partition actually happens, the system has no protocol to follow. It'll either stop responding entirely or it'll allow inconsistent data to propagate without any way to reconcile it. That failure mode can lead to corrupted databases that are nightmares to clean up. In the real world, you have to acknowledge that P is a fact of life, so your architecture must be either CP or AP. CA is really only a valid concept for a single node database where there's no network to split. Making the right design decision comes down to one question: what's the cost of being wrong versus the cost of being offline? This works by evaluating your specific use case against the cap trade-offs. What matters here is that there's no such thing as a best database. There's only the best database for your problem. If you're building a medical record system, a failure to show the latest medication could be life-threatening, so you'd lean towards CP. But if you're building a gaming leaderboard, being offline for an hour is a much bigger disaster than someone seeing the second place score for an extra minute. In an interview, the key is to show you can map these technical trade-offs back to business requirements. The failure mode of ignoring the business context is over-engineering a system that's either too slow or too unreliable for what the users actually need. Always start with the requirements, then use cap to justify your architectural path. Let's look at two contrasting examples. Banking versus social media. A banking system has to be CP. It works by ensuring that if a node can't verify a balance, it errors out. What matters here is that an incorrect balance isn't just a bug, it's a financial and legal disaster. The failure mode for a bank is a rejected transaction, which is annoying but much better than losing money. Now compare that to a social media feed, which is typically an AP system. It works by showing you whatever data is closest to you. Why? Because seeing a post from 10 minutes ago is a much better user experience than seeing a 503 service unavailable error. The failure mode here is just a slightly stale feed, which most users won't even notice. In a system design interview, using these kinds of clear high-stakes comparisons shows that you understand how CAP isn't just an abstract theory, but a practical tool for protecting the core value of an application. A classic real-world example of an AP-leaning system is Apache Cassandra. It's designed to be highly available and partition-tolerant from the ground up. It works by using a peer-to-peer architecture where any node can handle any request. What matters here is that it allows for massive horizontal scaling without a single point of failure. If a few nodes go down or the network splits, Cassandra just keeps on chugging. However, the trade-off is that it relies on eventual consistency. The failure mode is that two users might see different versions of the same row for a brief period. To mitigate this, Cassandra offers tunable consistency, which lets you decide on a per-query basis how many nodes need to agree. In an interview, mentioning Cassandra is a great way to show you know how modern databases implement CAP. It proves you understand that you can actually move the needle between A and C depending on what a specific part of your app needs at that moment. As you get more advanced, you will find that CAP doesn't tell the whole story. That's where the PACELC Theorem comes in. It works by extending CAP to describe how a system behaves during normal operation, not just during a partition. The acronym stands for, if there is a partition P, choose between availability A and consistency C. Else E, choose between latency L and consistency C. What matters here is that it forces you to think about performance when everything is running fine. If you want strong consistency even when there's no partition, your system is going to be slower because of the extra communication overhead. The failure mode of a PACELC unaware design is a system that's unexpectedly slow during peak times because you over-optimized for a consistency level you didn't really need. In an interview, bringing up PACELC shows a deep, nuanced understanding of distributed systems. It shows you're thinking about the 99% of the time when the network is healthy as well as the 1% when it's not. So let's pull this all together. We've seen that the CAP theorem isn't just an abstract triangle. It's a framework for making hard choices when the network inevitably fails. Since partition tolerance is non-negotiable in distributed systems, the real decision happens during a split. Do you prioritize consistency or availability? In an interview, a strong answer shows you understand that CP systems like MongoDB favor data integrity over uptime, while AP systems like Cassandra keep the lights on even if the data is slightly stale. It's about matching the system's behavior to the specific business requirements. Well, now you can move past the pick 2 myth and explain exactly how a system handles a crisis. You've got the mental model to justify whether a read should return the absolute latest data or just a fast response. And that's exactly the kind of trade-off reasoning that shows you're ready for high-level architecture discussions. That wraps up a look at CAP in the real world. Now, when you're in an interview, remember it is not only about memorizing the acronym. You've got to justify your choices, like why you'd pick MongoDB's consistency over availability during a partition split. Showing you can tune quorums or explain PACELC really signals that you understand the nuances of high-scale systems. If you found this helpful, hit subscribe. In the next episode, we will discuss consistency models, strong, eventual, causal, where we will discuss core understanding, strong consistency, eventual consistency. Catch you then and good luck. Welcome to Systemic Stack. This is episode 5 of the System Engineering series, and today we will explore consistency models, strong, eventual, causal, in a way that helps you prepare for system engineering interviews on this topic. Knowing exactly when to prioritize data truth over speed is a core skill for any senior engineer, right? We'll focus on the specific reasoning you need to justify these architectural trade-offs, so you can confidently explain why one model beats another when an interviewer asks you to scale a complex distributed system. We begin with a look at what consistency actually means in a distributed environment and how it forces those tough decisions within the CAP theorem. It's really about how data propagates across nodes, right? From there, we'll dive into strong consistency and linearizability. You'll see how protocols like Raft ensure absolute correctness, making a cluster behave like a single machine, which is a major signal interviewers look for when you're discussing high-stakes systems. Now, we'll shift gears to explore eventual consistency. We'll see why you trade immediate truth for massive scale and how background synchronization handles the heavy lifting. Then, we'll cover causal consistency, that vital middle ground where order-aware updates keep user interactions logical without a massive performance hit. We are also going into the weeds of implementation, specifically how quorum models and replication lag affect what the user actually sees. This is where you learn to justify architecture choices based on real-world constraints. Finally, we'll look at DNS and social feeds to see these models in action. By the end, you'll understand the precise trade-offs between truth and speed. When we talk about balancing truth and speed, we are really looking at the spectrum of data synchronization. On one end, you have absolute correctness where every node agrees on everything at all times. On the other, you have maximum performance where nodes just do their own thing and catch up later. In practice, this works by choosing how many nodes must confirm a write before the system tells the user, okay, we got it. If you wait for everyone to agree, your system is slow but perfectly consistent. If you don't wait, it's blazing fast, but some users might see stale data. What matters here is that no single model fits every use case. If you're designing a high-frequency trading platform, you can't afford a millisecond of disagreement. But if you're building a like button for a cat video, speed is king. A major failure mode here is choosing a model that's too strict for your scale, leading to a system that technically works but is so slow that users abandon it. Let's get our definition straight. Consistency is the guarantee that all nodes in a distributed system see the same data at the same time. It's the C in the CAP theorem, and it dictates how updates move through your network. Think of it as a unified state. If I update my profile picture, does every server in the cluster know about it immediately? What matters here is that without a clear consistency model, your system becomes unpredictable. The biggest failure mode here is a split brain scenario, where two parts of your system think different things are true, and they both start making decisions based on those lies. In an interview, when someone asks you to define consistency, they're checking if you understand that it's a safety property. It's a promise the system makes to the developer about what data will be visible when. If you can't articulate that promise, you can't build a reliable distributed service. We are talking about the fundamental glue that keeps a distributed system from falling into chaos. Now, we can't talk about consistency without hitting the CAP theorem. It's the ultimate reality check for distributed systems. You have consistency, availability, and partition tolerance. But the catch is that when the network breaks, and it will, you have to choose between consistency and availability. You can't have both. This isn't just some academic theory. It's a hard engineering constraint. If a network cable gets cut, do you stop taking requests to keep the data perfect, or do you keep serving users even if the data might be slightly out of date? In an interview, this is where you show your seniority. A strong answer isn't "we choose consistency." It's "we choose consistency because our financial ledger cannot tolerate a single cent of error, even if it means the app goes down for 5 minutes." The failure mode here is trying to ignore the trade-off. Systems that claim to be CAP complete usually have hidden failure points where they lose data or lock up entirely during a partition. Strong consistency is the gold standard for correctness. It ensures that once a write is acknowledged, every single subsequent read from any node will return that exact value. Effectively, it makes a complex distributed system behave like it's running on just one single machine. How does it do this? Usually through synchronous replication. Before the system tells you the write succeeded, it waits for all the nodes to confirm they've updated their local state. This is why it's so important for things like banking or inventory management. You don't want two people buying the last item in stock at the same time. The consequence, though, is latency. Your system is only as fast as your slowest node. If one server in your cluster has a minor network hiccup, your entire write operation stalls. This is the tail latency bottleneck. In an interview, you'd want to highlight that while strong consistency is the easiest to program against, it's the hardest to scale across multiple geographic regions. Taking strong consistency a step further, we have linearizability. This is the idea that operations appear instantaneous to any observer, even across a distributed cluster. It's a very strict ordering of events. To pull this off, you need heavy-duty coordination protocols like PACELC or Raft. These protocols involve a leader node that manages the order of operations and ensures a majority of nodes agree before anything is finalized. It's technically impressive, but it's also a massive performance tax. The bottleneck here is the coordination itself. You're constantly sending messages back and forth to reach a consensus. If the leader node fails, the system pauses while a new one is elected, which creates a temporary availability gap. In an interview, you should mention that linearizability is often overkill for most web apps, but essential for things like distributed logs or metadata stores. A common mistake is assuming strong consistency automatically means linearizable without understanding the underlying coordination costs that actually make it happen. On the opposite side of the spectrum, we find eventual consistency. This model prioritizes being always on and incredibly fast. It basically says, look, I'll take your write right now and tell you it's done. And eventually, I'll make sure all the other nodes catch up. The synchronization happens in the background, often using gossip protocols, where nodes chat with each other to exchange updates. What matters here is that it allows for massive scale and low latency. It's the reason why apps like Instagram or X don't crawl to a halt when millions of people post at once. However, the trade-off is the possibility of stale reads. You might post a status, refresh, and not see it for a second because your read hit a node that hasn't gotten the update yet. In an interview, you'd explain that eventual consistency is the go-to for high availability systems, but it requires developers to handle potential data conflicts manually, since the system doesn't guarantee a single truth immediately. So why exactly do we choose eventual consistency? It's all about high availability and low latency. By letting writes happen on any node and propagating them later, the system becomes incredibly resilient to regional failures. If an entire data center goes offline, users can still read and write to other nodes without skipping a beat. It's optimized for a world where the network is unreliable. But there's a catch. This flexibility introduces conflict resolution. If two users update the same record at the exact same time on different nodes, which one wins? This is where last write wins or conflict-free replicated data types come in. The failure mode here is data loss or corruption if your conflict resolution logic isn't robust. In an interview setting, make sure to talk about how eventual consistency shifts the burden from the infrastructure to the application logic. You're trading away system-level simplicity for the ability to handle millions of concurrent users without breaking a sweat. Causal consistency is that clever middle ground that bridges the gap between strong and eventual models. It focuses on the happens before relationship. If operation A causes operation B, then every node in the system must see A before they see B. For example, if I post a question and you reply to it, it would be weird for someone else to see your reply before they see my question. That's a causal break. How does this work? The system tracks dependencies. It doesn't force a total global order on everything, which would be slow, but it does enforce a relative order for related events. What matters here is that it provides a much more intuitive user experience than pure eventual consistency without the heavy performance hit of a strong model. A failure mode for causal system is the overhead of tracking these dependencies. If you have too many related events, the metadata you have to pass around can get pretty bloated, eventually slowing down the very system you were trying to optimize. To actually implement causal consistency, we use things like vector clocks or version vectors. These are mechanisms that allow nodes to track the history of an object without needing a perfectly synchronized global clock, which by the way doesn't really exist in a distributed world anyway. Each node maintains its own counter and shares it during updates, allowing other nodes to determine if one piece of data is a descendant of another or if they happen concurrently. This is how the system knows which version is newer in a causal sense. The practical impact here is that you get a more logical view of the world. However, the bottleneck is often the size of these vector clocks. In a system with thousands of nodes, the clock itself can become larger than the data it's tracking. This is a classic interview topic. How do you manage dependency tracking as the number of factors grows? If you don't prune those clocks or use a more efficient structure, your system's performance will degrade as it scales. Let's wrap our heads around the whole spectrum. Strong consistency is atomic and easy to reason about, but it's slow and risky for availability. Causal consistency is orderly and offers mid-range speed, keeping related events in sync. Eventual consistency is the speed demon, but it risks showing disordered or stale data. Choosing the right one is about the user's tolerance for the truth. In a system design interview, you'll want to categorize your data. Don't just pick one model for your whole app. Use strong consistency for your user accounts and billing, causal consistency for your common threads, and eventual consistency for your like counts or analytics. The biggest architectural mistake is applying a one-size-fits-all approach. If you treat every piece of data like it's a bank balance, your app will never scale. If you treat every piece of data like a like count, you'll lose user trust when their settings don't save. It's all about matching the model to the specific business requirement. Let's talk about the human side of this, stale reads. This is the classic "I just posted that" frustration. Imagine a user updates their bio, hit save, and the page refreshes to show their old bio. What happened? Their write went to node A, but their subsequent read was routed to node B, which hadn't received the update yet. This is a massive UX failure mode. To fix this, without going full strong consistency, we often use a trick called read your writes consistency. This ensures that a specific user always sees their own updates, even if others don't see them yet. We can do this by pinning a user session to a specific node or by tracking a version token in their browser. In an interview, mentioning read your writes as a specific optimization for eventual consistency shows you understand how to hide the underlying system's messiness from the user. It's about building a system that is technically eventual but feels strong to the person actually using it. When you're making these choices, you're essentially balancing accuracy against the user experience. High-stakes applications like financial tools or medical records absolutely requires strong consistency. If you're transferring money, accuracy is the user experience. A millisecond of speed isn't worth a lost transaction. On the flip side, social media apps or collaborative tools like Google Docs often lean into eventual or causal models. Why? Because a tiny delay in seeing a friend's post is worth the trade-off for a site that never feels laggy. The catastrophe happens when you mix these up. Imagine a social media app that locks up for 3 seconds every time you like a post because it's waiting for global consensus. That app is dead on arrival. Or imagine a bank that uses eventual consistency, allowing a user to withdraw more money than they have because the nodes haven't synced. In an interview, your goal is to show that you can map these technical models to these real-world business risks and user expectations. A perfect real-world example of eventual consistency is the domain name system, or DNS. When you change where a domain points, it doesn't update everywhere instantly. It takes hours, sometimes days, to propagate across the entire planet. This is because of the time to live, or TTL setting. Every server in the chain caches the result for a while to save time. This is the ultimate trade-off. The system is incredibly fast and basically never goes down globally, but it's eventually consistent by design. If DNS required strong consistency, every single web request on Earth would have to wait for a global lock. The internet would crawl to a stop. This shows us that eventual consistency isn't a flaw, it's often a necessary feature for global scale. In an interview, using DNS as an example demonstrates that you understand how caching and propagation delay are deliberate architectural choices used to manage massive worldwide traffic without sacrificing availability or performance. Social feeds like Facebook or X are great examples of how systems use a mix of these models. They often use causal consistency to ensure that if you reply to a post, your reply stays attached to the right parent. They also use a read your rights approach so you see your own posts immediately. However, for everyone else, the feed is eventually consistent. A friend in another country might see your post 2 seconds after you hit send, or maybe even 10 seconds later if the network is congested. And you know what? That's perfectly fine. The system doesn't need to stop the world to make sure every single person sees your lunch photo at the exact same microsecond. This hybrid approach is what allows these platforms to support billions of users. In an interview, being able to deconstruct a famous app into its different consistency needs, like saying the private messages need higher consistency than the public feed, is a high signal answer that proves you're thinking like a systems architect. That brings us to the end of our module on consistency modules. We've covered a lot of ground, from the absolute strictness of linearizability to the fluid, high-speed world of eventual consistency. You should now have a solid mental framework for why we make these trade-offs and how they impact both the system's performance and the user's experience. Remember, in a distributed world, there's no such thing as a free lunch. If you want speed, you give up some immediate truth. If you want truth, you give up some speed. In the next phase of this series, we're going to take these concepts and see how they collide with database partitioning. We'll look at how your choice of consistency module actually changes the way you store and shard your data across a cluster. It's one thing to understand the theory, but seeing it in the context of physical data storage is where the real engineering happens. I'll see you in the next module, where we'll dive into partitioning strategies. So, we've really broken down the spectrum of consistency models today, from the strict immediate truth of linearizability to the highly available eventual approach. You've seen how strong consistency uses protocols like Raft or PACSOS to make a distributed system feel like a single node. It's perfect for correctness, though it definitely hits your latency. On the flip side, we looked at how eventual consistency lets us scale by letting nodes sync in the background, using resolution strategies like last right wins to handle those inevitable conflicts. When you're in a design interview, the real signal you want to send is that you understand the trade-offs. It's never just about picking a model. It's about explaining why you'd sacrifice immediate accuracy for availability or vice versa based on what the user actually needs. You've got the mental framework now to defend those architectural choices with confidence. So, we've covered how to navigate the spectrum of consistency, from the immediate correctness of strong models to the high availability of eventual ones. For your next interview, remember that it's the reasoning behind the choice that counts. You'll want to articulate how replication lag or quorum sizes directly impact the user experience, like avoiding stale reads in critical paths. If you want to dive deeper, hit subscribe. In the next episode, we will discuss PACELC Theorem, where we'll discuss core understanding, partition scenario P, L scenario E. Keep practicing those system design trade-offs and stay sharp. Welcome to Systemic Stack. This is episode 6 of the System Engineering series, and today we will explore PACELC Theorem in a way that helps you prepare for system engineering interviews on this topic. Now, most folks stop at CAP, but real-world architecture is also about the 99% of the time the network is healthy. Mastering PACELC shows you've got the depth to justify latency trade-offs, signaling to an interviewer that you can design systems that stay fast and reliable under pressure. We'll start by breaking down why the standard CAP theorem often falls short when you're designing actual systems. CAP only focuses on what happens during a network failure, but we've got to account for the 99.9% of the time when things are running normally. So, we'll explore the partition scenario first, where we weigh consistency against availability, and I'll show you how to justify these choices in a system design interview. From there, we are diving into the else part of PACELC. This is where we look at the constant tug-of-war between latency and consistency while the system is healthy. It's a crucial shift in thinking because it proves trade-offs aren't just for emergencies. We'll examine how global distances and the speed of light impact your architecture, specifically focusing on replication lag. Finally, we'll put this into practice with deep dives into DynamoDB and Cassandra to see how top-tier engines handle these settings. By the end, you'll understand how to tune a distributed system to meet specific business needs without sacrificing performance. PACELC is really the evolution of how we think about distributed systems. It's not just an academic theory, it's a map of the trade-off spectrum that every global system designer has to navigate. If you're designing something like a global social media feed or a high-frequency trading platform, you can't just say where's CP or where AP. You need to understand what happens to your user's experience during the 99.9% of the time that the network is healthy. That's the part that CAP ignores. If you don't account for these variables, you'll end up with a system that's technically available but so slow that users abandon it, or a system that's fast but shows completely wrong data. Mastering this theorem gives you the language to explain these subtle shifts in behavior and helps you avoid the trap of oversimplifying complex distributed problems during an interview. It's about showing that you understand the full cost of every architectural decision you make. CAP is a great starting point, but it's fundamentally limited because it only talks about what happens when the network breaks. But let's be real, if your network is broken all the time, you've got bigger problems than a theorem. Most of the time, your system is functioning normally, and that's where CAP leaves a huge hole in your design. It doesn't tell you how to balance speed against data accuracy when everything is green. In a real-world interview, an interviewer isn't just asking what happens during a partition, they want to know why your system is slow on a Tuesday afternoon. If you only use CAP, you're ignoring the latency cost of keeping data synchronized. That's a massive failure mode in design because you might build a consistent system that's so slow it's practically useless, even though it never actually fails a CAP check. We need a way to talk about the system when it's healthy. Let's look at the core logic here. The formula breaks down into: if there is a partition, how do we trade consistency versus availability? Else, how do we trade latency versus consistency? It's a two-part decision. The first part is exactly what you know from CAP. If the nodes can't talk, do you shut down to keep data safe or stay up and risk being wrong? But the else part is the secret sauce. When the network is fine, you still have to decide if you want to wait for every node to agree, which adds latency, or if you want to return a result immediately. What matters here is that it forces you to acknowledge that consistency isn't free. Even in a perfect world, if you want everyone to see the exact same thing at the exact same time, your users are going to wait. That's a trade-off you have to justify when you're explaining your database choice to a lead engineer. This is where the rubber meets the road. Unlike CAP, which is basically an emergency plan, PACELC forces us to realize that trade-offs are a constant part of life. You're making these choices every single time a request hits your database. It is not only about surviving a disaster, it's about defining the user experience under normal load. If you choose to prioritize consistency at all times, your system will inherently be slower because of the handshakes required between servers. If you forget this, you might design a system that's perfectly consistent but fails to meet its service level agreements for response time. Interviewers love to see if you can articulate this tension. If you can explain that a slow system isn't necessarily broken, it might just be configured for high consistency, you're showing a much deeper understanding of how these things actually work in production environments. You're demonstrating that you're thinking about the user as much as the data. When a partition actually happens, meaning your servers can't talk to each other, you're forced into a corner. This is the P in our formula. At this point, you have two choices. You can either stop taking requests to ensure that no one gets the wrong data, which protects your consistency but kills your availability. Or you can keep the lights on and let nodes answer requests independently. The failure mode here is obvious. If you keep moving, your nodes will drift apart. One user sees an old balance while another sees the new one. If you stop, your app looks like it's down. In an interview, don't just say you'll pick one. Explain the consequence. If it's a banking app, you'd probably stop and wait because losing money is worse than an error page. If it's a likes counter on a photo, you'd keep it running. The right answer depends entirely on what the business can tolerate losing. Choosing a PC profile means that during a network split, you're going to sacrifice availability to keep the data pristine. You're telling the system, if you can't be 100% sure the data is right, don't say anything at all. This is typical for financial systems or any ledger where being wrong is worse than being offline. However, the failure mode is that your system effectively becomes a brick if a single cable gets cut in the wrong place. You might have 10 healthy servers, but if they can't reach a majority, they'll all stop working. It's a high-stakes choice. When you're explaining this, make sure to mention that PC systems usually use consensus protocols like Paxos or Raft. These tools are great for safety, but they can be a bottleneck for uptime because they're so sensitive to network health. You're trading reliability of service for reliability of data. In many enterprise settings, that's exactly the right move. On the flip side, we have PA, where availability is the priority. If the network splits, the system stays reachable. It's going to try its best to answer every request, even if it knows the data might be stale. This is what you'll see in things like shopping carts or social media feeds. The system assumes that it's better to show something rather than an error page. The catch, and this is a big one, is the split brain problem. Two different users could update the same record on two different sides of the partition. When the network heals, you have to figure out how to merge those conflicting updates. If you don't have a plan for conflict resolution, like last write wins or CRDTs, you're going to end up with corrupted data. That's the risk you're taking to keep the site online. It's a great example where the engineering challenge moves from the database to the application code. Now, we're in the else part of the theorem where everything is running fine. This is the LC trade-off. Even without a failure, if you want your system to be consistent, you're going to pay for it in latency. Every write has to be replicated to other nodes, and the system has to wait for those nodes to say got it before it tells the user the job is done. This round-trip time is a huge bottleneck. If your nodes are in different data centers, you're literally fighting the speed of light. If you ignore this, you'll find that your perfect database is actually the reason your app feels laggy. In an interview, you should point out that choosing EC, consistency over latency, means you're willing to make every single user wait longer just to ensure they always see the most recent data. It's not a bug, it's a conscious design choice that prioritizes accuracy over raw speed. Let's talk about the physical reality of global systems. If you've got a user in London and your database is synchronizing with a node in Sydney, that data has to travel across the planet. No matter how fast your code is, that physical distance creates a minimum latency. If you require full consistency across those regions, every single write is going to take hundreds of milliseconds. That might not sound like much, but it's enough to make a website feel broken. This is a classic architectural bottleneck. If you don't account for this, your global rollout will be a disaster. A smart move is to use LSIN or latency-sensitive configurations for global reads while accepting that some users might see data that's a few seconds old. It's all about managing that trade-off so the system remains usable across different geographic locations. In an interview, explaining this physical limitation shows you're thinking about real-world infrastructure, not just code on a screen. When we move beyond CAP and embrace PACELC, we are really moving into professional design thinking. You're no longer just picking from 3 letters. You're balancing 4 interconnected variables: partitioning, availability, consistency, and latency. It's a spectrum, not a toggle switch. This is exactly what an interviewer is looking for when they ask about database selection. They want to see that you understand that a database isn't just good or bad, it's a set of configurations. You might choose a database that is PAEC by default, but can be tuned to be PCEC when you're handling sensitive transactions. Being able to explain when and why you'd shift that slider is the difference between a junior dev who memorized a diagram and a senior engineer who understands how to build a resilient, high-performance system in the real world. It's about having the right tool for the right moment, rather than a one-size-fits-all approach. A great example of this in the real world is Apache Cassandra. It's famously flexible. You can actually tune it to behave differently for different types of data. Out of the box, it's often set up as a PAEL system, meaning it stays available during partitions and stays fast during normal operations by not waiting for every node. But you can change that. You can set the consistency level to quorum or all for a specific query, effectively pushing it towards the PC or EC side. This tunability is a powerful tool, but it's also a trap. If you set everything to all to be safe, your performance will tank and your system will become extremely fragile. Understanding how to walk that line in Cassandra is a classic interview topic because it shows you know how to map theoretical trade-offs to actual configuration settings. It's all about finding that sweet spot for your specific use case. Let's get into the weeds of those Cassandra settings because this is where the theory becomes real. If you set your read or write level to 1, you're going for maximum EL, lowest latency. You don't care if other nodes have the data yet. You just want an answer now. But if you move to quorum, you're demanding that a majority of nodes agree. This improves consistency but increases the chance of a failure if too many nodes are busy or down. The failure mode here is a timed out error, even when the database is technically up. If you're in an interview, you can explain that using quorum for both reads and writes gives you strong consistency, but at the cost of higher latency and lower fault tolerance. It's a classic example of how PACELC helps you predict exactly where your system will struggle under load or during a network hiccup. You're trading performance for peace of mind. We've just dismantled the idea that trade-offs only happen when things break. By extending CAP into PACELC, you now have a framework that accounts for a system's behavior 100% of the time. When a partition hits, yeah, you're still choosing between availability and consistency. But the else part of the theorem is where most of the engineering happens. You're constantly balancing latency against consistency even when the network is perfectly healthy. Well, in a design interview, this is exactly the signal that separates the juniors from the seniors. Instead of just talking about failure modes, you can articulate why a system might sacrifice immediate consistency for speed during normal operations. It's about understanding that every microsecond of performance has a cost and data accuracy. Keeping this mental model sharp ensures you're designing for the reality of distributed systems, where the trade-offs never actually stop. That's a wrap on the PACELC Theorem and how it sharpens our understanding of distributed trade-offs. In an interview, moving beyond CAP to discuss latency versus consistency during normal operations shows you're thinking about the full system lifecycle, not just disaster scenarios. You'll want to justify your choice by explaining how specific database configurations, like Cassandra's tunable consistency, directly impact user experience. If you found this helpful, subscribe to the channel. In the next episode, we will discuss fault tolerance basics, where we'll discuss core understanding, types of failures, failure detection. Thanks for watching and happy designing. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 7 of the System Engineering series, and today we will explore fault tolerance basics in a way that helps you prepare for system engineering interviews on this topic. Since failures are inevitable, interviewers want to see you build architectures that keep running even when hardware or networks fail. Well, we'll dive into failure detection and isolation methods to prevent those messy cascading outages. Mastering these patterns shows you can balance high availability against real-world costs with confidence. We'll start by pinning down what fault tolerance actually looks like in a live environment. It's fundamentally about maintaining service continuity even when specific parts of your stack go dark. From there, we're going to categorize the common ways things break, whether that's a disk crash, a flaky network, or a memory leak, so you know exactly what you're up against. Then we'll move into failure detection. This is where we talk heartbeats and health checks, and well, I'll show you how to nail that timeout logic that interviewers love to ask about. After that, it's all about the recovery side. We'll look at how to use retries and failover strategically, but we'll also focus on isolation patterns like bulkheads and circuit breakers to stop cascading failures in their tracks. We'll wrap up by weighing the costs of high availability against the reality of system complexity, using some real-world microservice examples. By the end, you will be able to justify specific resilience choices and build systems that survive the most common failure modes. At its heart, fault tolerance is really just a system's ability to keep doing its job even when some of its parts decide to stop working. It's all about continuity rather than perfection. In an interview, you'll want to emphasize that 100% uptime is a myth. What we're actually aiming for is graceful degradation. We achieve this by building in redundancy and isolation so that one failing component doesn't trigger a total system blackout. What matters here is that in a distributed world, components fail all the time, right? If your system isn't fault-tolerant, every minor disk error becomes a user-facing outage. However, there's a big trade-off here. Fault tolerance isn't free. It adds significant complexity and cost. If you over-engineer for every possible failure, you might end up with a system that's so slow or expensive that it's barely usable. The failure mode to watch out for here is the false sense of security, where you have redundant parts, but they all share a single point of failure you didn't notice. When we talk about hardware failures, we're looking at the physical stuff like disk crashes, power supply blowouts, or entire server racks going dark. Servers are essentially just boxes of metal and silicon, and eventually they're gonna break. Our primary defense here is redundancy. This means having extra hardware on standby or running multiple instances of a service across different physical machines. It's important because if you're running a single database on one server with no replica, you're basically playing a game of chicken with hardware mortality. And in interview, if you're asked about this, you should mention availability zones or regions as your safeguard. But keep in mind, a common failure mode is correlated failure. If you put all your redundant servers in the same rack and the top of rack switch fails, your redundancy doesn't mean much, does it? You have to ensure your hardware is physically separated enough that a single local disaster doesn't take out your entire backup plan along with your primary system. Now, network failures are a different beast. We often call the network the unreliable pipe because it's where we see packet loss, high latency, or total partitions where nodes are active but just can't see each other. This is a classic interview scenario where you have to discuss the CAP theorem. Network partitions matter because they force a choice between consistency and availability. If two parts of your system can't talk, do you stop taking requests or risk having mismatched data? The mechanism to handle this usually involves timeouts and retries, but the failure mode is tricky. A common mistake is assuming the network failure is always a hard failure, where the connection is just gone. Often, it's a gray failure, where the connection is just slow enough to cause a pileup of requests. This can lead to a split-brain scenario, where two different nodes both think they are the leader because they can't see each other, which can absolutely wreck your data integrity if you haven't planned for it. Software failures are often the hardest to track down because they are baked into the logic. We're talking about memory leaks, unhandled exceptions, or those lovely logic bugs that only show up under specific load conditions. Unlike hardware, adding more of the same software doesn't always help because the bug exists in every copy. What matters here is that a single buggy update can wipe out an entire cluster if you're not careful. To defend against this, we use things like process isolation and sandboxing to make sure one crash doesn't take down the host. In an interview, you might discuss how you use canary releases to limit the blast radius of a software failure. A major failure mode here is the cascading failure. This happens when one service fails and its neighbors try to pick up the slack, but they get overwhelmed and fail too, creating a domino effect that levels your whole infrastructure. It is not only about the crash itself, it's about how the rest of the system reacts to that crash. To fix a failure, you first have to know it's happening, and that's where health checks come in. This is a passive monitoring style, where an external watcher, like a load balancer, periodically asks a service, "Hey, are you okay?" The service responds with its status. What matters here is that it allows the system to automatically stop sending traffic to a node that's clearly struggling. In an interview, make sure to mention that a simple ping isn't enough. A server might respond to a ping, but have a corrupted database connection, making it effectively useless. A deep health check verifies the actual dependencies are working. The failure mode to avoid here is the shallow check problem. If your health check is too simple, it might report a service as healthy, even when it's failing to process any actual work. Conversely, if the check is too heavy or runs too often, the health check itself can become a source of load that actually pushes a struggling service over the edge into a full crash. While health checks are passive, heartbeats are active signals. This is where a component periodically broadcasts an "I am alive" message to a central controller or its peers. One simple way to picture this is a pulse. If the pulse stops, the rest of the system assumes the node has died and triggers a recovery. This is vital for cluster coordination and leader election. In an interview, you'll want to discuss the trade-off between heartbeat frequency and detection time. If you send heartbeats every millisecond, you'll detect failure instantly, but you'll burn a lot of bandwidth. If you send them every 10 seconds, your system might be down for a long time before anyone notices. A common failure mode is the false negative, usually caused by network congestion. If the network gets busy, heartbeats might get delayed. The system then thinks a perfectly healthy node is dead, starts a failover, and actually causes more instability by moving resources around unnecessarily. Balancing the timeout window is a key technical challenge you'll need to explain. It sounds like a cliche, but turning it off and on again is a legit recovery strategy. Automated restarts are incredibly effective for clearing out transient software states like memory leaks or deadlocks. If a process stops responding to health checks, the orchestrator just kills it and starts a fresh one. What matters here is that it's a fast, low-cost way to return to a known good state. In an interview, you'd mention this in the context of stateless services. Since they don't store data locally, they can be nuked and replaced without any loss. However, you have to watch out for the restart loop or crash loop back-off. This is a failure mode where the process crashes immediately upon starting because of a bad config or a poison message in a queue. If you just keep restarting it, you're just burning CPU cycles and potentially filling up logs or making the problem worse. You need a way to detect that the restart isn't helping and stop the cycle before it consumes all your resources. Retries are a go-to move for handling transient failures. If a request fails because of a quick network blip or a temporary lock on a database, just trying again a second later often solves the problem. It's essential for maintaining a high success rate in a noisy environment. But, and this is a big point for interviews, you can't just retry blindly. If you have 1,000 clients all retrying a failing service at the same time, you've effectively launched a DDoS attack on yourself. This is the thundering herd problem. Why it matters is that a small hiccup can turn into a total outage because the retry volume overwhelms the system as it tries to recover. The failure mode here is amplifying the load. To prevent this, you should never use immediate retries in a loop. You have to combine them with backoff strategies and limits on the total number of attempts. An interviewer will expect you to justify your retry policy based on whether the operation is idempotent or not. Automated failover is what happens when the system decides the primary instance is toast and shifts all the traffic to a secondary standby node. This is a cornerstone of high availability because it drastically reduces the recovery time objective or RTO. Instead of a human getting paged at 3 a.m. to fix a server, the system just points the DNS or a virtual IP to the backup. It matters because it keeps the service running even during major hardware failures. Now the bottleneck here is usually the data replication. If the secondary isn't perfectly in sync with the primary, you might lose data during the switch. In an interview, you should bring up the flapping failure mode. This is where a system keeps switching back and forth between the primary and secondary because of a shaky connection. Each switch causes a small outage or data inconsistency. To solve this, we usually implement fencing or stoneth to make sure the old primary is definitely dead before the new one takes over. The circuit breaker is a brilliant pattern for protecting a system from failing dependencies. It works like the one in your house. If too many requests fail, the circuit trips and goes into an open state, meaning it stops sending requests altogether for a while. This gives the failing service some breathing room to recover instead of being pounded while it's down. It matters because it prevents resource exhaustion, like filling up thread pools with requests that are just going to time out anyway. In an interview, be sure to explain the three states: closed, open, and half-open. The half-open state is where the system lets a few test requests through to save the service's backup. A failure mode here is incorrect threshold setting. If you set the failure rate too low, the circuit trips during normal minor fluctuations, causing unnecessary downtime. If it's too high, the circuit never trips and you get that cascading failure we talked about earlier. It's all about finding that sweet spot for stability. When you're retrying, you should almost always use exponential backoff. Instead of retrying every second, you wait 1 second, then 2, then 4, then 8. What matters here is that it gives a struggling system more and more time to recover as the failure persists. It's the direct solution to the thundering herd problem we mentioned earlier. If an interviewer asks how to make this even better, the answer is jitter. Jitter adds a bit of randomness to those wait times so that 1,000 clients don't all retry at exactly the same 4-second mark. This spreads the load out smoothly over time. The failure mode to keep in mind is the impact on user experience. While backoff protects the server, it increases the latency for the end user. If you back off too far, the user might have given up and closed the app long before the final retry even happens. You have to balance the technical need to protect the backend with the practical need to provide a responsive interface. Let's look at a real-world example to see how this all connects. Imagine an e-commerce checkout flow. One microservice is responsible for calculating shipping taxes and it suddenly starts lagging because of a slow database query. If the checkout service doesn't have a timeout or a circuit breaker, every person trying to buy something will have their request sit there waiting for the tax service. Pretty soon, all the available connections in the checkout service are tied up and the whole site goes down. This shows why isolation and fault tolerance matter so much. A single non-critical service shouldn't be able to kill the entire business process. In an interview, this is a great story to tell to illustrate the blast radius. The failure mode here was a lack of a fail-fast mechanism. A better design would be for the checkout service to use a cached tax rate or a default value when the tax service is slow, allowing the customer to finish their purchase while the engineers fix the underlying database issue. Chaos engineering is basically the ultimate test of everything we've talked about. It's the practice of intentionally breaking things in production to see if your fault tolerance actually works. You might shut down a random server or inject latency into a network link. It matters because until you actually test it, your recovery plan is just a theory. In an interview, you can talk about how this builds confidence in the system's resilience. However, you have to be smart about it. The failure mode here is obvious. You could actually cause a massive outage if your experiments aren't controlled. You need to have stop buttons ready to roll back the experiment instantly if things go sideways. It's not about causing chaos for the sake of it. It's about verifying that your automated failovers and circuit breakers trigger exactly when they're supposed to. If you can survive a chaos monkey attack during peak hours, you know your system is truly production ready and can handle almost anything the real world throws at it. Alright, so we've built a solid mental model of fault tolerance today by shifting our focus towards surviving failure rather than just hoping it doesn't happen. We looked at how hardware crashes, network partitions, and software bugs are basically inevitable, which is why we lean so heavily on health checks and heartbeats to spot trouble early. Now, the real nuance, and this is a big one for interviews, is how you tune those timeouts. You've got to balance fast detection against the risk of false positives from simple network jitters. We also walked through how automated restarts and retries can resolve transient issues without a human ever getting involved. Ultimately, it's all about that trade-off between the overhead of redundancy and the actual cost of downtime. Being able to explain the reasoning behind those choices shows you're designing for the real world, not just the happy path. So that wraps up our dive into fault tolerance. When you're in a high-stakes interview, don't just list patterns. You'll want to explain the specific failure modes you're avoiding, like how a circuit breaker stops a single slow service from tanking your whole checkout flow. Showing that you understand the cost to resilience trade-off is exactly what interviewers are looking for. It proves you can design for real-world bottlenecks. Make sure to subscribe. In the next episode, we will discuss redundancy and replication concepts, where we'll discuss core understanding, redundancy, replication. Happy studying, and I'll see you in the next one. Welcome to Systemic Stack. My name is Kabir Aland. This is episode 8 of the System Engineering series, and today we will explore redundancy and replication concepts in a way that helps you prepare for system engineering interviews on this topic. So knowing how to eliminate single points of failure is crucial because it's exactly what senior engineers look for during a design loop. We'll dive into the nuances of hardware redundancy versus data replication, helping you confidently explain trade-offs between cost and availability. It's all about showing you can build systems that stay resilient. We begin with a deep dive into identifying single points of failure, which is really the first thing an interviewer wants to see you spot in a system design. It is not only about adding hardware, so we'll distinguish between infrastructure redundancy and data replication. We look at the big architectural choices like active-active versus active-passive setups, helping you decide when to prioritize throughput or where a warm standby makes more sense. From there, it's about the data itself. We'll examine the trade-offs between synchronous and asynchronous replication, focusing on how each affects latency and consistency during a crash. To keep things running, we'll cover failover mechanics like heartbeats and health checks, so you understand how systems actually detect and survive a node death. Finally, we'll weigh the financial cost against the availability gains, moving from 3 nines to 5 nines. By the end, you'll have the framework to justify specific resilience strategies based on performance needs and recovery objectives. So, when we talk about redundancy and replication, we are basically looking for a way to build a system that doesn't care if a piece of it dies. It's all about resilience and fault tolerance. In an interview, you might be asked to design a system with 5 nines of availability. That sounds fancy, but all it really means is that your system stays up 99.999% of the time. To get there, you need a strategy for both your infrastructure and your data. Hardware redundancy is your safety net for the physical layer, while replication ensures that your data lives in more than one place. If you have a perfectly redundant server but only one copy of the database, you're still in trouble. What matters here is that users expect services to be instant and always on. A major failure mode people forget is that without these strategies, even routine maintenance becomes a nightmare because you have to shut everything down to make an update. We are building systems that can heal themselves or at least survive the carnage while we fix the problem. The ultimate goal of everything we are talking about is eliminating the single point of failure, or SPOF. Think of a SPOF as that one component which, if it stops working, takes the whole house down with it. It might be a single load balancer, a lone database instance, or even a specific network switch. In an interview, you need to show that you can trace a request from start to finish and identify where those bottlenecks are. Why does this matter? Well, if you don't find them, your high availability system is just a house of cards. A common failure mode is adding redundancy at the app layer, but forgetting that both app servers connect to the same single database. When that database crashes, it doesn't matter how many app servers you have. To fix this, you have to add fallback capacity at every single level of the stack. It's about creating paths for the data to flow even when the primary route is blocked. You want to make sure no single piece of equipment is ever holding the keys to the entire kingdom. Now let's look at redundancy. I like to think of this as the spare tire approach. It's mostly focused on the hardware or the virtual instances. If you've got a server with 2 power supplies, that's redundancy. If you have 3 different network interface cards so that a cable failure doesn't cut you off, that's redundancy. In a cloud environment, it usually means having standby instances ready to go. What matters here is that hardware is physical, and physical things break all the time. Hard drives fail, motherboards fry, and power strips trip. The failure mode here is often a lack of diversity. If you have 2 redundant power supplies, but they are both plugged into the same power strip, you still have a single point of failure. Interviewers look for this level of detail. They want to see that you understand that you need extra stuff, and more specifically, that the extra stuff needs to be independent. If your redundant components share a common dependency, they aren't actually providing the protection you think they are, and that's a dangerous mistake to make. While redundancy is about the equipment, replication is all about the data. It's the process of making sure that information is consistent across multiple nodes. If I write a user's profile to database A, replication is what gets that same data over to database B and C. What matters here is that data is the most valuable part of your system. If a server dies, you can buy a new one, but if the data is gone, it's gone forever. In a hub and spoke model, you've usually got a leader node handling the writes and pushing that info out to replicas. The failure mode to watch out for is replication lag. If your followers are a few seconds behind the leader and the leader crashes, you might lose those few seconds of data during the failover. In an interview, you'll need to explain how you handle that gap. Are you okay with losing a tiny bit of data for the sake of speed, or do you need every node to be perfectly in sync at all times? That's a key decision you'll have to defend. In an active-active setup, every node in your cluster is pulling its weight by processing requests simultaneously. From an interviewer's perspective, this is a high utilization strategy that looks great for throughput and efficiency. Since all nodes are already warm and running, if one fails, the others just keep going. It sounds ideal, right? Well, the failure mode here is a classic trap. If you're running your cluster at 80% capacity across 2 nodes and one goes down, the remaining node suddenly hits 160% load. It'll instantly crash, leading to a total system blackout. This is why you have to over-provision or implement strict rate limiting. You also have to deal with the headache of session stickiness or a shared state across those nodes. If a user session is on node A, but node A disappears, node B needs a way to know who that user is. So, while it's great for performance, it adds a massive layer of complexity to your load balancing and state management. Active-passive is a different beast altogether. Here, you've got one node doing all the heavy lifting while the other one just sits there waiting for its moment to shine. It's like a backup generator for your house. What matters here is that it's much simpler to manage than active-active. You don't have to worry about splitting traffic or managing complex sessions because only one machine is the boss at any given time. However, the failure mode is the cold start. When the primary fails, there's a delay while the passive node wakes up, checks the data, and starts taking traffic. If that switchover isn't perfectly automated, your system stays down until a human intervenes. There's also the risk that the passive node won't actually work when you need it, because it hasn't been tested under real load in months. In an interview, you'd want to mention how you'd monitor the health of that standby node to ensure it's actually ready to take over. It's cheaper and simpler, but it's definitely slower to recover than an active-active setup. Choosing between these topologies isn't just about picking the best one, it's about matching the strategy to your specific needs. This is where you show your seniority in an interview by discussing the topology selection matrix. You have to weigh the cost of having idle hardware in an active-passive setup against the architectural complexity of an active-active one. Then there's the recovery time objective or RTO. How long can your system be down? If the answer is 0 seconds, you're looking at active-active. If you can afford a minute of downtime to save a lot of money and complexity, active-passive might be the winner. Don't forget the recovery point objective or RPO, which is how much data loss you can tolerate. If your replication isn't perfect, a failover might mean losing the last few transactions. A common failure mode here is choosing a complex active-active setup for a small service that doesn't actually need it, which just leads to more bugs and maintenance overhead. Always pick the simplest solution that meets your availability targets. Synchronous replication is all about that all or nothing guarantee. When a write comes into the primary node, it doesn't tell the client success until every single replica has confirmed they've written the data to. What matters here immensely for financial systems or any use case where data loss is absolutely unacceptable. If the primary crashes, you know for a fact that your replicas are up to date. However, the bottleneck here is the network. Your write speed is now capped by the slowest replica in the chain. If one node in a distant region has a minor network hiccup, your entire application grinds to a halt. This is the classic trade-off between consistency and availability. In an interview, you'd mention that while this prevents data loss, it creates a massive performance hit and a new failure mode, where the system becomes unresponsive if a single replica is laggy. You're essentially trading off system-wide latency for total data integrity, which is a choice you have to justify based on the business requirements. On the flip side, we have asynchronous replication. This is built for speed. The primary node writes the data locally, tells the client everything is great, and then replicates that data to the followers in the background. It's incredibly fast because the client doesn't have to wait for the whole world to acknowledge the write. What matters here for high-performance apps, like social media feeds, where a tiny bit of lag is way worse than losing one like on a post. But the failure mode is pretty obvious. If the primary node crashes after telling the client success, but before it sends that data to the replicas, that data is lost forever. This is known as the replication gap. In an interview, you talk about this as a trade-off, where you prioritize availability and low latency over strict consistency. It's a very common pattern for read-heavy workloads where you want to scale horizontally, but you have to be prepared for the fact that your replicas might be slightly out of date at any given moment. Sometimes automation isn't the answer, and that's where manual failover comes in. You might think we'd want everything to be automatic, but in some high-stakes environments, you want a human to pull the lever. What matters here when your automated detection might be wrong or when a failover is so expensive or risky that you need a sanity check first. The biggest failure mode here is human error or just plain old speed. If a database goes down at 3 in the morning and you have to wait for an engineer to wake up and run a script, your uptime is going to suffer. However, manual failover avoids the dreaded split brain scenario, where two nodes both think they're the leader and start fighting over the data, which can cause massive corruption. In an interview, mention that you would use manual failover for very complex migrations or when data integrity is so critical that a false positive failover would be catastrophic. It's a safety valve, but it comes at the cost of a much slower response time. So, how does a system actually know when to fail over? That's where heartbeats and health checks come in. These are small, frequent signals sent between nodes to say, hey, I am still alive. If a node misses a few heartbeats, the monitoring system assumes it's dead and triggers the failover logic. What matters here is that it's the trigger for your entire resilience strategy. Without it, your redundant nodes are just sitting there while your users see error pages. But there's a failure mode you have to be careful about: false positives. If the network is just a bit congested, a node might miss a heartbeat even though it's actually fine. If your timeout is too aggressive, you'll end up with flapping, where the system keeps switching back and forth between nodes, which can actually cause more downtime than the original problem. In an interview, you should talk about quorum or consensus protocols, which help ensure that the system only fails over when it's absolutely sure a node is actually down, rather than just having a bad day. We have to talk about the elephant in the room, the cost of redundancy. It's definitely not free. You're paying for idle hardware, extra network bandwidth for all that replication traffic, and often extra software licenses for every node you add. What matters here is that every architectural decision has a price tag, and in the real world, you have a budget. If you tell an interviewer you'll just double everything, they'll want to know how you justify that cost. A major failure mode here is over-engineering. You might build a system that can survive a nuclear strike when you're actually just running a small blog. You have to balance the cost of downtime against the cost of the redundancy itself. If an hour of downtime costs $10,000, but the redundancy to prevent it costs $50,000 a month, the math doesn't work out. Part of being a great systems engineer is knowing where to draw that line. You want enough protection to keep the business safe without burning cash on resources you don't actually need. Even with the costs, the availability gains are usually worth it for any serious business. Moving from 3 nines, which allows for almost 9 hours of downtime a year, to 5 nines, which allows for only 5 minutes, is a massive leap. Redundancy is what makes that possible. It allows you to do rolling updates and maintenance without the users ever noticing. You can take one server offline, patch it, and bring it back while the others handle the load. What matters here is that it changes how your team works. You aren't afraid of deployments anymore. It also protects you from regional outages. If an entire data center goes dark, but you've replicated your data to another region, your business stays alive. The failure mode here is often configuration drift, where the secondary site isn't updated along with the primary. Then when you actually need to fail over, the secondary system crashes because it's running an old version of the code. You have to treat your redundancy as a living part of your stack, not just a static backup. Ultimately, resilience isn't something you just set and forget. It's a continuous process of finding and fixing the weakest link. Your system is only as strong as its most vulnerable non-redundant component. You might have redundant servers, databases, and power, but if you only have one DNS provider and they go down, you're still offline. In an interview, you'll stand out if you talk about chaos engineering, the practice of intentionally breaking things in production to see if your redundancy actually works. The ultimate failure mode is complacency. Assuming your failover works because it worked 6 months ago is a recipe for disaster. You need to test your recovery paths constantly. Whether it's through automated scripts or manual drills, you have to prove that the system can heal itself. Real resilience comes from the confidence that when a server inevitably catches fire, your users will never even see a spinning wheel. It's about building a system that can take a punch and keep moving forward. We've really broken down how to strip away those single points of failure that keep engineers up at night. By combining physical redundancy with smart data replication, you're essentially building a safety net that spans your entire infrastructure. Now, when you're in a design interview, keep in mind that it is not only about having extra servers. It's about justifying why you chose active-active for throughput or why the latency of synchronous replication is worth the data integrity. We looked at how those trade-offs between cost, latency, and recovery time dictate your whole strategy. Whether you're configuring a passive standby or managing state across multiple active nodes, the goal is the same, making sure the system doesn't blink when a component fails. You've now got a solid mental model to weigh these choices based on what a system actually needs to stay online. That wraps up our deep dive into redundancy and replication. When you're in an interview, remember that it's never just about adding more nodes. You've got to justify the cost and explain how you'll manage things like split brain or manual failover risks. I mean, showing you understand those trade-offs is exactly what interviewers are looking for, right? Practice explaining your choice between active-active and active-passive setups to show you can balance availability with complexity. In the next episode, we will discuss synchronous versus asynchronous systems, where we'll discuss core understanding, synchronous, asynchronous. Subscribe for more and find the full course details in the description. Good luck with your prep. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 9 of the System Engineering series, and today we will explore synchronous versus asynchronous systems in a way that helps you prepare for system engineering interviews on this topic. Deciding between blocking calls and eventual processing really dictates how your architecture handles scale and failures. We'll dive into these patterns so you can clearly justify why you choose one over the other when an interviewer probes your design for bottlenecks. This lesson opens with an exploration of core communication patterns, because how your components talk to each other fundamentally changes how your system scales and handles failure. We'll start by breaking down the mechanics of blocking calls and immediate responses. Then compare those against non-blocking execution and background processing. It's really about understanding the performance impact when you're choosing between waiting for a thread or running tasks in parallel. From there, we'll dive into the reliability side of things, looking at how retries prevent cascading failures in synchronous setups versus how message queues provide durability when things go wrong in async flows. You'll see these concepts in action as we look at real-world examples like REST and Kafka, which often come up in interviews when you have to justify choosing a specific architecture for a data pipeline or a user-facing API. We'll wrap up by looking at the specific trade-offs between simplicity and scale. By the end, you'll have a clear decision framework for selecting the right pattern for your next microservice. When we talk about synchronous versus asynchronous systems, we're really discussing the flow of control and data between components. In a synchronous world, the caller sends a request and just sits there, waiting for the result before it can do anything else. It's like a phone call where both parties have to be present. The consequence of this choice is that it ensures that when the call returns, you know exactly what happened. But this simplicity has a dark side. If the receiver is slow or hangs, the caller is stuck, wasting precious memory and CPU time doing absolutely nothing. In a high-stakes interview, showing you understand this link between communication and resource management is crucial. A common failure mode here is the cascading failure, where one slow service backpashes everything else until your whole stack is unresponsive. On the other hand, asynchronous systems let you fire and forget, which is great for throughput but introduces complexity in tracking the state of a request. Getting this choice right is the hallmark of a senior engineer. Communication patterns are the foundation of how your components interact, and they dictate the ceiling of your system's performance. At the core, it's about whether you're coupling the timing of the request to the timing of the response. The impact on your behavior here is that it determines how you handle load spikes and partial outages. If every part of your system is tightly coupled synchronously, a single bottleneck in a deep microservice chain will throttle your entire user experience. You'll see this manifest as high latency and timeouts that are hard to trace. Interviewers love to see if you can identify these potential choke points early on. The failure mode to worry about here is tight temporal coupling, where your system cannot function unless every single piece is up and fast at the exact same time. By shifting to asynchronous patterns where it makes sense, you decouple these components, allowing the system to be more resilient and elastic. It's about trading off immediate certainty for better overall availability and efficiency across your entire infrastructure. Let's look at blocking calls, which are the backbone of synchronous communication. How this works is simple. When a thread makes a request, it essentially goes to sleep and waits for the server to send back a response. This is significant because it keeps the programming model very straightforward. You don't need to worry about state transitions or callbacks because the next line of code only runs once the data is ready. However, the failure mode is quite dangerous. Thread exhaustion. Each of those waiting threads consumes memory, and if you have a slow-running downstream service, your entire pool of threads can fill up with workers that are just sitting idle. In an interview, you should point out that while this is easy to debug, it's a huge bottleneck for high concurrency systems. If you don't implement proper timeouts, a single slow database query can lock up your entire application server. It's a classic trade-off where you trade scalability for simplicity, and knowing when that trade is no longer worth it is key. The immediate response model is all about providing a definitive answer within a single transaction loop. How it works is that the server processes the request and sends the final result back before releasing the connection. The practical impact of this is that it provides strong consistency. The client knows immediately if the operation succeeded or failed without having to poll or wait for a notification later. It's perfect for things like authentication or checking a bank balance where you can't afford to be eventually right. But the failure mode here is a lack of flexibility. If the server is under heavy load and can't provide that immediate answer, the request simply fails or times out, leading to a poor user experience. In system design discussions, you'll want to highlight that this pattern can't easily handle long-running tasks. If you try to force a heavy data processing job into an immediate response loop, you'll likely hit gateway timeouts and leave your system's resources tied up far longer than necessary. Non-blocking execution changes the game by allowing the caller to initiate an action and then immediately move on to other work. How it works is that the system uses mechanisms like callbacks, promises, or futures to handle the result whenever it eventually arrives. The reason this is such a powerful approach is that it maximizes resource utilization. Your threads aren't sitting idle waiting for I/O, so a small number of threads can handle thousands of concurrent connections. It's why frameworks like Node.js or Vertex are so popular for high-throughput APIs. However, the failure mode you have to watch for is callback hell or complex state management. When you don't have a single linear execution path, it becomes much harder to reason about the order of operations or handle errors gracefully. In an interview, it's vital to mention that while non-blocking systems scale beautifully, they require much more sophisticated observability and error handling logic to prevent silent failures where a request is lost in the shuffle and never actually completes its lifecycle. Eventual processing takes the non-blocking idea further by decoupling the request from the execution entirely, usually through a message queue. How it works is that a client drops a message into a buffer and a separate worker process picks it up whenever it has capacity. This approach is vital because it provides incredible durability and load leveling. If you get a sudden burst of traffic, the queue acts as a shock absorber, so your workers don't get overwhelmed. The failure mode here, though, is the loss of real-time feedback. Since the user doesn't get an immediate result, you have to design the UI to handle an in-progress state, which adds complexity. Interviewers will look for your ability to explain how you'd handle poison pill messages, tasks that keep failing and could clog up your queue indefinitely. You need to account for dead letter queues and retry policies to ensure that a single bad task doesn't stop the entire processing pipeline from moving forward for other users. When we compare latency, the difference between waiting and parallel execution becomes stark. In a synchronous chain, if you need to call 3 services that take 100 milliseconds each, your total time is 300 milliseconds. How this works is cumulative. Each step is a sequential bottleneck. The real effect of this sequential approach is that as your microservice graph grows, your tail latency, that 99th percentile, explodes, making the app feel sluggish for many users. The failure mode is latency amplification, where a tiny bit of slowness in a low-level service ripples upward, causing timeouts at the edge. Conversely, with an asynchronous or parallel approach, you could trigger all 3 calls at once and be done in just over 100 milliseconds. In a design interview, showing the math on these latency savings is a huge plus. You're essentially trading a bit of architectural complexity to buy back hundreds of milliseconds for your users. Just remember that parallelizing everything isn't free. You'll need more concurrent connections and a way to aggregate those results back together once they arrive. Scalability and throughput are where asynchronous systems really shine. How it works is that by avoiding blocking, you ensure that every CPU cycle is spent doing actual work rather than waiting on a database or a network call. This efficiency is what allows you to handle far more requests per second on the same hardware compared to a synchronous setup. One simple way to picture this is a restaurant where the waiter doesn't stand at the table while the chef cooks the meal. They're free to serve other tables in the meantime. The failure mode here, though, is resource exhaustion elsewhere in the system. Because the entry point can accept so many requests, it can easily overwhelm downstream databases or legacy services that aren't built for that kind of volume. In an interview, you've got to discuss back pressure. If your async pipeline is pushing data faster than your database can write it, you'll eventually run out of memory or crash. Balancing this flow is the difference between a high-performance system and a chaotic one. Resilience in synchronous systems usually comes down to how you handle immediate failure. How it works is that if a service call fails, the client must decide right then and there whether to try again or give up. Having a solid retry strategy is essential because a well-implemented retry policy can mask transient network glitches and keep the system feeling stable. But the failure mode is the retry storm. If a service is already struggling and all its clients start hammering it with retries at the same time, you'll effectively launch a self-inflicted DDoS attack that prevents the service from ever recovering. In an interview setting, you should always mention exponential backoff and jitter as your defense mechanisms. These ensure that retries are spread out over time, giving the failing service some breathing room to reboot or clear its backlog. Without these, your synchronous resilience strategy might actually become the very thing that takes your entire platform down during a minor blip, leading to a much larger and more painful outage. In asynchronous systems, we achieve durability by using persistent message queues. How it works is that once a message is accepted by the broker, it's written to disk. Even if the consumer service crashes or the power goes out, that message stays safe until it's successfully processed. The core value of using a broker is that it guarantees no work is lost, which is vital for things like order processing or billing. The failure mode, however, is queue buildup. If your consumers are slower than your producers for an extended period, your queue can grow until it runs out of disk space or causes massive lag. In an interview, this is where you talk about monitoring consumer lag and scaling your worker pool dynamically. You also have to consider what happens if a message is processed twice and at least once delivery guarantee. Designing your consumers to be idempotent so they can handle the same message multiple times without side effects is a critical step in making an asynchronous system truly robust. Choosing between APIs and event-driven patterns depends entirely on the user's needs. Synchronous REST or GraphQL APIs are usually the way to go for user-facing interactions. How it works is that the user gets a response right away. And the reason we prioritize this for the front end is it matters for things like logging in or searching for a product where they're actively waiting for the screen to update. The failure mode here is a poor user experience if the backend is slow. The user sees a spinning wheel and might just leave. On the flip side, asynchronous event-driven patterns are perfect for background jobs like sending emails or generating reports. The user doesn't need to stay on the page for that. But the failure mode there is lost context. If something goes wrong in the background, the user might never know why their email didn't arrive. In an interview, emphasize that you choose the pattern based on the latency budget and the consistency requirements of the specific feature you're building. The trade-offs between these two patterns often boil down to complexity versus capability. Synchronous systems are much easier to build, test, and debug because the flow of logic is linear. How it works is predictable, and this is a major consideration because it matters when you're moving fast and need to ensure high data consistency. The failure mode, as we've seen, is that they don't scale well and are prone to cascading failures. Asynchronous systems offer incredible scale and robustness, but they introduce a lot of moving parts, like brokers, dead letter queues, and complex state machines. This increases the cognitive load on your team and makes the system harder to observe. In an interview, a great answer acknowledges that there's no free lunch. You might start with a synchronous approach for an MVP to save time, but you should have a plan to migrate critical paths to asynchronous patterns as your traffic grows. Being able to justify exactly when to make that jump shows you've got real-world architectural experience. Let's put this into practice by looking at REST versus Kafka. REST is the king of synchronous communication. How it works is over HTTP, where a client waits for a specific status code. Its widespread adoption is due to it being a universal standard that every developer understands, making integration simple. But the failure mode is that it's inherently point-to-point. If the endpoint is down, the request is dead. Now look at Kafka, which is the gold standard for asynchronous event streaming. How it works is by decoupling producers from consumers through a distributed log. This allows multiple different services to consume the same data at their own pace, which is perfect for microservices. The failure mode here is operational complexity. Running a Kafka cluster isn't trivial, and you can run into issues like partition imbalances or disk pressure if not tuned correctly. In an interview, comparing these two shows you understand that your choice of tool should match the communication pattern the business problem actually requires. When you're deciding on a pattern, a simple decision tree can help guide you. First, ask yourself if the user is waiting for an immediate result to take their next step. If yes, go synchronous. How it works is you provide that instant feedback, and this helps you maintain a smooth user journey. But watch out for the failure mode of long-tail latency, making the app feel broken. If the task can happen in the background, go asynchronous. How it works is you use a queue to decouple the work, which provides much-needed system stability and throughput. The failure mode here is that you now need to handle eventual consistency, where a user might not see their change reflected immediately. In a system design interview, this is your chance to show you're thinking about the human side of the system. It is not only about the bits and bytes, it's about matching the technical architecture to the user's expectations, while ensuring the system doesn't buckle under heavy load. We've really zeroed in on the core of how systems communicate. On one hand, you've got synchronous calls, where the client just sits there waiting, which is great for instant consistency, but tough on scalability when those service chains get long. On the other hand, we looked at how asynchronous systems use non-blocking patterns to keep the engine running, prioritizing throughput over immediate feedback. In a high-level design interview, this is where you show your depth. You aren't just picking a tool, you're deciding between resource efficiency and execution simplicity. Understanding that trade-off, knowing exactly when to use a direct REST call versus a message queue like Kafka, is what separates a senior engineer from the pack. You've now got the framework to balance latency against system availability without breaking a sweat, and that's a huge win for your architectural toolkit. So that wraps up our look at sync versus async communication. In a high-stakes interview, don't just pick a pattern. You've got to explain the why. Justify your choice by weighing the simplicity of a REST call against the massive durability of an event-driven queue. Show the interviewer you're thinking about failure modes, like how a synchronous bottleneck can cascade and take down an entire service chain. If you found this helpful, definitely subscribe to the channel for more technical breakdowns. I've put all the course details in the description for you to explore further. Keep practicing those architectural trade-offs, and I'll see you in the next session. Good luck with your designs. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 10 of the System Engineering series, and today we will explore back-of-the-envelope calculations in a way that helps you prepare for system engineering interviews on this topic. You see, being able to quickly estimate storage and latency shows you've got a grounded sense of how systems scale before you even write a line of code. In an interview, it's about demonstrating that you can reason through constraints and justify your architecture under pressure. Mastering these rough estimates helps you speak with authority and keep your design choices realistic. We'll start by looking at why being roughly right is way more valuable than being precisely wrong when you're designing at speed. It's about getting those mental models down. So we'll dive into the math of storage and bandwidth first, making sure you're accounting for things like metadata and protocol overhead that usually trip people up. From there, we'll move into the specific latency numbers you've just got to know by heart to sound credible in a technical discussion. Then, we'll transition into the heavy lifting, converting daily active users into queries per second. This is where we use the 80-20 rule to plan for peak traffic, which is a great way to show an interviewer you understand real-world bottlenecks. We'll also look at memory footprinting for caches and data structures to ensure your designs are realistic. Finally, we'll put it all together with the Fermi approach, walking through case studies for video platforms and ad servers. By the end, you'll have the confidence to justify any system architecture choice with solid back-of-the-envelope logic. Mastering these quick calculations is a non-negotiable skill for architects because it provides a reality check on every design decision. Think of it as a sanity test. If you're designing a messaging app and your math shows you need a petabyte of RAM for the user index, you've clearly got a bottleneck that needs a complete rethink. In an interview, this skill signals that you understand the physical limits of hardware and the financial limits of a cloud budget. It matters because it allows you to compare different strategies side by side without building a single prototype. A common failure mode for junior engineers is skipping this step entirely and diving straight into the API design. That's a mistake, because if the underlying infrastructure requirements aren't feasible, the most beautiful API in the world won't save the project. We use these estimates to bridge the gap between abstract requirements and concrete hardware. It's about developing a feel for the numbers so you can lead technical discussions with confidence and technical authority. The core philosophy here is that being roughly right is infinitely better than being precisely wrong. In the early stages of a design, you don't need 5 decimal places. In fact, if you spend 10 minutes trying to calculate the exact byte size of a JSON payload, you've already lost the room. What we are really doing is checking for feasibility. Does this require 10 servers or 10,000? Can we fit the hot data in memory, or is a disk-based solution mandatory? We often use powers of 2 because they align with how computers actually allocate resources, making the math surprisingly snappy once you get the hang of it. A common failure mode is analysis paralysis, where you get so bogged down in tiny details that you miss a massive bottleneck, like forgetting that your cross-region traffic might have 100 milliseconds of latency. By sticking to these quick estimates, you can quickly discard bad architectures before you've wasted time detailing them. It's about building a mental safety net for your technical decisions. So let's clear up the confusion between binary and decimal units, because this is where a lot of production bugs actually start. In the decimal world, a kilobyte is 1,000 bytes. Simple, right? But computers work in powers of 2, where a kibibyte is actually 1,024 bytes. Now that small difference might not seem like much when you're talking about a single file, but when you're scaling up to terabytes and petabytes, that roughly 10% gap becomes a massive discrepancy. If your storage team thinks in decimal and your engineering team thinks in binary, you're going to run out of disk space way sooner than you planned. What matters here is that it affects how you set up your monitoring alerts and how you buy hardware. In an interview, being precise about whether you're using KB or KIB shows a level of technical maturity that sets you apart. It's a small detail, but getting it wrong is a classic failure mode for capacity planning at scale. When we look at storage, we aren't just talking about the size of a single photo or tweet. We have to account for the hidden metadata and the long-term growth of the system. Let's say you're storing user profiles. You've got the name and email, sure, but you also have IDs, timestamps, and indexes that can double the raw data size. Now multiply that by a 5-year growth plan. If you ignore this, you'll hit a storage wall just as your product is taking off. One of the biggest failure modes in capacity planning is forgetting replication. If you calculate that you need 1 petabyte of space, you actually need 3 petabytes if you're using a standard triple replication strategy for durability. This changes the entire cost profile of your project. In an interview, always ask about the data retention policy. Do we keep everything forever, or do we purge old logs? That single question can change your storage estimate by an order of magnitude, showing the interviewer you're thinking about the full life cycle. Bandwidth is all about the flow of data, and you have to look at both ingress and egress separately. Ingress is everything coming into your system, like user uploads, while egress is everything going out, like content delivery. Often, egress is the bigger bottleneck and the bigger cost driver, especially for media-heavy apps. You also have to account for network overhead. Every packet has headers and protocol data that take up space, and if you are using something like HTTPS, there's an initial handshake cost. A common mistake is assuming you can use 100% of a network link's rated speed. In reality, congestion and protocol limits mean you're doing well if you hit 80%. If your calculations are too tight, you will see massive latency spikes as packets get queued up. In an interview, discussing the trade-offs between compressing data to save bandwidth versus the CPU cost of that compression shows you understand the deep interconnectedness of system resources. It's never just about one number, it's about the whole pipe. Latency is the silent killer of user experience, and you need to have the numbers everyone should know memorized to succeed. There's a massive gap between internal processing and network communication. A CPU can execute millions of instructions in the time it takes for a single packet to travel across the country. For example, reading from a solid-state drive is way faster than a disk seek, but even that is incredibly slow compared to a memory access. If your architecture involves multiple network hops between microservices, those latencies add up fast. A failure mode we see often is designing a system that works locally but crawls once it's distributed across different data centers. When you're in an interview, use these numbers to justify your architecture. If someone asks why you're using a cache, you can point out that a memory access is orders of magnitude faster than a database hit. Being able to quantify that speed difference is exactly what an interviewer wants to see to prove you can build responsive systems. Scaling from a few users to millions requires a shift in how you think about your infrastructure. You can't just keep buying a bigger server. Eventually, you have to go horizontal. We use daily active users as a starting point to estimate how many web servers and database instances we'll need. This is a classic quadrant problem. Low user count with low complexity is easy, but as users grow, you likely hit bottlenecks in your database connections or your load balancer's throughput. A key trade-off here is between server density and fault tolerance. If you put all your users on one massive machine, it's efficient, but you've got a single point of failure. If you spread them across 50 tiny machines, your management overhead goes through the roof. In an interview, explain how your infrastructure estimate accounts for redundancy. You don't just need enough servers to handle the load. You need enough to handle the load even when two of them go down. That's the difference between a school project and a production-grade system. Converting daily active users into queries per second is where we get practical. We usually assume that traffic isn't spread evenly over 24 hours. Instead, we use the 80-20 rule. 80% of your traffic happens in 20% of the time. This means your peak QPS can be 5 or 10 times higher than your average. If you design for the average, your system will crash every single day during the busy hours. This is a massive failure mode in real-world deployments. When you're doing this math, consider the read-to-write ratio too. A social media site might have 1,000 reads for every one write, which pushes you towards a read-heavy optimization strategy like heavy caching or database replicas. In an interview, walking through this funnel from millions of users down to specific requests per second shows you understand how to translate business metrics into technical requirements. It proves you're building a system that can actually survive the morning rush when everyone logs in at once. When it comes to memory, you can't just cache everything. RAM is simply too expensive for that. We usually rely on the Pareto principle or the 80-20 rule, which suggests that about 20% of your data is going to handle 80% of your traffic. So when you're sizing a cache, you're usually looking to fit that hot 20% into memory. To do this right, you've got to calculate the size of a single entry, including the overhead for keys and pointers, and then multiply it by 20% of your total unique objects. A common bottleneck occurs when your cache is too small, leading to high eviction rates and what we call cache thrashing, where the system spends more time moving data in and out than actually serving requests. If you don't account for the hit ratio, your database will get crushed by the overflow traffic. In an interview, always explain the trade-off between the cost of more RAM and the latency penalty of a lower hit ratio. It shows you're thinking about the budget too. Performing these calculations under pressure can be nerve-wracking, but the secret isn't being a mad genius. It's about how you communicate your thought process. You should never just go silent for 2 minutes while you scribble on a whiteboard. Instead, talk through your assumptions out loud. If you're estimating the number of users, say something like, I'm going to assume we have 10 million daily active users with a peak to average ratio of 5. This gives the interviewer a chance to steer you if your numbers are way off. It also shows you understand the why behind the variables. A major failure mode here is being overly defensive about your estimates. If an interviewer challenges a number, don't panic. Use it as a pivot to discuss a different trade-off or a more conservative scaling strategy. They are testing your ability to reason through ambiguity, not your ability to memorize constants. By being transparent about your logic, you demonstrate that you're a collaborative engineer who builds systems based on sound, defensible reasoning rather than just guesses. Let's put this into practice with a case study, sizing a video sharing site with 1 million daily uploads. First, we'll look at storage. If each video is 500 megabytes, that's 500 terabytes of new data every single day. Over a year, that's nearly 200 petabytes. But wait, we need to account for different resolutions, 1080p, 720p, and mobile versions, which might triple that storage requirement. Then there's the bandwidth. If 1 million people upload, but 10 million people watch, your egress is going to be massive. You'll quickly realize that a single data center can't handle this. You'll need a content delivery network to push that data closer to users. The bottleneck here isn't just disk space, it's the cost of moving all those bits across the wire. In an interview, this is where you discuss the trade-off between storing all versions of a video versus transcoding them on the fly to save space. Each choice has a huge impact on your final infrastructure estimate and your bottom line. Once you have your numbers, you need to perform a sanity check. Does the result actually make sense? If your calculation suggests you need 10,000 database servers for a simple note-taking app, something is definitely wrong with your assumptions or your math. This verification step is your last line of defense against proposing an absurd architecture. Use back-of-the-envelope results to validate or reject your ideas early on. If the math says a specific feature will cost $10 million a month in bandwidth, you might need to change the design or the business model. This process is a cascade. One assumption affects the next. If you realize your storage estimate was too low, your backup and recovery times will also be longer than you anticipated. In an interview, showing that you can self-correct when a number looks off is a huge green flag. It shows you have a sense of scale and aren't just blindly following a formula. It's about being an architect who can spot a red flag before it becomes a production disaster. Let's talk about where these estimates usually fall apart. The most common mistake is forgetting the hidden tax on your resources. You might calculate the raw size of a user record but completely ignore the indexing overhead, which can easily double your storage needs. Then there's replication. If you say you need a petabyte of storage but forget that you're running a triple replication scheme for durability, your budget is suddenly off by 300%. Another huge pitfall is ignoring logging and monitoring. In a high-traffic system, the metadata and telemetry you generate can actually rival the size of the application data itself. We also see people underestimate the impact of network hops. Every time you cross a service boundary, you're adding latency and serialization costs that don't show up in a simple logic calculation. If you fail to account for these overheads, you'll end up with a system that works on paper but hits a wall in production. In an interview, calling these out shows you've actually been in the trenches and seen systems fail. So we've nailed down the core of back-of-the-envelope calculations. The goal here isn't to hit a perfect decimal point, it's about being directionally right, so you don't design a system that's dead on arrival. We walk through those essential numbers every developer needs, like why a cross-continental network trip is orders of magnitude slower than a simple disk seek. We also tackle the math behind capacity planning, translating raw DAU numbers into real-world storage and bandwidth requirements. When you're in a high-pressure interview, your ability to rattle off these estimates shows you actually grasped the physical constraints of the hardware. It's about proving you can justify your architecture choices with logic rather than just guessing. You've now got the mental models to spot potential bottlenecks and scale issues before they ever hit production. That's how you lead a design discussion with confidence. That wraps up our deep dive into back-of-the-envelope calculations. Now, when you're in an interview, remember that your thought process matters far more than hitting a perfect number. So always show your work, explicitly state your assumptions about things like replication or overhead, and run those quick sanity checks to justify your design choices. It shows the interviewer you know how scale actually hits the hardware. Subscribe for more. In the next episode, we will discuss SLA, SLO, SLIs, where we'll discuss core understanding SLA, SLO. Good luck with your prep. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 11 of the System Engineering series, and today we will explore SLA, SLO, SLIs, in a way that helps you prepare for system engineering interviews on this topic. Well, these metrics are the bridge between business promises and actual system performance. Showing an interviewer you can define clear SLIs and manage error budgets proves you've got a handle on operational reality. We'll look at how to pick the right indicators so you can defend your reliability choices with confidence. This lesson starts by framing reliability as a measurable spectrum rather than a binary up or down state. You will see how service level management bridges the gap between business needs and technical capabilities, moving us from intuition to actual engineering. We are going to break down the specific hierarchy of SLAs, SLOs, and SLIs, which is often where interview candidates trip up. You'll learn why it's critical to differentiate between a contractual promise made to users and the stricter internal targets your team uses to keep things running smoothly. From there, we dive into the core metrics that drive these decisions, focusing on things like latency percentiles, error rates, and the classic nines of reliability. Well, it is not only about the definitions, it's about understanding how these numbers represent the actual user experience, right? Finally, we'll map these concepts together and analyze a real-world cloud SLA case study to see how exclusions and credits work in practice. By the end, you will understand how to justify reliability targets and technical metrics with the precision needed for a high-level system design interview. When we talk about the pillars of reliability, we are really talking about a shared language. In many organizations, a major failure mode occurs because engineers and business stakeholders aren't speaking the same dialect. The engineer says the database is slow, but the business lead wants to know if they're losing money. Mastering these terms allows you to bridge that gap. What matters here is that without this framework, you're just guessing at how much to invest in infrastructure. If you over-engineer for 100% uptime, you waste millions. If you under-engineer, you lose users. In an interview, the recruiter is looking for this nuanced understanding of balance. They want to see that you don't just want things to be perfect, you want them to be appropriately reliable. If you can't measure performance, you can't manage it, and you certainly can't improve it. So think of these pillars as the skeleton of your operational strategy. They provide the structure that allows a service to grow and scale without collapsing under its own complexity or failing to meet user expectations. Reliability engineering isn't just a set of tasks, it's a mindset that acts as a bridge. On one side, you have business needs like feature velocity and market growth, and on the other, you have technical capabilities like server capacity and network latency. The bridge between them is service level management. Now, why does this matter? Well, if you push features too fast without a reliability framework, your system breaks. If you focus only on stability, your product stalls. A major failure mode here is the silo effect, where developers don't care about reliability and SREs don't care about features. By using SLAs and SLOs, we create a common ground where both sides agree on a threshold of pain. This is a huge signal in interviews. If you're asked how to handle a team that keeps breaking production, you don't just say test more. You talk about building a foundation of reliability where data-driven targets dictate when it's safe to ship and when you need to freeze features to fix the core system. One of the first things to realize is that reliability is not a binary state. Your system isn't just up or down in the way we often imagine. It's actually a measurable spectrum. Moving from intuition to engineering means we stop saying the site feels sluggish and start saying the 95th percentile latency is at 350 milliseconds. This distinction is vital because human intuition is notoriously bad at catching slow regressions. A system can be slowly dying for weeks before anyone notices if you aren't tracking quantitative goals. In a system design interview, if you're asked about monitoring, don't just list tools like Prometheus or Datadog. Instead, explain that you need these quantitative goals to define what good looks like. A failure mode to watch out for is vanity metrics, where you measure things that look great on a dashboard but don't actually reflect the user's experience. You need to focus on metrics that correlate with actual user frustration or success, moving beyond gut feelings into the realm of hard, actionable engineering data. Let's start with the SLA, or the Service Level Agreement. This is the external promise. Think of it as a contract between a service provider and a customer. It's not just a technical goal. It's a legal and financial document that outlines what happens if you fail. If you promise 3 nines of availability and you hit 2, the SLA dictates the consequences, usually in the form of service credits or refunds. What matters here is that it sets the stakes for the entire organization. However, a huge failure mode is setting an SLA that's too high. If you promise 99.99%, but your underlying cloud provider only guarantees 99.9%, you've just created a massive financial liability. In an interview, show you understand this business technical alignment. You'd never set your SLA at the same level as your internal targets. You always need a buffer. The SLA is the absolute floor, the point where the business starts losing money and reputation. It's the external commitment that forces the technical team to maintain a certain standard of excellence to keep the company viable. Moving inside the company, we have the SLO or service level objective. This is the internal target set by the engineering team, and it's almost always stricter than the SLA. If your SLA is 99.9%, your SLO might be 99.95%. This gap is your safety margin or buffer. Why does this matter? Because it gives you an early warning system. If you breach your SLO, you're in trouble internally, but you haven't yet violated your contract with the customer. This leads us to one of the most important concepts in modern engineering, the error budget. If you meet your SLO, you have credit to take risks and ship new features. If you burn through that budget because of outages, you stop and focus on stability. A common failure mode is ignoring the SLO until the SLA is already breached. In an interview, you'll want to emphasize that SLOs are the heartbeat of that dev cycle. They tell the team when they are moving too fast and when they have room to experiment, keeping the system healthy before the lawyers have to get involved. To have an SLO, you need an SLI, which is the service level indicator. This is the raw, quantitative measure of some aspect of the service. If the SLO is the goal, the SLI is the thermometer. For example, if your goal is to be fast, your SLI might be the latency of successful homepage requests. You have to be very specific here. What matters here is that if your SLIs are poorly defined, your SLOs become meaningless. A classic failure mode is measuring the wrong thing, like looking at CPU usage instead of request success rate. Your users don't care if the CPU is at 10% if they're getting 500 errors. In an interview, when you're asked how to monitor a system, start with the SLIs that reflect user experience. You want to track the work the system is actually doing for the user, not just the health of the individual machines. It's the difference between knowing the engine is running and knowing the car is actually moving the passenger toward their destination at the expected speed. Latency is one of the most common SLIs, but it's also one where people make the most mistakes. When we talk about latency, we are measuring the time it takes for a system to process a request. The biggest trap you can fall into in an interview is talking about average latency. Averages are dangerous because they hide the outliers. If 9 users have a 10 millisecond response and the 10th user has a 10-second response, the average looks fine, but that 10th user is having a terrible experience. That's why we use percentiles like P95 or P99. This tells us the experience of the slowest 5% or 1% of users. What matters here is that it captures the long tail where the real system bottlenecks live. A failure mode here is ignoring the P99s until they start dragging down your overall metrics. High percentile latency usually points to resource contention, garbage collection pauses, or network congestion. When you explain this in an interview, you're signaling that you understand the reality of distributed systems, where the worst-case scenario is what actually defines your system's perceived reliability. Next up is the error rate, which is the ratio of failed requests to total requests. On the surface, it seems simple. Count the 500 errors and divide by total traffic. But in a real-world system, it's more complex. You have explicit errors like in HTTP 500, but you also have implicit errors. These are the silent killers, where the system returns a 200 OK, but sends back an empty body or corrupted data. Why does this matter? Well, if your monitoring only looks at status codes, you might think everything is green while your users are seeing blank screens. This is a classic failure mode in complex architectures. In an interview, you should talk about how you define a fail request. Does a 404 count? Usually not, because that's often a user error, but a 503 definitely counts. Distinguishing between client-side errors and server-side failures is key to building an accurate SLI. You want your error rate to reflect the actual reliability of your code and infrastructure, not just the fact that people are typing in wrong URLs. Availability is the metric everyone talks about, often expressed in nines. 99.9% availability sounds great, but it still allows for nearly 9 hours of downtime a year. If you move to 4 nines, you only have about 52 minutes. What matters here is that each 9 you add exponentially increases the cost and complexity of your architecture. You might need multi-region failover, more redundancy, and faster automated recovery. A major failure mode is focusing only on time-based availability, meaning the system is up while ignoring partial outages. If your service is up but the database is in read-only mode, are you really available? In an interview, show that you understand these trade-offs. More nines isn't always better if the cost of achieving them outweighs the business value. You have to find the sweet spot where the system is reliable enough that users stay happy, but you aren't spending your entire engineering budget on chasing a decimal point that doesn't actually change the user's perception of the service. Now, let's map how these three work together. It's a hierarchy. Your SLIs are the raw data points flowing from your servers. You aggregate those SLIs into SLOs, which are your internal targets for what those metrics should look like over a period of time, like a rolling 30-day window. Then those SLOs inform the SLAs you sign with your customers. This relationship ensures that your technical metrics are directly aligned with your business commitments. If they aren't aligned, you'll run into a massive failure mode, the watermelon effect. This is where your internal dashboards are all green, but the customer is seeing red. It happens when you're measuring the wrong things or setting the wrong targets. In an interview, explain that a robust system architecture isn't just about the code, it's about this flow of information. You need to be able to justify an architecture choice by showing how it helps you hit an SLI, which protects an SLO, which ultimately keeps you from breaching an SLA and losing money. To see how this works in the real world, we can look at a typical cloud SLA. If you read the fine print, you'll see it's rarely a simple up or down guarantee. They include exclusion clauses like scheduled maintenance or issues caused by the user's own code. They also define exactly how they calculate service credits. If the uptime drops below a certain point, you get 10% back. If it drops further, you get 25%. What matters here is that it shows that SLAs are about risk management, not just technical perfection. A common failure mode for developers is assuming a 4 nines SLA means they never have to worry about downtime. In reality, you have to design your system to be more resilient than the underlying services it relies on. In an interview, if you're asked about using a third-party API, you should mention checking their SLA and then building a fallback mechanism for when they inevitably breach it. You can't outsource your own reliability. You have to plan for the failure of every component in your stack. We've just laid out the entire hierarchy of reliability engineering. And honestly, mastering these three pillars is how you separate vague intuition from real systems design. You've got your SLIs, those raw metrics like P99 latency or error rates that tell you exactly what's happening on the ground. Then there's the SLO, which is your internal line in the sand. When you're in an interview, make sure you emphasize that your SLO should always be tighter than your SLA. That gap is your safety margin. It's the buffer that lets you fix issues before they become a legal or financial headache. We also looked at how error budgets turn these abstract goals into a practical tool for deciding when to ship features or focus on stability. So by tying these together, you're not just monitoring a dashboard, you're actually engineering reliability into the business model. That's how you maintain a high-performing system without burning out your team. So that wraps up our breakdown of SLAs, SLOs, and SLIs. When you are in an interview, try to focus on how these metrics actually drive engineering decisions. You'll want to explain, for example, how P99 latency captures the experience of your most frustrated users and how that feeds into the error budget to manage risk. Showing that you understand the tension between feature speed and system reliability is a huge signal for interviewers. For more, check the course details in the description and hit subscribe to stay ahead. In the next episode, we will discuss Idempotency Basics, where we'll discuss core understanding, definition, importance. Good luck with your preparation. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 12 of the System Engineering series, and today we will explore Idempotency Basics in a way that helps you prepare for system engineering interviews on this topic. Now, being able to explain how to prevent duplicate side effects like double charging a user during a network retry is a huge signal to an interviewer that you understand distributed reliability. We'll dive into how to implement these safeguards so you can speak confidently about data integrity and API safety. This lesson starts by breaking down the core concept of safe repeated operations, defining exactly how idempotency keeps distributed systems predictable. We look at the vital role this plays in preventing duplicate effects, like making sure a user isn't double charged just because they hit submit twice. From there, we move into the actual implementation, where you will learn how to use idempotency keys and choose between different generation strategies. It's important to understand the backend flow here, specifically how we store keys and cache results to keep things fast and consistent. We'll then apply these ideas to high-stakes scenarios like payment processing and handling network retries, which is a favorite topic in system design interviews. To ground everything in reality, we'll analyze how industry giants like Stripe and PayPal structure their API headers to manage billions in transactions safely. By the end, you'll have a clear framework for building robust, failure-tolerant APIs that never compromise on data integrity. When we talk about building reliable distributed systems, we're really talking about how we handle uncertainty. Think about it. Every time a client sends a request over the network, there are three possible outcomes. The request could fail to reach the server could crash while processing it, or the response could get lost on the way back. Without idempotency, a client wouldn't know if it's safe to retry that request. This is why mastering this pattern is such a massive deal in modern API design. In an interview, if you're asked how to make a system fault-tolerant, this should be one of the first things you mention. It allows the system to reach a consistent state even when the communication layer is unreliable. It is not only about handling errors, it's about designing your operations so that failure doesn't lead to corruption. We are basically building a safety net into the logic itself, ensuring that retrying a request doesn't lead to unintended side effects. Let's look at what we mean by safe repeated operations. The core idea here is that performing an action multiple times should produce the same final outcome as doing it just once. Imagine you're at an elevator and you press the call button 5 times. You don't get 5 elevators. The system just knows you want to go up. That's idempotency in action. In software, this is crucial because it eliminates the fear of duplicate work. If a process hangs and we aren't sure if it finished, we can just run it again. If we don't have this safety, we're constantly stuck in a limbo that usually leads to manual cleanups or inconsistent databases. Failure to implement this correctly often results in zombie resources or double billing, which are absolute nightmares to debug. When you're explaining this to an interviewer, emphasize that idempotency is what lets us build self-healing systems that can automatically retry without needing a person to step in. To get technical for a second, an operation is considered idempotent if it can be applied multiple times without changing the result beyond the initial application. Now, don't confuse this with nothing happening on the second call. Something does happen. The server recognizes the repeat and usually returns the same success response it gave the first time, but it doesn't actually perform the underlying state change again. It's like a math function where f of x equals f of x. If you set a value to 5, setting it to 5 again doesn't change anything. However, creating a new record usually isn't idempotent by default unless you specifically design it to be. In a system design interview, you will want to distinguish between operations that are naturally idempotent, like a get or a put, and those that require extra work, like a post. Understanding this distinction is the difference between a junior developer who just retries everything and a senior engineer who builds systems that handle those retries safely. One of the most common reasons we use idempotency is to prevent duplicate effects. You've probably seen those warnings on checkout pages that say, "Do not refresh this page or click back." That's basically the developer admitting their system isn't idempotent. If a user clicks submit and the network times out, their browser might try to send that payment request again. If your backend isn't prepared for that, you might end up double charging the customer's credit card. That's a huge failure mode that leads to massive customer dissatisfaction and expensive support tickets. It is not only about payments though. Think about creating a new user account or an order. If the request is resent because of a jittery connection, you don't want two identical orders in your database. By making the operation idempotent, the server can see that it has handled this specific request before and simply refuse to execute the logic a second time. It keeps the system clean and predictable. From a systemic perspective, idempotency acts as a critical safeguard for data integrity. In a distributed environment, you have multiple services talking to each other, and they often use message queues. These systems usually guarantee at least once delivery, which means a message might show up at your doorstep more than once. If your database logic isn't idempotent, those duplicate messages will slowly poison your data consistency over time. You'll find balances that don't add up or inventory counts that are completely off. This is why financial systems are so obsessed with this pattern. It ensures that even if a message is replayed 10 times during a recovery process, the final state of the database remains perfectly accurate. When you're in an interview, you can frame idempotency as the bridge between at least one's delivery and exactly one's semantics. It's the mechanism that turns a messy, repetitive stream of events into a clean, reliable record of truth for the entire business, which is a major signal of seniority. So, how do we actually build this? The most common way is through the use of idempotency keys. The client generates a unique string, usually a UUID, and attaches it to the request. When the server receives it, it checks its idempotency store to see if it's seen that key before. If it has, it just skips the actual processing and returns the cached result from the first time. This is a brilliant architectural pattern because it puts the responsibility of identifying the intent on the client. It solves the lost response problem perfectly. If the client doesn't get a response, it just tries again with the exact same key. The server sees the key, realizes it's already done the work, and just hands back the original success message. One thing to watch out for in an interview is the storage of these keys. They need to be stored in a fast, reliable place like Redis, and they must persist long enough to cover any reasonable retry window. There's a bit of a trade-off when it comes to how you generate these keys. On one hand, you have client-side generation using something like a UUID. This is great for binding a specific request to an intent, but you have to trust the client to generate it correctly. If the client accidentally uses the same key for two different orders, you've got a major problem. On the other hand, you can use natural keys from the business domain, like a combination of a user ID and an order ID. This can be more robust because it's tied to the actual data, but it might not be flexible enough if a user needs to genuinely repeat an action. Most high-scale APIs, like Stripes, lean toward the client-generated header approach because it's flexible and decoupled from the internal data structure. When you're discussing this, mention that the choice depends on your trust level with the client and the specific requirements for how long a duplicate should be blocked. Let's walk through what's actually happening on the backend. When a request hits the server, the very first thing it does is look for that idempotency key. It checks a fast access store to see if that key is currently in flight or already completed. If it's already completed, the server retrieves the previous response and sends it back immediately. No database writes, no external API calls, nothing. If it's a brand new key, the server marks it as processing and goes ahead with the logic. Once it's done, it saves the result and marks it as succeeded. This check then act flow is a classic pattern, but you have to be careful about race conditions. If two identical requests hit two different server instances at the exact same millisecond, they both might think they are the first one. That's a huge failure mode. To solve this, you need atomic operations or distributed locks in your key store to make sure only one process can claim that specific key at a time. Payments are the classic use case for a reason. Imagine a user is on a slow mobile connection and they hit Pay Now. The request goes out, the bank processes the charge, but the success message never makes it back to the phone because the signal dropped. The app sees a timeout and naturally tries again. If you don't have idempotency, the bank sees a second request and charges the user a second time. Now you've got a furious customer and a messy refund process to deal with. By using an idempotency key, the payment gateway recognizes the second attempt as a retry of the first. It sees that the charge was already successful and just says we're all good, without touching the user's balance again. This is why you'll see an idempotency header in almost every professional financial API. It's the primary defense against the chaos of unreliable networks and impatient users who just love to double-click when things seem slow. Beyond just user actions, idempotency is a lifesaver for background jobs and automation. Let's say you have a worker process that's responsible for syncing data between two systems. If the worker crashes halfway through, you want to be able to just restart it and have it pick up where it left off. Without idempotency, that's incredibly hard because the worker doesn't know which records it already processed. You might end up with partial updates or duplicate entries. With idempotent operations, the worker can just blindly retry everything. It sends the same data again, and the receiving system just ignores anything it's already handled. This makes your automation much simpler and more robust because you don't have to write complex state tracking logic for every single failure scenario. You just embrace the retry. In an interview, highlight that this simplifies the error recovery logic significantly, allowing developers to focus on the happy part, while the idempotency layer handles the messy what-ifs. One of the trickiest things to handle is when a response is lost in flight. The server did the work, the database is updated, but the client is sitting there wondering what happened. When the client retries with the same key, the server must be smart enough to ignore the request, and more specifically, to actually return the original result. If the server just returned a generic already processed error, the client might not know if the previous attempt actually succeeded or if it failed for some other reason. This is why caching the full response, including the status code and the body, is so important. It ensures the client gets the exact information it would have received the first time. A common mistake here is not having an expiration policy for these keys. You can't store every key forever, or your database will eventually explode. You have to decide on a validity window, say 24 hours, after which the key is cleared and the request is treated as brand new. If you look at the industry leaders like Stripe, PayPal, or Adyen, you'll see they all follow this pattern almost exactly. They've standardized the use of an idempotency header. These companies process billions of dollars, and this simply couldn't function without this safeguard. It's become such a standard that if you're building a public-facing API today and you don't include some form of idempotency for state-changing operations, it's considered a major architectural red flag. When you're in an interview, referencing these real-world examples shows that you're not just talking about theory. You understand the practical standards that the industry relies on. It also shows you understand that consistency and reliability are part of the product's value proposition, not just technical details. These companies have effectively offloaded the complexity of handling network failures onto a well-defined, header-based contract that both the client and the server understand perfectly, which makes their platforms much more developer-friendly. Let's look at the actual implementation in a request. Most of the time, this is handled through a custom HTTP header. You'll see things like idempotency key, followed by a unique value in the request metadata. The beauty of using a header is that it keeps your actual request body clean and focused on the business data. It separates the intent to do something from the metadata about the request itself. This makes it much easier to implement across different endpoints without having to change your data schemas. Some systems also use a request ID header for similar purposes, but usually an idempotency key is specifically reserved for ensuring that the side effects of a post or patch request only happen once. When you're designing your own APIs, think about where this logic lives. Does it live in your application code, or can it be handled by a middleware or a gateway? Ideally, it's a reusable component that your developers can just plug in. So we've walked through why idempotency is actually the backbone of reliability in distributed systems. It's the guarantee that repeating an action won't cause unintended side effects, which is absolutely vital when network failures are inevitable. In a system design interview, you've got to be ready to explain how idempotency keys serve as that unique fingerprint for each request. Whether you're using client-side UUIDs or natural business keys, the logic remains the same. Recognize the duplicate, skip the heavy lifting, and return the cached result. We also touched on the trade-offs, right? Adding this layer introduces some storage overhead and architectural complexity, but it's the price we pay to prevent critical failures like double charging a customer. Ultimately, mastering this pattern is about protecting data integrity when things get messy over the wire. You're now equipped to justify this choice whenever consistency is on the line. So that brings us to the end of our look at idempotency. Now, if you're heading into a system design interview, remember that just mentioning a key isn't enough. You need to talk through the storage trade-offs and how you'd handle race conditions when two identical requests hit at once. Well, showing that you can navigate those failure modes proves you're thinking about real-world consistency, not just happy path code. I hope this gives you a solid edge in your prep. For more topics like this, definitely subscribe to the channel and check the description for all the course details. Good luck with your studies, and I'll see you in the next one. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 13 of the System Engineering series, and today we'll explore monolith versus microservices architecture in a way that helps you prepare for system engineering interviews on this topic. Now, understanding these two architectural paradigms is vital because interviewers aren't just looking for a definition, they're testing your ability to navigate trade-offs like coupling and team autonomy. We'll look at how to justify choosing one over the other so you can speak confidently about scaling systems without falling into the trap of over-engineering. It starts by breaking down the growth pressure points that push a system from a single monolith toward a distributed architecture. We'll look at this as an evolutionary path rather than a one-time choice. From there, we dive into 6 core technical shifts that define the two models. You will see how we move from tight coupling and shared databases to team autonomy and independent deployments, which is really where the velocity argument comes from. We'll also analyze how failure isolation and surgical scaling change when you move away from a single process. Now, since no one does a total rewrite overnight, we'll explore the strangler fig pattern for safe migrations. We also have to be honest about the trade-offs, right? So we'll look at the massive jump in operational complexity and the observability requirements that come with microservices. We'll wrap up with the critical interview insight on when you actually shouldn't use microservices, ensuring you can defend your architectural decisions under pressure. By the end, you'll understand how to balance simplicity against long-term flexibility. Imagine you're the lead engineer at a rapidly growing fintech startup. You started with a clean, single code base that was easy to manage, but now your team has grown from 5 people to 50. Suddenly, you're noticing that simple features are taking weeks to deploy because every time someone changes the interest rate logic, it somehow breaks the user profile page. Your build times are creeping up toward 40 minutes, and if one developer makes a tiny memory leak mistake, the entire platform crashes for every single customer. This is the reality of a monolith hitting its limit. You're under immense pressure to ship faster, but the system's architecture has become a bottleneck. You have to decide, do you keep patching the existing structure or do you undertake a massive migration to microservices? If you choose wrong, you could paralyze the company for months. This scenario is exactly what interviewers want to see you navigate. They're looking for how you evaluate these constraints and manage the risk of a system that's essentially outgrown its own skin. When we talk about the evolution of architecture, we're really looking at a shift from simplicity to modularity. A monolith works as a single unified process where all the business logic, UI, and data access layers are bundled together. It's incredibly straightforward to develop at first, but it starts to fail when the system's complexity exceeds the team's ability to keep it all in their heads. Why does this matter? Well, it matters because your architecture is the foundation for your team's velocity. If your system is one giant block, you lose the ability to iterate on individual parts. Microservices, on the other hand, break that block into distributed units that talk over a network. This shift is meant to solve the problem of scaling, but it introduces a whole new set of failure modes, like network latency and partial failures. In an interview, don't just say microservices are better, explain that they are a response to specific organizational and technical bottlenecks. You have to show you understand that this evolution is a series of trade-offs, where you trade code simplicity for operational flexibility. So, how do you know when you've reached the growth pressure point? It usually shows up in 3 distinct ways: team friction, build paralysis, and catastrophic failure. Team friction happens when multiple groups are constantly stepping on each other's toes in the same code base, leading to endless merge conflicts. Build paralysis is when your CI/CD pipeline becomes so slow that developers stop testing properly, which eventually leads to the third problem: a single bug taking down the entire site. These are the red flags that tell you your monolith is becoming a liability. Why is this so important for your career? Because recognizing these signs early prevents a total system collapse. If you ignore these pressures, your failure mode is a big ball of mud, where no one understands how the system works anymore. In an interview, if you can point to these specific stressors as the why behind the migration, you will show that you're thinking like a seasoned architect. You're moving beyond just writing code and actually starting to manage the life cycle of the entire engineering organization. It's helpful to think of architecture as a journey rather than a destination. This evolutionary path isn't a straight line. It's a response to scale, team size, and the need for speed. Most successful companies actually start with a monolith because it's the fastest way to find product market fit. You don't want to deal with the overhead of 50 services when you only have 2 customers, right? But as you scale, you move towards modularity. What matters here is that it allows you to decouple your services, letting teams work independently. However, the failure mode here is premature decomposition, where you split things up too early and get crushed by the overhead of managing a distributed system. You will hear this a lot in interviews. Don't build microservices until you have a monolith that's worth splitting. The goal is to evolve the system just in time to support growth without over-engineering it. You need to justify each step of the path by pointing to the specific trade-offs of scale and organizational maturity that you're facing at that moment. Now, let's talk about what microservices actually are. They're a suite of small, independently deployable services that communicate over a network, usually via REST or gRPC. Each service is centered around a specific business capability, like orders or inventory, and is managed by a distinct team. This approach works by isolating the responsibilities of each unit, which matters because it means a change in the shipping service won't accidentally break the billing service. However, because these units are distributed, you have to worry about new failure modes like the fallacies of distributed computing. For instance, the network is not reliable and latency is never zero. In an interview, you should emphasize that microservices aren't just about small code bases, they're about independent life cycles. If you can't deploy one service without deploying 3 others, you don't actually have microservices. You have a distributed monolith, which is the worst of both worlds. Strong candidates will always highlight that true microservices require strict boundaries and an obsession with well-defined stable service contracts. One of the biggest concepts in this debate is the coupling spectrum. Monoliths are notorious for tight coupling, where internal components share memory and can easily call each other's private functions. This sounds efficient, but it leads to ripple effects where a tiny change in a utility class can break seemingly unrelated features. Microservices try to enforce loose coupling by putting a network boundary between services. This forces you to use clearly defined APIs. Why does this matter? Well, it protects the internal logic of a service, allowing you to rewrite the guts of the service of search without anyone else needing to know. But watch out, loose coupling isn't a guarantee. A common failure mode is leaky abstractions, where a service exposes its internal database schema through its API, which accidentally couples everyone back together again. When you're in an interview, talk about how you would use API versioning and consumer-driven contracts to maintain that loose coupling. It shows you understand that decoupling is an ongoing effort, not just a one-time architectural decision you make at the start. Autonomy and team velocity are where microservices really shine for large organizations. In a monolith, every team is forced to use the same programming language, the same libraries, and the same release cycle. If the data science team needs a specific Python library, but the main app is in Java, they are often stuck. Microservices change the game by letting each team choose the right tool for the job. What matters here is that it removes the lowest common denominator bottleneck, allowing for much faster iterations. One team can deploy 5 times a day, while another deploys once a week. The failure mode here, though, is tech debt sprawl. If every team uses a different language and database, your ops team will have a nightmare trying to support it all. In an interview, explain that while autonomy is great, you still need paved roads or standard platforms to keep the complexity manageable. It's a balance between giving teams the freedom to move fast and maintaining enough consistency so that the whole system doesn't become an unmaintainable mess of random technologies. Data ownership is arguably the hardest part of moving to microservices. In a monolith, you have a shared database where you can perform easy SQL joins across any table. It's simple and consistent. But in microservices, we insist on a database per service model. This ensures that the order service is the only thing that can touch the order tables. What matters here is that it prevents services from being secretly coupled through the database layer. However, this creates a massive challenge for data consistency. You can't just use a standard AC transaction across 2 different databases. Instead, you have to use patterns like Sagas or event-driven consistency to keep things in sync. This is a huge failure mode if not handled correctly. You might end up with an order that's paid for but never shipped. In an interview, this is where you show your depth. Explain how you'd use an outbox pattern or asynchronous events to handle cross-service updates while accepting that you're trading off immediate consistency for the sake of system-wide availability and service isolation. Let's look at how deployment works in these two worlds. With a monolith, it's an all-or-nothing affair. You package the entire application and deploy it as one giant unit. This is simple to manage initially, but as the app grows, the risk of every deployment skyrockets. One bad line of code in a secondary feature can roll back the entire release. Microservices, meanwhile, allow for independent deployments. You can update the payment service to fix a bug without even touching the search service. What matters here is that it dramatically reduces the risk of each change and allows for much faster feedback loops. The failure mode here is version mismatch. If service A expects a new field from service B, but B hasn't deployed yet, things will break. To ace this in an interview, talk about canary releases and blue-green deployments. These techniques let you test new versions with a small slice of traffic, ensuring that an independent deployment doesn't turn into a widespread outage across your entire distributed system. Scalability is handled very differently depending on your architecture. Monoliths scale horizontally by duplicating the entire application. If your image processing logic is hitting 100% CPU, you have to spin up a whole new copy of the entire app, including the parts that aren't busy. It's like buying a whole second car just because you need an extra seat. Microservices offer what I call vertical precision or surgical scaling. You can give the image processing service service 10 instances while keeping the user profile service at just 2. What matters here is that it's much more cost-effective and allows you to handle specific bottlenecks without wasting resources. A common failure mode here is failing to account for the overhead of the service mesh or the network itself. While you're scaling individual services, the total resource consumption might actually be higher than a monolith due to all the extra infrastructure. In an interview, emphasize that you'd use monitoring to identify which specific services are the bottlenecks, allowing you to scale intelligently based on real-time demand rather than just guessing. Failure isolation is all about the blast radius. In a monolith, the blast radius is the entire application. A memory leak or an unhandled exception in one module can crash the entire process, taking down every single user. It's a total system failure. Microservices are designed to contain that damage. If the recommendation service starts failing, the user might see an empty list, but they should still be able to check out and pay. What matters here is that it keeps the core business running even when parts of the system are down. But here's the catch. The failure mode to watch for is cascading failures. If service A waits for service B and B is slow, service A might run out of threads and crash, eventually bringing down the whole system anyway. To prevent this, you've got to use patterns like circuit breakers and timeouts. In an interview, explain how you'd use a tool like Hystrix or a service mesh to trip the circuit and prevent a local failure from becoming a global catastrophe. If you decide to migrate, please, whatever you do, don't try a big bang rewrite. It almost always fails because you're trying to hit a moving target. Instead, use the strangler fig pattern. This works by placing a proxy or an API gateway in front of your monolith and gradually peeling off specific features into new microservices. Over time, the new services grow and the monolith shrinks until it's eventually gone. What matters here is that it allows you to provide value and test the new architecture without stopping all feature development. The biggest failure mode here is purgatory, where you end up with a half-migrated system that's even more complex than before. In an interview, describe this as a multi-phase process. First, identify a low-risk module, extract its data, build the service, and then shift traffic. This methodical approach shows you that you're a pragmatic engineer who understands that you have to keep the business running while you're performing surgery on the system's heart. It's all about managing risk while moving towards a better architectural state. When we weigh the advantages, it really comes down to simplicity versus flexibility. Monoliths are the champions of initial speed. They've lower operational overhead, easier testing, and simpler deployments. For a small team, a monolith is often the right choice. Microservices, however, win on long-term flexibility and organizational scale. They allow large companies to grow their engineering headcounts without everyone getting in each other's way. What matters here is that your architecture must match your team's size and the product's complexity. A failure mode we often see is architecture to team mismatch, where a small team tries to manage 50 services and spends all their time on infra instead of features. In an interview, you'll sound very sharp if you can argue for both sides. Be ready to say, we should stick with a monolith because our domain isn't stable yet. Or, we need microservices because we have 4 distinct teams that are currently blocked by a single release train. It's about choosing the right tool for your specific organizational constraints at that point in time. Now, we have to talk about the hidden cost, operational complexity. Moving to microservices means you suddenly need a robust CI/CD pipeline, container orchestration like Kubernetes, and complex observability tools. Monitoring one app is easy, but monitoring 50 is a massive engineering feat. You need distributed tracing to see how a single request travels through 10 different services. What matters here is that without these tools, you'll be completely blind when something goes wrong. The failure mode here is a operational debt, where you build services but don't invest in the infrastructure to run them, leading to miserable on-call shifts and slow incident response. In an interview, mention that microservices require a DevOps culture, where teams take responsibility for running their own code. You'll want to talk about tools like Jaeger for tracing or Prometheus for metrics. Showing that you understand the infrastructure requirements proves you're not just a dreamer. You're an engineer who knows what it takes to actually keep a distributed system alive and healthy in a production environment. Here's a major interview insight. A strong candidate knows when not to use microservices. Don't use them if your team is small, if your business domain is still rapidly changing, or if you haven't identified your bounded contexts yet. Prematurely splitting a system often leads to distributed spaghetti, where services are constantly talking to each other in complex circular ways. What matters here is that the overhead of microservices can easily kill a startup before it even gets off the ground. The failure mode to highlight here is nanoservices, where you've broken things down so small that the network overhead and management cost outweigh any benefit of isolation. In an interview, if you're asked how to design a new system, always start by asking about the scale and the team size. If someone suggests microservices for a 2% prototype, be the person who says, wait, let's start with a modular monolith first. It shows you're focused on business value and avoiding the shiny object syndrome that leads to over-engineered, unmaintainable systems. We've covered the fundamental divide between these two architectural styles today. You now have a solid understanding of how they work, the pressure points that lead to change, and the technical trade-offs involved in each choice. This foundation is essential as we move forward. In our next sessions, we're gonna dive even deeper into the specific patterns that make microservices actually work in the real world. We'll look at API gateways, which act as the single entry point for your clients, and we'll explore event-driven architecture to handle that tricky data consistency problem we talked about. Why does this matter? Because knowing the theory is one thing, but knowing the implementation patterns is what gets you through a senior-level system design interview. We'll examine how these patterns solve the bottlenecks and failure modes we've identified so far. So take a moment to process what we've discussed and get ready to get even more technical. We are moving from the what and why into the how of building modern, scalable distributed systems. So we've broken down the big shift from monoliths to microservices, and it's clear this isn't just about code, it's about how your teams scale. We've navigated three main friction points: coupling, autonomy, and deployment independence. Well, a monolith offers simplicity and easy data joins, but as you grow, it becomes a bottleneck where one bad commit can sink the ship. Microservices solve that by enforcing hard boundaries and separate databases, though they introduce the headache of distributed consistency. In a system design interview, your strongest signal isn't just knowing how to split a service, it's being able to justify the operational tax you're paying for that autonomy. If you can articulate why a team might stick with a monolith to avoid overhead, you're showing the kind of maturity senior engineers actually care about. That wraps up our look at the monolith versus microservices divide. In an interview, your ability to justify when not to move to microservices is just as important as knowing the benefits. So always highlight how premature decomposition can be a major bottleneck. We've covered the two main architectural paths and how the strangler fig pattern manages migration risks. Now, for more deep dives, make sure to subscribe and check the description for the full course details. In the next episode, we'll discuss service decomposition strategies, where we'll discuss situation, core understanding, domain-driven design. It's been great having you here, and good luck with your system design prep. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 14 of the System Engineering series, and today we'll explore service decomposition strategies in a way that helps you prepare for system engineering interviews on this topic. Deciding exactly where to split a monolith is a high-stakes design choice. If you miss the mark, you're stuck with a brittle distributed monolith. We'll look at strategies like bounded contexts and business capabilities, so you can confidently justify your architectural boundaries when you're in the hot seat. We begin with the scaling wall, looking at why monoliths eventually struggle and how we can identify autonomous boundaries that let a system evolve. It starts by breaking down the four core pillars of decomposition: bounded context through domain-driven design, business capabilities, data sovereignty, and organizational alignment. Well, you'll see how to align services with what a business actually does, rather than just technical actions. From there, we'll dive into the database per service pattern, since true autonomy is impossible if you're still sharing data schemas across teams. We'll also cover Conway's law to show why your team's own communication structure basically dictates your technical architecture. Later, we'll tackle the challenge of service granularity, helping you find the sweet spot between fine-grained and coarse-grained services to keep coupling low. We'll wrap up by applying these strategies to a real-world e-commerce interview case, so you've got a framework to justify these trade-offs under pressure. By the end, you'll understand how to carve up a complex system into independent, manageable services. Let's set the scene with a situation you likely encounter in production. Imagine you're at a fast-growing startup with a massive Ruby or Java monolith. It's worked great so far, but now you've 50 engineers all trying to commit to the same repository. Deployments take an hour, merge conflicts are constant, and a tiny bug in the payment logic can crash the entire catalog. This scaling wall is exactly why decomposition matters. It's the transition from a single unit of deployment to a distributed system. The failure mode here is often a knee-jerk reaction where you try to split everything at once without understanding the dependencies. This usually results in a chaotic system where services are constantly waiting on each other. Well, to avoid that, you have to look at the constraints like data consistency and team structure. Identifying these pressure points early is what allows you to build a system that can actually survive the growth of the company without grinding to a total halt. Service decomposition is really the art of breaking the monolith in a way that preserves sanity. It works by applying specific mental models to define where one service ends and another begins. What matters here is that the success of your entire microservices journey depends on these initial lines. If you get the boundaries wrong, you'll end up with massive amounts of network traffic just to complete a single user action. A common failure mode in interviews is proposing a split based on technical layers, like putting all your database logic in one service and all your UI logic in another. That's a mistake because it forces every feature change to touch multiple services. Instead, we want to define boundaries using industry standard patterns like business capabilities or subdomains. Now, by mastering these patterns, you can justify your architectural choices to an interviewer by showing how your design minimizes cross-team coordination and maximizes the speed of feature delivery. It's about building for change, not just for the sake of being modern. To get decomposition right, we look at 4 core pillars: bounded contexts, business capabilities, data sovereignty, and organizational alignment. These pillars work together to ensure that each service is truly autonomous. Bounded contexts help us define the language of the service, while business capabilities ensure the service does something valuable for the company. Data sovereignty is the technical enforcement of those boundaries, and organizational alignment makes sure the teams can actually manage them. What matters here is that without these pillars, your architecture will likely crumble under the weight of its own complexity. I mean, the biggest failure mode here is ignoring the data. If you have 5 services all pointing to the same global database, you haven't actually decomposed anything. You've just made your system more fragile. So when you're explaining your strategy, always lean on these 4 concepts to show you're thinking about the full life cycle of the system, from the database schema all the way up to the team's communication patterns. You'll know you've hit the scaling wall when the monolith starts feeling like a liability rather than an asset. It works as a tipping point where the overhead of coordination outweighs the benefits of a shared code base. What matters here is that staying in a monolith too long leads to developer burnout and stagnant product growth. You see merge conflicts every day, and a single test failure in a module you don't even use can block your entire release. Now, the common failure mode here is premature decomposition. That's when a team moves to microservices before they actually have the scaling problems to justify the complexity. In an interview, you should be able to identify these specific pain points like deployment bottlenecks or resource contention as the valid triggers for a split. Drawing that first line is hard because it requires a deep understanding of which parts of the system are changing the fastest. If you can pinpoint the high churn areas and isolate them first, you've successfully navigated the first hurdle of the scaling wall. The core mission of decomposition isn't just about splitting code. It's about identifying autonomous boundaries that can evolve independently. It works by looking for areas of the system that have high internal cohesion but low external coupling. What matters here is that the goal is to allow a team to change their service's internal logic without needing permission from 3 other teams. A major failure mode is focusing too much on the technology stack instead of the business logic. If you split a service just to use a new programming language, you might be creating a boundary that doesn't actually align with how the business operates. This leads to chatty interfaces where services are constantly pinging each other for data. Well, in a system design interview, you want to show that you're prioritizing boundaries that reduce these dependencies. You're looking for seams in the logic where you can cut without leaving too many loose wires. True autonomy means a service can be deployed, scaled, and even rewritten without breaking the rest of the ecosystem. Domain-driven design, or DDD, gives us the concept of bounded contexts, which is arguably the most powerful tool for decomposition. It works by ensuring that a specific term or model has a single consistent meaning within a specific boundary. For example, the word product means something very different to a shipping service than it does to a marketing service. What matters here is that it prevents the God object problem, where one massive class tries to handle every single attribute in the entire company. The failure mode here is context leakage, where logic from one domain starts creeping into another because they share the same database tables or naming conventions. When that happens, your boundaries start to blur and you lose the benefits of microservices. So in an interview, explain how you'd use bounded context to encapsulate these models. You're basically creating a linguistic and logical wall that keeps each service focused on its specific job. This keeps the code clean and ensures that teams don't have to understand the entire universe to fix one small feature. One of the most practical ways to organize services is by business capabilities. This approach works by aligning your software with what the business actually does, like shipping, inventory, or billing. What matters here is that business functions are generally more stable than specific technical implementations. While the way you calculate tax might change, the fact that you need a billing function usually won't. A common failure mode is organizing by technical functions instead, like having a logging service or a validation service. This often leads to a nano service mess, where you have to jump through 5 different services just to complete one business action. When you're in an interview, try to map the system's requirements to these broad business categories. It shows you understand the big picture and aren't just focused on the code. By grouping related functions together, you reduce the need for cross-service communication and make the system much easier to reason about. It aligns the technical architecture with the organizational structure, which is a key principle for long-term maintainability. Functional decomposition takes the idea of business capabilities a step further by focusing on specific feature-based splits. It works by identifying distinct user-facing actions or technical workflows that can stand on their own. For example, in a streaming app, user profiles and video encoding are functionally very different. What matters here is that these different features often have very different scaling needs. You might need to scale your search feature to handle thousands of requests per second, while your account settings feature stays relatively quiet. If they're in the same service, you're forced to scale both together, which is a waste of resources. The failure mode here is over-fragmentation, where you split features so thinly that the overhead of managing the infrastructure exceeds the benefit of the split. In an interview, you'll want to justify a functional split by pointing to these different operational profiles. If one feature is CPU intensive and another is memory intensive, that's a perfect reason to split them. It allows for more efficient resource usage and much faster deployment cycles for the most critical features. If you remember one thing today, let it be this: data sovereignty is the bedrock of microservices. It works by ensuring that each service owns its own data schema and no other service can touch it directly. What matters here is that shared databases are the single biggest bottleneck in distributed systems. If service A and service B share a table, you can't change a column name in A without potentially breaking B. This creates a massive failure mode where your teams are once again locked in a high coordination cycle. You lose the ability to deploy independently. Now, in an interview, if you're asked how two services should communicate, never say they just read from the same database. That's a huge red flag. Instead, explain that they must communicate via well-defined APIs or events. Each service should treat its data store as a private implementation detail. This might feel like extra work, especially with data duplication, but it's the only way to ensure that your services can actually evolve and scale without bringing the whole system down. To implement data sovereignty, we use the database per service pattern. This works by giving every microservice its own private database, which could be an entirely different type of store depending on the needs of that service. For instance, your catalog might use a document store while your ledger uses a relational database. What matters here is that it allows you to pick the best tool for the job and ensures that schema changes are isolated. A primary failure mode is the distributed transaction nightmare. When you split your data, you can't easily use traditional SQL joins or transactions across services. If you try to force them, you'll end up with a slow, fragile system. In an interview, you should talk about how you'd handle this using eventual consistency or patterns like Sagas. You have to trade off that immediate consistency for the freedom of independent scaling. It's a classic architectural trade-off. By keeping data private, you prevent backdoor dependencies that would otherwise turn your clean microservices back into a tangled mess over time. You can't talk about decomposition without mentioning Conway's law. It basically states that a system's architecture will eventually mirror the communication structure of the organization that built it. It works as a sort of gravitational pull. If you've two teams that don't talk, they'll likely build two services that are hard to integrate. What matters here is that if your service boundaries don't match your team boundaries, you're gonna have constant friction. A common failure mode is designing a perfect architecture on paper that requires 5 different teams to collaborate on every single release. That's a recipe for disaster. In an interview, show that you're thinking about the human side of the system. You might suggest the inverse Conway maneuver, where you intentionally structure your teams the way you want your code to look. If you want independent services, you need independent cross-functional teams. This alignment reduces the cognitive load on developers and allows for much faster delivery. It's about making the path of least resistance lead to a good architecture rather than fighting against the org chart. Finding the sweet spot for service granularity is a constant struggle. On one end, you've coarse-grained services that might be too large and slow. On the other, you've fine-grained nano services that are so small they become an operational headache. This works by evaluating the trade-offs between agility and overhead. What matters here is that every new service adds complexity in monitoring, networking, and deployment. A massive failure mode is splitting services so small that a single business transaction requires 10 network hops. This introduces latency and creates many more points of failure. In a system design interview, you should argue for right sizing. Start with slightly larger services and only decompose further when you have a clear reason, like a specific scaling bottleneck or a team that's getting too big to manage one code base. You're looking for that balance where each service is small enough to be understood by one person but large enough to perform a meaningful business function without constant outside help. It's about being pragmatic, not dogmatic about service size. The ultimate goal of all these strategies is minimizing dependencies to achieve low coupling. This works by creating services that can be deployed, scaled, and tested in total isolation. What matters here is that the more your services depend on each other, the more you risk a cascading failure. That's a failure mode where one small service goes down and takes the entire system with it because everything is synchronously linked. To avoid this, you should lean towards asynchronous communication and event-driven patterns. In an interview, explain how using a message queue or an event bus can decouple your services. Instead of service A calling service B and waiting for a response, service A just emits an event and moves on. This makes the system much more resilient and allows services to handle spikes in traffic independently. Now you also have to watch out for logical coupling, where services still need to know too much about each other's internals. Keep your interfaces simple and your events focused on what happened rather than what to do next. That's how you build a truly robust distributed system. Let's look at a classic interview case, decomposing an e-commerce giant. If you're asked this, don't just start listing services. Start by identifying the bounded contexts. You'd likely have a catalog service for product info, a cart service for temporary storage, and a payment service for transactions. What matters here is that each of these has different requirements. Catalog is read-heavy, while payment needs extreme consistency. A failure mode here is putting inventory and catalog together just because they both deal with products. They are actually different. Inventory cares about warehouse counts, while catalog cares about marketing descriptions. By splitting them, you allow the warehouse team to update stock without affecting the customer-facing search. In your answer, emphasize that each service should own its own database and communicate via events, like order placed, to keep things decoupled. This shows you can apply DDD and data sovereignty to a real-world problem. It demonstrates that you're thinking about performance, team boundaries, and system reliability all at once. That's exactly what interviewers want to see in a senior-level candidate. We've just covered the heavy lifting of breaking down a monolith. The core mission here isn't just splitting up code. It's about finding those autonomous boundaries that actually let your teams move fast. We walked through 3 main strategies: using DDD's bounded contexts to keep your models clean, aligning with business capabilities like inventory or billing, and applying functional decomposition for specific features. The absolute non-negotiable we emphasized is data sovereignty. If you're still sharing a database, well, you're just building a distributed monolith. In a system design interview, you've got to demonstrate that you understand how Conway's law influences these boundaries. It's all about minimizing coupling so each service can evolve independently. Now you've got the mental model to justify exactly where those lines should be drawn and why. That wraps up our look at service decomposition. In an interview, don't just pick a pattern at random. You've got to justify your boundaries using 3 main perspectives: business capabilities, domain-driven design, and team alignment via Conway's law. Explain how you're balancing granularity to avoid the overhead of nanoservices while dodging the pitfalls of a distributed monolith. If this helped you sharpen your architectural thinking, subscribe to the channel and check out the full course details in the description. In the next episode, we'll discuss API composition, where we'll discuss situation, core understanding, definition. Best of luck with your system design prep. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 15 of the System Engineering series, and today we will explore API composition in a way that helps you prepare for system engineering interviews on this topic. In a microservices world, data often ends up fragmented, so knowing how to aggregate those responses is critical for system performance. We'll look at how moving from chatty client requests to chunky unified responses can slash latency for your users. Well, mastering these trade-offs shows interviewers you really understand how to build efficient, scalable front ends. This lesson opens with a look at the fragmented front-end nightmare, where we'll see exactly why hitting multiple services like user, order, and catalog from a mobile device is such a performance killer. We are going to define the API composition pattern and explain how a specialized aggregator service takes over the job of joining data. Well, it's basically doing what a monolithic database used to do. You'll understand the shift from chatty to chunky communication and why parallelizing requests is the only way to keep your tail latency from blowing up. Since systems eventually fail, we'll cover how to handle partial responses and use fallbacks so your UI stays functional even when a downstream service goes dark. We'll also dive into caching strategies and touch on GraphQL as a modern alternative for aggregation. Throughout the session, we'll frame things for the interview, focusing on the trade-offs between service autonomy and network efficiency. By the end, you'll be ready to justify and build a resilient aggregation layer for any microservices architecture. To really grasp why we are doing this, let's look at a high-scale production scenario. Imagine an e-commerce platform processing thousands of requests per second. As the system scales, the team splits the monolith into specialized services to allow for independent deployments. Suddenly, a simple product page needs data from 5 different databases. If you don't use API composition, you're offloading the architectural complexity to the user's device, which is a recipe for disaster. What matters here is that at scale, even a small increase in network chattiness leads to exponentially higher failure rates and customer churn. The common failure mode here is death by 1,000 cuts, where no single service is down, but the sheer number of network round trips makes the application feel unusable. In an interview, you want to frame this situation as a balance between backend modularity and front-end performance. You're trying to protect the client from the internal complexity of your infrastructure while maintaining the benefits of a decoupled service architecture that allows teams to move fast. In episode 15, we are focusing on mastering data aggregation within microservices to build high-performance user interfaces. The core of this approach works by creating a specialized layer that abstracts the complexity of the backend. It matters because it allows the front end to stay lean and focused on presentation rather than data orchestration. However, if this layer is poorly designed, it becomes a massive single point of failure for your entire application. An interviewer will look for your awareness of this bottleneck. You need to demonstrate that you know how to aggregate data without creating a new monolith in the middle of your stack. We'll explore how to handle the data flow from multiple microservices and merge them into a single clean response. The goal is to provide the user with a seamless experience while keeping the backend services decoupled and autonomous. This balance is tricky, but it's what separates a senior engineer from a junior one. We'll look at the specific strategies to ensure your aggregator is both fast and resilient. Imagine you're building a modern mobile app and designing the checkout screen. To render this single page, the app needs data from 3 specific sources: the user service for the shipping address, the order service for the current cart, and the catalog service for product images. Without an aggregation strategy, the mobile client is forced to manage 3 separate network requests. On a high-latency mobile network, this is a total nightmare. Each request involves a separate TCP handshake and TLS negotiation, which drains the device battery and makes the UI feel sluggish. This fragmentation is what we call the front-end nightmare. It doesn't just hurt the user experience, it also makes the front-end code extremely complex because developers have to coordinate these multiple calls and handle different error states for each one. If one service is slow, the whole page hangs. Understanding this bottleneck is crucial for your interviews because it highlights why we can't just leave data fetching to the client in a distributed system. We have to provide a unified entry point. At its heart, API composition is the act of gathering data from multiple upstream services and merging them into a single unified response body. It works by having an intermediate service take a single incoming request, fan it out to various microservices, and then stitch the results back together. What matters here is that it hides the complexity of your internal architecture from the consumer. From the client's perspective, there's just one endpoint and one JSON object. However, the failure modes here are significant. If your aggregator isn't designed to handle asynchronous processing, it will block on every request, leading to massive latency spikes. In an interview, you should emphasize that the aggregator's job is to fetch data, and more specifically, to transform and filter it so the client only gets exactly what it needs. This reduces the payload size and further improves performance. We are moving the heavy lifting of data joining from the database or the client into a specialized service layer that is optimized for this specific task. Technically, we define API composition as a structural pattern, where a specialized service acts as a join point. In a monolith, you'd just run a SQL join, but in microservices, your data lives in different databases. The aggregator performs this join logic in memory. It matters because it preserves the principle of service autonomy. Each service still owns its own data and database, yet the system can still present a unified view. The failure mode to watch for here is the logic trap. If you start putting too much business logic into this join point, you've accidentally created a distributed monolith. You want to keep the aggregator thin and focused purely on data transformation and orchestration. In an interview, explain that this pattern is the primary way we solve the data scattering problem in microservices. It allows each team to manage their own domain while still contributing to a cohesive user experience. It's about maintaining the architectural purity of your services without sacrificing the performance and simplicity the front end requires to be effective. The aggregation layer is a middle-tier service that handles three major responsibilities: service discovery, request parallelization, and data transformation. It works as a hub and spoke model where the aggregator is the hub and your microservices are the spokes. What matters here is that it centralizes the logic for talking to various backend components, allowing for better security, logging, and monitoring. However, the failure mode is that the aggregator can become a performance bottleneck if it isn't horizontally scalable. Because it handles every request, it must be lightweight. If it's doing too much computation or waiting synchronously for responses, the entire system slows down. In an interview, highlight that the aggregator needs to be stateless so you can spin up multiple instances to handle high traffic. You're effectively building a specialized gateway that understands your data models. By centralizing these concerns, you simplify the life of the front-end developer and ensure that your backend services remain isolated from the direct demands of the client, which is essential for maintaining a clean and scalable architecture. When we talk about performance, we are comparing chatty calls to chunky calls. Multiple small calls from a mobile device are chatty, leading to poor performance because of the expensive overhead of mobile connections. A single aggregated chunky call minimizes this handshake overhead. It works by reducing the number of round trips over the high latency air interface. What matters here is that mobile users are incredibly sensitive to latency. Even a few hundred milliseconds can lead to app abandonment. The failure mode here is that a chunky response can sometimes become too large, leading to long download times if you're not careful about filtering the data. In an interview, you should explain that the aggregator's role is to optimize this balance. You want to bundle enough data to avoid multiple trips, but not so much that the payload becomes a burden. This trade-off is a classic system design question. You're trading a bit of backend complexity for a massive gain in user perceived performance and battery efficiency on the device. It's a strategic decision to move the complexity where it's easiest to manage. Now, we have to talk about the long tail of latency, which is a major bottleneck in API composition. When your aggregator fires off parallel requests to multiple upstream services, the total response time is strictly dictated by the slowest service in the group. If your user and catalog services respond in 50 milliseconds, but the order service takes 500, your user is waiting for the full half second regardless. What matters here is that parallel execution isn't just a nice feature. It's a requirement. If you process these calls sequentially, the latencies add up and your performance collapses. In an interview, mention that this fan-out pattern introduces the risk of cascading delays. If one service starts lagging due to a noisy neighbor or a database lock, it can tie up resources on your aggregator. You'll need to implement strict timeouts and perhaps even hedging to prevent one slow dependency from dragging down the entire user experience. Managing this timing is the difference between a snappy interface and one that feels broken or unresponsive under load. To further reduce latency, the aggregator can cache the final result. This works by storing the merged response in a fast in-memory store like Redis. What matters here is that it avoids repeated expensive calls to upstream services for data that rarely changes, like product descriptions or user profiles. However, the failure mode here is cache inconsistency. If the catalog service updates a price, but the aggregator is still serving the old cached response, you have a major business problem. In an interview, you'll need to discuss cache invalidation strategies, such as TTLs or event-driven updates. You're basically creating a layer of protection for your backend services, reducing their load while giving users sub-millisecond response times for common queries. But remember, caching adds complexity. You have to decide if the performance gain is worth the risk of serving stale data. A strong answer will weigh the benefits of speed against the operational overhead of keeping that cache accurate. It's about finding the right balance for your specific use case and data volatility. Handling partial failures is where your architecture is truly tested. What happens if the order service is down but user and catalog are up? The aggregator must decide whether to fail the whole request or return a partial response with empty fields. What matters here is that a totally broken page is much worse than a page missing one small piece of data. This failure mode is common in distributed systems. If you don't design for it, one minor service outage can take down your entire front end. In an interview, you should explain how to design nullable fields or default values in your API contract. This allows the UI to render what it can, perhaps showing a temporary error message in the order section while still letting the user see their profile and the product details. You're building for graceful degradation. It's about being resilient to the inevitable hiccups of a network-based architecture. Showing that you've thought through these partial success scenarios signals to an interviewer that you understand the messy reality of production environments. To handle those failures we just talked about, you need to implement resilience patterns like circuit breakers and fallbacks. A circuit breaker works by tracking the failure rate of an upstream service and tripping if it exceeds a threshold, preventing further calls that would only fail and waste resources. What matters here is that it gives the struggling service room to recover and prevents your aggregator from hanging. When the circuit is open, you provide a fallback, which is often a default or placeholder value. For example, if the recommendation service is down, you might fall back to a hard-coded list of popular items. The failure mode to avoid here is a fallback that is itself slow or unreliable. In an interview, you should explain that these patterns ensure the UI remains functional and the system stays stable, even when parts of the backend are on fire. It's a proactive way to manage distributed complexity. By using these three tools, timeouts, circuit breakers, and fallbacks, you create a robust aggregation layer that can survive the unpredictable nature of microservices. An increasingly popular alternative to custom aggregation services is GraphQL. It works by allowing the client to define exactly what data it needs in a single query. The GraphQL server then acts as the aggregator, resolving data from multiple services based on that schema. What matters here is that it eliminates the overfetching and underfetching problems common with traditional REST aggregators. However, GraphQL has its own failure modes. It can be difficult to cache effectively compared to REST, and complex nested queries can easily overload your backend if you don't implement query depth limiting or cost analysis. In an interview, you might be asked to compare a custom aggregator with a GraphQL gateway. Your answer should focus on the trade-off between the flexibility GraphQL gives front-end teams and the increased complexity it adds to the backend infrastructure. It's a powerful tool for composition, but it requires careful management to ensure that a single deep query doesn't bring your whole microservices ecosystem to its knees. It's about choosing the right tool for your team's specific needs and scale. In a system design interview, expect questions on why you chose API composition over a database join or client-side logic. You need to focus on three key pillars: service autonomy, network efficiency for mobile, and team decoupling. Explain that it works by moving the join logic to a layer that can be optimized for the network. It matters because it allows backend teams to change their data schemas without breaking the mobile app, as the aggregator provides a stable abstraction. The failure mode to highlight is the risk of the aggregator becoming a bottleneck or a dumping ground for business logic. A strong answer shows you understand that this isn't just about making things easy. It's a strategic architectural choice to manage the trade-off between distributed system benefits and the realities of network latency. You're demonstrating that you can think about the system as a whole, from the database all the way to the user screen. Being able to justify these decisions with clear reasoning on performance and maintenance is what interviewers are looking for. To wrap up, let's look at some best practices for API composition. First, keep the logic in the aggregator minimal. It should be for orchestration, not business rules. Second, use asynchronous non-blocking calls wherever possible to ensure the aggregator doesn't waste resources waiting for I/O. Third, ensure the aggregator itself is horizontally scalable so it doesn't become a single point of failure. These practices work by keeping the layer lean and responsive. What matters here is that an inefficient aggregator can negate all the benefits of your microservices architecture. A common failure mode is forgetting to implement proper observability. Without good logging and tracing, it's impossible to tell which upstream service is causing a delay in the aggregated response. In an interview, emphasize that you'd include distributed tracing to monitor the health of the entire request chain. By following these three principles, you build an aggregation layer that is fast, resilient, and maintainable. It's about creating a production-grade system that can handle the complexities of real-world traffic and service dependencies without breaking a sweat. Thank you for joining this deep dive into API composition. You're now equipped to design and implement these patterns in your own microservices journey. We've seen how it works as a vital join point for distributed data and why it matters for maintaining a high-performance user experience, especially on mobile. Remember that while this pattern solves the fragmented front-end nightmare, you must always be vigilant about failure modes like cascading latencies and the trap of putting business logic in the wrong place. As you go into your next system design interview, keep the trade-offs of parallel execution, caching, and partial failures at the front of your mind. These are the details that show you've built real systems and understand the consequences of your architectural choices. Being able to explain the why behind the what is what will set you apart. Use these tools to build systems that are not only modular but also incredibly resilient and fast. I'm excited to see how you apply these concepts to your own projects and interview challenges. So we've just seen how API composition transforms a fragmented microservices backend into a clean, unified response. Think of it as moving the join logic from the database into a specialized aggregation layer. In an interview, you'll want to justify this by focusing on the performance shift from chatty to chunky requests. It's about minimizing those expensive mobile handshakes. We covered 3 critical implementation details you've got to get right: parallelizing calls to beat the slowest service bottleneck, implementing caching to save on latency, and gracefully handling partial failures. Whether you use a standard aggregator, a BFF, or GraphQL, the goal is shielding the client from internal complexity. Mastering these trade-offs shows you can balance architectural decoupling with a great user experience. That's a wrap on API composition. In your next system design interview, be ready to defend why you'd pick an aggregator over a database join. It's really about prioritizing service autonomy and saving the client from massive network overhead. You'll stand out by explaining how you'd manage partial failures with circuit breakers or sensible defaults. We've looked at how this pattern scales and where GraphQL fits in, so you're ready to tackle these trade-offs head-on. Subscribe to the channel for more technical deep dives, and you can find the full course details right in the description. In the next episode, we will discuss Backend for Frontend, where we'll discuss situation, core understanding, definition. Happy designing! Welcome to Systemic Stack. My name is Kabir Anand. This is episode 16 of the System Engineering series, and today we'll explore Backend for Frontend (BFF) in a way that helps you prepare for system engineering interviews on this topic. We've to address unique requirements for 3 main platforms: mobile, web, and tablets. So we'll look at how designing dedicated backends for each optimizes payloads. Explaining how these layers prevent overfetching is a solid way to show interviewers you understand the practical side of building high-quality multi-platform architectures. It starts by tackling the client diversity challenge, where you'll see why mobile, web, and tablet apps can't just share the same data shapes without crashing performance. From there, we'll break down the core definition of a backend for frontend or BFF and how these dedicated translation layers give frontend teams total ownership over their own API orchestration. Now, since performance is everything, we're going to compare the high-speed requirements of mobile against the SEO-focused needs of web clients. You will learn how to aggregate responses from multiple services into a single round trip, effectively killing off overfetching and high latency. We'll also examine the trade-offs, specifically how to balance independent team lifecycles against the risk of code duplication across different platforms. Since this is a favorite topic in system design interviews, we'll finish with the specific signals you need to look for to justify choosing a BFF over a shared API. By the end, you'll understand how to design client-specific backends that keep your applications fast and your teams unblocked. Think about a high-growth startup that started with a simple web app. Everything was fine with one REST API. But then they launched an iOS app, an Android app, and a tablet version. Suddenly, the mobile team is complaining that the API returns way too much data, which kills the battery life on older phones. Meanwhile, the web team wants more metadata for SEO that the mobile team doesn't care about at all. This is the classic engineering situation where a single generic API starts to fail under the weight of conflicting requirements. It's a massive constraint because every time you want to change a field for the web, you risk breaking the mobile app. In a production context, this leads to slower release cycles and a lot of finger pointing between teams. Understanding this tension is vital for interviews because it shows you recognize that architecture isn't just about code, it's about team autonomy and handling the physical constraints of different devices. When you're at scale, you can't just keep adding if statements to your main API responses. At its heart, the backend for Frontend pattern is all about mastering client-specific API orchestration. Instead of forcing every device to consume the same general-purpose API, we create a bespoke layer for each specific platform. Now it works by acting as a specialized proxy that speaks the exact language of the front end it serves. What matters here immensely in modern multi-platform architectures because it decouples the evolution of your UI from the evolution of your core business logic. If you don't have this, your backend becomes a rigid monolith that's scared to change because it doesn't know which of the 10 different clients might break. A major failure mode here is treating the BFF as just another layer of dumb pass-through code. If it doesn't actually add value through orchestration or data shaping, you've just added latency for no reason. In an interview, you want to emphasize that the BFF is a strategic choice to give front-end teams more control over their own data needs while keeping the core services clean and focused on the domain. We have to talk about the reality of client diversity because that's where the pressure starts. You've got mobile phones, desktop browsers, and tablets, and they all have very different needs. Mobile devices might be on a shaky 3G connection with limited processing power, so they need small, snappy payloads. On the flip side, a desktop web client usually has a big screen and a reliable fiber connection, so it can handle much richer data structures. If you ignore these differences, your mobile users end up frustrated by slow load times and your web developers get annoyed by having to make 5 different API calls just to render a single page. What matters here is that performance means something different to every device. A failure mode here is assuming a responsive design on the front end is enough. It's not. If the underlying data shape is still optimized for a different device, the user experience will suffer regardless of the CSS. In an interview, highlighting these 3 constraints, display size, processing power, and network reliability, proves you're thinking about the full system. The core shift here is moving away from the idea of a single monolithic API and toward backends tailored specifically to the consumer's needs. Well, one simple way to picture this is this. In the old way, the backend team defined the contract and every frontend team just had to deal with it. With a BFF approach, the frontend team actually has a say in how the data is served. It works by creating a tight coupling between the specific UI and its corresponding backend helper. A practical point here is that it solves the lowest common denominator problem, where the API only provides what every client needs, leaving everyone slightly unsatisfied. If you fail to implement this correctly, you might end up with BFF sprawl, where you've dozens of micro backends that are hard to monitor. In an interview, you should explain that the shift is about aligning your architecture with your organizational structure. When the team building the iOS app also manages the iOS BFF, they can move much faster. It's a fundamental change in how we think about the boundary. Let's get precise with the definition. A BFF is essentially a translation layer that sits between the client and your downstream services. It's usually owned and maintained by the same team that builds the frontend for that specific platform. So, if you're on the Android team, you own the Android BFF. It works by taking the complex, granular responses from your microservices and massaging them into exactly what the Android app needs to see. What matters here is that it creates a clear boundary. The core services focus on business rules, while the BFF focuses on user interface requirements. A common failure mode is letting business logic leak into the BFF. If you start putting your pricing algorithms or user registration rules in the BFF instead of the core services, you'll end up with inconsistent behavior across different platforms. In an interview, make sure to point out that the BFF is an orchestration and translation layer, not a replacement for your core domain services. It's the glue that makes the front-end to back-end communication seamless. The primary purpose here is optimizing the user experience. We want the UI to remain incredibly responsive, and that means the data it receives should be ready for immediate rendering without a ton of heavy client-side processing. Now it works by offloading the hard work of data joining and filtering from the device to the server. What matters here is that mobile CPUs are optimized for power efficiency, not for passing massive JSON blobs or performing complex data transformations. If the phone has to spend 3 seconds just cleaning up the data it got from the API, the app is gonna feel sluggish. A failure mode to watch for is when the BFF becomes too heavy itself, adding so much processing time that it cancels out the network gains. You're aiming for that sweet spot where the BFF does just enough to make the client's life easy. In a system design interview, emphasize that you're optimizing for the perceived performance of the end user. It's about making the app feel instant by delivering a perfectly shaped payload. When we look at mobile-specific requirements, efficiency and speed are the names of the game. Mobile apps really need 3 things: minimal payloads to save on cellular data, simplified error states so the UI doesn't crash on a bad connection, and specialized logic for things like push notifications. It works by having the BFF filter out all the extra fields that a desktop browser might need, but a 6-inch screen doesn't. What matters here is that every extra kilobyte of data over a cellular network increases the chance of a timeout or a failed request. If you don't optimize this, your app's retention rates will drop because users hate apps that eat their data plans or drain their batteries. A failure mode here is failing to account for different mobile versions. Sometimes an older version of the app needs a different data shape than the latest one. The BFF can handle that versioning logic so the core services don't have to. In an interview, showing you understand these mobile-first constraints like data caps and unreliable latency proves you're designing for the real world. Now, let's pivot to web requirements, which are often the opposite of mobile. Web frontends usually deal with larger payloads because they've more screen real estate to fill. They also have unique needs like SEO metadata generation and managing complex state across multiple browser sessions. The BFF for web works by gathering all the data needed for a server-side rendered or hydrated page, ensuring the user sees content as quickly as possible. What matters here is that if you rely entirely on the client to fetch data after the page loads, your SEO will suffer and users will see a bunch of loading spinners. A common failure mode is treating the web BFF exactly like the mobile one, which results in underfetching. If the web client has to make 10 more calls because the BFF was too aggressive with filtering, you've ruined the performance. In an interview, explain that the web BFF is often about balancing richness with initial load speed. You're trying to provide enough data for a full experience while keeping the time to interactive low. Aggregation is probably the most hands-on part of what a BFF does. It acts as an orchestrator, calling multiple downstream microservices and then stitching those results into a single, clean response. Instead of the client making one call to the user service, another to the order service, and a third to the recommendation service, it just makes one call to the BFF. It works by managing all those parallel backend requests and handling any partial failures gracefully. What matters here is that it drastically reduces the chattiness of your application. If a client is on a high latency network, 3 round trips could take seconds, whereas 1 round trip to the BFF, which then talks to other services over a super fast internal network, takes milliseconds. A failure mode to be careful of is the fan-out problem. If the BFF calls too many services at once without proper timeouts, one slow service can drag down the entire response. In an interview, talk about using patterns like parallel fetching and circuit breakers within the BFF to keep things robust. Let's talk about performance specifically regarding overfetching. By filtering data at the BFF layer, we prevent the client from receiving megabytes of unnecessary fields. It works by having the BFF act as a view model generator. It only picks the 5 fields the UI needs out of the 50 available in the database. What matters here is that it saves significant bandwidth and battery life, especially for users on limited plans or older hardware. Think about a user object that has history, preferences, and security logs. The mobile app probably only needs the user's name and avatar. If you send the whole object, you're just wasting resources. A failure mode here is overfiltering, where you remove something that the frontend actually needed, forcing a second API call. That completely defeats the purpose. In a design interview, you can frame this as a data shape optimization problem. You're showing that you're mindful of the cost of data, both in terms of network transit and the memory footprint on the client device. Another huge performance win is optimizing network latency. Moving orchestration to the backend reduces the number of round trips between the client and the server from many down to just one. Now it works because the communication between the BFF and the downstream microservices happens over a low latency internal network, which is much faster than the public internet. What matters here is that round trip time, or RTT, is often the biggest bottleneck in mobile performance. Even if you've got 5G, the physical distance to the server still introduces lag. If the client has to wait for 3 sequential requests to finish, the lag compounds. A failure mode is not implementing proper caching at the BFF level. If every request to the BFF results in a full refetch of all downstream data, you might actually increase the total time if the BFF itself is slow. In an interview, use this to explain how you're collapsing the network cost. You're moving the complexity from the unreliable edge to the reliable core. One of the best things about the BFF pattern is how it improves maintainability through separate life cycles. Each BFF evolves at the same pace as its specific front end. This works by allowing the mobile team to deploy a new version of their BFF with a new field without having to wait for the web team or the core API team to approve the change. What matters here is that it removes a massive deployment bottleneck. In a typical microservices setup, the shared general API becomes a point of contention where everyone is fighting for their changes to be prioritized. With a BFF, you've true team autonomy. A failure mode to watch out for is ownership confusion. If the backend team is still the one maintaining the BFF, you haven't really solved the bottleneck. You've just added another layer of code they have to manage. In an interview, highlight this as a DevOps or team topology benefit. You're aligning the software architecture with the way teams actually work, leading to faster feature delivery. We've got to address the elephant in the room: code duplication. This is a major challenge because common logic like authentication, logging, or rate limiting might end up being duplicated across multiple BFFs. If you have a web BFF, an iOS BFF, and an Android BFF, you might find yourself writing the same auth check 3 times. That's a huge failure mode because if the auth logic changes, you've got to update it in 3 places, and if you missed one, you've got a security hole. It works best when you handle these cross-cutting concerns via shared libraries, sidecars, or an API gateway that sits in front of all your BFFs. What matters here is that it balances the need for client-specific logic with the need for system-wide consistency. In an interview, don't just say BFFs are perfect. Acknowledge this trade-off. A strong candidate will say they'd use a BFF for UI-specific data shaping, but pull shared security logic into a common library or service mesh to avoid drift. When you're in an interview, the interviewer is really looking for the why. You should choose a BFF when team ownership of the API is critical or when the payload mismatch between clients is seriously hurting performance. It's not a default choice for a tiny app with one developer. That would be over-engineering. You should explain that you're choosing it to solve specific bottlenecks like high latency, overfetching, or slow release cycles caused by a shared API. What matters here is that it shows you can weigh the complexity cost against the performance benefit. A failure mode in an interview answer is recommending a BFF without mentioning the overhead of running and monitoring extra services. You need to show that you've considered the operational tax. So if an interviewer asks if a BFF is always better than a single GraphQL API, you can talk about how GraphQL solves overfetching but might not solve the team autonomy or custom orchestration issues as cleanly. It's about providing a nuanced answer. For our final implementation takeaway, the best advice is to start simple. You might start with a shared API, but you should move to a BFF the moment your front-end needs begin to outpace your backend's flexibility. It works by identifying that inflection point where the cost of managing one giant API exceeds the cost of running multiple small ones. What matters here is that it prevents you from building a premature abstraction that just adds unnecessary layers to a small system. However, once you hit scale, the BFF becomes a lifesaver for keeping your core services clean. A failure mode is waiting too long to make this switch, leading to a God API that no one is brave enough to refactor. In your final interview thoughts, emphasize that architecture is evolutionary. You're not just picking a pattern and sticking to it forever. You're choosing the right tool for the current stage of the product's growth. By showing that you understand the life cycle of a system, you're signaling that you're a senior level engineer. So let's bring it all together. We've seen how the one-size-fits-all API approach usually falls apart when you're dealing with the unique constraints of mobile, web, and tablet clients. The BFF pattern solves this by creating a dedicated translation layer for each specific platform. We covered 3 core functions: aggregating multiple downstream services into one response, optimizing payloads to prevent overfetching, and tailoring logic like push notifications or SEO to what the client actually needs. In a system design interview, you'll want to justify this choice by highlighting how it decouples front-end requirements from back-end service evolutions. Sure, there's a trade-off with some code duplication across your BFFs, but the real win is a significantly faster, more responsive user experience. It puts data control right where it belongs, with the teams building the UI. Well, that brings us to the end of our look at the backend for front-end pattern. In your next interview, justify using a BFF by focusing on how it handles three distinct client needs: mobile, web, and tablet. It's really about two core benefits, which are reducing network latency and enabling team autonomy. Showing you understand the trade-off between code duplication and client-specific optimization is exactly what interviewers want to hear. Subscribe for more architecture breakdowns and check the description for the full course details. In the next episode, we'll discuss circuit breaker pattern, where we'll discuss situation, core understanding, purpose. Thanks for watching and good luck with your studies. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 17 of the System Engineering series, and today we'll explore circuit breaker pattern in a way that helps you prepare for system engineering interviews on this topic. Understanding how to stop a slow dependency from crashing your whole architecture is a major signal for interviewers. We'll break down the three states: closed, open, and half open, to see how failing fast prevents cascading failures. Mastering this logic proves you know how to protect system resources when external services start to struggle. We begin with the core dangers of downstream latency and how it causes those nasty cascading failures that take down entire systems. You will see how isolating a single faulty component protects your memory and thread pools from exhaustion, which is a major talking point in system design interviews. Now, the heart of this lesson focuses on the three specific states: closed, open, and half open. We look at how these work together to monitor health and test for recovery without overloading your services. Well, we are also going to explore how to set up detection thresholds and fallback mechanisms, ensuring your application stays responsive even when a dependency is struggling. Then we'll cover the tricky business of integrating breakers with retries and handling those flaky external APIs that every production system eventually hits. We'll wrap things up by weighing the trade-offs between latency and availability, giving you a sharp perspective on when to prioritize a fail-fast approach. By the end, you'll understand how to build a resilient architecture that doesn't buckle under pressure. Imagine you're running a massive e-commerce platform during a flash sale. Traffic is spiking, and suddenly your recommendation service starts lagging because its database is under heavy load. In a naive system, every incoming request for the homepage waits for that recommendation service. Threads start piling up, memory usage climbs, and eventually your entire front end crashes. The problem isn't that the homepage is broken, but that it's waiting for something. That's it. This is the classic scenario where a circuit breaker is non-negotiable. You're dealing with high-scale constraints where a few hundred milliseconds of latency can snowball into a total outage within seconds. The real failure mode here isn't just the slow service, it's the resource exhaustion in the calling service. If you can't isolate that failure, you're essentially letting one weak link pull down the whole chain. We need a way to detect this pressure early and cut the connection before the damage spreads to the rest of your infrastructure. At its heart, the circuit breaker is the ultimate safety switch for distributed systems. You can think of it as a proxy that wraps a protected function call. Its job is to monitor for failures, and when things get too shaky, stop the calls from even reaching the struggling service. This is a fundamental concept for high-load environments because it moves us away from the hope-based strategy of just keep trying towards a more proactive fail-fast mentality. In an interview, you'll want to highlight that this goes beyond simple error handling and focuses on traffic management and system-wide health. If you don't use this, you're essentially gambling that your dependencies will always be fast. But we know that networks are unreliable and services get overwhelmed. By mastering this pattern, you're showing that you understand how to design for the unhappy path just as much as the happy path. It's about building a system that can take a punch and keep on standing. Let's talk about the silent killer, downstream latency. It's actually much worse than a service just crashing and returning an immediate error. When a dependency is slow, your upstream service keeps its threads open while it waits. In a high-traffic environment, those threads are a precious, finite resource. If the downstream service takes 5 seconds to respond instead of 50 milliseconds, your thread pool will saturate almost instantly. Once those threads are gone, your service can't handle new requests, even for features that have nothing to do with the failing dependency. This is how a small slowdown in a non-critical service leads to a total system crash. The failure mode here is resource starvation. Without a circuit breaker, you're basically letting a slow dependency dictate the uptime of your entire stack. In an interview, explaining this specific chain reaction shows you understand how bottlenecks actually propagate through a distributed architecture. It's not just that the UI is slow, it's that the backend is literally choking to death. The magic of the circuit breaker is how it prevents cascading failures. It essentially creates a fire break in your architecture. When the breaker trips, it halts the ripple effect by isolating the faulty component immediately. Instead of letting every request wait and fail, the breaker says no right at the gate. This allows the rest of your system to stay healthy and continue serving traffic for other features. Without this isolation, a failure in a minor microservice like a weather widget or a profile picture loader could potentially take down your entire checkout flow. In an interview, you'll want to emphasize that isolation is the key to availability. You're trading off a single feature's functionality to save the entire platform's life. The failure mode we're avoiding is the thundering herd, where a recovering service is immediately blasted with all the queued up requests. By breaking the circuit, we give that failing service the breathing room it needs to actually recover instead of being kicked while it's down. Protecting your system's core resources is really what this is all about. By failing fast, we preserve CPU cycles, memory, and especially those critical thread pools. When the circuit is open, we're not wasting cycles trying to talk to a service we know is down. We're also not letting memory fill up with request objects that are just gonna time out anyway. Think of it as guarding the vitals of your application. If one weak link breaks, the circuit breaker ensures it doesn't break the entire chain. In a technical discussion, this is a great place to talk about bulkheading. Just like a ship has compartments to prevent a single leak from sinking the whole vessel, circuit breakers create boundaries. If you don't have these, your services are too tightly coupled, and a failure in one becomes a failure in all. Showing you prioritize resource management demonstrates a deep understanding of operational stability. It's about being a responsible steward of the infrastructure you're running, ensuring the system stays lean. Now, let's look at the first of the three primary states, the closed state. This is the normal operating mode. In this state, requests pass through freely to the dependency and everything looks like business as usual. However, behind the scenes, the breaker is constantly monitoring. It's looking at error rates, success counts, and latency spikes over a specific window of time. If the error rate stays below a certain threshold, the circuit stays closed. But don't let the normal name fool you. This is where the most important telemetry happens. The failure mode here is often misconfiguration. If your thresholds are too sensitive, you might trip the breaker on a single blip. If they are too loose, you won't trip it until it's too late. In an interview, you should mention that the closed state is active, not passive. It's a monitoring phase where the system is gathering the evidence it needs to make a decision. Getting these metrics right is the difference between a resilient system and one that's constantly flickering. When things go wrong and that error threshold is finally hit, we move into the open state. This is the emergency mode. In this state, every single request to the dependency is failed immediately. The breaker doesn't even try to reach the network. This is the essence of failing fast. By rejecting calls instantly, we stop the resource drain on our own system and stop putting pressure on the downstream service. It's a bold move because it means that feature is officially down, but it's a controlled failure. The failure mode to watch for here is the lack of a proper fallback. If you just return a 500 error to the user, you're missing the point. You want to have a plan for what happens when the circuit is open. In an interview, point out that choosing to stay in the open state is a strategic move to protect the system. By intentionally cutting the line, you prevent a much larger catastrophe from happening while keeping resources free. After a set timeout, the breaker moves into the half-open state. This is essentially a probationary period. The system isn't quite sure if the dependency is healthy yet, so it allows a small, limited number of test requests to go through. It's like gingerly sticking a toe in the water to see if it's still freezing. If these trial requests succeed, the breaker assumes the service has recovered and transitions back to closed. If they fail, it immediately trips back to open and starts the timer again. This state is critical because it prevents that thundering herd problem I mentioned earlier. If we went straight from open to closed, a service that's just barely coming back online would be instantly crushed by a massive wave of traffic. In an interview, this is a sophisticated point to make. It shows you understand the nuances of service recovery, and by a gradual transition is safer than an all-or-nothing approach. It's about being smart and cautious rather than just aggressive with traffic. Configuring your failure detection thresholds is where the theory meets the real world. You have to decide exactly when the breaker should trip based on three key metrics. First, we use a sliding window of recent calls to calculate error percentages. Second, we set a minimum throughput count so we don't trip the breaker on a single failure when traffic is low. And third, we monitor latency thresholds. If requests are taking way too long, even if they aren't technically errors, we still might want to trip the breaker to protect our threads. A major failure mode here is setting static thresholds that don't account for natural traffic fluctuations. In an interview, you can show depth by discussing how these thresholds might need to be dynamic or tuned based on the specific behavior of the dependency. It's a balancing act. Too sensitive and you lose availability, too slow and you lose stability. You have to know your service's typical performance profile to set these accurately. So, what do we actually tell the user when the circuit is open? This is where fallback mechanisms come in. Instead of just showing a generic error page, you want to maintain as much of the user experience as possible. Maybe you can return cached data from a previous successful call or show a default static response. For a recommendation service, you might just show top trending items instead of personalized ones. Or you could even point to a secondary backup provider. The goal is graceful degradation. The system is partially broken, but the user might not even notice. A failure mode to avoid is a cascading fallback failure, where the fallback itself is also down or overwhelmed. When you're in an interview, explaining your fallback strategy proves you're thinking about the product and the user experience, not just the code. It shows you understand that availability isn't binary, it's a spectrum. A smart fallback keeps the business running even when the tech is having a bad day. Managing the transition from open back to closed requires a strategy of gradual retry and recovery. We don't want to just flip the switch. We want a path back to health. This often involves exponential back-off, where we wait longer and longer between retry attempts if they keep failing. This gives the struggling service more time to stabilize. We also use quiet periods to ensure we aren't constantly hammering a service that's clearly having a bad time. The danger here is a recovery loop, where a service starts to recover, gets hit by test traffic, fails again, and gets stuck in a cycle of flipping between states. To avoid this, we can use jitter or randomized wait times to prevent all our client instances from retrying at the exact same millisecond. In an interview, talking about how you handle the recovery to health phase shows you're thinking about the system's long-term stability and its relationship with other services. It's about being a good citizen. It's really important to coordinate your breaker state with your retry logic. Sometimes developers make the mistake of having both systems running independently, which can cause total chaos. If your retry logic is aggressively attempting to reconnect while the circuit breaker is trying to protect the system, you are essentially fighting yourself. You might end up spamming a failing service even though the breaker is supposed to be in open mode. The right way to do this is to have the retry mechanism check the breaker state first. If the circuit is open, don't even bother retrying, just go straight to the fallback. In an interview, this is a great point to bring up. It shows you understand the interaction between different resilience patterns. A common failure mode is retry storms, where thousands of clients all retry at once and keep a service from ever recovering. By integrating these two patterns, you ensure that your system is both persistent when it makes sense and protective when it has to be. We often use circuit breakers to shield our applications from third-party API flakes. When you're calling an external service, like a payment gateway or a social media API, you've zero control over their uptime or rate limits. If their API starts returning 429 too many requests or 503 service unavailable errors, you need to back off immediately. Wrapping these external calls in a breaker prevents your app from being blocked by someone else's problems. It also prevents you from being permanently banned if you keep hitting a rate-limited endpoint. The failure mode here is treating external APIs as if they are as reliable as your own local database. They aren't. In an interview, highlighting how you protect your system from untrusted external dependencies is a strong signal. It shows you're thinking about the boundaries of your system and how to maintain high availability even when your partners are having an outage. It's about building a defensive perimeter that keeps your core business logic safe. If you're in an interview and the topic of protecting dependent systems comes up, you really want to focus on three things: resource exhaustion, the fail-fast philosophy, and how circuit breakers differ from simple timeouts. A timeout is a reactive measure. It stops a single call after it's already been too long. A circuit breaker is a structural measure. It stops all calls because it knows the service is struggling. The primary objective is to prevent a catastrophe rather than just catching an individual error. The biggest failure mode people forget is monitoring the breaker itself. If a breaker trips and stays open and nobody knows, you have a silent failure. Mention that you need alerting on state changes so engineers can investigate why the circuit opened in the first place. Highlighting the fail-fast benefit shows you prioritize system-wide health over a single failing request. It's a hallmark of a senior engineer to choose a clean failure over a messy, slow death. Finally, let's talk about the trade-off between latency and availability. Adding a circuit breaker isn't free. There's a tiny bit of performance overhead for monitoring and managing the state of every call. You're adding logic, storing metrics in memory, and potentially adding a wrapper around your network client. However, the availability benefits of preventing system-wide crashes far outweigh this millisecond level cost. The real trade-off is often in the complexity of configuration. If you set your timeouts too tight or your error thresholds too low, you might lose availability because the breaker is too helpful, tripping on minor network blips. If you're too loose, you risk a system-wide crash we've been trying to avoid. In an interview, being able to articulate this balance shows you don't just follow patterns blindly. You understand that every architectural choice has a cost. The failure mode to mention is over-engineering. Don't put a circuit breaker on every tiny local function call, only on the high-risk boundaries. Alright, so we've covered how the circuit breaker pattern acts as a safety valve for your distributed architecture. It's the primary defense against cascading failures, ensuring that one slow dependency doesn't hog all your threads and bring the whole system down. You should now have a solid mental model of the three distinct states: closed for normal operation, open to fail fast and protect resources, and half open to carefully test if a service is back online. When you're explaining this in a design interview, remember that it's all about resource preservation and knowing exactly when to stop digging a hole. Tuning those failure thresholds and sliding windows is the secret to getting that balance right, allowing your system to stay responsive even when the world around it's falling apart. That wraps up our look at the circuit breaker pattern. For your next interview, keep in mind that it's all about that fail-fast philosophy. You'll want to clearly explain the three states: closed, open, and half-open, and how they stop resource exhaustion. Be ready to justify the trade-off between the monitoring overhead and the massive availability boost you get by shielding your system from downstream flakes. Now, if you're finding these insights useful, subscribe to the channel and check out the course details in the description. In the next episode, we'll discuss Bulkhead Pattern, where we'll discuss situation, core understanding, definition. Thanks for hanging out and good luck with your system design practice. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 18 of the System Engineering series, and today we will explore Bulkhead Pattern in a way that helps you prepare for system engineering interviews on this topic. Now, in high-pressure design loops, you've got to show you can prevent one failing service from sinking your entire platform. We look at two main approaches: resource isolation and service isolation. Mastering these partitions helps you explain why capping thread pools is the best way to keep a system resilient when things go sideways. It starts by looking at the Titanic effect, where a single slow subsystem can drag down an entire platform if we don't isolate resources correctly. So we'll define the bulkhead pattern as a strategy for partitioning resources, making sure that failures are contained within specific compartments. There are three main isolation strategies we'll explore: thread pools, connection pools, and dedicated service hardware. You'll see how these levels of isolation allow a system to operate in a degraded mode instead of suffering a total blackout. Along the way, we'll compare bulkheads to circuit breakers so you know exactly when to reach for each tool. Well, we'll also tackle the tricky trade-offs, specifically how resource isolation can lead to underutilization if you aren't careful. This is exactly the kind of nuance interviewers look for when they ask about fault tolerance in high-scale systems. By the end, you'll understand how to identify critical paths and set clear boundaries to keep your platform afloat during a crisis. Let's set the scene for why we even need this. Imagine you're running a massive e-commerce platform during a flash sale. Most of your system is humming along, but there's a legacy third-party service for gift wrapping that starts lagging. Because your main application waits for a response from this service, every customer request starts hanging. What matters here is that those waiting requests aren't just sitting there, they are holding onto valuable worker threads. The specific failure mode here is thread exhaustion, where the slow legacy service eventually consumes all available threads in the pool, making it impossible for customers to even search for products or check out. It's a classic situation where a non-critical feature kills the entire business. Interviewers love this scenario because it tests if you can identify that the problem isn't just the slow service, but the lack of a boundary between that service and the rest of your architecture. You've got to prevent that small leak from sinking the entire ship. The bulkhead pattern gets its name from the physical partitions in a ship's hull. If one section of the ship is punctured, that specific compartment floods, but the others stay dry. and the ship stays afloat. In software architecture, it works by ensuring that resources are segmented so that one failing component can't hog everything. What matters here is that it creates fault tolerance by design. Instead of trying to make every service perfect, you accept that things will break and focus on limiting the blast radius. A common failure mode occurs when developers assume that simple timeouts are enough to stop a failure. Well, they aren't. Even with timeouts, a spike in requests to a slow dependency can still saturate your thread pool before those timeouts even kick in. By implementing bulkheads, you're building structural integrity into your microservices. It's about moving from a fragile all-or-nothing system to a resilient one that can take a hit and keep on moving. To master these isolation strategies, you need to think about three specific layers: the thread level, the connection level, and the physical level. What matters here is that the bottleneck in your system isn't always obvious. It could be your CPU, your database handles, or even the network bandwidth. In an interview, you'll want to explain that you don't just apply one bulkhead everywhere. You have to analyze the specific resource under pressure. If you only isolate threads but your database connections are all in one giant pool, a slow query can still lock up your entire system. That's the failure mode we call resource leakage, where the boundary you thought you built is actually porous. We'll explore how to navigate these trade-offs because isolation isn't free. It usually comes at the cost of higher complexity and potentially wasted resources. Knowing when to use which strategy is what separates a junior developer from a systems architect who can build truly resilient, global-scale infrastructure. Let's talk about the Titanic effect because it's the perfect metaphor for system design. On the Titanic, the bulkheads didn't go all the way to the top, so when one compartment flooded, the water just spilled over into the next. In engineering, this happens when we have shared resources like a global thread pool or a single database. What matters here is that the failure isn't isolated, it's contagious. When one subsystem gets hit with a latency spike, it starts a chain reaction that consumes every available resource until the entire platform goes dark. The failure mode is a complete system blackout caused by a minor non-essential component. During a system design interview, if you are asked how to prevent a noisy neighbor or a cascading failure, referring to this effect shows you understand the danger of shared fate. You need to prove that you can design compartments that are truly watertight, ensuring that if the review service goes down, the checkout service doesn't even feel the ripple. Technically, bulkheads work by partitioning resources, which means we are dividing our system into isolated pools with strict caps. Instead of a first-come, first-served model where any request can take any resource, we pre-allocate and limit resources for specific workloads. What matters here is that it enforces a predictable limit on how much damage any one service can do. For instance, you might say the search service gets 40 threads while checkout gets 60. This prevents a failure mode where a surge in search traffic starves the checkout process of the resources it needs to actually make money. However, a major risk here is setting these limits incorrectly. If your partitions are too small, you'll start rejecting healthy traffic even when the rest of the system is idle. That's why partitioning requires a deep understanding of your traffic patterns. In an interview, emphasize that bulkheads are about intentional resource management, not just slapping limits on everything. It's a calculated move to protect the core business value. Thread pool isolation is probably the most common way to implement this pattern. It works by creating separate pools of threads for different downstream dependencies or service types. What matters here is that if service A starts hanging, it will only exhaust its own dedicated pool of threads, leaving the pool for service B completely untouched and healthy. This ensures that your system can still handle other types of requests even during a partial outage. If you don't do this and use a single global pool, you'll hit a failure mode where every incoming request, regardless of what it's trying to do, gets queued behind a backlog of failing tasks. In an interview, you should mention libraries like Hystrix or Resilience 4G, which make this easier to implement. But also be ready to discuss the overhead. Managing multiple thread pools adds context switching costs and memory pressure. You're trading off some raw performance for a massive gain in reliability, which is almost always the right call in distributed systems. Now, let's look at connection pool isolation, which is just as critical. This works by restricting the number of database or API connections available to specific modules. Think about it. If you have 100 database connections and one buggy reporting query takes 30 seconds to run, a sudden burst of those reports could easily grab every single connection handle. What matters here is that once those handles are gone, your mission-critical login service can't talk to the database either. The failure mode here is a total database lockout triggered by a low-priority task. To fix this, you'd give the reporting module a strict limit of, say, 5 connections. This way, the slow queries are contained within their own tiny sandbox. When you're explaining this in an interview, focus on the resource side protection. You're not just protecting the caller, you're protecting the downstream resource from being overwhelmed by a single aggressive consumer. It's a proactive way to manage your most precious and limited resources. If logical isolation isn't enough, you move to service isolation with dedicated resources. This works by physically separating services onto different hardware, containers, or clusters. What matters here is that it provides the strongest possible boundary. CPU or memory spikes on one node won't impact the performance of another node at all. For example, you might isolate your payment processing onto its own dedicated cluster to ensure it's never slowed down by a memory leak in the recommendation engine. The failure mode this prevents is the noisy neighbor problem, where a resource-heavy process on the same machine starves everything else of CPU cycles. However, the trade-off here is significantly higher infrastructure costs and operational complexity. In an interview, you'll want to justify this by identifying your most critical paths. You don't isolate everything physically, just the parts of the system that are too important to fail. It's about being strategic with your budget to maximize the availability of your core business logic. The ultimate goal of using bulkheads is to prevent widespread outages by enabling degraded mode. This works by ensuring that when a failure occurs, it stays local. What matters here is that it allows the system to continue serving customers even if some features are temporarily unavailable. For instance, if the user profile service is down, the user might not see their avatar, but they can still buy the item in their cart. This is what we call graceful degradation. Without bulkheads, your failure mode is a binary state. The system is either fully up or fully down. Interviewers are looking for this mindset. They want to see that you prioritize core functionality over 100% feature parity during a crisis. By isolating resources, you're choosing to let a limb go to save the body. It's a sophisticated approach to reliability that recognizes that a partially working system is infinitely better for the user experience than a completely dead one that returns a 500 error. It's easy to confuse bulkheads with circuit breakers, but they serve different purposes. A bulkhead works by allocating and capping resources ahead of time, while a circuit breaker works by stopping requests to a service once it's already failing. What matters here is that bulkheads are proactive structural defenses, whereas circuit breakers are reactive behavioral ones. You actually want to use them together for the best results. A major failure mode occurs when you rely solely on a circuit breaker. If it doesn't trip fast enough, your threads could still be exhausted in that brief window of failure. The bulkhead provides the floor that limits that initial damage. In an interview, a great way to show expertise is to explain how these two patterns complement each other. The bulkhead ensures there's always capacity for other services, while the circuit breaker prevents us from wasting any more time on the failing one. Using both creates a multi-layered defense strategy that can handle almost any type of service instability. We have to talk about the catch, and that's resource utilization. Bulkheads work by earmarking resources, which inevitably leads to some waste. What matters here is that resources reserved for Service B cannot be used by Service A even if Service B is completely idle. You might have 10 threads sitting empty while Service A is struggling because it hit its limit. This is the classic trade-off between high resiliency and maximum efficiency. The failure mode here is over-provisioning, where you end up paying for a lot of idle hardware just to maintain your isolation boundaries. In a system design interview, you need to acknowledge this cost. You don't just say use bulkheads for everything. Instead, you explain how you'd monitor usage and tune those limits over time. A senior engineer knows that 100% utilization is actually a risk, not a goal. We intentionally leave some slack in the system to act as a buffer against spikes and failures. It's about finding that sweet spot. When you're in an interview, your ability to discuss bulkheads is a test of your architectural maturity. You should start by identifying the critical paths and the shared resources in the system. Show the interviewer you're thinking about the blast radius. A great response involves 3 steps. First, identifying which services are most likely to fail or be slow. Second, determining which resources they share. And third, applying bulkhead boundaries to isolate them. What matters here is that it shows you can think proactively about fault tolerance. A common mistake or failure mode in an interview is suggesting isolation for every tiny component, which would make the system unmanageable. You need to demonstrate that you can pick your battles. Focus on protecting the money-making path. Mentioning that you'll monitor the rejection rates of your bulkheads shows you understand the operational side too. It's about proving you can design a system that's functional and more specifically also resilient enough to survive the chaos of production. We've covered how the bulkhead pattern transforms a fragile monolithic resource pool into a resilient partition system. By isolating resources into three main categories, thread pools, connection pools, and dedicated service clusters, you're effectively building firewalls that stop a single failure from cascading across your entire platform. In a system design interview, it's vital to articulate the core trade-off here. You're intentionally capping resource utilization for some services to protect the overall availability of the system. Well, this allows you to maintain a degraded mode where your most critical features stay online even if a secondary service is struggling. It's all about failure containment. When you can explain why you're willing to leave some resources idle just to prevent a total outage, you're showing that you really understand how to build systems that survive the real world. That's a wrap on the bulkhead pattern. In a system design interview, you've got to demonstrate how you'd protect core business functions by isolating failures. So, when an interviewer asks about resilience, highlight how partitioning thread pools or connection pools prevents one slow service from dragging down the whole platform. It's a classic trade-off where you're sacrificing some resource efficiency for overall system safety. Show them you can identify shared bottlenecks and define clear boundaries between services. Subscribe to the channel for more deep dives. In the next episode, we will discuss traffic protection patterns, where we'll discuss situation, core understanding, rate limiting. Happy designing and good luck. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 19 of the System Engineering series, and today we will explore traffic protection patterns in a way that helps you prepare for system engineering interviews on this topic. Now, knowing how to shield services from spikes is vital for uptime. In an interview, you'll need to justify picking a token bucket over a leaky bucket or a fixed window. We'll look at these strategies so you can confidently explain how to keep a system standing when traffic gets heavy. We begin with the traffic tsunami scenario to see how unmanaged spikes can melt a database, setting the stage for why we need a solid philosophy of traffic control. The lesson moves into the core mechanics of four protection strategies: rate limiting, throttling, and the classic bucket algorithms. We look at the token bucket for handling bursts versus the leaky bucket for smoothing out flow. Now, we'll also contrast the simplicity of fixed windows with the precision of sliding windows, so you've got the tools to choose the right implementation for your scale. Beyond just volume, we explore how to neutralize bots and spam, ensuring automated actors don't drain your resources. Well, we'll also tackle the tricky trade-off between keeping the system stable and avoiding a poor user experience with too many 429 errors. That balance is a huge signal in system design interviews. By the end, you'll understand how to architect a layered defense that keeps your APIs resilient even during the most massive traffic events. Let's set the scene for a real-world engineering challenge you might encounter. Imagine you're running a high-scale API that suddenly gets hit by a massive, unexpected spike in requests. Maybe it's a flash sale, a breaking news event, or even a coordinated scrap attack. This is where your system's limits are truly tested. In this situation, the primary goal is to maintain service for as many legitimate users as possible while preventing the backend from being crushed. This context matters because it shifts your perspective from how do I process everything to how do I survive. Failure to handle this situation correctly results in a retry storm, where clients keep hitting an already dying server, making the problem exponentially worse until everything hits a dead stop. In an interview, the recruiter wants to see that you understand the production pressures of managing shared resources. You have to think about how you'll prioritize traffic when CPU and memory are at their limits. If you can't articulate a strategy for these high-pressure scenarios, it suggests your designs might fail when they are needed most. We'll look at how to build that resilience today. In this 19th episode of our series, we are treating traffic protection as a masterclass in API safeguarding. This goes beyond simple firewalls. It's about intelligent, application-aware defense against excessive traffic, malicious bots, and those sudden infrastructure-level spikes we just discussed. What matters here immensely because your API is the front door to your business. If the door jams or gets broken down, everything behind it is at risk. We'll explore how these patterns work at the edge, often at the API gateway or load balancer level, to intercept and manage requests before they ever touch your expensive business logic. A common failure mode here is implementing protection too deep in the stack. If you're checking rate limits inside your database-heavy microservice, you've already lost half the battle because the connection overhead is already consuming resources. By moving these protections to the perimeter, you're effectively shielding your core assets from unnecessary stress. You'll want to highlight this perimeter-first approach in any system design interview to show your thinking about resource efficiency and failure isolation across the entire ecosystem. It's a fundamental shift in how we view system safety. When we talk about the traffic tsunami, we are describing a system under extreme fire from three main sources: sudden spikes, persistent abuse, and unmanaged growth. It's that moment where your request volume looks like a vertical wall on the monitoring chart. This scenario matters because it's the point of no return for unprotected systems. Without a solid strategy, your database will inevitably melt under the connection pressure and your latency will skyrocket as the thread pools fill up. The failure mode here is often a complete system brownout. Even if the traffic subsides, your services might stay stuck in a failed state because of lingering backlogs or corrupted cache states. You've got to realize that it is not only about malicious actors. Sometimes your own mobile app might have a bug that causes it to retry a failed request 1,000 times a second. That's a self-inflicted tsunami. In an interview, being able to identify these different types of surges shows you have the practical experience to expect the unexpected. We are going to learn how to build the breakwaters that can absorb this energy and keep the core system calm and functional. The core philosophy of traffic control is really about being the gatekeeper of your system's sanity. It's built on two main pillars: ensuring fair resource allocation and maintaining stability under load. Think about it. Why should one aggressive user or a single buggy client be allowed to degrade the experience for everyone else? This philosophy matters because it moves us away from a first-come, first-serve model, which is inherently fragile during a crisis. Instead, we implement fairness, so everyone gets their slice of the pie, but no one can take the whole thing. A significant failure mode occurs when you forget the fairness part and only focus on stability. If your global rate limit is too blunt, you might accidentally block your most important high-value customers while trying to stop a minor bot. In your interview, you should emphasize that traffic control is a business decision as much as a technical one. You're essentially defining the contract of your API's availability. You're deciding what happens when the system is pushed to its limits and how you protect the overall health of the platform at the expense of individual outliers. Rate limiting is the most common tool in our kit, acting as a strict barrier that rejects any request exceeding a specific threshold. It works by checking a counter for a given key, like an IP address or API key, and if the count is over the limit, it returns a 429 too many request error immediately. What matters here is that it's your most effective way to prevent total resource exhaustion at the edge. However, the biggest failure mode is setting these limits too low or too high without proper monitoring. If they're too strict, you ruin the user experience and drive people away. If they're too loose, they don't actually protect you from a real surge. Another mistake is using a single global limit for everything. In a real system, you'll want different tiers of limits. In an interview, you'll stand out by discussing how you'd handle these limits across a distributed system. Do you use a centralized Redis store or keep local counts? Each has its own trade-offs regarding latency and accuracy. You've got to find that sweet spot where the limit is high enough for normal use but tight enough to stop an attack. Throttling is a more nuanced approach than rate limiting. Instead of a hard rejection, throttling focuses on managing a gradual slowdown of incoming traffic. It works by introducing artificial latency or queuing requests when the system starts to feel the heat. What matters here is that it buys your backend services precious time to recover or auto-scale without necessarily dropping every user. It's like a pressure release valve rather than a shut-off switch. Well, the danger here is that if you throttle for too long, your internal queues can fill up, leading to a failure mode called memory exhaustion. If you're holding on to thousands of pending requests, your server might crash anyway. Also, clients might time out while waiting for a throttle response, leading to those dreaded retries we talked about earlier. When you're explaining this in a design interview, highlight that throttling is great for smoothing out small bumps, but you still need rate limiting as a fallback for when things truly get out of hand. You're looking to provide a degraded but still functional experience rather than a complete blackout for the end user. The token bucket algorithm is a favorite for engineers who need to handle bursty traffic. It works by having a bucket that fills with tokens at a fixed rate. Every incoming request must spend a token to be processed. If the bucket is empty, the request is rejected. What matters here is that it allows for controlled bursts. If a user hasn't made a request in a while, tokens accumulate and they can send a bunch of requests at once. But once those tokens are gone, they are restricted to the steady refill rate. The failure mode here is often related to bucket size. If the bucket is too large, a sudden burst from many users simultaneously can still overwhelm your database. On the flip side, if the refill rate is too slow, users will feel constantly throttled even during low usage periods. In an interview, you should mention that token bucket is highly efficient because it doesn't require keeping track of every request timestamp, just a single counter and a last refill time. It's a great balance between flexibility for the user and protection for the infrastructure, provided you tune the parameters correctly. Now, the leaky bucket algorithm is a bit different because it focuses on achieving a smooth, constant traffic flow. Imagine a bucket with a small hole at the bottom. You can pour water in as fast as you want, but it only leaks out at one steady rate. In our systems, requests enter a buffer and are processed at a strictly constant speed. What matters here is that it's ideal for transforming jagged, unpredictable traffic into a predictable stream that your backend can handle without sweating. It's particularly useful for things like background processing or logging, where timing isn't as critical as stability. However, the failure mode is buffer overflow. If requests come in faster than the leak rate for too long, the bucket fills up and new requests are simply discarded. This can lead to significant data loss if you aren't careful. In a system design session, you choose leaky bucket when your downstream service has a very specific inflexible throughput limit. It's the ultimate tool for avoiding those sharp spikes that trigger cascading failures, though it comes at the cost of potential increased latency for the requests sitting in the bucket. The fixed window approach is the simplest way to implement rate limiting. It works by dividing time into discrete blocks like 1-minute intervals and counting requests within each block. When a new minute starts, the counter resets. It's incredibly easy to implement, which is why people love it for basic setups. But there's a major failure mode you have to watch out for, often called the boundary burst. If a user sends their entire quota at the very end of one window and then another full quota at the very beginning of the next, they've effectively doubled the allowed rate in a very short span of time. What matters here is that concentrated burst could still be enough to knock your service offline. In an interview, if you suggest a fixed window, you should proactively mention this limitation. It shows you aren't just reading a textbook, but you actually understand how these things behave in production. It's a great choice for low-stakes APIs where simplicity outweighs precision, but for high-traffic sensitive endpoints, you're going to want something a bit more sophisticated to prevent those boundary-driven spikes from causing trouble. To solve the problems with fixed windows, we use the sliding window algorithm. This provides much more accurate request enforcement by tracking requests over a rolling time frame rather than discrete blocks. It works by looking back from the current millisecond to the start of the window, ensuring that the total count never exceeds the limit at any point in time. What matters here is that it completely eliminates those boundary spikes we just talked about, providing true rate adherence. However, the trade-off here is complexity and resource usage. To be perfectly accurate, you'd need to store a timestamp for every single request, which can become a bottleneck in high-throughput systems. A common failure mode is choosing a sliding window implementation that consumes too much memory, eventually causing your rate-limiting service itself to fail. In an interview, you can talk about sliding window logs versus sliding window counters to show you understand how to approximate this behavior more efficiently. It's all about balancing that need for precision against the overhead of maintaining the state. If you need strict enforcement without the boundary issues, this is your go-to pattern. Bot protection is about more than just numbers. It's about identifying the nature of the traffic. It works by using heuristics, behavioral analysis, and device fingerprinting to tell the difference between a real person and an automated script. What matters here is that bots can consume massive amounts of bandwidth and compute resources without providing any business value. Or worse, they might be trying to scrape your data or brute force passwords. A classic failure mode here is being too aggressive and blocking legitimate automated traffic, like search engine crawlers or accessibility tools that your users rely on. You could also run into issues with false positives, where a human on a slow or shared connection looks like a bot and gets locked out. When discussing this in an interview, mention that bot protection should be multi-layered. You don't just look at IP addresses, you look at request patterns, headers, and even mouse movements if you're on the front end. It's a cat and mouse game, so your system needs to be adaptable. Using a specialized service at the edge is often the best architectural choice here to keep that heavy lifting away from your code logic. Spam mitigation focuses on protecting the integrity of the data being sent to your system. It works by analyzing the content of requests to block repetitive or low-value input that could drain your resources. Think about comment sections or messaging apps. If one person can post 10,000 times a minute, they'll degrade the service for everyone and fill your database with junk. What matters here is that spam doesn't just waste storage, it ruins the user experience and can even lead to your domain being blacklisted by email providers or search engines. The failure mode here is a high false positive rate. If your filter is too broad, you might mark legitimate user feedback as spam, which is a quick way to lose customer trust. In an interview context, you should explain how spam mitigation is different from rate limiting. Rate limiting stops the how often, while spam mitigation stops the what. You might use machine learning models or simple signature matching to identify these patterns. Balancing this protection while ensuring that valid, unique content gets through is a subtle but vital part of maintaining a healthy, high-quality platform for your users. Finding the right balance in traffic protection is a classic engineering trade-off between user experience and system safety. If your rules are too strict, you are going to lose users who get frustrated by constant 429 errors or slow load times. If they're too loose, your system will eventually crash during a search, which is the ultimate failure. What matters here is that every business has a different Goldilocks zone. A banking app might prioritize security and stability over everything else, while a social media site might lean towards a smoother user experience even if it risks some occasional lag. A common failure mode is treating all traffic equally. In a sophisticated system, you might have different limits for free versus paid users, or for critical versus non-critical API endpoints. In your interview, emphasize that there's no such thing as a perfect limit. You have to constantly monitor your metrics, look at your error rates, and adjust your strategies based on real-world behavior. Demonstrating that you understand this dynamic tension shows you're ready for the messy reality of managing production systems, where business goals and engineering limits often collide. When you're in a system design interview, your goal is to show you can scale these protection strategies effectively. Don't just list the algorithms. Talk about where they live in the architecture. Should you use global limits in a centralized store like Redis or local limits on each individual server? Centralized is more accurate, but adds latency and a single point of failure. Local is faster, but can be bypassed if the load balancer isn't distributing traffic perfectly. These are the kinds of trade-offs interviewers love to hear. You should also discuss fallback mechanisms. What happens if your rate-limiting service goes down? Does the system fail open and allow everything, or fail closed and block everyone? Most production systems choose to fail open to preserve user experience, but you need to justify that choice. Mentioning things like circuit breakers and shadow rate limiting, where you log what would have been blocked without actually blocking it, shows you have a mature approach to rolling out these protections. It's all about demonstrating that you can build a system that's both secure and highly available under any circumstances. Now that we've covered the arsenal, it's time to activate your protection protocol. Traffic protection is your first and most vital line of defense. By applying these patterns, rate limiting, throttling, and intelligent bucket algorithms, you're ensuring that your APIs stay up even when the entire world is knocking at your door at once. What matters here is that a resilient system is a trustworthy system. If you can't guarantee availability, your users will find someone who can. The ultimate failure mode is complacency. Just because you have a rate limiter doesn't mean you're safe forever. Traffic patterns change, new botnets emerge, and your own app scale will grow. You need to treat these protections as a living part of your stack that requires regular tuning and monitoring. In an interview, wrap up by showing you're committed to this iterative process. You aren't just checking a box, you're building a layer of the infrastructure that evolves alongside the business. It's about having the right tools in place and the operational wisdom to use them effectively when the next traffic tsunami inevitably hits your servers. So, we've walked through how to keep your infrastructure from crumbling under a traffic tsunami. We explored two primary strategies: hard rate limiting to block excess requests and throttling to gradually slow things down. When you are in a system design interview, you've got to be ready to justify your choice between the four core algorithms we covered. You need to know when to use a token bucket for bursts, a leaky bucket for smoothing flow, or the fixed and sliding window approaches for time-based enforcement. It's vital to articulate the trade-off between keeping the system stable and maintaining a decent user experience. Choosing a flexible, burst-friendly strategy over a rigid one shows you're thinking about the actual product impact, right? You've now got the full toolkit for defending your APIs against both sudden spikes and persistent abuse. That wraps up our look at traffic protection patterns. When you're in a high-stakes interview, remember that it's all about finding that Goldilocks zone between strict system protection and a smooth user experience. You'll want to justify your choice of these 6 strategies, from simple fixed windows to burst-friendly token buckets, based on the specific failure modes you're trying to prevent. Don't forget to discuss whether you're enforcing limits at the local level or globally via an API gateway. If you found this helpful, hit that subscribe button, and you can find the full course details in the description. In the next episode, we will discuss Saga pattern, distributed transactions, where we'll discuss situation, core understanding, problem. Catch you then, and good luck. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 20 of the System Engineering series, and today we will explore Saga pattern, distributed transactions, in a way that helps you prepare for system engineering interviews on this topic. When microservices break traditional ACD boundaries, you've got to manage consistency yourself. We'll look at the 2 main flavors, orchestration and choreography, to see how they handle complex failures. Mastering these patterns is how you show interviewers you can actually build reliable long-running workflows in a distributed environment. It starts by tackling the distributed workflow dilemma, where business processes crossing service boundaries break traditional AC transactions. We'll define distributed transaction management and introduce the Saga concept as a sequence of local transactions. You're going to learn about the 2 major architectural styles, orchestration, which uses a central brain to coordinate steps, and choreography, which relies on a decentralized event-driven flow. Well, since things often go wrong in distributed systems, we'll also examine the outbox pattern for event persistence and the logic of compensation, the specific way we undo actions without a physical rollback. We'll contrast forward and backward recovery models before putting these ideas into practice with real-world scenarios like order management, payments, and complex travel bookings. Finally, we'll dive into some heavy-hitting interview insights, looking at the trade-offs between visibility and decoupling when choosing between 2PC and Sagas. By the end, you'll understand exactly how to design resilient workflows that maintain data consistency at scale. Let's set the scene with a real engineering situation you'll probably find yourself in during a system design interview. Imagine you're building a global e-commerce platform that needs to handle thousands of orders per second. Each order touches 3 distinct services: order management, payment processing, and inventory. In the old days, you'd just wrap all those database updates in one big transaction and call it a day. But at this scale, each of those services has its own database, maybe even using different technologies. If the payment service succeeds, but the inventory service fails because an item just went out of stock, you can't just roll back a database call that happened 3 services ago. This is where the risk of data inconsistency becomes a real threat to the business. Without a pattern like Saga, you'd end up with customers who've paid for items that don't exist, leading to a massive loss of trust and operational chaos. Understanding this scenario is how you prove you're thinking about production-grade reliability. Now, let's get into the mechanics of the Saga pattern itself. It works by treating a complex business process as a series of small local transactions. Each service involved performs its own update and then emits an event or message to trigger the next step in the chain. This approach is essential because it respects the autonomy of microservices, ensuring that one service's database doesn't need to know the internal details of another. Why is this so popular in high-end systems? It's because it avoids the long-lived locks that destroy performance in distributed environments. However, you have to watch out for the main failure mode here. Atomicity is lost at the global level. Unlike a single database transaction, there's no magic button to undo everything instantly if step 4 fails. You're essentially trading off the simplicity of ACID for the scalability of base consistency. In an interview, being able to articulate that you're knowingly making this trade-off for performance is a huge green flag for senior roles. The core of our problem is what we call the distributed workflow dilemma. When you have a process spanning 3 separate services like order, payment, and stock, each one has its own isolated database. This isolation is great for scaling, but it creates a massive headache for consistency. You can't use a standard SQL begin transaction across 3 different network-connected databases. If the network blips or a service crashes midway, you are left in a state where the data is no longer synchronized. What matters here is that a business can't survive with ghost orders that were paid for but never reserved in inventory. The typical failure mode in native implementations is the dual write problem, where you update a database but fail to notify the next service. Without a formal pattern like Saga, you'll inevitably face race conditions and data corruption that are nearly impossible to debug after the fact. It's these kinds of boundary issues that interviewers use to see if you actually understand the limits of distributed computing. Defining distributed transaction management starts with acknowledging that we are moving away from the safety net of the two-phase commit protocol, or 2PC. While 2PC works by having a coordinator ask every participant to prepare and then commit in unison, it's notoriously slow and creates a single point of failure. In a modern microservices setup, we need a way to manage data consistency without those heavy blocking locks. Distributed transaction management in Sagas is all about coordinating these independent local transactions so that they eventually reach a consistent state. What matters here is that it allows each service to remain highly available and performant. The failure mode you have to worry about here is lack of isolation. Since other transactions can see the intermediate changes before the entire saga is complete, you can run into dirty reads or lost updates. In an interview, you should be ready to explain how you'd mitigate these isolation issues, perhaps by using a pending state or versioning, to show you've thought through the deep consistency challenges. The Saga concept relies on breaking a workflow into local sequences. Each step in the sequence is a standard local transaction that updates a database and then publishes a message to the next service. It's like a relay race, where each runner does their part and then passes the baton. This design is crucial because it keeps each step short-lived, which reduces database contention and improves overall system throughput. However, the complexity lies in what happens when the baton gets dropped. A major failure mode is message loss or duplicate processing. If a message is lost, the whole saga stalls forever. If it's duplicated, you might bill a customer twice. This is why you need to ensure your message broker is reliable and your services are idempotent. When an interviewer asks how you'd handle a partial success in a distributed system, this concept of sequential local updates is your foundational answer. It shows you know how to build a chain of events that is both decoupled and progress-oriented. Let's talk about Saga orchestration, which is essentially the central brain approach. In this model, you have one dedicated service, the orchestrator, that tells every other participant exactly what to do and when to do it. It's like a conductor leading an orchestra. What matters here is that it provides a single point of truth for the entire workflow state, making it much easier to monitor and debug when things go sideways. You can look in one place to see exactly where an order is stuck. However, there are two main risks. The orchestrator can become a single point of failure, and it can also become a bottleneck if it's managing too much logic. If the orchestrator goes down, the entire business process grinds to a halt. In an interview, use this as a chance to talk about trade-offs. Orchestration is fantastic for complex workflows where you need high visibility, but you have to be careful not to turn it into a god service that knows too much about everyone else's business. On the flip side, we have Saga choreography, which is a decentralized, event-driven flow. In this setup, there is no central brain. Instead, each service knows which events to listen for and what to do next. It's like a dance where every performer knows their cues without a director shouting orders. What matters here is that it maximizes decoupling. Services don't even need to know the others exist. It's incredibly flexible and scales beautifully. But here's the catch. The failure mode here is a complete loss of visibility. When you have 20 services exchanging events, it becomes very difficult to figure out why a specific transaction failed or where it currently is in the system. You also risk creating cyclical dependencies, where service A triggers B, which triggers C, which accidentally triggers A again. In an interview, you'd choose choreography for simpler, highly scalable workflows, but you'd better have a plan for distributed tracing and monitoring to explain how you'll actually keep track of what's happening in production. To make choreography actually work in the real world, you have to solve the problem of event persistence. You can't just update your database and then send a message to a broker in two separate steps, because one might succeed while the other fails. This is the classic dual write failure mode. The outbox pattern is our savior here. It works by saving the event into an outbox table within the same local transaction as your business data. A separate process then polls that table and pushes the messages to the broker. What matters here is that it guarantees that your database update and your event notification are atomic. It's all or nothing. If you don't use this, your system will eventually drift out of sync and you will spend your weekends manually fixing data. Interviewers love to dig into this specific detail because it separates people who just know the theory from those who've actually built reliable distributed systems. It's the difference between a system that looks good on paper and one that survives a network partition. Since we can't do a physical rollback in a distributed system, we have to master the art of compensation. A compensating transaction is a semantic undo. For example, if you've already authorized a payment but the shipping service fails, you can't just delete the payment record. You have to issue a refund. What matters here is that it brings the system back to a consistent business state, even if the technical state has moved forward. You need to design these undo actions for every single step of your saga. The failure mode to watch for is a nested failure, where the compensation itself fails. If your refund service is down while you're trying to undo an order, you're in a very awkward position. In a system design interview, always mention that compensating transactions must be idempotent because they might be retried multiple times. Showing that you understand the difference between a technical rollback and a business level compensation shows a high level of senior level maturity and practical experience with long-running workflows. When things go wrong, you have to choose between two main recovery strategies, forward and backward recovery. Forward recovery is about pushing through. If a step fails, you keep retrying it until it succeeds, which works best when failures are transient, like a temporary network blip. Backward recovery is the undo path, where you execute all the compensating transactions for the steps that already finished. What matters here is that not every error can be fixed with a retry. If a customer has no money, no amount of retrying will make that payment succeed. The failure mode for forward recovery is getting stuck in an infinite retry loop that consumes resources. For backward recovery, it's the risk of failing to undo a high-stakes action. In an interview, the key is to explain that you'd use forward recovery for critical steps that must happen and backward recovery for business logic errors. Being able to distinguish when to use each strategy demonstrates that you're thinking about the specific nature of the failure rather than just applying a one-size-fits-all solution. Let's look at a concrete use case, order management. When a user clicks buy, we might authorize their card and then check the inventory. If we find out the item is actually out of stock after the payment is already authorized, we have to trigger a compensation flow to cancel that authorization. What matters here is that it prevents the customer from being charged for something they'll never receive. In this scenario, the failure mode is often a race condition where the stock level changes between the time the user added it to the cart and the time the payment went through. Without a solid Saga implementation, you'd end up with a manual reconciliation nightmare for your support team. In an interview, walk through this flow step by step. First the happy path, then the specific error point, and finally how the system recovers. It's a classic example that everyone understands, making it perfect for demonstrating your grasp of the Saga pattern's practical utility and its necessity in high-volume e-commerce environments. Payment processing is another great use case for Sagas, especially when dealing with multi-step wallet deductions and external gateways. Imagine a scenario where you have to deduct money from a user's internal credit balance and then call an external API like Stripe for the remainder. These two systems fail in completely different ways. If the external gateway call fails after the internal balance is deducted, you need a way to reliably credit that money back. What matters here is that financial data demands 100% accuracy. You can't just lose money in the system. The common failure mode here is a timeout on the external API where you don't know if the payment actually went through or not. This is why you need a Saga to manage that uncertainty. In an interview, focus on how you'd use a pending state and an orchestrator to manage these multi-leg financial transactions. It shows you're capable of handling high-stakes data where consistency is non-negotiable and failure handling must be bulletproof. Travel reservations offer perhaps the most complex sequential dependencies. Think about booking a flight, a hotel, and a car rental all at once. If you successfully book the flight, but the hotel is suddenly unavailable, you can't just leave the user with a flight to nowhere. You have to call the airline's API to cancel that flight. What matters here is that travel APIs are often slow and have very specific rules for cancellations and refunds. A major failure mode here is partial availability, where the car and flight are booked, but the hotel is gone and the user's credit card has already been hit. Sagas manage this by ensuring that the car and flight are only finalized once every part of the trip is secured. In an interview, highlight how you would handle these long-running processes that might take seconds or even minutes to complete. It's the perfect use case for showing how Sagas manage external world side effects that are outside of your direct database control. When you are in an interview, you should expect two primary comparisons, 2PC versus Sagas and orchestration versus choreography. You need to be ready to explain that while 2PC offers strong consistency, it's a performance killer in high latency distributed environments because it locks resources. Sagas, on the other hand, trade off that immediate consistency for high availability and throughput. A common failure mode in these interviews is failing to address observability. If you suggest a choreography-based Saga, you must mention how you will track the state of a transaction that spans 5 different services. You need distributed tracing or a centralized log. If you don't, the interviewer will think you've never actually run this in production. You should also justify why orchestration is often better for complex business logic, as it puts the brain in one place, whereas choreography is great for simple, highly decoupled systems. Being able to weigh these trade-offs is what gives off that senior signal that companies are looking for. You are now equipped with the architectural tools to design resilient, consistent workflows in distributed environments. We've covered a lot of ground, from the basic dilemma of distributed databases to the complex trade-offs between central orchestration and event-driven choreography. Remember, the Saga pattern is not a one-size-fits-all solution. It's a strategy for managing complexity at scale. The key is to always think about your failure modes first. How will you undo an action, and how will you know if a process is stuck? What matters here is that as systems grow, the number of things that can go wrong grows exponentially. If you can build systems that fail gracefully and maintain data integrity, you're already ahead of most developers. In your next project or interview, don't just reach for the simplest solution. Think about the consistency requirements and choose the right pattern for the job. Mastering these distributed patterns is exactly how you level up from a coder to a system architect. So, we've broken down how to maintain consistency when your business logic outgrows a single database. The Saga pattern is our go-to solution for distributed transactions, replacing rigid ACID locks with a sequence of independent local updates. We explore the two main implementation styles: choreography, where services react to events, and orchestration, which uses a central brain to manage the flow. In a system design interview, your ability to choose between these is a huge signal. You've got to justify why you'd pick the decoupled nature of choreography versus the simplified visibility of an orchestrator. Remember, because we can't physically roll back a remote database, we rely on compensating transactions to undo work semantically, like issuing a refund rather than just deleting a record. Well, mastering these failure modes and ensuring event atomicity with the outbox pattern is exactly what makes your distributed workflows actually production ready. You're now equipped to handle complex sequences across any number of microservices. Well, that wraps up our deep dive into the Saga pattern. When you're tackling this in a system design interview, remember that your choice between orchestration and choreography usually comes down to the trade-off between central visibility and service decoupling. We looked at 3 main use cases: orders, payments, and travel, to show how those local transactions and compensations actually keep things consistent without a global log. If you want more, make sure to subscribe and check the description for the full course details. In the next episode, we will discuss Idempotent APIs, where we'll discuss situation, core understanding, definition. Catch you later, and good luck with your designs. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 21 of the System Engineering series, and today we will explore idempotent KPIs in a way that helps you prepare for system engineering interviews on this topic. Look, network failures are inevitable, so knowing how to prevent double billing or duplicate orders is a massive signal that you can design truly reliable systems. We'll break down the behavior of put versus post and see how unique idempotency keys keep your state consistent even when clients retry. It's a critical concept for any high-stakes architecture. It starts by looking at the chaos of unreliable networks where lost acknowledgements force clients to retry, potentially causing double billing or corrupted data. So, we'll define exactly what idempotency is and how it ensures that making the same request multiple times has the same outcome as making it once. From there, we'll dive into the technical details of HTTP methods, contrasting the safety of put against the inherent risks of post. Now the focus shifts to the system design side, where we'll break down the 4-step check, process, store logic and the storage strategies needed to track requests using tools like Redis. We'll also cover key expiry and cleanup, which is a detail that often separates a junior dev from a senior architect. We'll apply all this to high-stakes scenarios like payment processing and order management to see how we prevent ghost transactions. Finally, we'll wrap up with interview-specific insights on how to explain these design choices under pressure. By the end, you'll know how to build APIs that stay consistent even when the network fails. Imagine you're building a global payment gateway. In this environment, scale is massive and constraints are tight. You've got thousands of requests per second, and some of those requests will inevitably hit a network snag. Maybe the client times out or the server processes the charge, but the acknowledgement gets lost in transit. This is the exact situation where things get dangerous. If the client retries that payment because they didn't get a confirmation and your system isn't idempotent, you've just double charged the customer. That's a huge failure mode that leads to massive support tickets and lost user trust. In an interview, you'll want to describe these high-stakes environments where at least one's delivery isn't enough without a way to deduplicate logic. We're talking about systems where state consistency is the only thing standing between a smooth user experience and a total financial or data catastrophe. It's about being defensive in your design choices. Let's talk about the chaos of the network. It's never a matter of if it fails, but when. In a typical cycle, a client sends a request, the server does the work, but then the ACK or acknowledgement disappears. The client is now in a state of total uncertainty. Did the server actually do the work, or did the request fail before reaching it? Because they don't know, they are forced to retry. Without idempotency, this simple necessary retry becomes a massive risk for data corruption. If you're building an inventory system, a lost ACK could mean you deduct stock twice for a single order. In an interview, explaining this cycle, request, process, lost ACK, retry, shows you understand the fundamental uncertainty of distributed systems. It's not just a technical edge case, it's the default reality we have to design for to keep our systems from drifting into an inconsistent state. That's why we build for failure. So what's the core fix? It's idempotency. At its heart, this is a property where an operation can be applied multiple times without changing the final outcome after that first successful application. It's what makes retrying a safe operation for the client. Think about a safe retry versus an unsafe retry. In a safe scenario, if I tell a system, set the light to green, and I say it 10 times, the light is still just green. That's idempotent. But if I say toggle the light and I say it 10 times, the final state depends entirely on how many times that command was received. In API design, we want to shift as many operations as possible towards that first safe category. When you can guarantee that repeating an action won't cause unintended side effects, you've removed a whole class of bugs and race conditions that plague distributed systems. It's all about making the system predictable. Formally, an idempotent API ensures that the side effects of making the same request multiple times are identical to making it just once. The math here is simple. F of x equals f of x. No matter how many times you apply the function, the result is the same. Now, in the real world, this doesn't mean the server returns the exact same HTTP response every single time. You might get a 201 created the first time and a 200 OK the second, but the underlying state of the system remains consistent. What matters here is that it decouples the client's retry logic from the risk of duplicating resources. Failure to implement this means you're leaving your database's integrity up to the reliability of the public internet, which is a recipe for disaster. When an interviewer asks for a definition, they are looking for that specific distinction between the response code and the side effects on the data store. Why do we go through all this trouble? Well, without it, every network timeout turns into a full-blown crisis for the user and the business. Retry safety is the get-out-of-jail-free card that lets clients be aggressive about fixing their own connection issues without accidentally double-charging a customer or creating ghost resources. If your system can't handle a retry gracefully, the client has to just give up or risk a catastrophic error, and neither of those is a good user experience. The consequence of skipping this is high. You'll end up with desynchronized state between your microservices, leading to manual data cleanups and angry users. In your interview, highlight how idempotency reduces the operational burden of error handling. It's about moving the complexity away from the user and into a robust architectural pattern that treats failure as a normal, manageable event rather than an exceptional disaster. Now let's look at how the tools we already use handle this. The HTTP put method is actually idempotent by design. When you send a put request, you are essentially saying, replace the resource at this URL with this exact data. If you send that same update 5 times, the end state is still that same resource with that same data. It's like overwriting a file. The first time changes the content and the next 4 times just set it to the same thing again. This makes retries for put request inherently safe. However, the failure mode here is often a partial update or a race condition where 2 different clients try to put the same resource simultaneously. That's why you still need to be careful with versioning or e-tags. But fundamentally, the verb itself is built to handle repetition without creating multiple distinct records. It's an elegant solution to a common synchronization problem. Post is a totally different story. By default, post is not idempotent. Every time you send a post request, you're usually telling the server to create something entirely new. So if you retry a post because of a timeout, you are at higher risk for creating duplicate resources or even worse, duplicate charges. This is the post challenge. If the server processed the first request but the response was lost, the second post will just create a second entry in your database. This is a classic bottleneck for reliability. To fix this, we have to manually layer idempotency on top of post using things like unique idempotency keys. If you don't do this, you're basically leaving your system open to double entry bugs. In an interview, explain that while post is the go-to for creation, it's the most dangerous verb to retry without a solid deduplication strategy in place to protect the database. So, how do we actually implement this prevention logic on the server? It's a 4-step flow: check, process, and store. First, the server checks if it has already seen the specific idempotency key provided by the client. If the key exists, the server knows this is a retry, so it skips the work and returns the previous result. If the key isn't there, the server proceeds to process the request. Once done, it stores the result and the key atomically. This atomicity is the make or break part. If you process the request but fail to store the key, you've left the door open for a duplicate execution on the next retry. This logic protects your database from being flooded with identical entries. When explaining this, emphasize that the check must happen before any side effects occur. Otherwise, you've already lost the battle against duplication. It's a simple but powerful sequence. Where do we keep all these keys? Since every request needs a quick check, storage is a major architectural choice. For high-performance APIs, we often lean on Redis. It's fast, handles massive lookup volume, and supports a TTL or time to live. This TTL is crucial because we don't want to bloat our primary database with millions of temporary keys that are only relevant for a short retry window. Other options like DynamoDB or even your primary RDBMS work too, but they might add more latency to every request. The trade-off here is between speed and persistence. If your Redis cache goes down, do you lose your idempotency guarantees? A strong interview answer discusses this failure mode and might suggest a more persistent store for high-value transactions like payments while using an in-memory cache for less critical operations. It's about matching the storage choice to the business impact of a failure. Idempotency isn't for eternity. You have to decide on a retry window, which is the period during which you'll honor an idempotency key. If a client retries a request after 24 hours, should you still treat it as the same transaction? Probably not. We use cleanup strategies like TTLs to purge old keys and keep the system efficient. The danger here is if a client retries after the key has been purged, the server will think it's a new request and process it again. That's a classic failure mode to watch for. To mitigate this, your client and server need an agreement on how long those keys are valid. In an interview, discussing how you tune this window based on the specific business use case, like minutes for a search but hours for a bank transfer, shows that you're thinking about the practical constraints of storage and consistency. Let's look at the most famous use case: payments. This is where getting it right is non-negotiable. When a user hits pay, the mobile app generates a unique idempotency key. If the network drops and the app retries that button 5 times, the payment gateway uses that key to ensure the customer's bank account is only hit once. Without this, you'd be dealing with thousands of refund requests and a massive PR nightmare. The key here is often tied to a specific transaction or order ID. If the server sees a key it already processed, it just sends back the success message from the first attempt. This pattern is the gold standard for financial systems. In an interview, using this as your primary example proves you understand the real-world stakes of data integrity and the direct impact it has on the business's bottom line. It's about trust as much as tech. Another big one is e-commerce order placement. You don't want to ship 2 iPhones just because a user had a spotty Wi-Fi connection. By using idempotency keys, the system ensures that the flow from cart to order is stable. Even if the inventory service or the shipping service gets the request multiple times, the state remains consistent. A major bottleneck here can be the ghost transaction, where an order is created but the client doesn't know it, leading to inventory being locked up for a user who thinks their purchase failed. Proper idempotency prevents this by allowing the client to safely query for the status of that specific request key. It keeps your inventory counts accurate and prevents your shipping department from wasting resources on duplicate packages. It's all about keeping the different pieces of your distributed microservices in sync even when the network is acting up. If you're in a system design interview and the interviewer asks what happens if the network fails right after the client sends a request, that's your cue to talk about idempotency. You need to show you can design a reliable API from scratch. Mention the importance of the idempotency key, how you'd store it in something like Redis with a proper TTL, and what response codes you'd return. A key detail is to discuss the already processed scenario. Usually you'll return a 200 OK or a 204 no content to tell the client, hey, we got this already, you're all set. Don't forget to mention atomicity in the storage layer. If you can't guarantee the key is saved at the same time the transaction is processed, you haven't really solved the problem. Show them you're thinking about the edge cases where things fail halfway through and how you'd recover gracefully. So, we've really demystified how idempotency transforms unreliable network failures into safe, predictable retries. I mean, the core idea is simple. Making the same request twice should never result in two different side effects. In a high-level design interview, you'll want to explain the difference between methods like put, which is idempotent by nature, and post, which requires us to step in with unique idempotency keys. We covered the critical four-step logic, checking for the key, processing the work, and then storing the result atomically to prevent race conditions. Using a fast storage layer like Redis with a TTL is a smart way to track these keys without hitting your main database too hard. Basically, you're building a system that can handle chaos gracefully, ensuring data consistency no matter how many times a client hits that retry button. That's how you design for true reliability. That brings us to the end of a look at idempotent APIs. When you're in a system design interview and they throw that classic network failure scenario at you, well, you're now ready to explain how idempotency keys and storage strategies like Redis prevent double billing. It's really about showing an interviewer you can handle those messy failure modes with precision, right? If you want more on building reliable systems, hit subscribe. In the next episode, we will discuss retry patterns, where we will discuss situation, core understanding, immediate retry. Keep practicing and I'll see you in the next one. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 22 of the System Engineering series, and today we will explore retry patterns in a way that helps you prepare for system engineering interviews on this topic. In a distributed world, network noise and database locks are inevitable, so mastering how your system recovers is a huge green flag for interviewers. We look at 7 core strategies, including exponential backoff and jitter, to ensure you can build resilient communication without accidentally triggering a retry storm. It's about moving beyond basic oops to production-grade stability. We begin with the fundamental chaos of distributed systems, specifically focusing on how to distinguish between two categories of errors, transient blips and permanent failures. This distinction is crucial because it tells us exactly when a retry is helpful and when it's just wasting resources. From there, we look at the immediate retry approach and the risks of triggering a retry storm that could crash a struggling service. To solve that, we explore 2 core strategies, exponential backoff and jitter. You will see how these work together to prevent thundering hertz and keep traffic flow manageable. We'll also tackle the constraints of latency budgets and how combining retries with circuit breakers provides a necessary safety valve. Well, it's also important to cover what happens when retries actually fail, so we'll look at dead letter queues and the essential role of idempotency in keeping your data consistent. By the end, you'll have a clear framework for building resilient communication, which is exactly the kind of depth interviewers are looking for when they ask about system reliability. Let's set the scene with a situation you'll likely encounter. Imagine you're operating a high-traffic microservices architecture, where services are making thousands of requests per second. Suddenly, a downstream database experiences a minor 2-second lag. If your services aren't using smart retry patterns, they might immediately surface errors to the user. Or even worse, they might all try to hit the database again the exact millisecond it recovers, knocking it right back down. What matters here is that at scale, small constraints like connection pool limits and network congestion become major bottlenecks. The failure mode here isn't just a single error, it's a cascading failure across your entire fleet. In an interview, explaining this context shows you understand that your code doesn't live in a vacuum. You're demonstrating that you know how to protect the system's stability while still trying to provide a seamless experience for the user. It's all about finding that balance between being persistent enough to succeed and being polite enough not to overwhelm your dependencies. Mastering retry patterns is about more than just a simple loop. It's about designing for resiliency. It works by intercepting exceptions from remote calls and deciding based on the error type whether to wait and try again. What matters here is that network reliability is essentially a myth in cloud environments. You have to assume that every call could fail. The primary failure mode here is over-optimism, assuming that if you just try again enough times, it will eventually work. This can lead to resource exhaustion, where your application spends all its time retrying dead requests rather than serving new ones. In a system design interview, you want to show that you've thought about the trade-offs of these patterns. You aren't just adding retries to be safe, you're doing it with specific limits and guardrails. It's about building a system that can gracefully handle the unhappy part just as well as it handles the successful one, ensuring that transient issues stay transient instead of becoming permanent outages for your users. In a world of microservices, chaos is the only constant. We're talking about temporary network blips, database locks, and downstream service reboots that are completely inevitable. These events work as noise in your system, and how you handle that noise determines your overall uptime. What matters here is that if every minor interruption triggers a high-severity alert, your team will burn out and your users will lose trust. However, the failure mode to watch for here is amplification. If your retry logic is too aggressive, it can turn a tiny blip into a total system collapse. One simple way to picture this is a feedback loop in an audio system. A small sound gets amplified until it's a deafening roar. In an interview, when you're asked about service communication, bringing up this chaos shows you're a realist. You're acknowledging that the network is unreliable and that you've built your architecture to absorb these shocks rather than letting them pass through to the end user. It's about creating a buffer that keeps the system stable under pressure. A critical part of any retry strategy is distinguishing between transient and permanent errors. Transient errors like a 503 service unavailable or a 429 too many requests are temporary issues where a retry actually makes sense because the situation might change in a few milliseconds. Permanent errors like a 404 not found or 401 unauthorized will never succeed no matter how many times you try. Retrying a 401 is just a waste of compute and time. What matters here is that it saves your system from spinning its wheels on problems that require a code change or human intervention. The failure mode here is misclassification. If you treat a permanent error as transient, you're just adding unnecessary latency and load to your system. In an interview, you should mention that your retry logic always inspects the error code first. This shows you're thinking about the cost of each retry and that you're prioritizing system efficiency. It's a key sign of a senior level understanding of how distributed systems actually behave under stress, Now, the simplest approach is the immediate retry mechanism. It works by having the client resubmit a failed request the very moment it receives an error, with no delay at all. It's effective for those incredibly brief sub-millisecond network glitches that happen occasionally. It matters because it offers the lowest possible latency for a successful recovery. Well, the downside is that it's extremely risky. The major failure mode is that it's incredibly aggressive. If the downstream service is already struggling with load, hitting it again immediately is the worst thing you can do. You're effectively kicking someone while they're down. From an architectural perspective, this is often too blunt an instrument for modern high-scale systems. In an interview, you'd explain that while you might start with this for very specific low-risk calls, you generally want something more controlled. It's important to justify why this simple approach might be insufficient and what better alternatives you'd consider to protect the health of the broader ecosystem of services. When immediate retries go wrong, you get a retry storm. This works as a massive synchronized wave of traffic where every client hits the failing service simultaneously. It matters because this can turn a minor slowdown into a total outage, creating a self-inflicted denial of service attack. The failure mode here is a complete system collapse. Instead of just one service being slow, every service that calls it starts to time out because they're all stuck in a loop of failed retries. In an interview, you'll want to describe this as a thundering herd on steroids. It's a perfect example of how local optimizations trying to make your one request succeed can lead to global failures. The trade-off is between individual request success and the stability of the entire platform. When you're designing these systems, you have to be a good citizen and realize that being too persistent can actually be destructive. Explaining this risk shows you have the architectural foresight to avoid building systems that accidentally destroy themselves when things get a little bit bumpy. To avoid those storms, we use exponential backoff. Instead of hammering a service, we increase the delay between each attempt. This works by giving the failing service more and more time to recover as we continue to fail. It matters because it effectively throttles the traffic, allowing the downstream system to clear its queue and get back on its feet. However, a failure mode here is increased user latency. If you back off too far, the user might be waiting seconds for a response that should have taken milliseconds. You're trading off a quick error for a slow success. In an interview, this is a great place to talk about the balance of system health and user experience. You're showing that you know how to give a struggling dependency some breathing room. It's a much more sophisticated way to handle failure than just trying again as fast as possible. By spreading out the load over time, you significantly increase the chances that your later retries will actually land when the service is ready. The back-off algorithm usually follows a formula like delay equals a base time multiplied by 2 to the power of the attempt number. So if your base is 100 ms, your sequence is 100, 200, 400 and so on. This works by creating an expanding window of time between requests. It matters because it provides a predictable mathematical way to scale back your regression. But there's a failure mode. You have to cap the maximum delay. Without a limit, the wait times could eventually reach minutes, which is useless for a real-time app. When you're explaining this in an interview, be sure to mention the importance of a max back-off ceiling. You also need to think about how to choose that initial base value. Too small and you're still too aggressive, too large and you're making the system feel slow. It's a fine-tuning process that depends on your specific service level objectives. Showing that you understand the math and the practical limits of this algorithm signals that you're ready to implement this in a real production environment. Even with back-off, you can still face the thundering herd if all your clients are perfectly synchronized. If 1,000 clients fail at the same time and use the same formula, they'll all retry at the exact same 100 ms mark, then the 200 ms mark, and so on. This works as a series of massive pulses that can still crash a server. The solution is jitter, which is just adding some randomness to the delay. Instead of exactly 100 ms, maybe one client waits 95 ms and another waits 105 ms. What matters here is that it breaks that synchronization, turning those pulses into a steady, manageable flow of traffic. The failure mode here is using a poor random distribution that doesn't actually spread the load. In an interview, bringing up jitter is a massive green flag. It shows you've thought about how your code behaves when it's running on thousands of machines at once. It's about moving from a single client mindset to a total system mindset, which is exactly what senior engineers are expected to do in high-scale environments. We also have to consider latency budgets and timeouts. Every request has a total time it's allowed to take. This works by setting an overall limit for the entire operation, including all its retries. It matters because if your total retry time exceeds the calling service's timeout, you're just wasting work on a request that has already been abandoned by the user. A major failure mode is zombie requests, where your retry loop keeps running long after the caller has given up and moved on. This clogs up your threads and resources for no reason. In an interview, you should talk about how you coordinate these timeouts across the entire call chain. You want to fail fast if you know you're going to exceed your budget anyway. It's about being efficient with your resources and recognizing when an operation is a lost cause. This prevents a single slow dependency from causing a backup that affects every other part of your service, which is a key part of maintaining overall system throughput. For even better protection, we integrate circuit breakers with our retries. While retries say, try again, circuit breakers say, stop trying entirely for a while. This works by tracking the failure rate. If it gets too high, the circuit opens and all requests fail immediately without even trying the downstream call. It matters because it gives a failing service total relief, which is often the only way it can truly recover from a massive overload. The failure mode to watch for is a misconfigured threshold where the circuit opens too easily or stays open too long, causing unnecessary downtime. In an interview, explain how these two patterns complement each other. Retries handle the small transient blips while the circuit breaker handles the sustained outages. This dual-layered defense is a hallmark of a robust architecture. It shows you're not just hoping things work. You've built a system that can actively protect itself and its neighbors when things go south, which is exactly what a resilient distributed system needs to do. So, what happens when you've exhausted all your retries and the circuit breaker is still open? This is where dead letter queue or DLQ escalation comes in. It works by taking that failed request and moving it to a separate storage area for later processing or manual inspection. What matters here is that it ensures that even when things are broken, you don't just lose data. The failure mode here is silent failure, where nobody is actually monitoring the DLQ and it just fills up until it crashes the queuing system. In an interview, you should describe this as an ultimate safety net. It allows the system to admit defeat on a specific request without losing the user's intent. You might have a background worker try it again an hour later, or an engineer might look at it to see if it was a malformed payload. By offloading these failures, you keep your main processing pipelines clear and responsive. It's a critical part of building an auditable, reliable system that can handle the worst-case scenarios gracefully. You absolutely cannot talk about retries without talking about idempotency. It's the absolute rule for safe retry execution. It works by ensuring that doing the same thing multiple times has the same effect as doing it once. What matters here is that if a call succeeds on the server but the response is lost on the network, the client will retry. If that's a payment call, you don't want to bill the customer twice, right? The major failure mode is retrying a non-idempotent operation, which leads to duplicate data and corrupted state. In an interview, you must mention idempotency keys, unique IDs the server uses to recognize a duplicate request and return the cached result instead of reprocessing it. This is the safety mechanism that makes all our other retry strategies possible. Without it, retries are actually dangerous. Showing you understand this risk is a huge signal to an interviewer that you're a senior engineer who cares about data integrity just as much as you care about system availability. When you're answering an interview question about reliability, you want to show you have a complete framework. Interviewers aren't just looking for the word retry. They want to hear about 5 main things: identifying transient errors, using exponential backoff, adding jitter, respecting latency budgets, and ensuring idempotency. A strong answer will also mention circuit breakers as a way to protect the downstream service. You're signaling that you understand the trade-offs, that retries improve availability but increase load and latency. A classic failure mode in these interviews is suggesting infinite retries. Avoid that at all costs. Instead, talk about your limits and what happens when those limits are hit, like using a dead letter queue. By covering these points, you show you've dealt with these issues in production and that you're prepared to handle the messy, unpredictable nature of real-world distributed systems. It's about demonstrating that you can build a system that is both persistent and safe, which is exactly what companies are looking for in their senior talent. So, we've wrapped up how to handle those inevitable blips in distributed systems. The mental model here is all about balancing persistence with politeness. We covered 3 core strategies: immediate retries for quick fixes, exponential backoff to give services room to breathe, and jitter to break up those dangerous thundering herd traffic spikes. In a design interview, you've got to show you understand the trade-offs. Sure, retries build resilience, but without idempotency and strict retry limits, you're just risking a serious attack. By layering in circuit breakers and dead letter queues for the persistent failures, you're not just blindly hammering a server, you're building a sophisticated recovery loop. That's the difference between a brittle system and one that's truly production ready. That's a wrap on episode 22. We've covered why building resilient communication means balancing retries with safety. For your next system design interview, remember that a simple retry whoop isn't enough. You'll want to demonstrate how you manage the 7 core elements: immediate retries, exponential backoff, jitter, retry limits, circuit breakers, idempotency, and dead letter queues. Explaining how these prevent cascading failures shows you've got a handle on real-world bottlenecks. If you're finding this useful, hit subscribe to keep leveling up. In the next episode, we will discuss leader election, where we'll discuss situation, core understanding, purpose. Good luck with your preparation, and I'll see you there. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 23 of the System Engineering series, and today we will explore leader election in a way that helps you prepare for system engineering interviews on this topic. So, knowing how a cluster designates a single coordinator is essential for preventing data chaos and split brain scenarios. In an interview, being able to explain the mechanics of Raft or Paxos shows you've got the depth to maintain consistency and serializable writes when things inevitably go sideways. We begin with the technical chaos that erupts when a distributed cluster lacks a single voice, establishing why a coordinator is essential for serializing writes and keeping history predictable. This leads into the core process of leader election, where we designate one node as the authoritative source of truth. We'll explore 2 primary use cases, distributed scheduling and metadata management, to see how a leader prevents duplicate work and keeps the system's view of data consistent. Then, we dive into the heavy hitters, Raft and Paxos. These algorithms are the backbone of consensus, and knowing how they handle votes and proposals is a high-value signal for any system design interview. Once a leader is in place, we'll look at how heartbeats and failover mechanisms manage the transition when that leader eventually crashes. It's also vital to prevent the split brain nightmare, so we'll examine how quorums ensure only one leader can act at a time. By the end, you'll understand how these components weave together into a complete consensus system to keep your architecture resilient and synchronized. You've built a high-scale application with a cluster of 5 nodes. Everything seems fine until 2 different nodes decide to run the same cleanup task at the exact same time. They both try to update the same row in your database, Or worse, they both try to delete the same file from S3. This is the classic race condition, but at a cluster-wide level. Without a leader, your system is basically a group of people trying to drive a car where everyone has their own steering wheel. It's a mess. In an interview, you might be asked how to scale a task scheduler. If your answer is just run more nodes, the interviewer is waiting for you to spot this exact problem. You need a way to ensure that for certain critical operations, only one node is the boss. The constraint here is reliability. If that boss node dies, the whole system shouldn't just stop. You need a dynamic way to pick a new one without human intervention. That's the real-world engineering challenge we are solving here. Imagine that 5-node cluster again. If every node thinks it's the boss and starts scheduling tasks or updating global counters, you're looking at total chaos. We call this a lack of coordination, and the consequence is usually data corruption or inconsistent state. To keep things consistent, the cluster needs one node to act as the coordinator, the single source of truth for specific operations. Now, why does this matter? Well, it simplifies the architecture significantly. Instead of every node trying to reach a consensus with everyone else for every tiny update, which is incredibly slow and complex, they just talk to the leader. But here's the catch. That leader is a single point of failure. If it crashes and you don't have an election mechanism, the whole operation grinds to a halt. A common failure mode in interviews is forgetting that while a leader solves consistency, it introduces a bottleneck. You have to design the election so it's fast enough that the downtime during a leader change is barely noticeable to the rest of the system. At its heart, leader election is the formal process where a distributed group of nodes agrees on a single master or leader. This node becomes the authoritative voice for the cluster state. It's how we move from a collection of independent actors to a unified system. What matters here is that it creates a clear hierarchy for decision making, which is much more efficient than a pure peer-to-peer model for things like writing to a database. In an interview, you'll want to emphasize that this leadership is temporary. The node is only the leader until it fails or a network partition occurs. One major failure mode to watch out for is the zombie leader, a node that thinks it's still the leader but has been cut off from the rest of the group. If it continues to issue commands, it can cause massive inconsistencies. That's why we use concepts like terms or epochs to ensure that an old leader can't override a new one. It's about ensuring that at any single point in time, there is only one valid authority. Coordination is the secret sauce that makes distributed systems feel like a single cohesive unit. Its main job is to serialize writes and prevent duplicate tasks. If two nodes try to update the same record, the leader decides who goes first, ensuring a predictable, linear history of events. Without this, you'd have to use heavy all-to-all consensus for every single operation, and that just doesn't scale. It's far too slow. By electing a leader, we consolidate that responsibility. However, there's a massive trade-off here. The leader becomes the primary bottleneck for the entire cluster's throughput. If you're being interviewed on system design, you should mention that while coordination solves consistency, it limits how many writes you can handle per second. A common failure mode happens when the leader gets overloaded with coordination overhead and starts lagging on heartbeats, causing the cluster to mistakenly think it's dead and trigger an unnecessary expensive election. Balancing this coordination load is the difference between a stable system and one that's constantly flapping between leaders. Let's look at a practical example, a cluster of workers that needs to run a heavy daily report. If you have 5 workers and no leader and the clock hits midnight, all 5 might try to run that report simultaneously. You've just slammed your database with 5 times the necessary load and you've probably generated 5 identical reports. It's a waste of resources and potentially dangerous for your data integrity. By electing one node as the scheduler, you ensure that the job runs exactly once. The leader is the only one authorized to trigger the task. In an interview setting, this is a great way to demonstrate your understanding of resource efficiency. But consider the failure mode. If the leader fails right as the task is supposed to start and the election takes too long, the report might not run at all. You have to build the system so the new leader can pick up exactly where the old one left off, which usually requires some form of persistent state shared among the nodes or stored in a highly available store like Zookeeper. Think about systems like Kafka or HDFS. They handle massive amounts of data, but someone has to keep track of where that data is. That's metadata management. A leader node, often called a controller or name node, manages the partitions and monitors the health of all other nodes. This ensures that every client gets the same, consistent view of the cluster. If every node tried to manage its own metadata view, the system would quickly fall apart as nodes went in and out of sync. What matters here is that it decouples the data movement from the control logic. However, the bottleneck here is the metadata itself. If it can't keep up with the updates, the whole cluster slows down. An interviewer might ask how you'd handle a massive burst of new partitions. If your metadata leader is the bottleneck, the system can't scale. A critical failure mode is when the metadata leader's storage gets corrupted or its network lags, leading to stale metadata being served, which results in clients trying to read data from nodes that no longer have it. When we talk about how to actually pick a leader, Raft is usually the go-to because it was designed specifically to be understandable. It uses a system of terms and heartbeats. If a node doesn't hear from the leader for a while, it becomes a candidate and asks the other nodes for votes. If it gets a majority, it's the new leader. It's a very democratic, step-by-step process. What matters here is that it provides a clear, provable way to reach consensus. In an interview, you describe this as a majority win system. But the failure mode here is split votes. If multiple nodes become candidates at the exact same time, they might split the votes, so nobody gets a majority, and the cluster just sits there until a timeout triggers a new round. Raft solves this using randomized election timeouts. Basically, every node waits a different amount of time before trying to become leader again. This ensures that one node usually wakes up first and wins the election before the others even start, keeping the transition smooth and fast. Long before Raft, we had PACELC. It's the mathematically rigorous grandfather of all consensus algorithms. It's built around roles like proposers, acceptors, and learners. While Raft is easier to explain, PACELC is what many of the original giant systems like Google's Chubby were built on. It's designed to ensure agreement even in incredibly unreliable networks where messages can be lost, delayed, or reordered indefinitely. What matters here is that it's the gold standard for correctness. However, the trade-off is extreme complexity. Implementing PACELC correctly is notoriously difficult, and many early versions had subtle bugs that only showed up under rare network conditions. In an interview, mentioning PACELC shows you know the history and the deep theory. But you should also acknowledge that most modern teams prefer Raft or specialized variants because they're easier to maintain and debug. A failure mode in PACELC implementation is often live lock, where two proposers keep preempting each other, preventing the system from ever reaching a final decision, effectively stalling the entire cluster indefinitely. Getting elected is only half the battle. The leader has to prove it's still capable of leading. This is where heartbeats come in. These are small, periodic messages the leader sends to all the followers. It's essentially the leader saying, I am still here and I am still the boss. This constant pulse is what keeps the cluster stable. If the followers stop receiving these heartbeats for a predefined timeout period, they assume the leader has crashed or been partitioned away, and they'll immediately trigger a new election. What matters here is that it's our primary mechanism for fault detection. However, there's a delicate balance with the timeout duration. If the timeout is too short, a tiny network blip can cause a false positive, leading to unnecessary elections that disrupt the system. If it's too long, the system sits idle for ages before realizing the leader is gone. In an interview, you'll want to discuss this trade-off between availability and stability. It's a classic tuning challenge in distributed engineering where you're adjusting for network jitter. When that leader does eventually fail, and in distributed systems it will fail, the system enters the failover phase. This is the transition where the cluster detects the loss and promotes a new candidate. The goal is to do this without losing any data or violating the consistency rules we've worked so hard to establish. This is critical because the faster and more reliably you can failover, the higher your uptime or availability will be. In an interview, this is where you talk about the recovery time objective or RTO. A major failure mode during failover is when the new leader isn't fully caught up with the old leader's state. If it starts taking new commands before it has finished syncing the old logs, you end up with a hole in your data history. This is why protocols like Raft ensure that only a node with a sufficiently up-to-date log can actually win an election. You're trading a slightly longer election time for the guarantee that the new leader won't accidentally revert the system to an older state. The absolute worst-case scenario in leader election is split brain. This happens when a network partition cuts the cluster in half and both sides think the leader on the other side is dead. If both sides elect their own leader, you now have two nodes claiming to be the boss of the same data. They'll both start accepting rights and your data will diverge into two conflicting histories. It's a nightmare to fix. To prevent this, we use quorums. A leader must have the support of a strict majority, more than half of the entire cluster to act. Since you can only have one majority in any partition, you can only have one leader. This is a crucial point for interviews. You prioritize consistency over availability in this scenario. The failure mode of a quorum system is that if you lose too many nodes, say 3 out of 5, the remaining 2 can't form a majority. Even though they are healthy, they can't elect a leader, and the system becomes read-only or goes offline entirely. That's the price you pay for guaranteed consistency. It's important to remember that leader election isn't just an isolated trick, it's a core component of a broader consensus system. These systems are designed to ensure that even when nodes fail or networks act up, every healthy node eventually agrees on a single value or a specific sequence of events. Leader elections of the whole cluster. Since the leader often has to wait for a majority of followers to acknowledge a right, one or two slow followers can create a significant bottleneck for the entire system's latency. So, we've broken down why leader election is the secret sauce for keeping a distributed cluster from falling into total chaos. The big takeaway here is that having one authoritative voice prevents double scheduling and keeps your metadata consistent. In a design interview, you'll want to highlight that this isn't just about picking a boss, it's about consensus. We looked at rafts, terms, and heartbeats versus the rigorous foundations of Paxos. We also covered how those heartbeats act as a life support system. If they stop, the cluster does a failover to keep things moving. By mastering these three components, consensus algorithms, health monitoring, and split brain prevention, you can confidently explain how to maintain a single source of truth even when the network gets messy. That's how you build a system that's both predictable and resilient, right? That's a wrap on leader election. Well, you've now got the tools to explain how heartbeats and quorums keep a cluster sane. In an interview setting, focus on the trade-offs of your design choices. For instance, explaining why a specific timeout length matters for balancing fast failover against system stability is a huge signal. Make sure you can justify why a majority quorum is non-negotiable for avoiding split-brain scenarios. So for more deep dives, go ahead and subscribe. In the next episode, we will discuss distributed locking, where we will discuss situation, core understanding, purpose. Happy system designing. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 24 of the System Engineering series, and today we will explore distributed locking in a way that helps you prepare for system engineering interviews on this topic. When distributed processes compete for the same resource, it's easy for things to break without a central source of truth. So we'll dive into two main lock types, exclusive and shared, and see how tools like Redis and Zookeeper handle them. Showing you can navigate these implementation trade-offs is exactly what interviewers want to see when you're designing reliable, high-scale systems. We begin with the competition problem, where we'll see what happens when distributed processes clash over the same resource and how mutual exclusion provides that necessary source of truth. It starts by breaking down the two main lock types, exclusive and shared, before we dive into real-world implementations like Redis and the red lock algorithm. Now, it is not only about setting a flag, it's about reliability, right? So we'll explore how leases and time to live values keep things moving if a process crashes, and we'll address the risks of deadlocks and clock drift. We are also going to spend some time on consistency, especially why things like fencing tokens and monotonic ordering are absolute requirements to prevent delayed processes from corrupting your data. Finally, we look at the high-level trade-offs for your interviews, comparing these locks to standard database transactions. By the end, you'll have a clear framework for deciding when and how to coordinate distributed resources without sacrificing system correctness. Let's set the scene with a real engineering challenge. Imagine you're building a massive payment processing system that handles thousands of transactions a second across a global cluster of microservices. You have a specific requirement. No user should ever be double charged for a single purchase. However, because of network retries and load balancing, multiple instances of your billing service might receive the exact same payment request at the same time. This is where distributed locking becomes critical. Without it, those instances would all try to process the payment simultaneously, leading to duplicate entries and unhappy customers. The failure mode here is a direct hit to your company's reputation and bottom line. You're operating under strict constraints of high availability and low latency, yet you cannot compromise on correctness. In this production context, a local mutex on one server won't help you because the requests are hitting different machines. You need a way for these machines to talk to each other and agree on who has the right to process that specific transaction ID before anyone touches the database. Mastering resource coordination is really about mastering the chaos of high-scale systems. Distributed locking works by allowing one node to claim a temporary exclusive right to a resource across the entire network. What matters here is that in a world where nodes can fail or lag at any moment, we need a reliable way to ensure that tasks that should only happen once actually only happen once. Think about a bad job that generates a daily report. If 5 nodes started, you're wasting money and potentially corrupting the file. The primary failure mode to keep in mind for your interviews is the loss of liveness. If a node grabs the lock and then crashes without releasing it, the resource could be stuck forever. We solve this by introducing timeouts, but that leads to its own set of problems, like a lock expiring while the node is still working. Understanding how to navigate this tension between safety and liveness is the hallmark of a senior system engineer. We are going to break down how to handle these edge cases throughout this lesson. Imagine you've got 3 different worker nodes, all trying to update the same user profile or subtract from the same inventory count at the exact same millisecond. This is the competition problem. Without a locking mechanism, you're looking at classic race conditions, where the final state of your data depends entirely on the random timing of network packets. It's a huge issue because it leads to silent data corruption that's incredibly hard to debug after the fact. You might see a balance of $10 become 20 instead of 15 because 2 processes read the polled value simultaneously. The failure mode here isn't just a crash, it's an inconsistent database that looks fine on the surface but is fundamentally wrong. In an interview, you'll want to highlight that this isn't just about speed, it's about correctness. We need a way to ensure that these competing processes queue up and wait their turn, transforming a chaotic free-for-all into a predictable, serial stream of updates that preserves the integrity of our shared state. The core of distributed locking is about establishing a single central source of truth for resource ownership. In a distributed environment, you've got dozens or hundreds of nodes, but they all need to agree on which one owns a specific resource right now. This coordination works by having a central lock manager, like Redis or Zookeeper, that acts as the ultimate arbiter. What matters here is that it prevents the split brain scenario, where 2 different nodes both think they are the leader or the sole worker for a task. If you don't have this central coordination, your system effectively has no memory of who is doing what, leading to total chaos in your data layer. The failure mode to watch for here is the bottleneck. If every single operation requires a round trip to the lock manager, that central hub becomes a massive point of contention. In an interview, you'll want to discuss how to minimize this by only locking the specific granular resources you need rather than putting a giant lock over your entire database. It's all about balancing that central control with the performance needs of a distributed system. At its heart, distributed locking is about enforcing mutual exclusion. This simply means that if process A is working on a resource, process B is strictly forbidden from touching it until process A is finished. It's the digital equivalent of a one person at a time bathroom lock. What matters here is that it's the only way to guarantee that complex multi-step operations remain atomic and consistent. Without mutual exclusion, you risk a collision, where 2 processes try to write to the same file simultaneously, resulting in a corrupted mess that neither can use. The failure mode here usually stems from network delays. If a process takes too long and the lock manager thinks it's gone, it might grant the lock to someone else while the first process is still mid-write. This is why mutual exclusion in a distributed system is much harder than on a single machine. You can't just stop the world. You have to account for the fact that exclusive is a relative term when clocks drift and networks lag. When an interviewer asks about safety, they're asking how you maintain this exclusion despite those environmental failures. Let's talk about exclusive locks, also known as write locks. These are the most restrictive type of lock you can use. How they work is simple. If a node holds an exclusive lock, no other process can read or write to that resource, period. This is absolutely essential for operations that change data, like updating an account balance or modifying a configuration file. If you allowed someone else to read the data while it was being updated, they'd get a dirty or partial view that could lead to further errors downstream. The trade-off here is high consistency at the cost of high contention. The failure mode is quite clear. If an exclusive lock is held for too long, it creates a massive traffic jam. Every other service that needs that resource is effectively frozen, which can lead to cascading timeouts across your entire system. In an interview, you should mention that while exclusive locks are the safest bet for data integrity, they are the most dangerous for system availability. You have to keep the lock held time as short as humanly possible to avoid killing your throughput. Shared locks, often called read locks, offer a more flexible approach for high-traffic systems. How they work is by allowing multiple nodes to hold the lock at the same time, provided they are all just reading the data. However, as soon as a writer wants to change something, it has to wait until every single reader has released their shared lock. What matters here is that it significantly boosts performance for read-heavy workloads, while still preventing a writer from changing the data out from under someone's feet. It's a great way to scale, but there is a specific failure mode you need to know for interviews: writer starvation. If you have a constant stream of new readers coming in, the writer might never get a chance to acquire the exclusive lock it needs, causing it to wait indefinitely. You've got to implement a queuing strategy that prioritizes writing writers to keep the system healthy. Understanding this balance between maximizing read throughput and ensuring writers don't get blocked forever is exactly what an interviewer is looking for when discussing complex locking architectures. When we talk about high-performance locking, Redis is usually the first name that comes up. The basic implementation uses the setNX command, which basically says set this key only if it doesn't already exist. It's fast and memory first, which is why it's so popular. However, a single Redis instance is a single point of failure. To solve this, we use the red lock algorithm, which involves getting a majority vote from 5 independent Redis masters. You need 3 out of 5 to agree before the lock is considered valid. What matters here is that it provides a layer of fault tolerance that a single instance just can't match. But here's the catch, and this is a big one for interviews. Redlock has some known failure modes related to system clocks and GC pauses. If one node's clock jumps forward, it might expire a lock prematurely, letting another process grab it while the first one still thinks it's in control. You've got to understand these nuances to justify using Redis over a more strictly consistent tool like Zookeeper or etc. It's a classic speed versus safety trade-off. SLIs-based locks are the industry standard for preventing orphan locks in distributed systems. Instead of a lock that stays active until the process says it's done, you grant the lock with a time to live or TTL. One simple way to picture this is a rental agreement that automatically ends unless you renew it. What matters here is that if a worker node crashes or loses network connectivity, the lock will eventually expire on its own, allowing other nodes to take over the work. Without leases, a single crash could lock up a resource forever. However, the failure mode here is the split brain effect caused by long process pauses, like a stop-the-world garbage collection. If a process is paused for 10 seconds, but its lease is only 5 seconds, the lock will expire while the process is asleep. When the process wakes up, it still thinks it has the lock and might try to write to the database, causing corruption. In an interview, explain that you need to keep leases long enough to cover the work, but short enough to recover quickly from failures, and always use renewal heartbeats for long-running tasks. Deadlocks are the nightmare of any distributed system. This happens when 2 or more processes are stuck in a circular wait. Process A holds lock 1 and waits for lock 2, while process B holds lock 2 and waits for lock 1. Neither can move and they'll wait forever if you let them. To prevent this, we typically use 2 main strategies: lock ordering and timeouts. Lock ordering means we always acquire locks in a specific alphabetical or numerical sequence, which breaks the circularity. Timeouts ensure that if a process can't get a lock within a certain window, it gives up and releases everything it's holding to try again later. What matters here is that a deadlocked system is effectively a dead system. The failure mode often occurs during unexpected spikes in load, where timing becomes unpredictable, causing processes to back up and time out simultaneously. In an interview, you should emphasize that you never request multiple locks without a strict order and a fail-fast timeout policy. It's about building a system that is self-healing rather than one that requires manual intervention to clear stud processes. A common mistake is thinking that a distributed lock alone is enough to guarantee consistency. It's not. A lock is just a piece of metadata. It doesn't actually stop a rogue or delayed process from writing to your database. What matters here is that if a node's lock expires due to a network delay, but it still sends a write request to your storage layer, that storage layer will accept it unless you've built in extra protection. To ensure true correctness, you need validation at the storage layer itself. This usually involves something called monotonic ordering, where every lock comes with an increasing version number. The database checks if the incoming request's version is higher than the last one it saw. If it's not, the write is rejected. This failure mode, where a late write overwrites a newer correct write, is one of the most subtle and dangerous bugs in distributed computing. In an interview, always make it clear that the lock is the first line of defense, but the storage layer must be the final authority on whether a write is actually safe to commit. Fencing tokens are the secret weapon for making distributed locks safe. When a client acquires a lock, the lock manager also gives it a fencing token, which is just a number that increases every time a lock is granted. What matters here is that it provides a way for the storage layer to identify and ignore requests from zombie processes that have lost their locks. Imagine process A gets token 33, but then it hits a long GC pause. The lock expires and process B gets the same lock with token 34. Process B completes its work, then process A wakes up and tries to write using its old token 33. The database sees that it has already processed token 34 and simply rejects the outdated request from A. This failure mode prevention is essential for absolute data integrity. In an interview, if you mention fencing tokens, you're signaling that you understand the deep consistency issues discussed by experts like Martin Kleppmann. It's a high-level concept that proves a lock isn't a magical shield, but part of a larger, coordinated safety protocol between the lock manager and the database. Clock drift is one of those silent killers in distributed systems that can turn a perfectly designed locking strategy into a mess. We often rely on wall clock time to determine when a lease expires, but in a distributed environment, no two clocks are perfectly in sync. If one server's clock runs slightly faster than the others, it might decide a lock has expired and release it, while the actual lock holder is still busy processing. What matters here is that it breaks the fundamental guarantee of mutual exclusion. The failure mode here is catastrophic. You end up with two different processes believing they both have the exclusive right to write to a resource. This is exactly why we can't trust local system time for critical safety properties. In an interview, mentioning how NTP sync issues or hardware clock instability can compromise your lock's validity shows you're thinking about real-world physics, not just abstract code. It's a sophisticated point that demonstrates you understand why we need more robust mechanisms, like logical clocks or fencing tokens, to protect our data from the inaccuracies of physical hardware. In an interview, you're often asked if a distributed lock is even the right tool for the job. It's a bit of a trap because sometimes the best lock is no lock at all. You've got to weigh the complexity of managing a distributed lock against simpler alternatives, like using database-level transactions or optimistic concurrency control with version numbers. Distributed locking adds a lot of moving parts and latency, and it can become a massive bottleneck if every request has to wait on a central lock manager. The failure mode here is often a distributed deadlock or a performance collapse where the system spends more time managing locks than doing actual work. You'll want to show the interviewer that you're not just picking a shiny tool, but actually calculating the trade-offs. If your database supports ACID transactions, that's almost always a safer and faster bet. We only reach for distributed locks when we are coordinating across different types of resources, like a file system and a database, where no single transaction can cover the whole operation. Showing that restraint is key. We've just unpacked how distributed locking handles the chaos of multiple processes fighting for the same resource. To keep things consistent, we rely on mutual exclusion, ensuring only one owner holds the keys at a time. We explored two main lock types, exclusive locks for total isolation and shared locks for concurrent readers. In a system design interview, you've got to be ready to explain why we use lease-based locks with a TTL. It's our primary safety net against orphan locks if a process crashes. Whether you're leaning on Redis with Redlock or a consensus-heavy tool like Zookeeper, the trade-off is always between performance and strict correctness. You've now got the mental model to coordinate shared resources effectively without risking race conditions. Well, that's the foundation of distributed locking mastered. That wraps up a look at distributed locking. When you are in an interview, remember that a lock isn't a magic fix. You've got to show you understand the failure modes. Be ready to explain how fencing tokens prevent delayed processes from corrupting data and why relying on local node clocks is usually a bad move. It's all about that trade-off between complex coordination and simpler database transactions. If you're finding these deep dives helpful, go ahead and subscribe to the channel. In the next episode, we will discuss Sidecar Pattern, where we'll discuss situation, core understanding, definition. Good luck with your preparation. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 25 of the System Engineering series, and today we will explore Sidecar Pattern in a way that helps you prepare for system engineering interviews on this topic. It's a crucial concept for modern cloud-native design, since it lets us offload concerns like logging and MTLS without cluttering the main app code. In an interview, knowing when to deploy these companion containers shows you've got a deep grasp of how to build modular, maintainable systems at scale. It starts by breaking down the core architecture of the sidecar pattern, using the classic motorcycle metaphor to see how companion containers add power without changing the main application's engine. We'll look at how auxiliary services are deployed in orbit around your code, sharing the same lifecycle while remaining independent. So, we're going to focus on three specific responsibilities: handling unified logging, offloading security through MTLS, and managing advanced networking logic like retries and circuit breaking. Now, it's also important to understand the actual mechanics of local interprocess communication. So we'll examine how these containers talk to each other over localhost to keep latency low. To help you reason through architectural choices in an interview, we'll compare the sidecar approach against shared libraries and walk through real-world examples like Envoy and Fluentd. By the end, you'll understand how to justify using sidecars to achieve the separation of concerns and operational agility that modern cloud-native systems require. Imagine you're running a polyglot microservices environment with services written in Go, Python, and Java. You need to implement MTLS, structured logging, and circuit breaking across all of them consistently. Writing and maintaining libraries for every single language is an absolute maintenance nightmare. That's where the sidecar pattern enters the picture. It works by running a separate process in the same network and disk namespace as your app. What matters here is that it provides a uniform operational layer regardless of the language your app is written in. However, you've got to watch for the resource overhead. If you have 1,000 pods, you now have 1,000 extra containers to monitor and resource. A common failure mode here is under-provisioning. If the sidecar starves for CPU, it can bottleneck the main application's performance. In an interview, you will want to highlight this specific trade-off between the ease of management and the increased infrastructure cost you're accepting. Mastering companion containers is really about building modular systems that scale effectively. How it works is straightforward. You deploy two containers together as a single atomic unit. What matters here is that it allows your application developers to focus strictly on their core job without worrying about how logs get shipped or how traffic gets encrypted. A common failure mode in these modular systems is tight coupling. If the sidecar depends on specific file paths or environment variables in the main container that change during an update, the whole system breaks on deployment. In a system engineering interview, you want to show you understand that while modularity is great, it introduces a lifecycle dependency that must be managed through health checks and careful orchestration. You're effectively trading binary simplicity for operational flexibility. We'll explore how this separation allows different teams to move at different speeds, which is a massive win for large organizations, provided they can handle the slight increase in architectural complexity. Auxiliary services literally orbit your main application. They share the same life cycle, meaning they start and stop together. Why does this matter? It ensures that required infrastructure, like a logging agent or a security proxy, is always available exactly when the app is running. It works through local inter-process communication, usually via local host or shared volumes. A big failure mode you have to watch out for is startup race conditions. If your application starts up and tries to send traffic before the sidecar proxy is fully ready, those initial requests will fail, potentially triggering a crash loop. You've got to ensure the sidecar is healthy and ready to go before the main process begins its work. Interviewers often look for this kind of depth. It is not only about knowing what a sidecar is, but knowing how to manage the synchronization between these two processes. It's that shared faith that makes the configuration so powerful, but also quite delicate. Think of the motorcycle sidecar metaphor to ground this concept. The motorcycle is your core business logic, and the sidecar is the extra seating or storage you've added. It works by attaching to the frame without redesigning the engine or the transmission. What matters here is that you can upgrade the sidecar, say to update your security certificates or change your logging format without even touching your application code or needing a recompile. The risk or the failure mode is the weight it adds. If the sidecar is too heavy, buggy, or consumes too much fuel, it drags down the entire vehicle's performance. In an interview, explain how this isolation protects the engine from infrastructure-level crashes. If the sidecar process dies, you can often configure the system to restart just that container, though in many orchestrators, the whole pod might restart. It's a perfect way to visualize the physical proximity and the separate but linked nature of these two components. We use sidecars to offload cross-cutting concerns like logging, monitoring, and security. It works by intercepting or observing the main app's behavior from a separate process. What matters here is that it keeps your application code pure and language agnostic. You don't want your developers wasting time debugging a Java logging library when they should be building features. The failure mode here is silent failures. If your logging sidecar stops shipping logs but doesn't actually crash, you might lose days of critical data without knowing it. You need robust monitoring for the sidecar itself, not just the app. Interviewers love it when you discuss how this offloading simplifies the developer experience while intentionally shifting that complexity to the platform team. It's a strategic move to centralize operational logic, but it requires the platform team to provide high-quality, highly reliable sidecar images that won't break the apps they are supposed to be helping. When we look at the responsibility of unified logging, the sidecar tails the app's log files or captures the standard output stream. It works by acting as a local buffer and then shipping that data to a central aggregator. What matters here is that the app doesn't need to know anything about Splunk, ELK or S3. It just logs to the console as it normally would. A classic failure mode in this setup is disk exhaustion. If the sidecar can't ship logs fast enough to the remote server and the local buffer fills up, it might fill the shared disk space, causing the main app to fail when it tries to write its own files. You have to balance the shipping frequency with the local resource constraints to keep the whole system stable. In an interview, mention that this approach prevents a slow logging backend from ever blocking your main application's execution threads, which is a huge win for latency consistency. Security and MTLS are perhaps the most common uses for sidecars today. How it works is the sidecar intercepts all incoming traffic, handles the decryption, and then hands it to the app over a plain text localhost connection. What matters here is that individual developers don't have to manage complex cryptography libraries or keep track of local certificate files. The failure mode you have to account for is certificate expiration. If the sidecar's automation fails to rotate a certificate, the app becomes completely unteachable even though the code itself is perfectly fine. In an interview, emphasize that this centralizes security policy enforcement, making it much easier to audit and rotate secrets across your entire fleet in one go. It's a powerful way to implement a zero-trust architecture. Just remember that you're shifting the trust to the local network space, assuming that the localhost connection between the sidecar and the app is secure from outside tampering. For networking, sidecars manage things like retries, circuit breaking, and load balancing. It works by proxying all egress and ingress traffic through the sidecar's network stack. What matters here is that it provides resiliency as a service. Your app doesn't need custom retry logic for every downstream dependency. However, a major failure mode here is retry storms. If the sidecar is configured to retry too aggressively without an exponential backoff, it can accidentally DDoS a downstream service that's already struggling to recover. You need to show you understand that while sidecars add incredible power, they also require very careful tuning of timeout and retry policies to avoid these kinds of cascading failures. Interviewers want to see that you can think about the holistic behavior of the system, not just the individual service. It's about making the network smarter, but that intelligence needs to be managed so it doesn't become a liability during an outage. Communication between the app and the sidecar happens via local inter-process communication, using localhost or shared volumes. It works because they share the same network stack within a Kubernetes pod or a similar host abstraction. What matters here is that the latency is extremely low, usually sub-millisecond, which minimizes the performance hit of having an extra hop. However, the failure mode to watch for is port collision. If your sidecar and your main application accidentally try to bind to the same port on localhost, one of them will fail to start. In an interview, you should explain that while IPC is fast, it's still an extra hop that needs to be accounted for in your total latency budget. If you're building a system with a 10 millisecond SLA, adding a sidecar might take up a significant chunk of that if not optimized. It's a reminder that there's no such thing as a truly free architectural abstraction. Every layer has a cost. This pattern creates a very clean separation of concerns. Developers focus on building business features, while SREs and platform engineers focus on the sidecar configurations. It works by decoupling the release cycles of the infrastructure from the application. What matters here is that you can roll out a critical security patch to 500 different services just by updating the sidecar image in your deployment pipeline. The failure mode here is version mismatch. If the sidecar expects a specific log format or API version that the app hasn't been updated to provide yet, you'll see errors in production. You've got to ensure your contracts between the app and its sidecar are well defined and backwards compatible to avoid breaking things during rolling updates. In a design interview, highlight that this separation is what enables a large organization to scale its operational standards without slowing down the individual product teams who are shipping features daily. Take Envoy Proxy as the gold standard example of this pattern. It works as the data plane sidecar in popular service meshes like Istio. It matters because it provides deep observability and fine-grained traffic control without you having to change a single line of your application code. The failure mode you'll often run into is CPU and memory overhead. Since Envoy inspects every single packet to apply routing rules and collect metrics, it can consume a significant amount of resources. In an interview, point out that while Envoy is incredibly powerful, you are essentially trading off higher infrastructure cost for better visibility and control. You have to size your pods correctly to account for this extra overhead, or you'll see your nodes running out of memory. It's a classic architectural trade-off where you're buying operational sanity with hardware, which is usually a good deal at scale, but you have to be intentional about it. Another great example is using Fluentd agents. It works by scraping log files or listening to local streams and then forwarding them to a central sink like ELK or Splunk. What matters here is that it prevents your application from being blocked by slow network I/O when writing logs to a remote server. The failure mode here is log loss during a restart. If the sidecar crashes or the pod is evicted before it finishes flushing its internal buffer to the remote server, those logs are gone forever. To mitigate this, you often need persistent volumes of very reliable flush mechanisms. It's a great example of how sidecars manage operational complexity at the edge of your system. When you're explaining this in an interview, focus on the fact that the sidecar acts as a shock absorber for the rest of your logging infrastructure, protecting the application from failures in the data pipeline. Comparing sidecars to shared libraries is a very common interview question. Shared libraries offer the lowest possible latency because there's no inter-process communication hop, but they lock you into a specific programming language inversion. Sidecars work by providing language-agnostic services, which matters tremendously for polyglot environments where teams use different tools. The failure mode for libraries is dependency hell, where updating one library breaks several others in your app. For sidecars, the failure mode is the operational tax of running and monitoring hundreds or thousands of extra containers. You have to decide if the agility and independence provided by sidecars outweighs the slight latency increase and the extra resource cost. There's no single right answer, and showing that you can weigh these two approaches based on a company's specific needs, like their language diversity and their scale, is exactly what an interviewer wants to see in a senior candidate. When an interviewer asks why we use sidecars, they are looking for you to mention operational agility and heterogeneous environments. Explain that it works by standardizing the how of the platform while letting teams choose the what for their applications. What matters here is that it creates a clear, clean boundary between development and infrastructure. A failure mode you should definitely mention is the increased complexity of debugging. When a request fails, you have to determine if the problem is in the app, the proxy sidecar, or the network itself. This requires better tracing and observability. Showing you've thought about the monitoring challenges of this pattern is a huge green flag for an interviewer. You're demonstrating that you don't just follow trends, but you actually understand the maintenance burden they introduce. Use this to pivot into a discussion about distributed tracing and how sidecars can actually help inject the headers needed to make that tracing work. So we've broken down how the sidecar pattern acts as a companion container to your main application. Well, the logic is simple. You're offloading those annoying cross-cutting concerns so your business code stays clean. We covered three primary responsibilities: shipping logs to central sinks, managing security through MTLS, and handling resilient networking like retries and circuit breaking. Because these processes share the same lifecycle and communicate over localhost, you get low latency interactions without the app ever needing to know the complex plumbing exists. In a system design interview, this is your go-to move for justifying separation of concerns. Just remember the trade-off. You're paying a bit of a tax and resource overhead for that modularity. It's a powerful way to standardize platform features across any language or stack in your cluster. That wraps up our look at the sidecar pattern. When you're tackling this in a system design interview, focus on the operational agility it provides. You've got to highlight how offloading the three core responsibilities, logging, security, and networking, allows dev teams to stay polyglot and focus on features. It's really about that clean separation of concerns. If you want more technical deep dives, make sure to subscribe. And in the next episode, we will discuss service mesh fundamentals, where we'll discuss situation, core understanding, service mesh. Good luck with your prep, and I'll see you there. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 26 of the System Engineering series, and today we will explore service mesh fundamentals in a way that helps you prepare for system engineering interviews on this topic. Dealing with hundreds of microservices means you'll eventually hit a wall where manual networking fails. We are diving into how the control and data planes automate security and observability. Understanding these layers allow you to justify when a mesh is actually worth the complexity, which is a huge signal in design interviews. This lesson opens with the microservice chaos factor and how separating communication from application code creates a cleaner infrastructure layer. You'll understand the core architecture, specifically how the centralized control plane coordinates with the data plane's sidecar proxies to manage traffic locally. From there, we'll dive into the three pillars of mesh functionality. First is security, where we examine how MTLS provides identity and how authorization policies enforce access control. Second, we'll walk through traffic management, including dynamic routing, retries, and the circuit breaking patterns that stop cascading failures. Third, we cover unified observability through golden signal metrics, logs, and distributed tracing. We'll wrap up by looking at the critical trade-off between operational overhead and system control, which is exactly the kind of nuance interviewers look for when they ask when it's actually worth adopting a mesh. By the end, you'll be able to identify exactly when a service mesh becomes a necessary asset rather than just additional complexity. Let's set the stage with a real-world scenario you might encounter in a senior engineering interview. Imagine you're at a company that's just exploded from 10 microservices to 200. Suddenly, the simple way you handle retries, security, and logging isn't working anymore. It works fine when everyone's using the same language and library, but as teams diversify, your networking logic starts to fragment. This situation matters because it's where the limits of manual management are reached. You're facing inconsistent timeouts and blind spots in your monitoring that make debugging a nightmare. If you ignore this shift in scale, your primary failure mode will be a death by 1,000 cuts, where small network blips cause massive, unpredictable outages. Interviewers want to see that you recognize this inflection point, where the cost of managing communication in code becomes higher than the cost of implementing a mesh. It's about spotting the bottleneck before it brings the entire engineering organization to a standstill. And that's the context we're operating in today. At its heart, mastering service mesh fundamentals is about owning the infrastructure layer to ensure your distributed system is secure, observable, and fully controlled. It works by abstracting the network away from your business logic, providing a consistent way for services to talk to each other regardless of what language they are written in. What matters here is that it gives you a global knob to turn for security policies and traffic rules without ever touching a line of application code. In a technical interview, being able to articulate this separation of concerns shows a high level of architectural maturity. A common failure mode here is treating the mesh as just another library. If you don't respect it as a fundamental layer of your stack, you'll end up with leaky abstractions that confuse your developers. Think of this as the nervous system of your microservices. It's what allows the entire body of your application to coordinate effectively, and understanding its underlying mechanics is the first step towards building truly resilient enterprise-grade cloud environments. We have to talk about the microservice chaos factor because it's the primary driver for mesh adoption. As your service count grows into the hundreds, managing security and traffic manually within your code becomes completely unmanageable. It works well enough for a small team, but at scale, every team starts implementing retries and headers slightly differently. What matters here is that inconsistency leads to fragile systems where you can't guarantee how a request will behave as it hops through 10 different services. The failure mode here is a total loss of visibility. You'll have an error happening somewhere in a deep chain and you won't have the unified metrics to find it. In an interview, pointing out that manual management is error-prone and doesn't scale is a key observation. You are highlighting that the chaos isn't just about the number of services, but the lack of a standardized way to govern their interactions. This chaos is exactly what we are aiming to solve by shifting the responsibility from the developer to the platform. Defining the infrastructure layer is the first step in bringing order to that chaos. A service mesh works as a dedicated layer that sits right next to your applications, handling all service-to-service communication independently of the business logic. What matters here is that it creates a clear boundary. Developers focus on features while the platform handles the network. If you don't define this layer clearly, you end up with networking code scattered across every repository, which is a major failure mode for long-term maintainability. In an interview setting, you want to emphasize that this layer provides a uniform way to apply policies. Whether a service is written in Go, Java, or Python, the mesh treats them all the same way. The failure to treat networking as infrastructure leads to dependency hell, where you're constantly updating client libraries across dozens of teams just to change a timeout setting. By establishing this dedicated layer, we ensure that the network is a reliable, invisible utility rather than a constant source of friction for the engineering organization. Decoupled communication management is the superpower of a service mesh. It works by pulling complex networking logic like circuit breaking and retries out of the application code and moving it into the mesh. What matters here is that it allows your services to stay lean and focused on their actual jobs. Imagine the relief for a developer who no longer has to worry about implementing complex MTLS handshakes or sophisticated load balancing algorithms themselves. However, the failure mode you need to watch for is the added latency and resource overhead that comes with this decoupling. Every request now has to pass through an extra hop, and if your mesh isn't tuned correctly, that can add up. In an interview, it's crucial to acknowledge this trade-off. You're gaining developer velocity and operational consistency, but you're paying for it with a bit of extra CPU and millisecond delay. A strong candidate knows that decoupling isn't a free lunch. It's a calculated decision to trade some performance for a massive increase in system-wide reliability and manageability. The control plane is the centralized brain of the entire service mesh. It works by taking your high-level policies like service A can only talk to service B and translating them into specific configurations for all the proxies in the system. What matters here is that it gives you a single point of authority to manage the entire network's behavior. Without a centralized brain, you'd be back to manually configuring hundreds of individual endpoints, which is a recipe for disaster. Now, a critical failure mode to discuss in an interview is the availability of the control plane itself. If it goes down, your data plane proxies will usually keep running with their last known configuration, but you will be unable to push any new changes. This stale state can be dangerous if you need to quickly block a compromised service or change a routing rule during an incident. You've got to ensure the control plane is highly available and resilient, because while it's not in the direct path of every request, its absence freezes your ability to adapt to changes. Now, let's talk about the data plane, which is made up of sidecar proxies. These proxies work by running right alongside every single service instance, intercepting all the incoming and outgoing traffic. What matters here is that it's where the actual work of the mesh happens. Things like encryption, load balancing, and metrics collection are all executed right here at the edge. A major failure mode for the data plane is resource exhaustion. If your sidecar consumes too much memory or CPU, it can starve the actual application it's supposed to be helping. In an interview, you should mention that the sidecar pattern is what enables the mesh to be language agnostic, which is a huge architectural win. However, you also have to be aware of the sidecar sprawl problem. Managing the lifecycle of thousands of these proxies requires robust automation, or else you'll end up with version mismatches and inconsistent behavior across your cluster. The data plane is where the rubber meets the road, providing the local enforcement for the global policy set by the control plane. Mutual TLS or MTLS is how a service mesh handles identity and security. It works by requiring both the client and the server to present certificates to each other, ensuring that both ends of the conversation are authenticated and the traffic is encrypted. What matters here is that it moves us towards a zero-trust architecture, where we don't assume the internal network is safe. In an interview, you'll want to highlight that the mesh automates the issuance and rotation of these certificates, which is a massive task to do manually. The failure mode here is usually related to certificate expiration or a failure in the certificate authority within the control plane. If the automation fails and certificates aren't renewed, your services will suddenly stop trusting each other, leading to a complete system-wide outage. It's a high-impact failure that proves why robust monitoring of your mesh's health is non-negotiable. You're trading the simplicity of plain text communication for a much stronger security posture, but you're also taking on the responsibility of managing a complex, distributed identity system. Dynamic request routing gives you incredible control over how traffic flows through your system. It works by allowing the mesh to inspect things like HTTP headers or cookie data to decide exactly where to send a request. What matters here is that it's the foundation for modern deployment strategies like A/B testing or canary releases, where you might want to send only 5% of traffic to a new version of a service. A common failure mode is misconfiguring these routing rules, which can lead to traffic black holes or requests being sent to the wrong environment. In an interview, explaining how dynamic routing reduces the risk of new releases is a great way to show you value operational safety. You can shift traffic away from a failing version in seconds without having to redeploy any code. It's a powerful tool for maintaining high availability, but it requires clear visibility to ensure that your traffic is actually going where you think it is. Without that feedback loop, dynamic routing can quickly become a source of confusion during a complex rollout. Standardizing network resilience is much easier with automatic retries and timeouts. The mesh works by enforcing these rules at the proxy level, so every service gets a consistent safety net without developers having to write custom logic. What matters here is that it prevents one slow service from dragging down the entire system by holding onto connections for too long. However, there's a significant failure mode you must mention in an interview, the retry storm. If a downstream service is struggling and every upstream service starts retrying multiple times, you can actually amplify the failure and knock the service completely offline. That's why it's vital to combine retries with jitter and back-off strategies. The goal is to be resilient to transient blips without making a bad situation worse. When you're asked about this in a system design interview, always mention that while the mesh makes it easy to add retries, you have to be careful with the configuration to avoid accidentally DOSing your own infrastructure. It's about finding the balance between persistence and system-wide stability. Failover and circuit breaking are your last lines of defense against cascading failures. These work by having the mesh monitor the health of service instances and tripping a circuit breaker if failure rates exceed a certain threshold. What matters here is that it stops a failing service from being bombarded with requests, giving it a chance to recover while protecting the rest of the system. In an interview, emphasize that this is how you achieve graceful degradation. You'd rather return a controlled error than let the whole system hang. A failure mode to watch for is setting these thresholds too aggressively, which might eject faulty instances during a minor spike in latency, actually reducing your capacity when you need it most. Conversely, setting them too high makes them useless during a real crisis. Getting this right requires a deep understanding of your service's baseline performance. When you can explain the mechanics of how a mesh ejects an unhealthy pod from the load balancing pool, you're demonstrating the kind of operational thinking that top-tier companies are looking for. Unified metrics collection is one of the most immediate benefits of a service mesh. It works by having every sidecar proxy automatically record the 4 golden signals: latency, traffic, errors, and saturation. What matters here is that you get a consistent bird's-eye view of your entire system's health without having to ask developers to instrument every single endpoint manually. In an interview, highlight how this solves the missing metrics problem that often plagues large microservice architectures. A major failure mode here, however, is metric cardinality explosion. If you're not careful about how you label and store this data, the sheer volume of metrics from hundreds of proxies can overwhelm your monitoring system and lead to massive storage costs. You've got to find the right balance between granular detail and operational overhead. When you can talk about the importance of having a standardized dashboard for every service link, you're showing that you understand how observability is the key to maintaining complex distributed systems over the long haul. Standardized access logs provide a clear, consistent audit trail for every interaction in your mesh. It works by having the proxies generate logs in a uniform format, capturing details like source, destination, response code, and request duration. What matters here is that when you're debugging a cross-service issue, you don't want to spend time translating different log formats from 5 different teams. You want a single, coherent narrative of what happened. From an interview perspective, the failure mode to discuss is the sheer volume of logs and the resulting ingestion bottleneck. Logging every single request can be incredibly expensive and can even impact the performance of your logging pipeline. Strong candidates will talk about sampling strategies, only logging a percentage of successful requests while capturing all errors. This gives you the visibility you need for debugging and auditing without breaking the bank or slowing down the network. It's about being pragmatic with your data collection so that your logs remain a helpful tool rather than an unmanageable mountain of expensive noise. Distributed request tracing is what allows you to reconstruct the full path of a single request across many microservices. It works by having the mesh inject and propagate unique trace headers as a request moves through the system. What matters here is that in a complex environment, a single user action might touch 20 different services, and without tracing, you'd have no way to see where the slowness is actually coming from. In a technical interview, you need to point out a crucial failure mode: header propagation. While the mesh does the heavy lifting, the application code still has to pass those headers from the incoming request to any outgoing calls. If a developer forgets to do this, the trace is broken and you lose visibility. This is a common pitfall that proves that even with a mesh, you still need a baseline of cooperation from the application. Tracing is the only way to truly understand the performance bottlenecks in a distributed system, and mastering it is a hallmark of a senior system engineer. Security in a service mesh goes beyond encryption. It's about fine-grained access control. This works by applying authorization policies that specify exactly which services are allowed to call which APIs. What matters here is that it enforces the principle of least privilege at the network level, ensuring that even if a service is compromised, the attacker can't easily move laterally through your system. In an interview, you should mention that these policies are managed centrally but enforced locally by the sidecar proxies. A significant failure mode is misconfiguration, where a policy is too restrictive and accidentally blocks legitimate traffic, causing a production outage. You also have to consider the complexity of managing these policies as your system evolves. Without clear ownership and naming conventions, your security rules can become a tangled mess that nobody understands. The goal is to create a ring of protection around your APIs that is both robust and maintainable, giving you confidence that your data is only being accessed by the services that absolutely need it. One of the most important things for an interview is knowing when not to adopt a service mesh. It works best when you have a large, complex system, but the overhead is real. What matters here is that a mesh adds operational complexity, latency, and resource costs. If you only have 5 microservices, a mesh is almost certainly overkill. A massive failure mode in many organizations is resume-driven development, where teams adopt a mesh because it's trendy, only to find that it makes their simple system much harder to manage. In an interview, you'll score points by arguing that a mesh should only be introduced when the pain of managing communication manually exceeds the cost of running the mesh. You're showing that you're an architect who thinks about the bottom line and operational reality, not just the newest tech. Always weigh the benefits of observability and security against the increased cognitive load and infrastructure costs. The right time to adopt is when your chaos factor is actually preventing you from moving fast and staying reliable. So, we walked through how a service mesh effectively tames microservice chaos by decoupling communication from your application code. I mean, instead of baking retries and security into every individual service, you're using this dedicated infrastructure layer to handle it globally. Remember the two-part architecture? The control plane serves as your central brain for policy, while the data plane uses sidecar proxies to manage the actual traffic. This setup is what unlocks MTLS for identity and those advanced routing patterns like canary releases. When you're in an interview, be ready to defend the operational trade-off. You're trading some complexity for massive wins in observability and governance. It's all about knowing when your scale makes a mesh necessary, rather than just an extra layer of overhead. That brings us to the finish line for Service Mesh Basics. When you're in an interview, keep in mind that they aren't just testing your knowledge of sidecars. They want to see if you can justify the operational tax. You've got to weigh 3 key areas: unified metrics, standardized logging, and distributed tracing, against the risk of added latency and configuration bloat. A strong answer shows you know exactly when the overhead becomes worth the effort. So don't just jump into a mesh by default. Now, if you want to dive deeper, don't forget to subscribe for more architecture breakdowns. It's been great having you here. Good luck with your system design prep. Imagine your app going viral overnight, only for the servers to buckle under the weight of your own success. Static infrastructure is either a massive waste of money or a ticking time bomb. Welcome to the System Engineering series. My name is Kabir Anand. This is episode 27, and today we will explore auto-scaling systems in a way that helps you prepare for system engineering interviews on this topic. Mastering elasticity shows interviewers you can design self-healing systems that balance cost and performance, aligning capacity directly with real-time user demand. This lesson opens by tackling the inefficiency of static infrastructure and the risks of daily traffic swings. You'll see how we move from manual management to automated elasticity. We'll break down the architecture into 4 key parts: auto-scaling groups, Kubernetes HPA, continuous monitoring, and load balancing. Understanding how these tools coordinate is a massive signal in system design interviews because it shows you can handle real-world load. From there, we'll weigh the differences between horizontal and vertical scaling and look at how specific metrics, whether it's CPU usage or request rates, drive those decisions. We'll also cover protective layers like cooldown periods to keep your system stable and predictive scaling to anticipate spikes before they even hit. Now, the goal is finding that balance between being reactive and being proactive. By the end, you'll understand how to architect a self-healing system that grows and shrinks autonomously while maintaining high availability and cost efficiency. Let's set the scene with a real-world engineering challenge. Imagine you're building the infrastructure for a global event like the FIFA World Cup 2026. This isn't just steady growth, it's a series of massive, jagged spikes. When a goal is scored, millions of users hit the app simultaneously to check stats or watch highlights. If you have a static fleet of servers, you're stuck. You've either over-provisioned, which wastes money when no games are on, or you've under-provisioned, meaning the app crashes exactly when users need it most. In an interview, you'd frame this as a constraint problem, where latency must stay low despite a 300% surge in traffic. The failure mode here is clear. If your system can't spin up new nodes in under 60 seconds, the request queue fills up, and your users see nothing but timeout errors. This situation demands a system that recognizes load and acts autonomously before the performance degrades, shifting from a human-monitored model to a machine-driven one. The core of this module is mastering elasticity to handle those sudden spikes without manual intervention. Why does this matter so much? Well, in a production environment, the cost of human error is high. If an engineer has to wake up at 3 in the morning to add servers, you've already lost. Autoscaling works by setting up a feedback loop between your load and your resource count. When the traffic wave hits, the system senses the pressure and adds capacity automatically. However, there's a major failure mode to watch out for: the boot storm. This happens when you try to scale out, but your new instances take too long to initialize, or they crash the database by opening too many new connections at once. In an interview, you'll want to highlight that scaling isn't just about adding more CPUs. It's about ensuring the entire ecosystem, including your networking and data layers, can actually support that new capacity without falling over under the sudden weight of the initialization process. Traffic doesn't just sit still, it's defined by daily fluctuations. Most apps see a predictable camel hump pattern where usage peaks during the day and drops off a cliff at night. If you're running a fixed number of servers, you're essentially paying for a ghost town for 8 hours a day. That's a massive efficiency leak. What matters here is that every dollar spent on idle compute is a dollar not spent on feature development. The way we solve this is by defining scaling policies that track these curves. But here's the catch. The failure mode here is often lagging metrics. If your system only checks usage every 5 minutes, you might miss a rapid surge, leading to a period of high latency where users experience sluggishness before the servers actually arrive. You'll want to explain to an interviewer that solving for fluctuations requires balancing the granularity of your monitoring against the cost of the monitoring itself, ensuring you're not reacting to noise while still catching the actual signal of a real traffic surge. When we look at the cost of fixed infrastructure, we see two extreme failure modes. On one side, you have the waste scenario. You provision for the absolute peak, but 80% of that compute sits idle most of the time. It's expensive and honestly just bad engineering. On the flip side, you have the crash. You try to be frugal and provision for the average load, but then a single marketing campaign or social media mention sends traffic past the ceiling. The system hits a bottleneck, the CPU maxes out, and every subsequent request fails. This is why auto-scaling is a non-negotiable requirement for modern cloud-native apps. It bridges the gap between these two extremes. In an interview, the key insight is that fixed infrastructure creates a hard ceiling on your business growth. If your infra can't scale, your revenue can't scale during peak moments. You'll want to emphasize that an elastic system is essentially an insurance policy against success, making sure your infrastructure is an enabler rather than a bottleneck for the product's reach. The ultimate goal here is matching capacity to demand in real time. It sounds simple, but the mechanics are quite sophisticated. It works by creating a target tracking policy, where you tell the system, I want my average CPU to stay at 50%. If it goes higher, add a server. If it goes lower, remove one. What matters here is that it optimizes for both performance and cost simultaneously. However, you have to be careful with the failure mode of oscillation. If your thresholds are too close together, the system might keep adding and then immediately removing servers, which is called thrashing. This creates instability and can actually lead to service outages. In an interview, you should talk about how you'd set a buffer or a cooldown period to prevent this. You're trying to achieve a state where the resource graph perfectly mirrors the traffic graph. When done right, this ensures that no matter if you have 10 users or 10 million, the latency remains consistent, providing a seamless experience that feels the same regardless of the total load. The big idea here is automated elasticity. We're effectively building a self-healing system that breathes. It expands when it needs more air and shrinks when the pressure subsides. A practical point here is that it removes the human bottleneck from the operations loop. You aren't relying on a person to make a judgment call. You're relying on predefined logic. It works through a continuous cycle of observe, decide, and act. The system observes metrics, decides based on rules, and acts by calling cloud APIs. But there's a risk, configuration drift. If your automated scaling launches instances using an old disk image or a buggy script, you'll scale up a fleet of broken servers, making the outage even worse. In an interview, mention that automated elasticity requires rigorous image management and automated health checks. You need to be sure that every new server added to the pool is actually healthy and ready to work. If you don't have that validation, your scaling engine becomes a tool for distributing failure at high speed, which is a nightmare scenario for any production environment. When architecting the scaling engine, you have to coordinate several moving parts. There are three main components you'll need to explain in an interview: the scaling group, the controller, and the monitoring agents. The monitoring agents are like the eyes of the system, constantly collecting telemetry like CPU load or memory usage. They feed this data to the controller, which is the brain. The controller evaluates the data against your scaling policies. If the rules are triggered, the controller tells the scaling group, the muscle, to change the instance count. What matters here is that it provides a clear separation of concerns. A failure mode to consider here is network partition. If the controller can't talk to the monitoring agents, it might think the load is zero and shut down your entire fleet. You'll want to discuss how you'd implement safety min-max limits to prevent the system from ever scaling down to zero servers, even if the metrics suggest it. These guardrails are what transform a basic script into a robust, production-grade scaling engine that can be trusted with your most critical traffic. For those of you working with containers, the Kubernetes Horizontal Pod Autoscaler or HPA is the standard. It works by monitoring the resource metrics of your pods, like CPU or memory utilization. If the average usage across all pods exceeds a target percentage, the HPA controller tells the deployment to increase the replica count. Why does this matter? Well, containers are much faster to scale than virtual machines, often starting in seconds rather than minutes. This makes your system much more responsive to rapid shifts. But there's a specific failure mode, resource quotas. If your cluster doesn't have enough physical nodes to host the new pods, the HPA will try to scale, but the pods will stay in a pending state. In a system design interview, you'd mention that you need a secondary layer, like a cluster autoscaler, to add more physical hardware when the HPA runs out of room. This two-layer scaling is a sophisticated detail that shows you understand how container orchestration interacts with the underlying infrastructure to ensure actual capacity is always available. The load balancer is the piece that actually distributes the incoming traffic across your changing fleet. As the scaling engine adds or removes servers, the load balancer must stay in sync. It works through a process called registration. When a new server starts, it tells the load balancer, "I'm here and ready to work." The load balancer then starts sending it a share of the requests. What matters here is that without it, your new capacity is just sitting there doing nothing. A common failure mode is improper health checks. If the load balancer sends traffic to a server that's still booting up, the user gets an error. You have to configure grace periods to ensure the server is fully initialized before it takes its first request. In an interview, mention that you'd use connection draining during scale-in events. This ensures that when a server is being shut down, the load balancer stops sending it new requests but allows it to finish the ones it's currently processing. This prevents users from having their active sessions dropped, making the scaling process completely invisible to them. When you're building or discussing these systems, you should focus on three key scaling concepts: growth mechanics, driving metrics, and safety measures. Growth mechanics involve deciding whether you're adding more machines or making existing ones bigger. Driving metrics are the signals you use to trigger that growth, whether it's CPU, memory, or even the number of messages in a queue. Finally, safety measures are the guardrails, like cooldown periods and maximum instance limits that prevent the system from going haywire. Understanding these three pillars matters because it allows you to tune the system for your specific workload. A failure mode here is using the wrong metric. For example, scaling a memory-intensive app based on CPU usage. In an interview, you'd explain that choosing the right signal is the difference between a stable system and one that's constantly on the brink of failure. You want to show that you don't just apply a one-size-fits-all approach, but instead analyze the specific bottlenecks of the application to determine which of these three concepts needs the most attention. Horizontal auto-scaling or scaling out is the most common approach in cloud-native design. It works by adding more identical machines to your pool. What matters here is that it gives you virtually unlimited ceiling. You can just keep adding servers as long as the cloud provider has them. It's great for high availability because if one server fails, you have many others to pick up the slack. However, there's a significant bottleneck, the database. As you scale out your web tier to 100 servers, they all might try to connect to the same database simultaneously. This is a classic failure mode called connection exhaustion. In an interview, you should explain that horizontal scaling requires a stateless application tier. If your app stores user sessions on the local hard drive, scaling out will break things because a user's next request might go to a different server that doesn't know who they are. You'll want to highlight that you'd use a centralized session store like Redis to ensure that horizontal scaling remains seamless and data stays consistent across the entire fleet. Vertical auto-scaling, or scaling up, means making your existing machines more powerful by adding more CPU or RAM. This is how many legacy systems handle load. It's often simpler because you don't have to worry about distributing traffic or managing a cluster. You just have one big box. But it has a massive failure mode. There's a hard limit to how big a single server can get. Eventually, you can't buy a bigger machine. Also, scaling up usually requires a restart, which means downtime. That's why it's rarely used for web traffic in modern systems. Why does this matter for your interview? Well, you might use it for specialized tasks like a heavy data processing job where a single thread needs a ton of memory. But for a high traffic API, you'd almost always argue for horizontal scaling instead. In a system design session, if an interviewer asks why not just get a bigger server, your answer should focus on single points of failure and the diminishing returns of vertical scaling costs compared to the flexibility of a distributed horizontal fleet. Choosing the right scaling metrics is critical. There are three main types: system metrics, custom metrics, and scheduled actions. System metrics like CPU or memory are the easiest to set up, but they're often a lagging indicator. For instance, a CPU spike might happen after the app is already slow. Custom metrics are often better. You might scale based on active sessions or request latency. What matters here is that it targets the actual user experience. Finally, scheduled actions are for predictable events, like scaling up at 8 a.m. before people start their workday. A failure mode to watch for is metric poisoning. This happens if a single malfunctioning client sends thousands of requests, causing your system to scale up unnecessarily and run up a huge bill. In an interview, discuss how you would sanitize or rate limit these metrics to ensure the scaling engine only reacts to legitimate aggregate demand. Using custom application level metrics shows you're thinking about the business logic, while scheduled scaling proves you're proactive about known traffic patterns, which is a sign of a mature engineering mindset. Predictive scaling is where things get really smart. Instead of waiting for the traffic to hit, it uses machine learning to look at historical data and forecast future demand. It works by identifying cycles, like knowing that every Tuesday at 2 p.m., traffic triples. It preemptively starts adding servers at 1:45 p.m. so they are warm and ready when the surge arrives. What matters here is that it completely eliminates the warm-up lag associated with reactive scaling. It's like having a weather forecast for your servers. However, the failure mode is unpredictable anomalies. If a major news event happens on a Monday, the predictive model won't see it coming because it's looking at historical Tuesdays. You'll want to tell an interviewer that you should never use predictive scaling alone. It must always be backed up by a reactive policy. Think of it as a belt and suspenders approach. The predictive model handles the known patterns, while the reactive model acts as a safety net for the unexpected. This combination provides the most stable and cost-effective scaling strategy for modern high-volume production environments. Cooldown periods are an essential safety feature in any auto-scaling setup. It works by putting a lock on scaling actions for a set amount of time after a server is added or removed. For example, after adding a server, the system might wait 5 minutes before checking the metrics again. What matters here is that it prevents thrashing. Without a cooldown, the system might see high CPU, add a server, see the CPU is still high while the new server is booting, and add 10 more by mistake. This leads to massive over-provisioning and instability. The failure mode here is a cooldown that's too long. If you set it to 30 minutes and your traffic is doubling every 5 minutes, your system won't scale fast enough to keep up and you'll crash. In an interview, you'd explain that the cooldown period should be tuned to match your main time to boot. If your servers take 3 minutes to become healthy, your cooldown should be at least 3 minutes. This ensures the system only makes a new decision after the previous action has had a chance to affect the metrics. When you're in the hot seat for a system design interview, you need to show you can make crucial design decisions. There are 4 main categories you should cover: metric selection, timing strategies, capacity boundaries, and cost management. For metric selection, you're deciding if you're tracking CPU or something more specific like queue depth. Timing strategies involve balancing reactive versus predictive models. Capacity boundaries are your min and max limits. This is your financial guardrail to ensure a bug doesn't spin up 10,000 servers and bankrupt the company. Finally, cost management involves choosing between on-demand instances for speed and spot instances for savings. A failure mode to mention is max limit bottlenecks. If you set your maximum too low, your system will stop scaling while users are still pouring in. Explain that these aren't just technical settings, they are business decisions. You're balancing the cost of failure against the cost of infrastructure. A strong candidate shows they can navigate these trade-offs by considering the specific needs of the product and the company's budget constraints. Choosing between scaling on CPU versus request rate is a classic interview trade-off. CPU scaling works well for compute-heavy apps like image processing. It matters because it's a direct measure of host health. But it can be misleading. An app might be slow due to database logs even if CPU is low. Request rate scaling, on the other hand, is a leading indicator. It tells you how much work is coming in before the CPU even feels it. What matters here is that it allows you to be more proactive. However, the failure mode for request rate is that it doesn't account for request complexity. If 1000 requests suddenly become 10 times more expensive to process, your request rate stays the same, but your servers will catch fire. In an interview, you might suggest a composite approach. Use request rate as your primary trigger for speed, but keep CPU as a secondary safety trigger. This gives you the best of both worlds, the responsiveness of traffic monitoring and the reliability of resource-based health checks, ensuring the system stays stable regardless of how the workload changes. Deciding between reactive and predictive strategies is about balancing simplicity and stability. Reactive scaling is simple to reason about. It's if this, then that. It's great for most apps, but it will always be behind the curve because it reacts to events that have already started. Predictive scaling is more stable during known peaks, but it's more complex to configure and can be wrong. Why does this matter? Well, for a business where downtime costs $1 million a minute, you want the stability of prediction. For a small startup, the simplicity of reactive scaling is usually enough. The failure mode for a purely reactive system is the flash crowd, a sudden massive influx of users that happens so fast the system can't keep up. In a system design interview, you'd frame this as a risk profile decision. You'd advocate for a hybrid strategy where predictive scaling handles the daily camel humps and reactive scaling covers the black swan events. This shows a deep understanding of how to build a resilient, multi-layered defense against traffic volatility in the real world. So we have broken down how to stop worrying about manual server management and let the system handle the heavy lifting. The core mental model here is elasticity, matching your infrastructure's footprint to actual user demand. To nail this in a design discussion, you should focus on 3 specific components: the scaling policy, the metrics you're monitoring, and the cooldown periods that prevent thrashing. Whether you're using AWS auto-scaling groups or Kubernetes HPA, you're essentially trading a bit of orchestration complexity for massive gains in efficiency and uptime. Interviews want to see that you understand this trade-off. They look for your ability to pick the right signal, like request rates over simple CPU usage, to ensure you're scaling before the lag hits. Well, that's the goal. Building a system that grows and shrinks without anyone ever having to wake up. So, that's how you handle a sudden traffic surge. In an interview, be ready to justify why you chose specific metrics, like using request rate over CPU for IO-bound tasks. We covered 2 main strategies, reactive and predictive scaling. You're balancing lower infrastructure costs against the added orchestration complexity. So don't ignore cooldown periods or your system might start oscillating. It's really about scaling before users feel the lag, Next, we will move into why great systems sometimes say no, load shedding, where we will discuss situation, problem, and goal. If your application keeps local state and memory, how does that change your approach to horizontal scaling? Let me know in the comments. Happy designing! Ever wonder why a system crashes even after you've scaled your resources? It's usually because it tried to handle too much and hit a cascading death spiral. Welcome to the System Engineering series. My name is Kabir Anand. This is episode 28, and today we will explore load shedding in a way that helps you prepare for system engineering interviews on this topic. In interviews, showing how you'd strategically sacrifice low priority traffic to save the whole application proves you understand true platform resilience. It starts by breaking down the tipping point where incoming requests saturate your platform's capacity. You'll see how trying to be polite and accepting every request actually triggers a cascading death spiral that takes the whole system down, right? We'll then dive into the 4 architectural pillars that keep things stable: admission control, priority queues, overload protection, and rate limiting. Understanding these is crucial for system design interviews because you've got to explain how to filter traffic at the edge before it burns those expensive downstream resources. We're also going to explore 5 core concepts, including how to implement priority handling so your must-have requests aren't lost in the noise, and how to use graceful rejection to return a clean error instead of just letting a connection hang. Finally, we tackle the hard design decisions and the fundamental trade-off between absolute availability and service level. We look at why failing to say no is actually a massive mistake in large-scale engineering. By the end, you'll know exactly how to switch from performance mode to survival mode to keep a platform alive. To ground this in reality, imagine you're managing the backend for a massive global event like the FIFA World Cup 2026. When tickets go on sale, you don't just get a little extra traffic, you get a literal tidal wave of millions of concurrent users hitting your API. Now, your system has a fixed physical limit, and once you cross that line, every extra request you try to process actually makes the system slower for everyone. What matters here is that if you try to be polite and accept everyone, your database connection pools will exhaust, and your memory usage will spike until the whole platform reboots. The failure mode here isn't just a slow site, it's a complete blackout where 0 tickets get sold. In an interview, you want to use this scenario to show you understand that capacity isn't infinite. You have to explain that at some point, the system must stop trying to be helpful and start protecting its own vitals to ensure that at least some users can actually complete their purchases. So, episode 28 is all about mastering the art of intentional rejection. This is what we call load shedding, and it's a fundamental pillar of site reliability engineering. It works by having a predefined threshold where the system starts dropping new incoming requests to ensure that the ones already in flight can actually finish. Why does this matter? Because in a high-stakes environment, a system that tries to do everything ends up doing nothing. If you don't build in these rejection points, you're essentially leaving a system's fate up to chance. A major failure mode people overlook is the retry storm, where clients keep hitting your servers even harder when they see a delay, which just compounds the pressure. In an interview, being able to describe load shedding as an intentional design choice rather than an accidental error shows a deep level of architectural maturity. You're showing that you prioritize the availability of the overall platform over the success of any single individual request during a crisis. Let's look at the tipping point, which is where things start to go wrong. Every system has a maximum capacity, often defined by CPU, memory, or thread pools. When incoming request exceeds this limit, the system enters a state of saturation. It works like a restaurant with only 10 tables. If 100 people walk in at once and you try to serve them all, the kitchen will collapse. What matters here is that once you're saturated, the time spent switching between tasks starts to outweigh the time spent actually doing the work. In a production system, this manifests as soaring P99 latencies. A common failure mode here is the lack of early detection, where the system doesn't realize it's overwhelmed until it's already too deep in the weeds to recover. When an interviewer asks how you'd handle a sudden 10x traffic spike, you need to talk about identifying this tipping point before the resource exhaustion starts to cascade and take down your downstream dependencies like your database or cache. The problem we're fighting is the cascading death spiral. This is a brutal failure mode where a small delay in one service causes a backlog that eventually poisons the entire architecture. It works through a feedback loop. Requests slow down, so the client-side timeouts trigger, and then the clients or mobile apps start retrying those same requests. Now you have the original load plus a massive wave of retries. What matters here is that it creates a state of permanent congestion where the system is doing 100% work but achieving 0% throughput. Imagine a highway and a small fender bender causes a backup that eventually blocks every single exit for miles. That's a death spiral. In an interview, you should emphasize that the goal of load shedding is to break this loop by dropping the extra load before it reaches the bottleneck. If you don't, the system will eventually crash or lock up entirely, requiring a manual, painful cold start that could take your entire team hours to resolve while users are staring at blank screens. The goal here is a mindset shift towards preservation over completion. It works by having the system acknowledge that it cannot fulfill its entire mission, so it switches to survival mode to protect the most critical services. Why does this matter? Well, in a complex app, not all requests are created equal. You'd much rather fail a request to update a user's profile picture than fail a request to process a credit card payment. A common failure mode in poorly designed systems is treating every request as equally important, which leads to critical transactions being dropped while trivial ones clog up the queue. In an interview, you can use the example of an e-commerce site where you shed the recommended product service during a peak sale so that the add to cart and checkout flows remain perfectly responsive. This strategic rejection ensures that even if the user experience is slightly degraded, the business's core functions continue to operate and generate revenue while the storm passes. The big idea here is selective sacrifice. It's the realization that losing a few individual requests is infinitely better than losing the entire application for all users. This works by drawing a line in the sand. Once we hit 90% utilization, we start discarding the bottom 10% of traffic. What matters here is that it keeps the system in a predictable state. Without selective sacrifice, the system eventually hits a wall and becomes unpredictable, where some requests take 50 milliseconds and others take 30 seconds before eventually timing out. A failure mode to watch out for is shedding the wrong traffic, like accidentally dropping authentication requests, which then prevents anyone from doing anything. When you're explaining this in an interview, contrast a healthy system that is rejecting some traffic with a dead system that is accepting everything but processing nothing. You are making a conscious trade-off. You are sacrificing the perfect experience for a few to guarantee a functional experience for the many. That's what high availability engineering is really all about. When we look at the architecture, there are three main components that make load shedding work: admission control, priority queues, and overload protection. Admission control acts as the first line of defense at the edge, deciding whether to let a request in at all. Priority queues then organize the accepted requests, ensuring that the most important tasks get processed first. Finally, overload protection monitors the internal health of the system, like CPU and memory, and triggers the shedding logic when thresholds are breached. This structure matters because it prevents your application logic from even seeing the excess load, which saves precious resources. A common failure mode is placing these checks too deep in the stack, where you've already spent memory and CPU just to pass a request you're going to drop anyway. In an interview, walk through these three layers and explain how they provide a defense-in-depth strategy. By filtering at the gateway, prioritizing at the queue, and monitoring at the resource level, you create a robust safety net. Admission control is your system's gateway mechanism. It works by evaluating incoming requests right at the entry point, like an API gateway or a load balancer, before they ever reach your application servers. Why does this matter? Because parsing a JSON body or establishing a database connection is expensive. If you know you're at capacity, you should stop that request at the front door to save those resources for work you actually intend to finish. For example, if your gateway sees that your backend latency has doubled, it can start returning errors immediately. A failure mode here is a lack of coordination, where the gateway keeps sending traffic because it doesn't realize the backend is struggling. In an interview, describe this as the check and action phase. You check the system's health, and if it's poor, you take the action of denying entry. This prevents your core application from being overwhelmed by a sheer volume of connections, keeping the environment stable for the requests that have already been admitted. Priority queues are how we handle the ordering of work under pressure. It works by tagging incoming requests with a priority level based on metadata, such as whether a user is on a paid tier or if the request is for a critical path like a checkout. When the system is busy, these high priority items move to the front of the line, while lower priority tasks wait or get dropped. What matters here is that it ensures that your most valuable or time-sensitive operations aren't stuck behind a wall of less important background tasks. Imagine a scenario where a system is processing thousands of email notifications. You don't want a login request to wait 10 seconds because the queue is full of low priority alerts. A common failure mode is priority inversion, where a low priority task holds a lock that a high priority task needs, effectively stalling the whole system. In an interview, explain how you'd use weighted queues to ensure that even during a peak, your must-have features stay responsive. Overload protection is the brain of the operation. It works by using sensors and circuit breakers to monitor system health metrics like CPU usage, memory pressure, and request latency in real time. When these metrics hit a specific threshold, the protection mechanism flips a switch to move the system from a normal state to a protected survival state. Why does this matter? Because it automates the response to a crisis, removing the need for a human to intervene when a spike happens at 3 in the morning. For example, If memory usage hits 85%, the system might automatically start rejecting any request that requires large memory allocations. A major failure mode is having thresholds that are too sensitive, leading to flapping, where the system constantly toggles between accepting and rejecting traffic. In an interview, you should discuss how you'd set these thresholds based on load testing to ensure they trigger early enough to prevent a crash but late enough to avoid unnecessary service interruptions. Now let's talk about the rate limiter, which is a specific form of throttling. It works by enforcing limits on how many requests a particular user, IP address, or API key can make within a certain time frame. What matters here is that it prevents a single noisy neighbor from monopolizing all your system's capacity and causing a localized overload. Imagine one developer script goes haywire and starts calling your API 10,000 times a second. Without a rate limiter, that one user could take down the entire platform for everyone else. A common failure mode is using a global lock for your rate limiter, which can actually become a bottleneck itself as you scale. In an interview, explain how you'd use a leaky bucket or token bucket algorithm to smooth out bursts of traffic. You want to show that you're protecting the system's total capacity by ensuring that every user gets their fair share, while aggressively cutting off anyone who exceeds their quota during times of high stress. As we dive deeper into key load shedding concepts, there are 5 foundational terms you need to be comfortable with for a system design interview. These are load shedding itself, admission control, priority handling, graceful rejection, and overload protection. Each of these represents a different layer of the defensive strategy we've been discussing. Together, they form a hub-and-spoke model where the central goal is system stability, supported by these specialized subconcepts. It's important to understand how they differ. For instance, rate limiting is about individual quotas, whereas load shedding is about the system's overall health regardless of who is sending the traffic. A common mistake in interviews is using these terms interchangeably. If you can clearly articulate how priority handling informs the admission control layer during an overload event, you are demonstrating a sophisticated understanding of how to build a self-healing architecture. We're going to break each of these down further so you have a concrete mental model for how they function in a real production environment. The core concept of load shedding is the intentional dropping of work to maintain performance. It works by having the system proactively decide to fail some requests rather than slowing down for everyone. Why does this matter? Because the throughput of a system usually drops off a cliff once it's overloaded. If you shed the excess load, you can keep the throughput at its maximum possible level. Think of an elevator that only holds 10 people. If 15 try to squeeze in, it won't move at all. Load shedding is the person at the door saying only 10 can enter so the elevator can actually do its job. A major failure mode here is a lack of visibility. If you don't log exactly why and when you're shedding load, you'll have no idea why your error rates are spiking. In an interview, frame load shedding as a feature that guarantees availability for the remaining workload, transforming a catastrophic failure into a managed partial degradation that is much easier to handle. Admission control is all about filtering at the edge. It works by stopping requests at the highest possible layer in your stack, like the CDN or the load balancer, before they ever hit your compute resources. Why does this matter? Every layer a request passes through consumes something, bandwidth, CPU cycles, or memory. By rejecting a request at the edge, you're essentially getting a free rejection that doesn't hurt your backend's health. For example, if your application is struggling with database logs, your admission control can look at the incoming traffic and drop anything that isn't a read-only request. A failure mode to avoid is a static admission policy that doesn't adapt to real-time backend pressure, which could lead to rejecting traffic when you actually have spare capacity. In an interview, highlight how this creates a cascading defense, where each layer of the architecture is only responsible for the traffic that the layer above it has already validated and deemed safe to process. Priority handling is the intelligent part of the shedding decision. It works by using metadata like a user subscription tier, the type of request, or even the age of the request to decide what stays and what goes. What matters here is that it allows you to align your system's behavior with business goals. In a quadrant-style decision matrix, you'd prioritize high-importance, high-urgency tasks like completing a payment over low-important tasks like fetching a list of recently viewed items. A common failure mode is starvation, where low-priority tasks never get processed because the system is constantly under just enough load to keep them in the queue forever. To counter this in an interview, you might suggest a strategy where even low-priority items have a small guaranteed slice of capacity. This shows you're thinking about the whole system's fairness, not just the top-tier users. By making shedding decisions based on value, you ensure the most impactful work always gets the resources it needs to succeed. Graceful rejection is about how you say no. It works by returning a standard well-formed error like an HTTP 503 service unavailable, often accompanied by a retry after header that tells the client exactly when it's safe to try again. Why does this matter? Because if you just hang the connection or timeout, the client stays in limbo, holding on to its own resources and likely retrying more aggressively. A graceful rejection helps the entire ecosystem recover because it gives the client the information it needs to back off. For example, a mobile app that receives a 503 can show a friendly "we are busy, try again in a minute" message instead of just spinning a loading wheel until it crashes. A common failure mode is returning a generic 500 error, which doesn't tell the client that the failure is due to load, causing them to treat it like a bug and potentially retry immediately. In an interview, emphasize that a clear standard response is a vital signal that helps prevent retry storms. Overload protection defines the boundary where the system switches from performance mode to survival mode. It works by creating concentric layers of defense around the system's core. Think of it as a set of rules. If latency exceeds 1 second, stop background jobs. If it hits 2 seconds, start shedding 20% of traffic. If it hits 5 seconds, shut down everything except the health check endpoint. What matters here is that it prevents the system from ever reaching a state of total collapse. A failure mode to watch for is deadly embrace, where the protection logic itself uses so much CPU to decide what to shed that it actually speeds up the crash. In an interview, you want to explain that survival mode is a temporary, highly optimized state designed to keep the lights on. You're defining exactly how the system should behave when it's pushed to its absolute limit, ensuring that there's always a predictable path back to normal operations once the load subsides. The shedding strategy is where you make the final design decisions. It works by evaluating whether to process a request immediately, delay it in a queue, or reject it outright based on real-time health data. What matters here is that the right choice depends on the nature of the work. If you're building a video processing system, you might choose to delay the work since it's not time sensitive. But if you're building a real-time trading platform, a delayed request is a useless request, so you're better off rejecting it immediately. A failure mode is tail latency issues, where you queue up so many requests that by the time you process them, the user has already given up and left. In an interview, you should walk through this zigzag path of decision making. Explain that you consider the request priority and the current system pressure to find the most efficient path. By demonstrating this nuanced approach, you show that you're not blindly dropping traffic and, more specifically, carefully managing the flow to maximize successful outcomes. In an interview, you'll likely be asked to justify the trade-off between availability and service level. This is a classic architectural choice. By implementing load shedding, you are choosing to have high overall platform availability at the cost of a reduced service level for specific users or non-critical features. It works because it prevents a localized problem from becoming a global outage. Why does this matter? Because a system that is 100% available for 90% of users is much better than a system that is 0% available for 100% of users. A failure mode here is failing to communicate this trade-off to stakeholders who might be surprised when they see errors during a peak instead of just slowness. When you're explaining this, focus on the partial availability concept. You're intentionally failing some requests to ensure the overall system stays upright. This shows the interviewer you're thinking like a business-minded engineer who understands that some revenue is always better than no revenue. The most common mistake engineers make is what I call the polite failure. This happens when you continue to accept every incoming request until every single component becomes overloaded and the entire platform locks up. It's born from a desire to be helpful, but in high-scale systems, it's a disaster. It works by filling up every queue and exhausting every thread until the system can't even process a simple health check, leading the load balancer to think the whole cluster is dead. Why does this matter? Because once you're in a total lockup, you often have to do a hard restart, which clears caches and puts even more pressure on your database. A failure mode is the herd effect, where all your servers fail at once because they're all being too polite. In an interview, contrast this with the protect the cause strategy. Explain that by being rude and saying no early, you're actually being more responsible by maintaining a working service for as many people as possible. Alright, so we've broken down why load shedding is essentially your system's survival instinct. When traffic spikes past your maximum capacity, trying to be a hero and serving every single request is exactly what triggers a cascading death spiral. Instead, you've got to implement those 4 architectural pillars we discussed: admission control, priority queues, rate limiters, and overload protection. In a high-level design interview, your goal is to show you understand this critical trade-off. It's always better to sacrifice low-priority traffic than to let the entire platform collapse. You're building a system that's smart enough to say no so it can stay alive for everyone else. Remember that golden rule. Save the system first because individual requests don't matter if the whole application is offline. That's the core of resilient, high-scale engineering. That wraps up why great systems have to say no. Now, in an interview, you've got to show you understand the four main tools for survival: admission control, priority queues, overload protection, and rate limiting. It's about making a deliberate choice so the whole platform doesn't lock up. You're basically trading off service levels for a few users to keep the system alive for everyone else. In the next episode, we'll explore keep your app running when everything breaks, graceful degradation, and work through the situation, problem, and goal. Here's a question for the comments. If your database is redlining, would you shed write requests or read requests first to save the system? Happy engineering! What happens when your recommendation engine crashes right in the middle of a traffic spike? If your whole app goes down with it, well, you've got a major architectural problem. Welcome to the System Engineering series. My name is Kabir Anand. This is episode 29, and today we will explore graceful degradation in a way that helps you prepare for system engineering interviews on this topic. Understanding these patterns shows interviewers you can protect core user journeys and maintain stability when downstream dependencies are under pressure. This lesson opens with a look at a high-pressure scenario where a single service failure during peak traffic threatens to take down your entire application. We'll see how shifting the focus from technical perfection to business continuity helps preserve those mission-critical user journeys. To achieve that, we'll dive into four specific architectural pillars: fallbacks, cached responses, feature flags, and service isolation. You'll understand how these work together to keep the core alive while shedding non-essential weight. Now, implementing this effectively requires some tough engineering triage, so we'll walk through how to distinguish mandatory features from the nice-to-haves that can be temporarily removed. We'll also weigh the trade-offs between high availability and feature richness, which is a key signal interviewers look for when you're designing at scale. Finally, we examine three major failure modes, like missing fallbacks and cascading failures, to ensure your strategy doesn't actually make the system more fragile. By the end, you'll know how to prioritize business survival by making intentional sacrifices in your design. Let's set the scene with a real-world engineering situation. Imagine you're managing a global streaming platform during a massive live event, like the finals of a major tournament. Your traffic is 10 times its normal peak. Suddenly, your metadata service, which provides movie descriptions and thumbnails, starts returning 500 errors because the database is locked up. What matters here is that without a degradation strategy, your homepage won't load at all, even though the video delivery network is perfectly healthy. It's the ultimate all-or-nothing jab. In an interview, you'd explain that the system works by detecting this latency and switching to a cached or simplified view. A failure mode here often happens when the timeout for that metadata service is set too high, which means your front-end servers are still waiting around while the users get frustrated and leave. If you don't have a plan to fail fast and serve a good enough version of the page, the entire platform collapses. It's about recognizing that a partial failure shouldn't ever turn into a total system-wide outage. When we talk about graceful degradation, the fundamental idea is that failure is inevitable. In large-scale systems, it's not a question of if a service will fail, but when. This works by designing your application with multiple operational levels, like a ship with watertight compartments. Why does this matter? Because high availability isn't just about preventing crashes, it's about managing how you fail so the business stays alive. If your recommendation engine dies, users should still see their search results. A common failure mode is blind trust, where a service assumes its dependencies will always be there, leading to unhandled exceptions that bubble up to the UI. During an interview, you want to show that you're thinking about the blast radius of any single component. You should consider three main things: how you detect the failure, how you bypass the broken component, and how you communicate that to the user. If you can't describe the fallback path for a feature, then you haven't actually designed a resilient system. It's about building a safety net that's always ready to catch the falling pieces. Now, let's zoom in on the specific situation of a peak traffic service failure. This usually happens when a downstream dependency, like a search index or a personalization engine, becomes a bottleneck. It works by consuming more and more resources, like thread pools or memory, until the calling service starts to lag. What matters here is that peak traffic is usually the time when your business makes the most money, so an outage is incredibly expensive. A major failure mode is the retry storm, where your app keeps hitting the dead service, making the problem even worse. For example, if your search bar is down during a flash sale, you're losing conversions every second. You need to be able to tell an interviewer how you'd swap that search bar for a static list of top selling items to keep the traffic moving. It's about being pragmatic. If you can't provide the perfect experience, you provide the most useful one possible. Well, if you don't prepare for these spikes, your system is basically a house of cards waiting for a single gust of wind to knock it over. The problem we are fighting is the single point of total failure. This is when one small, non-essential part of your stack brings everything else down. It works like a chain reaction. Your UI waits for the API waits for the database, and the database is stuck on a single slow query. What matters here is that it creates a fragile architecture, where the weakest link dictates the uptime of the entire system. A classic failure mode is tight coupling, where your front-end code won't even render if a tiny side widget fails to load. Think about a news site where the entire article disappears just because the related stories box couldn't fetch data. In an interview, you'd explain that you've identified the 4 most critical dependencies and built circuit breakers for each. If you don't isolate these points, a minor bug in a secondary service becomes a catastrophic event. It's about ensuring that a problem in the engine room doesn't sink the entire ship. You have to decouple these dependencies so that they fail in isolation rather than in a cascading mess of errors. Our primary goal is to protect operational critical journeys. This means identifying the parts that absolutely must work, like account login, adding items to a cart, or the final checkout process. It works by prioritizing resources for these flows by letting others, like profile updates or review submissions, fail if necessary. What matters here is that your business survives on successful transactions, not on whether a user can change their avatar during a traffic spike. A common failure mode here is a lack of prioritization, where an engineer treats a like button with the same urgency as a buy button. If the system is under load and you're using resources for non-essential metrics instead of clearing payments, that's a massive design flaw. In an interview, you should be able to list the top 3 critical parts for your app and explain exactly how you'd keep them alive during a crisis. For instance, you might disable all analytical logging temporarily just to free up enough bandwidth for the checkout service to finish its work. It's about keeping the core of the business beating no matter what. The design principle here is functionality versus availability. In simple terms, it is always better to serve a simplified, slightly broken page than a generic 500 error screen. This works by having the system detect an error and immediately falling back to a basic mode of the UI. What matters here is that it maintains user trust and keeps them in the app. A major failure mode is the zombie state, where the app looks like it's working, but none of the buttons actually do anything because the backend is dead. That's actually worse than an error page because it wastes the user's time. You want to show an interviewer that you understand the trade-off. You're sacrificing the perfect feature set for the available feature set. For example, if the live chat is down, replace it with an email contact form instead of just leaving a broken icon. Well, it's about being honest with the system state while still providing value. If you can't provide the latest data, provide the last known good data. Availability is the foundation. Without it, functionality doesn't even matter. To actually build this, we use 4 primary architectural pillars: fallbacks, caching, feature flags, and isolation. This 4-part framework works by creating multiple layers of defense. Fallbacks provide a plan B, caching provides a safety net of old data, feature flags allow us to turn off broken parts manually, and isolation prevents one failure from spreading. What matters here is that it gives you a toolbox to handle different types of outages. A common failure mode across these pillars is tail configurations, where your fallbacks haven't been tested in months and don't actually work when you finally need them. In an interview, you should walk through these 4 components as your standard blueprint for resiliency. For instance, if a service is timing out, the isolation pillar, like a bulkhead, prevents that timeout from hogging all the connections. Right? So if you're asked how to make a system more reliable, these 4 pillars are your best friends. They are the difference between a system that crashes and one that gracefully adjusts to the pressure. Now, let's break down how each one of these works in practice. Mechanism 1 is fallback services. This works by defining a secondary route for any request that fails or takes too long. If your fancy machine learning recommendation engine is down, the system might fall back to a simple top 10 list stored in a static file. What matters here is that it ensures that the UI never shows an empty or broken state to the user. A failure mode to watch for is recursive failure, where the fallback service itself is also down or overloaded, leading to a total collapse anyway. You've got to make sure your fallback is as simple and robust as possible. In an interview, you'd explain that there are two types of fallbacks: local fallbacks, like returning a default value, and remote fallbacks, like calling a backup cluster. If you're designing for a massive event, you might have a static version of your entire site ready to go in case the dynamic backend fails. It's about having a backup plan that's actually capable of handling the load. Well, if you don't have a fallback, you don't have a reliable system. You just have a hope that things won't break. Mechanism 2 involves cached responses, and this is a huge one for graceful degradation. It works by storing the last successful response from a service and serving that stale data if the live source is currently unavailable. What matters here is that users would much rather see a list of recommendations from 10 minutes ago than a spinning loader or an empty box. A common failure mode here is cache poisoning, where you accidentally cache an error message and serve that to everyone. Or simply failing to set an expiration, so users see incredibly old data long after the crisis is over. In an interview context, you should discuss the stale while revalidate pattern. It's a great signal of seniority. For example, if your inventory service is down, show the last known stock count with a small disclaimer instead of just saying error. You're balancing accuracy against availability, right? It's about making sure the app stays interactive even when the data flow is interrupted. Using cache as a fallback is one of the cheapest and most effective ways to prevent a total outage during high traffic windows. Mechanism 3 is feature flags, which act as a digital kill switch for your application. This works by wrapping non-essential features in a conditional block that can be toggled on or off without redeploying any code. What matters here is that it allows engineers to manually shed load in seconds when they see the system starting to struggle. For example, you might disable the typing indicator in a chat app or the live view count on a video during a peak moment to save database writes. A failure mode here is flag debt, where you have so many old flags that no one knows what they do. Or worse, you accidentally toggle the wrong one during a crisis. In an interview, you'd mention that there are two main uses for flags: canary releases and emergency circuit breaking. If the system is redlining, you should have a documented list of features to kill in order. It's a proactive way to manage a system's performance. Well, it's basically like having a set of breakers in your house. If one circuit is drawing too much power, you trip it to save the rest. Mechanism 4 is service isolation, often called the bulkhead pattern. It works by partitioning system resources like memory, threads, or CPUs into separate pools so that a failure in one cannot consume the resources of another. What matters here is that in a shared environment, one slow service can hog all the available threads in an application server, making it impossible for healthy services to respond. A classic failure mode is resource exhaustion, where the isolation wasn't strict enough and the splash from one failure still hits other components. Imagine a ship where a leak in the cargo hold doesn't sink the whole vessel because of the walls between compartments. In an interview, you should explain that you're using three types of isolation: process isolation, thread pool isolation, and network isolation. For example, your payment processing should never share a thread pool with your social media feed. If the feed gets slow and starts queuing up requests, it shouldn't be able to block a payment from going through, right? It's all about containing the damage and making sure the core engine stays protected from external noise. Engineering decisions around degradation always involve a triage process. You have to decide which features are mandatory and which are sacrificial. This works by mapping out every feature in your app and assigning it a priority level based on business impact. What matters here is that when the system is failing, you don't have time to debate. You need a pre-approved plan for what to shut down. A failure mode here is political inertia, where every department claims their feature is critical, leading to a system that can't shed any load at all. In an interview, you'd show your seniority by explaining how you'd categorize features into 3 groups: core, supporting, and optional. For instance, in an e-commerce app, the buy button is core, related products is supporting, and social sharing is optional. If you don't have this list, you can't implement effective feature flags or fallbacks. Well, it's about making the hard choices before the crisis hits, so the system can react automatically when the metrics start to tank. Triage is the bridge between business goals and technical reality. Mandatory features are the non-negotiables of your application. These are the functions that directly impact the primary transaction or identity of the app. If these fail, the app is effectively down. It works by ensuring these services have the highest level of redundancy and the most aggressive resource isolation. What matters here is that these features are your zero fail zone. A common failure mode is including too much fluff in the mandatory path. For example, if your login service waits for an analytics tracker to respond before letting the user in, you've made a non-essential service mandatory. That's a huge mistake. In an interview, you'd emphasize that you keep the critical path as lean as possible. You should consider 2 points here. What is the absolute minimum data needed to complete the task, and how do we protect that path at all costs? If you're building a ride-sharing app, the mandatory features are requesting a ride and seeing the driver's location. Everything else, like the history or the referral bonuses, is secondary, right? So you protect the core, and everything else is up for grabs during a crisis. On the flip side, we have the nice to haves, features that can be temporarily removed without breaking the main flow. This works by designing the UI to be elastic, so it still looks good even when elements like people also bought or notification counts are hidden. What matters here is that removing these features can instantly reduce the load on your databases and APIs by 40 or 50%. A failure mode to watch for is a broken layout, where the UI looks totally glitched because an engineer didn't account for what happens when a component disappears. In an interview, you'd explain that you've built the front end to handle null data gracefully for these components. For example, if the frequently bought together service times out, the component just doesn't render, and the rest of the product page shifts up to fill the space. Well, it's about having a graceful exit for secondary features. You want to show that you've thought about the user's psychological experience. If they don't know a feature was supposed to be there, they won't miss it when it's gone for a few minutes. The core trade-off we are making is availability versus functionality. When we choose high availability through degradation, we're explicitly accepting a lower quality user experience to prevent a total outage. It works by favoring a limited state over a failed state. What matters here is that an unavailable system is the worst possible outcome for any business. However, a major failure mode is feature drift, where the degraded version of your app becomes so out of sync with the main version that it starts causing data corruption or confusion. For example, if your degraded checkout doesn't apply coupons, users will be angry when they see the final price. In an interview, you'd justify this trade-off by explaining the cost of downtime versus the cost of a simplified UI. You have to be able to argue why stability is worth the loss of feature richness during a peak event. Right, so you're trading off perfection for survival. It's a tactical retreat that allows you to live to fight another day. If you can't explain this trade-off to stakeholders, you'll struggle to get buy-in for your resilience architecture. Now, let's talk about the failure modes of degradation itself. Implementing these strategies is complex, and if you're not careful, they can actually make your system even more fragile. It works, or rather it fails, when the recovery mechanisms themselves become the source of the problem. What matters here is that a broken safety net is more dangerous than no net at all, as it gives you a false sense of security. We are going to look at 3 specific failure modes: missing fallbacks, cascading failures, and dependency timeouts. A high-level failure mode to keep in mind is testing neglect. If you don't regularly practice chaos engineering by manually breaking things in staging, you will have no idea if your degradation logic actually works. In an interview, you'd mention that you don't just write fallback code, you verify it through simulated outages. For instance, if your fallback logic has a bug, it might trigger an infinite loop that crashes your servers faster than the original error would have. Well, the key takeaway is that degradation logic is still code, and all code can fail. Let's look at the first of these common traps. The most common failure mode is simply having missing or lazy fallbacks. This works when an engineer writes a try-catch block but only uses the catch to log the error and move on, leaving the UI with a null value it doesn't expect. What matters here is that it leads to those undefined or blank spots on a page that make the app look unprofessional and broken. A failure mode here is the silent fail, where the backend thinks everything is fine because the error was caught, but the user is staring at a dead screen. For example, if you're fetching a user's name and it fails, don't just show null, show valued customer. In an interview, you'd point out that every external call needs a specific, meaningful fallback action. You should consider two things: what is the safest default value, and how do we notify the monitoring system without crashing the user session. If you don't have a plan for the catch block, you haven't actually finished the feature. It's about being thorough and ensuring that every path through the code ends in a valid state for the user. Failure mode 2 is the dreaded cascading failure. This works when a system tries to be too helpful by retrying a failed request over and over without any delay. If a database is already struggling under high load, 10,000 clients all retrying at the same time will act like a self-inflicted DDoS attack. What matters here is that it can turn a minor hiccup into a total system blackout in seconds. The failure mode here is a lack of exponential backoff and jitter. If everyone retries at exactly 1 second intervals, you get massive spikes of traffic that keep the service from ever recovering. In an interview, you'd explain that you use circuit breakers to stop these retries immediately when a failure threshold is hit. For example, if the payment gateway is timing out, the circuit breaker opens and the app immediately returns a temporary delay message instead of hitting the gateway again. Right. So it's about giving the struggling service some breathing room so it can actually fix itself. If you don't control your retries, your degradation strategy will actually accelerate your system's demise. The third failure mode is dependency timeouts. This works or fails when your system waits too long for a primary service to respond before switching to the fallback. If your timeout is set to 30 seconds, the user has already closed their browser and left by the time your graceful fallback kicks in. What matters here is that high latency is often indistinguishable from an outage in the eyes of a user. A common failure mode is using default timeouts, which are often far too long for modern web applications. In an interview, you'd argue for aggressive timeouts. For instance, if a recommendation service usually takes 50 milliseconds, set the timeout to 200. If it hasn't responded by then, it's probably struggling. So just skip it and move to the fallback. Well, it's about maintaining a fast time to glass. You should consider three factors: the P99 latency of the service, the user's patience threshold, and the cost of serving a stale response early. If you don't fail fast, you're not failing gracefully. You're just failing slowly, and that's much worse for the business. The most common mistake engineers make is treating every feature as equally critical. This flat priority list makes it impossible to shed load effectively, because when the system is under pressure, you don't know what to kill first. This works by creating an all-or-nothing dependency graph, where every service depends on every other service. What matters here is that it leads to an architecture where the entire system is only as reliable as its most fragile, least important component. A failure mode here is when a low-priority logging service fills up the disk, and suddenly the core database can't write transaction logs. In an interview, you'd explain that you avoid this by strictly enforcing service tiers. For example, Tier 1 services have zero external dependencies and guaranteed resources, while Tier 3 services are strictly optional. If you don't have this hierarchy, your graceful degradation will be anything but graceful. Right? So you have to resist the urge to make everything high priority. If everything is a priority, then nothing is. You need to be the one who decides what gets sacrificed so the core can survive the storm. So, we've broken down how to keep a system standing even when dependencies are crumbling around it. The heart of graceful degradation is a conscious trade-off. You are choosing to serve a reduced feature set to ensure the core application stays available. We explored 4 key pillars to make this happen: fallback services, cached responses, feature flags, and service isolation. Think about it. If your fancy machine learning recommendations go dark during a traffic spike, you'd much rather show a static list of top sellers than a broken UI, right? In an interview setting, showing you can distinguish between nice-to-have features and the critical path, like a checkout flow, is exactly the signal an interviewer wants. It proves you're prioritizing business continuity over technical perfection. Just remember the golden rule. Keep the business alive, not every single feature. That's how we keep the lights on when downstream services start failing. In a system design interview, you'll stand out by identifying the critical user flow before you even touch the architecture. You've got to show you can balance four main strategies: fallback services, cached responses, feature flags, and service isolation. If you treat every feature as mandatory, you're just inviting those three classic failure modes, like missing fallbacks, cascading crashes, or those painful timeout delays. It's all about keeping the business alive, even in a limited state. Now, if your real-time search index goes offline, would you rather show no results at all or just a set of popular static links? Drop your answer in the comments. Catch you next time.
Throwing more hardware at a sluggish system is an expensive way to discover you're optimizing the wrong component. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 30 of the System Engineering series, and today we will explore performance bottleneck analysis in a way that helps you prepare for system engineering interviews on this topic. We'll look at identifying which of the four main resources is actually throttling your flow. Showing you can troubleshoot systematically instead of guessing is a massive green flag for interviewers. This lesson opens with a scaling paradox, so we can see why throwing more hardware at a problem often fails if you haven't identified the one dominant resource limitation. We'll dive into the architecture of performance by examining the 6 key areas where systems typically stall: application logic, caching, databases, networking, async queues, and external dependencies. You learn how to spot specific issues like thread contention or database locking that act as invisible ceilings on your throughput. Next, we move into the actual investigation strategy, where we look at 4 essential tools: metrics, tracing, profiling, and load testing, to move from guesswork to data-driven discovery. This is exactly where you show an interviewer you can troubleshoot systematically rather than just shooting in the dark. From there, we explore your 4 main engineering options: optimizing code, caching data, redesigning architecture, or scaling infrastructure. We'll weigh the trade-offs between high-risk engineering effort and recurring infrastructure costs. Finally, we'll cover common failure modes like hidden bottlenecks and dependency latency. By the end, you'll have a systematic framework for isolating the true throughput limit of any distributed system. Let's set the stage with a real situation. Imagine you're managing a high-traffic service, like a ticketing system for a massive global event. As the load increases, users start seeing timeouts. Your immediate response is to double your server count from 10 to 20 instances, but the throughput stays flat and latency actually starts to climb. This works as a perfect test of your diagnostic skills. It matters because it demonstrates that the system has hit a hard ceiling that horizontal scaling can't fix. One classic example of this failure mode is a database connection pool that's already saturated. Adding more app servers just puts more pressure on that single pool, potentially crashing the database entirely. In an interview, being able to articulate why doubling the fleet didn't double the capacity shows you understand the underlying constraints of distributed systems. It is not only about the number of servers, it's about how those servers interact with the shared resources that don't scale as easily as your application logic does. When we analyze performance bottlenecks, we are trying to figure out why horizontal scaling fails when you're solving for the wrong resource limitation. It works by identifying where the request pipeline is being throttled. What matters here is that if you misidentify the bottleneck, every dollar you spend on scaling is wasted. Think of a scenario where your web servers are waiting for a third-party API to respond. Adding more web servers won't make that external API faster. It might even make it slower if you start hitting the rate limits. The failure mode here is treating the system as a black box where more input is expected to equal more output. To excel in an engineering interview, you need to show you can peel back the layers and find the specific resource, like disk I/O or network bandwidth, that's actually causing the stall. We are going to look at the tools and metrics that help you prove exactly where that friction is occurring so you can make a data-driven scaling decision. The scaling paradox is a frustrating reality where you've just doubled your server count but throughput remains flat while latency increases. This phenomenon works because of coordination overhead and resource contention. It matters because it proves that more infrastructure doesn't always equal more speed. For instance, if you have a shared global lock in your code, doubling the number of servers just increases the number of threads fighting for that same lock. This is a classic failure mode where the infrastructure scale doesn't match the performance output. In an interview, you should explain that scaling linearly is the dream, but real-world systems often hit sublinear or even negative scaling at a certain point. A concrete example is a distributed cache that becomes a hotspot. As you add more clients, the cache gets overwhelmed by the sheer volume of connection requests, even if the data itself is small. Identifying this paradox early prevents you from wasting time on infrastructure changes that don't address the core architectural limitation. A very common problem is optimizing the wrong component. This happens when engineers focus on the most visible or easiest part of the system rather than the one actually throttling the flow. It works by creating a false sense of progress. For example, you might refactor a Java function to be 20% faster, but if that function only takes up 1% of the total request time, the user won't notice a thing. What matters here is that engineering time is your most expensive resource. A failure mode here is premature optimization, where you fix things that aren't broken, while the real bottleneck, like a slow database query, remains untouched. In an interview, you can distinguish between the visible component and the actual bottleneck. Consider a system where the UI is slow. You might spend weeks optimizing JavaScript, only to realize the real delay is a backend service waiting on a legacy mainframe. Always look for the widest part of the latency tail before you start rewriting code, or you'll just be moving the bottleneck around without actually removing it. To fix a system, your goal must be to systematically isolate and identify the specific resource limiting your throughput. There are 4 main resources you need to check: CPU, memory, I/O, and network. This works by looking at the saturation levels of each. If your CPU is at 90%, adding more servers might actually help. But if your CPU is at 10% and latency is high, you're likely blocked on I/O or the network. What matters here is that each resource requires a different fix. For instance, a memory bottleneck might cause constant garbage collection, which looks like a CPU spike but is actually a memory issue. A failure mode is assuming high CPU always means you need more compute. If the CPU is high because of context switching between thousands of threads, adding more servers might just create more context switching across the cluster. In an interview, emphasize that you analyze these 4 resources independently to find the true limit before recommending any architectural changes or hardware upgrades. There is a fundamental design principle called the law of the dominant bottleneck. It states that every distributed system has exactly one dominant bottleneck at any point in time. This works because systems are chains of dependencies, and a chain is only as strong as its weakest link. Solving anything other than that one dominant bottleneck is essentially wasted effort. What matters here is that it forces you to be precise in your diagnosis. For example, if your database disk is maxed out, making your application code faster won't increase total throughput because the data still can't be written any faster. A common failure mode is whack-a-mole engineering, where teams fix minor issues without ever identifying the primary constraint. In an interview, you should mention that as soon as you fix the dominant bottleneck, a new one will inevitably appear somewhere else. The trick is to find the one that gives you the most headroom for the least amount of effort. If you don't focus on the dominant one, you aren't actually improving the system's capacity. To find a bottleneck, you have to understand how data flows across the entire architecture. You should consider 6 main areas: application logic, caching layers, databases, networking, queues, and external dependencies. This works by tracing the journey of a single request from the user's browser to the final data store and back. It matters because a delay in any one of these 6 areas can ripple through the entire system. For instance, if your message queue has high consumer lag, your frontend might look fast, but the actual work isn't getting done. A major failure mode is ignoring external dependencies, like third-party payment APIs that might be down or slow. In a system design interview, you can use this hub-and-spoke model to systematically check each component. If the application is fast and the database is idle, maybe the bottleneck is actually the network bandwidth between your data centers. By visualizing the flow across these 6 components, you ensure that no hidden stall goes unnoticed in your performance analysis. Application logic bottlenecks are often the hardest to spot without deep profiling. This works by analyzing how your code executes in a production environment. There are 4 main issues to watch for: inefficient algorithms, thread contention, garbage collection pauses, and synchronous blocking calls. For example, if you're using a synchronous call to fetch a user's profile on every request, your app server's threads will sit idle waiting for the network, even if the CPU is low. What matters here is that it limits how many concurrent users you can handle. A common failure mode is ignoring garbage collection in languages like Java or Go. If your heap is misconfigured, the stop the world pauses can cause massive latency spikes that look like network issues. In an interview, you'd explain that you use profiling tools to see exactly where the execution time is spent. If 60% of your time is spent on a single reject check, that's your bottleneck. Fixing that code is much cheaper and more effective than doubling your server count. Storage and persistence layers are where most systems eventually hit a wall. When looking at these, we separate the cache from the database. It works by evaluating hit ratios and locking mechanisms. For the cache, you're looking for poor hit ratios or high serialization overhead. In the database, you're usually facing one of 4 problems: locking, slow queries, disk I/O limits, or connection pool exhaustion. What matters here is that the database is typically the most difficult part of the stack to scale horizontally. A typical failure mode is having a single hot row that every transaction needs to update, creating a massive queue of waiting requests. For example, a global counter for likes on a viral post can become a major bottleneck if not handled correctly. In an interview, you should discuss how you'd use read replicas or sharding to alleviate database pressure. If the bottleneck is connection pool exhaustion, adding more app servers actually makes it worse because each new server tries to grab more connections from an already empty pool. Network and asynchronous queue stalls can be incredibly deceptive because they don't always show up on server-level CPU metrics. Network bottlenecks usually come down to 2 things: bandwidth saturation or high packet loss. For queues, you're looking at 3 main points: consumer lag, producer-side pressure, or message serialization delays. This works by monitoring the depth of your queues and the throughput between service nodes. It matters because even if your code is perfect, a slow network or a backed up queue will make the system feel unresponsive. Imagine a scenario where you're sending massive JSON payloads over the network. The time spent serializing and deserializing those objects can actually become the bottleneck. A failure mode here is ignoring the long tail of network latency, where a few slow packets cause a backup of all subsequent requests. In a system design interview, emphasize the need for observability on your message brokers. If the queue is growing faster than you can process it, you found your bottleneck, and scaling the producers will only make the crash happen sooner. The external dependency wall is a ceiling on your performance that's outside your direct control. This works by placing your system speed at the mercy of third-party APIs, authentication providers, or legacy internal systems. It matters because no matter how much you optimize your own code, you can't go faster than your slowest external partner. For example, if your checkout process relies on a legacy inventory system that takes 2 seconds to respond, your total latency is at least 2 seconds. A common failure mode is failing to implement proper timeouts or circuit breakers for these dependencies. If an external API hangs, it can tie up your threads and cause a cascading failure throughout your entire cluster. In an interview, mention that you'd use asynchronous patterns or caching to decouple your performance from these external factors. If you can't avoid the dependency, you have to design around it, perhaps by using a queue to process those requests in the background so the user isn't stuck waiting for a response you don't control. To move from gut feelings to a real solution, you need a data-driven investigation strategy. This works by using a specific sequence of 4 tools: metrics, tracing, profiling, and load testing. First, metrics tell you that something is wrong, like a spike in error rates. Tracing then shows you where the request is getting stuck across service boundaries. Profiling lets you deep dive into the specific functions or lines of code causing the delay. Finally, load testing allows you to validate your bottleneck theories by pushing the system to its breaking point in a controlled environment. What matters here is that it prevents you from guessing and making changes that don't work. A common failure mode is skipping straight to load testing without having metrics in place, which just breaks the system without telling you why. In an interview, explaining this four-step pathway shows that you have a disciplined, professional approach to performance engineering. You aren't just trying things, you're following the data to find the root cause. In an interview, you'll often be asked to choose between metrics and distributed tracing. Metrics work by aggregating data into counters and gauges, like average CPU or requests per second. They are great for identifying that a problem exists. Tracing, on the other hand, tracks a single request as it moves through various services, showing you exactly how much time was spent in each hop. What matters here is that metrics can hide bottlenecks in the averages. For example, your average latency might look fine, but a trace could reveal that 10% of requests are waiting 5 seconds for a database lock. A failure mode is relying solely on metrics and missing the P99 outliers that are ruining the experience for your most active users. Use metrics for high-level health and tracing for surgical precision when investigating specific latency spikes. When you combine them, you get a full picture. Metrics tell you the system is sick, and tracing tells you which organ is failing. This distinction is critical for any senior-level design discussion. Once you've narrowed down the service that's slow, you use profiling and synthetic load testing. Profiling works by taking snapshots of the application stack trace to see exactly which functions are consuming CPU or memory. What matters here is that it identifies the specific hot path in your code. Load testing works by simulating heavy traffic to see how the system behaves under pressure. The goal here is to find the breaking point before your users do. For example, you might run a load test and find that at 5,000 users, your connection pool exhausts and everything stops. A failure mode for load testing is using clean data that doesn't reflect the messy, varied nature of real-world requests. In an interview, you should explain that you use profiling to optimize the code and load testing to validate that the optimization actually increased the system's total capacity. This combination ensures that your changes aren't just theoretical, but actually make the system more robust when the real traffic hits. After finding the bottleneck, you have a menu of 4 engineering decisions to make. Optimize the code, add caching, redesign the architecture, or scale the infrastructure. This works by weighing the cost of the change against the expected performance gain. What matters here is that you don't always want to jump to the most complex solution first. For instance, if a query is slow, adding an index is much cheaper than redesigning your entire data model to use a NoSQL store. A failure mode is choosing the most exciting technology rather than the most effective one. In an interview, you want to show that you are thinking about the business impact. If you can solve a performance problem by adding a Redis cache in a day, that's usually better than spending a month refactoring the core engine. You need to justify why you chose one path over the others based on factors like development time, operational complexity, and long-term maintenance costs. This strategic thinking is what interviewers are really looking for. The first 2 items on our decision menu are optimizing code and caching data. Code optimization works by refactoring algorithms and reducing complexity, like changing an O of n squared operation to O of n. Caching works by storing the results of expensive computations or database hits so they can be reused. What matters here is that these are often the lowest hanging fruit that provide massive gains with minimal infrastructure changes. For example, if you're calculating a complex shipping rate on every page load, caching that result for 5 minutes can drop your CPU load by 80%. A failure mode for caching is not having a clear invalidation strategy, which leads to users seeing stale or incorrect data. In an interview, you'd explain the trade-off. Code optimization is a one-time effort that pays off forever, while caching adds architectural complexity and requires you to think about consistency. Both are powerful tools for widening a bottleneck before you even think about adding more servers. If code and caching aren't enough, you move to architecture redesign and infrastructure scaling. Redesign works by changing how components interact, such as moving from synchronous REST calls to an asynchronous event-driven model using a queue. What matters here is that it decouples services, so one slow component doesn't block the rest of the system. Scaling works by adding more horizontal or vertical capacity, but only after the system is as efficient as it can be. For example, if your app is CPU bound, moving to a larger instance type, vertical scaling, might be simpler than adding 20 small instances. A failure mode is scaling infrastructure to mask poor architecture. If you have a massive memory leak, adding more RAM is just a temporary band-aid. In an interview, argue that architecture changes are for long-term scalability, while scaling infrastructure is for handling immediate growth. You should always aim to optimize the unit of work before you start multiplying the units of hardware. Every engineering decision involves a trade-off between effort and cost. On one side, you have engineering effort, which includes expensive high-risk code changes. On the other, you have infrastructure costs, which are immediate and recurring. This works by calculating the long-term ROI of each approach. It matters because a startup might choose to throw money at cloud servers to save developer time, while a giant like Google will spend months optimizing code to save millions in hardware costs. A failure mode is failing to account for the human cost of complex architectures. If only one person knows how the new system works, you've created a different kind of bottleneck. In an interview, you should walk through this quadrant grid. Is the fix low effort and high impact? Do it now. Is it high effort and low impact? Never do it. Being able to explain why you're choosing a more expensive hardware solution to save 3 months of dev time shows that you understand the business context of engineering. Recognizing performance failure modes is about spotting patterns before they crash the system. There are 3 main patterns to watch for: hidden bottlenecks, dependency latency, and the dangers of queue buildup. This works by monitoring the health of the connections between services, not just the services themselves. What matters here is that a small failure in one area can trigger a cascade that brings down the entire stack. For example, if a small logging service starts responding slowly and your main application waits synchronously for it to finish, your whole site will slow down. This is the cascading failure mode. Another failure mode is the queue of death, where requests pile up so fast that the memory usage spikes and the server crashes. In an interview, you need to show you can design for these scenarios using techniques like fail-fast settings or shed loading. If you don't account for these patterns, your system will be fragile regardless of how many servers you have. Finally, let's look at latency and hidden bottlenecks. A hidden bottleneck is often resource saturation in a small overload component, like a NAT gateway or a single database partition. Dependency latency occurs when a slow upstream service causes a cascade of slow downstream responses. This works by visualizing the entire request path as a timeline. It matters because the user perceived latency is the only metric that truly counts. For example, if your backend takes 50 milliseconds, but your CDN is misconfigured and adds 2 seconds, the user thinks your app is slow. A failure mode is focusing on average latency while ignoring the tail latency, where a few % of users experience terrible performance. In an interview, explain how you'd use a percentile approach, focusing on P95 or P99 to find these hidden stalls. Identifying that one slow service in a chain of 5 is the key to unlocking the throughput of the entire system. Without this visibility, you're just guessing where the friction lives. Alright, let's wrap this up. We've seen that blindly adding servers is a recipe for high builds and flat performance because of the law of the dominant bottleneck. Remember, at any given moment, there's exactly one resource, be it your app logic, the database, or even a hidden queue that's truly throttling your throughput. If you're in an interview and asked to fix a slow system, don't just suggest adding more hardware. Instead, show them you can systematically trace the flow across all 6 layers we discussed: the app, cache, database, network, queues, and external APIs. You've got to identify the specific resource like CPU, memory, or I/O that's hitting its limit. The golden rule here is simple: never optimize what you haven't measured. Once you solve one bottleneck, well, you know it's just gonna move somewhere else. So stay sharp. So that's how we track down why scaling isn't always the answer. In an interview, the key is showing you can troubleshoot systematically without guessing. Don't just throw hardware at it. Use 4 main tools: metrics, tracing, profiling, and load testing to find the dominant constraint. Well, keep in mind that once you fix a database lock, the bottleneck usually moves elsewhere, like to a hidden queue or a network link. You'll need to justify the engineering effort of code changes versus the cost of extra servers. If you double your server count but throughput stays flat, which specific metric would you check first to identify a resource lock? Let me know in the comments. See ya! Physical distance is the one constraint software can't rewrite. When your users are global, every millisecond of travel counts against your performance. Welcome to the Systemic Stack. My name is Kabir Anand. This is episode 31 of System Engineering series, and today we will explore CDN architecture in a way that helps you prepare for system engineering interviews on this topic. We are diving into how edge servers bridge the geographical gap, giving you the logic needed to handle tough interview questions on cache intelligence. This lesson opens with a look at the physical reality of the global latency crisis, showing how thousands of miles of fiber optics create unavoidable delays for users. Well, to solve that, we'll dive into the architecture of CDNs, tracing the request journey through the edge nodes to the origin. You'll get a clear handle on the mechanics of cache hits and misses, along with how TPL and invalidation prevent your data from going stale. From there, we move into the actual engineering decisions, like balancing performance against freshness and choosing between four major industry players: Cloudflare, CloudFront, Akamai, and Fastly. We're also going to look at the darker side of things, failure modes like origin overload and cache poisoning, so you can spot the architectural traps that sink real systems. We'll wrap up by looking at specific strategies for APIs versus HTML, which is a common testing ground in system design interviews. By the end, you'll understand how to justify every layer of your content distribution strategy to keep your origin server protected and your users happy. Think about the engineering pressure behind a global event like the FIFA World Cup 2026. You've got millions of fans trying to access live scores, video highlights, and ticket info simultaneously from every corner of the planet. If your only data center is in Virginia, a fan in Buenos Aires or Tokyo is going to experience massive lag that makes the app feel broken. At this scale, the constraints aren't just about server CPU or memory, they're about the speed of light. Physical distance creates a flaw for how fast a request can possibly travel. In a production context, you're also dealing with unpredictable traffic spikes that can crush a central origin server if you don't have a buffer. The situation we are solving for is high-volume, globally distributed traffic where latency directly correlates to user churn and lost revenue. In an interview, you'd frame this by identifying that the bottleneck isn't the code itself, but the geographical gap between the producer and the consumer. So, we're doing a deep dive into CDN architecture to see how we can bridge that geographical gap between our users and our data centers. The core idea is simple. Don't make the user come to you, take the data to them. But the implementation is where the real engineering challenges live. We are moving away from a centralized model where everything lives in a single home region to a distributed model where we have hundreds or thousands of smaller outposts. This architectural shift changes everything from how we handle DNS to how we manage data consistency. Imagine you're updating a news headline. You now have to think about how that change propagates across the globe. We'll be looking at the trade-offs between stale data and high latency, and how to design a system that stays resilient even when individual edge nodes go down. It's a fascinating look at how we can manipulate the network layer to create a seamless experience for a global audience, regardless of their physical location. Let's talk about the global latency crisis. Imagine a user in Tokyo trying to access a server physically located in New York. We are talking about a distance of roughly 6,700 miles. Even if that data could travel through fiber optics at the speed of light with zero interference, the round-trip time, or RTT, would still be significant. In the real world, you have to account for every single router, switch, and gateway along the way. Every millisecond of delay is a moment where the user might lose interest. Research consistently shows that even a 100-millisecond delay can lower conversion rates by several percentage points. For an e-commerce site, that's not just a technical metric, it's a direct hit to the bottom line. If a page takes 3 seconds to load because the packets are hopping across 5 different continents, the user experience is essentially degraded beyond repair. This is the crisis we are managing, the relentless pressure to keep RTT as low as humanly possible to keep users engaged and active. The distance problem is rooted in physics and the way the internet is physically constructed. We often think of the internet as this abstract cloud, but it's actually a massive web of cables. many of them running across the floor of the ocean. Packets crossing the Atlantic or Pacific face unavoidable delays just by the sheer volume of material they have to pass through. Beyond just the speed of light in glass, there's the issue of routing hops. A request from a mobile phone doesn't just go straight to the destination. It hits the local cell tower, then the ISP's backbone, then potentially several Tier 1 network providers before it even gets close to the target data center. Each hop adds a few milliseconds of processing time and increases the chance of packet loss or congestion. One simple way to picture this is a cross-country road trip with dozens of toll booths and traffic lights. Even with a fast car, those stops add up. To provide a high-performance experience, we have to find a way to bypass this long-distance journey for as many requests as possible. This is exactly why CDNs exist. They solve the distance problem by placing edge servers geographically closer to the user. One simple way to picture this is moving your storefront into the user's neighborhood instead of making them drive to your headquarters in another state. When a user in London wants a photo from your app, they don't have to wait for it to travel all the way from a server in California. Instead, the CDN serves it from a local point of presence or POP right there in London. There are two big benefits to this model. First, the latency drops because the physical path is shorter. Second, it offloads an enormous amount of work from your central origin server. If a million people want the same image, your origin only has to send it once to the CDN, and the CDN handles the other 999,999 requests. This distribution isn't just a performance optimization. It's a fundamental requirement for any application that expects to handle significant traffic without burning through massive amounts of bandwidth and compute resources at the origin. To really master this, we need to visualize the request journey from start to finish. It's not just a straight line, it's a series of decisions. It all starts in the user's browser, where they type in a URL. Instead of going directly to your server's IP address, the request is intercepted and routed. The journey consists of three main phases: the initial connection to the closest CDN node, the internal check within that node to see if the data is already there, and if it's not, the trip to the origin server. Once the origin provides the data, it doesn't just go to the user, it flows back through the CDN where it's stored for the next person. When you're in an interview, being able to walk through this path step by step shows you understand how the network layers interact. For example, if a user in Paris requests a video, the system must decide which specific server in France or Europe is the best one to handle that load at that exact moment. In step 1, we focus on the handoff from the user to the edge server. When the user initiates a request, the system has to figure out which point of presence or POP is the nearest. There are two primary ways this happens: DNS-based routing or Anycast IP routing. With DNS, the name server looks at the user's IP and returns the address of the closest edge node. With Anycast, multiple servers across the globe share the same IP address, and the internet's routing protocols automatically send the request to the topologically nearest one. Imagine a user sitting in a cafe in Berlin. When they hit enter, the network logic ensures they connect to a server in Berlin or Frankfurt rather than one in New York. This initial connection is where we save the most time because we are cutting out thousands of miles of travel right at the start. If this routing isn't optimized, the rest of the CDN's performance doesn't matter because the user has already faced a massive delay just getting to the front door of the network. The interaction between the edge and the origin. When the request hits the edge server, the node checks its local storage. If the content isn't there, we have a cache miss. At this point, the CDN must act as a proxy and fetch the content from your main origin server. This is where the latency is highest because we are finally making that long-distance trip. However, there's a huge silver lining here. Once the edge server gets the data from the origin, it doesn't just pass it to the user and forget it. It caches a copy locally. So when the next user in that same city asks for the exact same file, the CDN can serve it instantly from its local disk. It's like a library. The first person to ask for an obscure book might have to wait for it to be shipped from another branch, but once it's on the shelf, everyone else in town can walk in and read it immediately. This cycle of fetch and cache is what makes the system so efficient over time. A CDN is only as effective as its cache intelligence. It's not enough to just store files. The system has to be smart about what it keeps and for how long. We have to manage 4 key factors: cache hits, cache misses, expiration, and updates. A hit is our goal. That's when the data is served locally. A miss means we failed to save the trip to the origin. But we can't just keep everything forever because data changes. If you're a news site and the top story changes, you don't want to serve yesterday's news just because it's cached. The intelligence comes in the form of headers and rules that tell the edge nodes exactly how to behave. For example, if a user updates their profile picture, we need a way to tell the CDN that the old version is no longer valid. This is a classic engineering trade-off. If you cache for too long, users see stale data. If you cache for too little, you overwhelm your origin server with constant fetches. Finding that balance is the mark of a great architect. Let's break down the mechanics of cache hits versus cache misses. There are three main metrics we look at here. First is the cache hit ratio, which is the percentage of requests served by the CDN without going to the origin. A high ratio, say 95%, means your system is performing beautifully. Second is the latency penalty of a miss. When a miss occurs, the user feels the full weight of the origin fetch plus a tiny bit of CDN overhead. Third is the origin load. Every miss is a direct hit to your backend infrastructure. Imagine you're running a sale on your site. If your hit ratio drops during peak traffic, your origin server could suddenly be hit with 10 times the load it's used to, potentially leading to a crash. In a system design interview, you should emphasize that maximizing the hit ratio isn't just about speed. It's about protecting your core infrastructure from a meltdown scenario. You want to design your assets so they are as cacheable as possible to ensure that hit column is always much taller than the miss one. Freshness is all about timing, and we manage it using two main tools: time to live, or TTL, and invalidation. TTL is a countdown timer we attach to every piece of content. For example, you might set a TTL of 1 hour for a weather icon. For those 60 minutes, the CDN will serve the cached version without asking the origin for updates. But what happens if something changes unexpectedly? That's where invalidation comes in. This is a manual or programmatic purge command that tells the CDN to delete a specific file or even an entire directory from its cache immediately. Think of a breaking news event or a price correction on an e-commerce site. You can't wait for a 3-day TTL to expire if the price is wrong. Invalidation is powerful but expensive and sometimes slow to propagate globally. You have to be careful. If you invalidate everything at once, you'll trigger a massive wave of requests to your origin as every edge node tries to refetch the data simultaneously. It's a delicate balance of automated expiration and surgical manual intervention. As an architect, you're faced with three big decisions that dictate how your CDN performs. First, what content should actually be cached? You have to distinguish between public assets and sensitive user data. Second, how long should that content stay in the cache? This is the TTL strategy we just discussed, and it varies wildly depending on how often the data changes. Third, where should it be distributed? You might not need to cache your content in every single POP globally if 90% of your users are in North America. These choices aren't just one-time settings. They require constant tuning based on traffic patterns and performance logs. If you get these wrong, you either end up with a system that's barely faster than the origin or one that's consistently serving outdated, incorrect information to your users. In an interview, walk the interviewer through these three pillars to show you're thinking about the practical business and technical implications of your configuration, rather than just treating the CDN as a black box. When it comes to content selection, we generally see a split between static and dynamic assets. Static assets like images, CSS files, and JavaScript bundles are the low-hanging fruit. They don't change based on who's looking at them, so they are incredibly easy to cache for long periods. You can host a 5 MB hero image on a CDN and save millions of bytes of origin bandwidth. Dynamic content, like a user's personal dashboard or their shopping cart, is much trickier. In the past, we simply didn't catch this at all. Today, however, we use complex rules or edge computing to handle it. For example, a CDN might cache a generic HTML template, but then use an edge side include to fetch the user's name separately. This allows you to still get some performance benefit without accidentally showing one user's private info to someone else. There are two categories here: cacheable, which is your static stuff, and dynamic, which requires either bypass logic or very short specific TTLs to remain safe and accurate. Setting duration and location logic is a game of balancing performance against freshness. You have to choose your points of presence based on where your users actually live. If your logs show a massive spike in traffic from Sao Paulo, but your CDN doesn't have a pop there, those users are still suffering. For duration, we look at the volatility of the data. A logo might have a TTL of a year, while a trending now list might only be fresh for 60 seconds. There's also the concept of tiered caching. Instead of every edge node going to the origin, they might go to a regional shield first. This middle layer aggregates requests. So if 10 nodes in Europe need the same file, only one request actually goes back to the origin in the US. This adds a bit of complexity, but it's a massive win for origin stability. When you're making these calls, you're always weighing the cost of a slightly stale response against the heavy latency and infrastructure cost of a fresh one. There are four dominant players in the CDN landscape that you likely encounter in production environments. First, there's Cloudflare, which is famous for its strong focus on security and DDoS protection, making it a go-to for many startups. Second is Amazon CloudFront, which is deeply integrated into the AWS ecosystem, making it the logical choice if your origin is already in S3 or EC2. Third, we have Akamai, the industry veteran with an absolutely massive global footprint, often preferred by large enterprises with high traffic needs. Finally, there's Fastly, which carved out a niche by offering high programmability and very fast invalidation times, perfect for dynamic content that changes frequently. Each of these has different strengths. For instance, if your priority is purging cache in under a second, Fastly might be the winner. If you want a set-it-and-forget-it experience with great security defaults, Cloudflare is often the move. Understanding these differences is key when you're asked to justify a vendor choice based on specific project requirements. Even the best designed systems can fail, and CDNs are no exception. When a CDN fails, it can lead to two major types of problems: total outages or subtle dangerous bugs. We've seen real-world examples where a single misconfiguration at a major provider took down half the internet for several hours. This often happens due to a bad update to the edge logic that propagates everywhere at once. Beyond total downtime, you have to worry about security vulnerabilities. If your CDN isn't configured correctly, it might cache sensitive session cookies or private API responses, leading to a massive data leak. Learning from these failures is what makes your architecture resilient. In an interview, you should be ready to discuss how you'd monitor for these issues. You'd want to track your error rate at the edge versus the origin and have a failover plan, like a secondary CDN or a way to bypass the CDN entirely if it starts returning 500 errors. Resilience isn't just about avoiding failure, it's about how you handle it when it happens. Two of the most frustrating failure modes are stale content and cache poisoning. Stale content is a user experience nightmare. Imagine a limited time offer that's already ended but still appears because a CDN node hasn't updated. Or worse, a security patch for a web app that isn't reaching users because the old vulnerable JavaScript is still cached. Then there's cache poisoning, which is a serious security threat. This happens when an attacker sends a specially crafted request that tricks the CDN into caching a malicious or incorrect response from the origin. For example, they might trick the CDN into caching a redirect to a phishing site. Once that malicious response is in the cache, every legitimate user who requests that page is sent to the attacker's site. Preventing this requires very strict header management and ensuring your origin only responds to valid expected requests. It's a reminder that the CDN isn't just a performance layer, it's a part of your security perimeter that needs to be defended. One of the most dangerous architectural bottlenecks is the thundering herd problem. This happens when a heavily cached popular file expires simultaneously across all your edge nodes. Suddenly, instead of serving that file from the cache, thousands of edge servers all realize they have a miss at the exact same time and rush to fetch it from your origin. This can create a massive instantaneous spike in traffic that effectively performs a DDoS attack on your own servers. Another common issue is poor invalidation logic, where you accidentally purge your entire cache globally when you only meant to update one file. Both of these result in origin overload. To prevent this, we use two main techniques: request collapsing, where the edge node only sends one request to the origin even if multiple users are asking for it, and stale while revalidate, where the CDN serves a slightly old version while it fetches the new one in the background. These safeguards are essential for maintaining stability during high traffic events like a product launch. In an interview, you'll likely face a discussion on strategy selection. The interviewer might ask, how would you handle a mix of static images, frequently updated stock prices, and private user profiles? A strong answer shows you know that not all bytes are created equal. You'd explain that you'd set long TTLs for the images, use a no cache or very short TTL for stock prices, and mark user profiles as private so they never hit the CDN. You need to demonstrate that you're thinking about the cache control header, which is the primary way we communicate these rules. They might also push you on the trade-off between consistency and availability. If your origin is down, do you want the CDN to keep serving old content or show an error? There's no single right answer, but a great candidate can explain the consequences of each path. Being able to weigh these options shows you have the practical experience to build a system that's both fast and reliable under pressure. Let's look at the specific resource strategies for APIs and HTML as they are handled very differently. For APIs, the data is often highly dynamic and user-specific. We usually set the cache control to private or no store to ensure the CDN doesn't accidentally share one person's data with another. However, you can still use the CDN to terminate SSL connections closer to the user, which speeds up the initial handshake. For HTML, it's a bit of a hybrid. You want to cache it as much as possible for SEO and speed, but since the HTML is the skeleton of your page, you need an aggressive invalidation strategy. If you update your site's layout, you need that HTML to update quickly. There are two main approaches here. Using versioned URLs for your assets so the HTML can point to new files immediately, or using cache tags that allow you to purge all related content with one command. This level of granularity is what separates a basic setup from a professional high-performance architecture that stays fresh without sacrificing speed. Well, we've just covered how CDNs effectively shrink the globe by tackling the distance problem head-on. The core mental model relies on three main components: the edge servers, the origin, and the routing logic that ties them together. We saw how Anycast or DNS steers users to the nearest point of presence, turning a massive transoceanic round trip into a local hop. But the real engineering happens in the cache intelligence. You're balancing two competing pressures, keeping your TTLs long enough to maintain a high hit rate and protect your origin, yet short enough to avoid serving stale data. In a design interview, you've got to articulate that trade-off clearly. A CDN reduces latency by moving content closer, but it won't fix slow backend computation. Mastering that distinction ensures your architecture stays both fast and reliable under load. So, we've seen how CDNs bridge the gap between global users and your origin. In an interview, show you understand that a CDN focuses on proximity. You're still responsible for the actual computation at the origin. You likely need to justify why you treat dynamic APIs and static images differently. Well, explaining those three big risks, stale content, origin overload, and poor invalidation, shows you're designing for resilience. In the next episode, we will explore when the cloud isn't close enough, edge computing basics, and work through the latency wall, why edge computing exists, and compute journey. If you're hitting a massive traffic spike, why might you deliberately choose to serve stale content? Put your thoughts in the comments. Happy engineering! When milliseconds mean the difference between an autonomous car stopping or crashing, the cloud's simply too far away. Welcome to the System Stack. My name is Kabir Anand. This is episode 32 of System Engineering series, and today we will explore edge computing basics in a way that helps you prepare for system engineering interviews on this topic. So mastering these trade-offs allows you to explain why latency-sensitive workloads like AI inference or high-speed gaming require us to bypass the middle mile and move logic closer to the user. This lesson opens with a deep dive into the latency wall, where we look at why high-pressure systems like autonomous vehicles or trading platforms can't wait for a round trip to a distant data center. We'll trace the compute journey through four main stages: the device, edge nodes, regional centers, and the core cloud, to see how each hop impacts performance and resource availability. From there, we'll break down three primary use cases, covering real-time gaming, IoT, and AI inference, so you can see how local processing keeps these systems safe and responsive. Now, choosing what to move to the edge is a massive interview topic. So we'll compare high-frequency edge logic against heavy-duty cloud processing. We'll also check out real-world platforms like Cloudflare Workers and AWS Wavelength to see how these abstractions actually hit the wire. Finally, we'll tackle the engineering friction of distributed state and debugging before landing on a selective strategy for your next design. By the end, you will understand how to justify edge placement while avoiding unnecessary system complexity. Now, let's ground this in a real engineering situation. Imagine you're building a smart traffic management system for a major city. You have thousands of cameras and sensors at intersections, capturing high-resolution video and LiDAR data. If you try to stream every single bit of that raw data to a centralized cloud for processing, you'll immediately hit two massive walls. First, the bandwidth costs would be astronomical. Second, and more importantly, the time it takes to upload that data, process it, and send a signal back to change a light to avoid a collision is just too long. In this production context, the scale of data and the need for immediate action create a high-stakes environment where traditional cloud architecture fails. You're forced to think about localized processing nodes that can make decisions in milliseconds. If the system relies on a distant server and the network link jitters or drops, the consequence isn't just a spinning loading icon. It's a total breakdown of urban safety and traffic flow. When we talk about the shift toward the network edge, we're really talking about a fundamental change in where the brain of the system lives. For years, the cloud was the destination for everything because it offered massive scalability and easy management. But as we build ultra-low latency applications, we are finding that the center of the network is becoming a bottleneck. Moving to the edge means placing computation resources as close as possible to where the data is actually generated. This mechanism bypasses the long, unpredictable path through the public internet. If you keep everything centralized, your application's performance is at the mercy of every router and switch between the user and your data center. By shifting to the edge, you're reclaiming control over the latency budget. In an interview, you'd explain this as a move from a hub-and-spoke model to a more distributed mesh where the edge node handles the immediate time-sensitive logic while the core cloud focuses on long-term storage and heavy-duty analytics across the whole system. Let's look at why high-pressure environments make centralized cloud setups completely unusable. Imagine you're designing the system for an autonomous vehicle cruising at 70 miles per hour. At that speed, the car covers about 100 feet every second. Now, if that vehicle detects an obstacle and needs to decide whether to brake, sending that data to a centralized data center and waiting for a response takes time. Even a typical round trip of 200 milliseconds becomes a massive system failure because in that tiny window, the car has already traveled 20 feet. We see a similar pressure in high-frequency trading, where a millisecond of delay means millions in lost opportunity. In these scenarios, the consequence of relying on distant servers isn't just a slow UI, it's a total breakdown of the system's primary function. You're essentially fighting the speed of light. If the processing doesn't happen locally or at a very nearby edge node, the safety and financial requirements of the application simply can't be met, leading to physical accidents or complete market irrelevance. The latency wall is a fundamental constraint dictated by the physics of fiber optics and network routing. Even if your code is incredibly optimized, distance equals delay. You have to account for the physical distance signals travel, the overhead of handshakes, and the congestion of the middle mile. For many modern applications, staying under a 50 millisecond threshold is the goal. But once your data has to travel across a continent, you've already hit the wall. Think about a remote surgery system where a surgeon uses a robotic arm from another city. If there's a 300 millisecond delay between the surgeon's hand movement and the robot's action, the system becomes dangerous and unusable. This isn't a software bug you can patch, it's a structural limitation of centralized networking. When you hit this wall, the user experience doesn't just degrade, it breaks the core promise of the service. In an interview, you should highlight that the only way to scale past this wall is to shorten the physical path, which is exactly what edge computing aims to do. So, why does edge computing exist? The core objective is to execute computation right where the action is, bypassing what we call the middle mile of the internet. This is the messy part of the web where your packets hop through various ISP networks and peering points, adding unpredictable jitter. By moving logic to the edge, you're creating a shortcut. Well, it is not only about speed, it's also about data reduction. If you have 1,000 industrial sensors in a factory, you don't want to flood your corporate network with every single all-clear heartbeat. You use edge nodes to filter that noise and only send up the critical alerts. If you fail to implement this, your core cloud will be overwhelmed by trivial data and your network costs will skyrocket. Edge computing acts as a first responder and a filter, ensuring that the heavy lifting happens locally so the central system can focus on the big picture without being bogged down by every micro event happening at the thousands of remote sites. To understand how this works in practice, let's follow the compute journey. There are 4 distinct hops in this architecture. First is the device itself, like a smartphone or an IoT sensor, which handles immediate low-level tasks. Second is the edge node, which could be a CDN point of presence or a 5G telco hub located just miles from the user. Third is the regional cloud, a smaller data center closer to a major city. Finally, you have the core centralized cloud where the massive data warehouses live. Each step away from the user adds more latency, but offers more compute resources and cheaper storage. Now, if you misplace a workload, like running a real-time physics engine in the core cloud, this system will lag and frustrate users. Conversely, if you try to run a massive machine learning training job on a tiny edge node, the node will run out of memory and crash. A strong engineering answer describes how you balance these 4 layers, placing time-sensitive logic at the edge and heavy, data-intensive processing at the core. It's important to realize that edge computing isn't a general replacement for the cloud. It's a specialized tool for high-demand workloads. Think of it as a specialized fast lane. While the centralized cloud remains the king of bulk storage and complex global analytics, the edge is where real-time interactions live. For instance, consider a facial recognition system for building security. You don't want to send high-def video to a data center across the country just to unlock a door. You process the image at the edge to give the user a seamless experience. If you try to use the edge for everything though, you'd run into problems with data consistency and high costs. Because edge resources are generally more expensive and limited than centralized ones. So, the edge shines when you have specific constraints around latency, bandwidth, or autonomy. When these factors aren't present, the centralized cloud is usually the more cost-effective and simpler choice. Mastering this distinction is what interviewers look for when they ask about distributed system design. Let's look at a concrete example: real-time gaming. In this world, lag is the ultimate enemy. Imagine the infrastructure needed for a massive event like the FIFA World Cup 2026. If a gaming company is hosting a tournament around that event, they can't have players in different cities facing different delays. By processing player inputs and physics calculations at the edge node nearest to each gamer, the system ensures competitive fairness. If you were to process all those moves in a central server, a player in New York would have a massive advantage over someone in a more remote location due to the shorter distance to the data center. The consequence of a centralized approach here is a broken game loop, where inputs feel sluggish and unfair. By using edge nodes, you synchronize the state locally and only push the final results to the global leaderboard. This mechanism keeps the experience tight and responsive, preventing the jitter and disconnects that would otherwise ruin the competitive integrity of the match. In the world of IoT and autonomous systems, the edge is a safety requirement. Take an industrial robot in a manufacturing plant. It needs to react instantly if a human steps into its work zone. If that safety logic depends on a cloud connection that might be unstable, a simple network hiccup could lead to a catastrophic injury. By running the safety-critical decision-making locally on an edge gateway, the robot can shut down in milliseconds regardless of whether the internet is up or down. We see the same thing with self-driving cars. They must be able to navigate and avoid obstacles even when passing through a tunnel with zero connectivity. If you design these systems to be cloud-first for every decision, you're building a fragile system that fails the moment it loses its data. The edge provides the operational continuity that these high-stakes systems demand, ensuring they remain functional and safe even in the face of network partitions or high-latency spikes. Video analytics and AI inference are another huge area where the edge is transformative. Imagine a retail chain using AI to track inventory levels via shelf cameras. Uploading thousands of streams of 4K video to the cloud 24/7 would destroy their bandwidth and cost a fortune. Instead, they use edge appliances to run the AI models locally. These nodes process the raw video, identify that a shelf is empty, and then only send a tiny text notification to the central inventory system. This mechanism drastically reduces data egress costs and lightens the load on the core infrastructure. If the edge node fails, you might lose some real-time tracking, but your entire network won't be saturated by useless video data. In an interview, you should emphasize that the edge is perfect for data thinning, turning massive amounts of raw, unrefined data into small, actionable insights before they ever hit the long-haul network, making the overall system much more efficient. When making architecture choices, you're always balancing performance against cost and complexity. Moving logic to the edge isn't free. It requires specialized deployment tools and often involves paying a premium for edge compute providers. So the question you'll face in a system design interview is, how do you decide what goes where? You have to look at the latency requirements first. If the user needs a response in under 50 milliseconds, the edge is your only choice. Then look at the data volume. If you're generating terabytes of data that only needs once a day analysis, the core cloud is better. A common mistake is to over-engineer by putting simple CRUD operations at the edge, which just adds sync complexity without any real user benefit. You have to justify every piece of logic you move out of the center. If you fail to strike this balance, you'll end up with a system that is either too slow for the user or too expensive and complicated for the business to maintain. Specifically, edge workload should focus on high-frequency updates and safety-critical logic. For example, in a modern web app, you might use edge functions to handle UI state transitions or personalized content delivery. If you're doing A/B testing, running that logic at the edge means the user doesn't see a flash of the original content while the server decides which version to show. It happens instantly at the CDN layer. Another great edge use case is authentication. By verifying a user's session token at the edge node, you can reject unauthorized requests before they even touch your expensive backend servers. If you don't do this, your core infrastructure is forced to process every single bot and malicious request, which wastes resources and increases your attack surface. So, the edge is your first line of defense and your best tool for creating that instant feel in high-frequency user interactions where every millisecond counts towards engagement and security. On the flip side, centralized cloud infrastructure is where you want to handle heavy data storage and massive batch processing. Think about global financial reporting or training a large language model. These tasks require massive amounts of CPU and GPU power that you just can't find at a distributed edge node. Centralized clouds are also much better for archival storage and global analytics where you need a unified view of data from all over the world. If you try to do this at the edge, you'd have to constantly sync data between thousands of nodes, creating a massive overhead and likely resulting in inconsistent data. The consequence of misplacing these heavy workloads is extreme inefficiency. You'd be paying for expensive edge compute to do something a standard VM could do for a fraction of the cost. In an interview, always frame the centralized cloud as the source of truth and the heavy lifter that supports the agile, fast-acting edge nodes. Now let's talk about the real technologies making this possible. We are seeing a rise in edge as a service models that simplify deployment. There are three main categories of players here. First, you have programmable CDNs like Cloudflare and Fastly that let you run code at their points of presence. Second, you have telco integrated zones where cloud providers like AWS or Azure place servers directly inside 5G networks. Third, you have specialized IoT edge platforms for factories and warehouses. These technologies allow developers to deploy code globally with a single command, but the underlying mechanism is quite complex. If you don't understand how these platforms handle traffic routing, you might find your edge code is actually running further away than you expected. Choosing the right platform depends on whether your workload is more web-focused or mobile device-focused. Failure to pick the right category can lead to poor integration with your existing cloud stack and increased operational friction when you try to scale. Serverless edge platforms like Cloudflare Workers and Fastly Compute at Edge are game changers for web performance. They allow you to run lightweight JavaScript or Rust code directly on CDN points of presence. This means when a user in Tokyo requests a page, the logic executes in Tokyo, not in a data center in Virginia. It's perfect for things like custom headers, localized content, or real-time image resizing. Because these environments use isolates instead of full containers, they start up in milliseconds, avoiding the cold start problem of traditional serverless functions. However, the trade-off is that you have restricted access to file systems and long-running processes. If you try to run a heavy image processing library that isn't optimized for these environments, the function will time out or hit memory limits. In an interview, you'd highlight these platforms as the go-to for optimizing the last mile of the web experience, while acknowledging their resource constraints compared to full VMs. For more heavy-duty hybrid needs, we have solutions like AWS Wavelength and Azure Edge Zones. These services actually bring standard cloud VMs and containers directly into the 5G carrier networks. This is huge for mobile applications. Imagine an augmented reality app where digital objects are overlaid on the real world in real time. By hosting the rendering logic in an AWS wavelength zone at the telco hub, the data never even has to leave the cellular network to hit the public internet. This reduces latency to single-digit milliseconds. Well, if you don't use these specialized zones, the AR objects will drift or lag as the signal bounces through the broader internet, completely breaking the immersion. For an engineer, this means you can use the same Docker containers and APIs you use in the core cloud, but run them at the extreme edge. It's a powerful way to bridge the gap between high-performance mobile needs and standard cloud development workflows. Deployment and distributed state are where edge computing gets really tricky. It's one thing to deploy code to 3 data centers, it's another to manage it across 3,000 edge nodes. You have to ensure every node is running the same version of your logic and handle the split brain scenarios that happen when the network partitions. Managing data consistency is the biggest headache. If a user updates their profile at an edge node in London, how quickly does that change reflect for a user in Singapore? If you use a traditional asset database, the latency of the sync will kill your performance. If you use an eventually consistent model, users might see stale data. The consequence of a poor state management strategy is a buggy, confusing user experience. In an interview, you should talk about using conflict-free replicated data types, or CRDTs, and edge local caching to balance the need for speed with the reality of distributed state. Synchronization and debugging are the final operational hurdles. When you have a massive geographic footprint, observing what's happening in real time is incredibly difficult. You can't just log into a single server to see what went wrong. You need a centralized logging and tracing system that can aggregate data from thousands of locations without overwhelming your network. If you don't have robust observability, a bug that only appears in one specific region can be almost impossible to track down. For example, a localized network congestion issue in one city might make your edge node look like it's failing when it's actually just a connectivity problem. This increases troubleshooting friction and can lead to long outages. As a system engineer, you need to build telemetry first, ensuring that every edge node reports its health and performance in a way that gives you a global view. Otherwise, you're flying blind in a very complex distributed environment. Let's walk through a classic interview discussion. An interviewer might ask, should we move our entire backend to the edge to maximize performance? A junior candidate might say yes, but a strong engineer knows the answer is only for the latency-sensitive components. You'd explain that moving low-frequency CRUD operations like updating a user's billing address to the edge adds massive complexity with almost zero perceptible value to the user. Instead, you'd suggest a hybrid approach. Keep the heavy transactional data in the core where consistency is easier to manage and push the performance-critical parts like the API gateway, authentication checks, and real-time notifications to the edge. This shows the interviewer you understand the trade-offs between performance and operational overhead. You're demonstrating that you don't just follow trends. You make decisions based on the specific needs of the workload, avoiding the edge everything trap that leads to unmaintainable and overly expensive systems. The ultimate engineering lesson here is the Goldilocks principle of compute. You want to push only the latency-sensitive or bandwidth-heavy workloads towards the edge. If you push too much, you drown in complexity. If you push too little, your performance suffers. Think of it as a filter. The edge handles the now and the local, while the core cloud handles the always and the global. For example, a smart security camera should detect motion and recognize faces at the edge to give instant alerts. But the long-term storage of that video and the training of the recognition models should happen in the core cloud, where storage is cheap and compute is plentiful. If you ignore this balance, you will end up with a system that is either too slow to be useful or too expensive to be viable. This selectivity is the hallmark of a senior system designer who knows how to leverage the strengths of both worlds to build a robust, scalable, and high-performance architecture. Alright, we've really broken down why the cloud isn't always enough. We started with the latency wall, that hard physical limit where distance breaks things like high-speed gaming or autonomous vehicles. To solve this, we mapped out the four-step compute journey, starting at the device, hitting the edge node, then regional cloud, and finally the code. It's all about bypassing that middle mile. Now, while tools like Cloudflare Workers or AWS Wavelength are powerful, edge computing shouldn't be your default for everything. You've got to balance those speed gains against the real engineering hurdles of distributed state and synchronization. In an interview, your strength is showing you can justify that added complexity. Keep the heavy lifting in the central cloud and only push the truly latency-sensitive workloads out to the edge. So, we've seen why the edge is vital for hitting those sub-50 ms latency targets. In an interview, it's crucial to justify the extra complexity. You've got to show you understand the four-stop journey: device, edge node, regional cloud, and the core. For example, in an autonomous vehicle system, you'd run emergency braking logic at the edge but send telemetry to the core for long-term analysis. Don't fall for the trap of moving every microservice to the edge. Keep simple CRUD operations central to avoid massive sync nightmares. In the next episode, we'll talk about stop moving data across the planet, data locality, and look at the hidden cost where performance disappears and the locality principle. If a user's moving between geographic edge nodes, how would you handle their session state without constantly hitting the core database? Drop your thoughts in the comments. Happy coding! When a user in Tokyo waits for a database in Frankfurt, physics imposes a lag tags no amount of code optimization can fix. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 33 of System Engineering series. And today we will explore data locality in a way that helps you prepare for system engineering interviews on this topic. So we'll look at four main placement strategies that minimize this distance, helping you justify architectural choices when global latency starts to impact system performance. It starts by looking at the global request crisis, where physical distance creates a massive lag tax on the user experience. We'll examine exactly how performance disappears where requests hop across regional boundaries or poll remote storage, which often stalls threads and adds unnecessary overhead. From there, we'll dive into the locality principle and a crucial design choice, whether to pull data to your app or move the compute logic directly to the data. This leads into four main placement strategies: regional databases, local caches, partitioning, and geo-distribution. So you'll know how to keep hot data within the immediate network segment. We are also going to break down how real-world systems like Redis, Cassandra, and HDFS handle these challenges through features like rack awareness. Of course, locality isn't free, so we'll look at the traps of cross-region traffic and the operational costs of stale replicas. Finally, we'll use the data-to-code ratio to decide when compute should travel to the data. By the end, you'll understand how to minimize distance to ensure your system respects the laws of physics. Let's set the scene with a real-world scenario that highlights why what matters here. Imagine we're preparing for a massive event like the FIFA World Cup 2026, where fans from every continent are trying to access ticket data, live scores, and player stats simultaneously. If your primary database is sitting in a single data center in North America, a fan in Sydney or Mumbai is going to have a terrible experience. Every click they make has to travel halfway around the world and back. This creates a massive constraint where the speed of light becomes your biggest competitor. You're dealing with hundreds of milliseconds of unavoidable latency before your code even starts executing. When you're operating at this kind of scale, you can't just optimize your SQL queries to fix the lag. The problem is structural. You have to decide where the data lives relative to the user to avoid a total system stall under the weight of global demand. Think about a user in Tokyo who triggers a process that seems simple on the surface. But behind the scenes, the application fetches metadata from a server in London, sends logs to a service in New York, and finally writes a record to a master database in Frankfurt. Even if you're using the fastest fiber optics available, you're hit with a lag tax that ruins the user experience. Each of those hops involves physical distance, routing through various internet exchange points, and potential congestion. The consequence is a request that feels sluggish and unresponsive, even if your backend code is highly optimized. If one of those links fails or slows down, the entire process hangs. This is the global request crisis in action. It's a common failure mode where architects forget that while the internet makes the world feel small, the physical reality of packets traveling thousands of miles still dictates the ceiling of your system's performance. In distributed systems, we often see performance disappear into thin air, and it's usually not because the CPU is pegged or the memory is full. The culprit is often the physical distance between your application logic and its dependencies. When your app is sitting in one region and its database is in another, you are introducing latency leaks that accumulate over time. Every single network round trip adds up. If a single page load requires 10 database calls and each call has a 30 millisecond network penalty, you've just added 300 milliseconds of delay before the user sees anything. This is a critical point to bring up in an interview because it shows you're looking at the system holistically rather than just focusing on code level optimizations. You need to account for the speed of light. If you don't minimize that physical gap, no amount of multi-threading or efficient indexing will make the system feel truly fast to a global audience. Whenever a request crosses a regional boundary, it's almost guaranteed to incur at least 100 milliseconds of physical latency. In a modern microservices mesh, where services are constantly talking to each other, these synchronous hops can quickly accumulate into seconds of total delay. Let's say service A calls service B, which then calls service C. If those services are scattered across different global regions, you're essentially stacking those latency penalties on top of each other. The consequence of this design is a brittle system where the slowest network link determines the overall response time. It also increases the surface area for failure. A submarine cable cut or a regional routing issue can suddenly take down parts of your application that you thought were local. When you're explaining this in an interview, emphasize how these regional boundaries act as high friction zones that need to be navigated carefully through asynchronous patterns or better service placement. Fetching small records from a remote database or constantly polling distributed storage across a wide area network creates what we call network chatter. This chatter is a major performance killer because it stalls your execution threads while they wait for data to arrive from thousands of miles away. It also increases connection overhead since your system has to maintain state over long distances. For instance, if your application is in London and it's pulling tiny user profile updates from a database in Singapore, the actual data transfer might take microseconds, but the wait for the round trip takes forever. This inefficiency can lead to a failure mode where your application servers are idle most of the time, just waiting on the network, which effectively lowers your overall throughput. To fix this, you have to transition from a chatty communication style to a chunky one, where you fetch larger blocks of data less frequently, or better yet, move the data closer to the compute. The locality principle is a foundational rule in systems engineering. You must keep data physically close to the services that consume it. The goal here is to minimize the distance to data as much as possible. By ensuring that high-frequency interactions happen within the same rack or at least the same availability zone, you virtually eliminate the network lag that plagues distributed systems. Think about a high-frequency trading platform. They pay millions to have their servers in the same building as the exchange because every meter of cable adds nanoseconds of delay. While most of us aren't building trading bots, the logic still applies. If your application frequently reads from a cache, that cache should be sitting right next to it, not across a regional border. When you follow this principle, you're designing for the best-case scenario of physics, which results in a system that is not only faster, but also more predictable and resilient to wide-area network fluctuations. There's a powerful alternative to moving data that many people overlook: moving the compute instead. Sometimes it's significantly cheaper and faster to send your application logic to where the data already lives rather than pulling massive data sets across the network. There are three common ways to do this: using stored procedures in a database, implementing MapReduce jobs, or deploying edge functions. For example, if you're analyzing a petabyte of logs stored in a specific region, you don't want to stream all that data to a central server. Instead, you deploy a small piece of code to run on the storage nodes themselves, process the data locally, and only send back the small summary results. This reduces network congestion and dramatically speeds up processing time. In an interview, suggesting this approach when dealing with large-scale data analytics shows that you're thinking about bandwidth costs and the sheer physical effort of moving bits across a wire. As an architect, you have to choose the right data placement strategy based on three key factors: how often the data is accessed, what your consistency requirements are, and where your users are located. There isn't a one-size-fits-all solution here. If you have a global user base, but the data is rarely updated, you might choose a very different path than a system with high-velocity writes that must be seen globally in real time. For example, a social media feed can handle a bit of lag between regions, allowing for aggressive local caching. However, a global inventory system for a popular product launch might require more complex sharding to ensure users aren't buying items that are already out of stock elsewhere. You're always navigating the trade-off between keeping data local for speed and keeping it synchronized for accuracy. Understanding these pressures allows you to justify why you chose a specific hub and spoke or mesh architecture during a technical deep dive. A very effective way to handle locality is by using regional databases combined with local caches. You can set up regional databases to handle local writes, which keeps the primary interaction within the same geographic area. To speed up reads even further, you use a multi-layered caching strategy, specifically L1 and L2 caches. An L1 cache might live directly in the application's memory, while an L2 cache like Redis sits in the same network segment. This setup keeps your hot data, the stuff people are looking at right now, just a few microseconds away. Imagine a news site where the latest breaking story is cached in every region. When a user in London hits the site, they get the data from a London-based cache rather than waiting for a request to hit a master server in California. This drastically reduces the load on your primary database and ensures that the most frequent requests are served at the highest possible speed. Partitioning and geo-distribution, often called sharding, involve breaking your data up by user geography and spreading it across the globe. This ensures that a user in India always connects to a data shard located in an Indian data center. There are two big benefits to this. First, the user gets incredibly low latency because the data is literally just a few miles away. Second, it helps with data sovereignty laws, as you can keep a country's data within its borders. Think about a ride-sharing app. A passenger in Paris doesn't need to see the location of drivers in New York. By sharding the data so that Paris-based requests only hit European servers, you optimize the system for everyone. The trade-off you'll need to explain in an interview is the complexity of cross-shard queries. If that Paris user travels to New York, the system has to handle moving their data or querying a remote shard, which is where the design gets interesting. When it comes to implementation, selecting the right technology stack is absolutely critical because modern tools have different ways of handling locality. You should be familiar with four main categories: in-memory localizers, geo-distributed databases, rack-aware file systems, and cloud-native storage. Each of these technology families addresses the distance-to-data problem in a unique way. For instance, some databases handle replication and sharding automatically, while others require manual configuration. If you choose a tool that isn't designed for multi-region awareness, you'll end up fighting the technology just to get basic performance. In an interview, being able to name-drop specific tools like Redis or Cassandra and explaining exactly how they manage data placement gives your answers a lot of credibility. It shows you aren't just talking about abstract concepts, but you understand the practical engineering needed to make locality work in a production environment. We look at a few of these in detail now. Redis is often the go-to tool for achieving sub-millisecond local access. By deploying Redis as a sidecar or within local clusters in every region, you provide an ultra-fast data bridge for your application nodes. It excels at keeping frequently accessed state like user sessions or rate-limiting counters right where the compute happens. One common pattern is using Redis for local-site caching, where the app first checks the local Redis instance before ever reaching out to a slower, remote database. This effectively shields your backend from the vast majority of read traffic. However, a failure mode to watch out for is cache inconsistency. If you're running Redis in multiple regions, you have to decide how and when to sync them. If you don't have a solid plan for cache invalidation, users in different parts of the world might see conflicting information, which can lead to confusing bugs that are notoriously difficult to track down and fix. Cassandra was practically built for geo-distribution and wide column locality. One of its most powerful features is the network topology strategy, which allows you to define exactly how many replicas of your data exist in each physical data center. This means you can tell Cassandra to keep 3 copies of a piece of data in the US East region and 3 copies in the EU West region. This design ensures that even if an entire undersea cable is cut, users in Europe can still access their data from the local replicas. The consequence of this high availability is that Cassandra often relies on eventual consistency. When a user in London writes data, it's saved locally immediately, but it might take a few seconds to sync to the US. In an interview, you'd want to discuss how you'd handle that delay, perhaps by using local quorum reads to ensure the user always sees their own most recent changes while maintaining high performance. The Hadoop Distributed File System, or HDFS, uses a concept called rack awareness to manage data locality. Within a large data center, there are 3 main components to consider: the individual nodes, the racks they sit in, and the switches that connect them. HDFS is smart enough to know that talking to a node in the same rack is much faster than talking to one in a different rack. By default, it tries to place data replicas such that at least one is on a different rack to protect against a localized hardware failure, like a top-of-rack switch dying. This strategy balances the need for high throughput with the need for resilience. If your application logic is scheduled on a node that already has the data block it needs, you get data local execution with zero network overhead. This is a classic example of moving compute to data that remains a gold standard for big data processing architectures. Cloud providers have built-in locality features that you should leverage. Amazon S3, for example, uses regional buckets. When you store an object in an S3 bucket in the Tokyo region, that data stays in Tokyo unless you explicitly tell it to replicate elsewhere. This is vital for both performance and compliance. On the other hand, Google Bigtable offers multi-cluster routing, which automatically serves data from the nearest available cluster to the requester. This means if you have clusters in the US, Europe, and Asia, Bigtable will route the traffic to the one with the lowest latency. The failure mode to keep in mind here is the egress cost. Moving data between regions in the cloud is expensive. If you accidentally set up a service in one region to pull data from a bucket in another, you will see a massive spike in your monthly bill. Interviewers love to see that you're mindful of these hidden operational costs when designing global systems. It's important to remember that data locality isn't a free lunch. While it solves many performance problems, it introduces significant architecture pitfalls. Incorrectly implemented strategies can lead to severe operational overhead and data integrity issues. One major risk is the increased complexity of your deployment pipeline. Managing 5 regional databases is much harder than managing one. You also have to deal with the split brain scenario, where different regions think they have the most up-to-date information but are actually out of sync. This can lead to data loss or corruption if not handled with robust conflict resolution logic. In an interview, you should be prepared to discuss these danger zones. You aren't just selling locality as a magic fix, you're acknowledging that it requires a more sophisticated engineering team and better monitoring to manage the trade-offs between speed and consistency. Being honest about these risks shows a level of seniority that interviewers look for in lead architect roles. One of the biggest traps in global architecture is relying on cross-region traffic for real-time consistency. This often leads to what we call the slowest common denominator problem. Imagine you have a transaction that requires a synchronous OK from nodes in London, New York, and Sydney. The entire system's speed is now limited by the furthest, slowest node and the current state of the global internet. If a packet gets dropped in the Pacific, your whole system in London hangs. This bottleneck can turn a high-performance application into a frustratingly slow experience for everyone, regardless of their location. The consequence is a funnel effect where your local speed is wasted because you're waiting on a global sync step. To avoid this, you have to find ways to decouple your regional operations. In an interview, explain how using asynchronous replication or Saga patterns can help break this dependency on the slowest link and keep the system moving. When you optimize for locality, you're usually choosing a path that leads to eventual consistency, and that comes with two major risks: stale replicas and high replication costs. Stale replicas can lead to time travel bugs, where a user updates their profile, refreshes the page, and sees their old data because they hit a replica that hasn't synced yet. This is incredibly frustrating for users and can look like a bug in your code when it's actually an architectural trade-off. On the operational side, you have to worry about cloud egress costs. Every time you replicate data across regional boundaries, you're paying the cloud provider. If you're not careful, the cost of keeping all your global nodes perfectly in sync can spiral out of control. You have to categorize these pitfalls into system accuracy and operational cost to decide if the performance gain is truly worth it for your specific use case. In an interview, you might be asked, should compute travel to data or data travel to compute? This is a classic test of your architectural judgment. The answer almost always depends on the data to code ratio. If you have a massive dataset, say several terabytes of transaction history, it's much more efficient to move your small piece of code to the data. This is what MapReduce and stored procedures are designed for. On the flip side, if you have high-velocity logic that needs to react instantly to user input, you want the data to be already sitting in a local cache. Think about the trade-off like this. Moving a 100 kilobyte script to a petabyte of data is easy, but moving a petabyte of data to a 100 kilobyte script is a nightmare. By focusing on this ratio, you give the interviewer a clear logical framework for your decision-making. It shows you understand that efficiency is about minimizing the total work done by the network. If there's one thing I want you to take away from this whole discussion, it's this: the fastest byte is the one that never has to cross the network. As engineers, we often get caught up in complex algorithms and micro-optimizations, but the biggest wins come from respecting the laws of physics. You want to minimize the physical distance, eliminate unnecessary network hops, and keep your data as close to the user as possible. When you do this, you're not just making the app faster, you're making it more reliable and cheaper to operate. This golden rule of locality should guide your design from the very first day. Whether you're building the next global social network or a small internal tool, always ask yourself where the data is and how far it has to travel. If you can keep that distance to a minimum, you've already won half the battle in building a high-performance, scalable distributed system. So, we've broken down why the fastest byte is the one that never has to cross a network. When you're designing global systems, you've got to respect the lag tax created by physical distance. We saw how a simple request spirals into seconds of delay if your app in Tokyo is constantly chatting with a database in Frankfurt. To fight this, you've got 4 name placement strategies: regional databases, local caches, data partitioning, and geo-distribution. In a high-level design interview, your goal is to decide whether to bring data to the compute or move the compute to the data using something like edge functions. Whether you're leveraging Redis for speed or Cassandra for distribution, well, the logic stays the same. You're balancing consistency against the massive overhead of cross-region traffic. It's almost always cheaper to move your code than to haul gigabytes across the WAN. Well, that's how physics dictates our architecture. In an interview, you'll need to balance 4 strategies: regional databases, local caches, partitioning, and geo-distribution. Always justify your approach using the data-to-code ratio. If the data is massive, move the compute. Otherwise, bring the data closer. Just watch for stale replicas, which can trigger those nasty time travel bugs for users. Next, we'll jump into move more data without paying more, compression strategies, where we'll explore the bandwidth problem, the compression toolbox, and where compression wins. In a system where storage is cheap but egress is expensive, would you prioritize CPU-heavy compression or just accept the network lag? Let me know in the comments. Stay sharp. Ever wonder why your cloud bill spikes even when traffic stays flat? Well, it's usually the hidden weight of your data payloads dragging down performance. Welcome to the System Engineering series. My name is Kabir Anand. This is episode 34, and today we'll explore compression strategies in a way that helps you prepare for system engineering interviews on this topic. Deeply understanding the trade-off between CPU overhead and network throughput demonstrates the architectural maturity interviewers expect when you're deciding between algorithms like gzip or Brotli. We begin with a real-world scaling crisis, where a massive e-commerce platform hits a wall of skyrocketing cloud egress costs and latency spikes. This sets the stage for understanding the bandwidth problem and how large payloads trigger a domino effect on transfer speeds and infrastructure fees. From there, we'll open up the compression toolbox to compare two main web standards, gzip and Brotli, while also weighing the trade-offs between lossless and lossy mechanisms. Applying these strategies involves more than simple file zipping. We'll identify high ROI targets like APIs and static assets, while also pinpointing exactly where compression can backfire. Think CPU bottlenecks or tiny payloads that actually grow after processing. To bring it all together, we'll explore modern implementations using NGNX and Z-Standard to see how these tools operate at scale. By the end, you'll understand how to balance network bandwidth, CPU consumption, and storage savings to justify every byte you send across the wire. To ground this in reality, let's look at a typical production situation. Imagine you're scaling a service that handles millions of daily requests. As your data model evolves, your payloads grow from 10 KB to 100 KB because of new metadata requirements. Suddenly, your cloud egress fees are skyrocketing, and your mobile users in low bandwidth regions are seeing significant delays. The mechanism here is simple. More data means more packets, more round trips, and more expensive transfer. The consequence is a degraded user experience and a shrinking profit margin. If you ignore this, the failure behavior manifests as timing out requests and hitting the limits of your network throughput. In an interview, you'd want to describe this as a point where the cost of infrastructure starts to outpace the value of the data being sent. We need a way to reclaim that bandwidth without adding so much latency that the cure becomes worse than the disease. That's the tension we'll be resolving throughout this module. Our main objective is mastering data compression to reduce costs and improve performance without sacrificing too many compute resources. This is a classic architectural trade-off where we exchange CPU cycles for network bandwidth. If you're designing a system for a global audience, you've to decide where that processing happens. Compressing on the server saves bandwidth, but consumes CPU. Decompressing on the client saves bandwidth, but can drain a mobile device's battery. There are three primary pillars to this strategy: maximizing throughput, minimizing storage footprint, and managing the computational overhead. When you apply these correctly, you're essentially making your infrastructure more elastic. If you fail to balance these, you might find that while your payloads are small, your servers are pegged at 100% CPU just trying to zip the data. In a system engineering interview, you should emphasize that compression isn't a free lunch. It's a calculated decision based on your specific resource constraints, such as whether your system is more CPU-bound or network-bound. Let's look at the scaling crisis through a concrete example. Imagine a global e-commerce platform that just added rich product metadata to its search results. Because of this change, they face a 300% increase in cloud egress costs and a 200 millisecond spike in P99 latency. The mechanism at play is the increased size of the JSON response, which now requires multiple TCP segments to transmit. The consequence is that every single search now takes longer and costs more to deliver. This is where the clogged pipe analogy comes in. As the payloads get heavier, the network infrastructure struggles to keep up, leading to congestion and packet loss. The failure behavior here isn't just a slow side. It's a direct hit to the bottom line as the platform pays for more bandwidth than necessary. An interviewer will look for your ability to identify this correlation between payload size and operational cost, and how a 200 millisecond delay can lead to massive drops in user conversion rates. The bandwidth problem isn't just about speed. It's a central issue that creates a cascading impact across three critical areas: latency, storage, and infrastructure costs. First, in terms of latency, larger payloads mean more time spent on the wire. Second, for storage, uncompressed logs or backups can fill up disks 3 times faster than compressed ones. Third, infrastructure costs rise because you're built for every gigabyte that crosses region boundaries. The mechanism here is the physical limitation of the network and storage medium. If you're sending 500 KB of uncompressed data when it could be 50 KB, you're effectively using 10 times more resources than required. The consequence is a system that's brittle and expensive to scale. The failure behavior often shows up during peak traffic, like a major sale or a World Cup event, where the sheer volume of uncompressed data overwhelms the network interfaces. Interviewers want to see that you understand these interconnected ripples and don't just view compression as a localized optimization. When we talk about payload latency, the mechanism involves the relationship between packet size and round trips. Larger payloads often exceed the maximum transmission unit or MTU, which is typically 1500 bytes. This means a large response must be broken into many packets. The consequence is an increase in the time to first byte and the overall transfer time, especially in high latency network environments where every round trip adds significant delay. For instance, a user on a 3G network in a developing country will feel every extra kilobyte much more than someone on a fiber connection. The failure behavior here is a hanging connection, where the browser waits for all segments to arrive before it can even begin passing the data. In an interview, you can demonstrate depth by explaining how reducing a 100 KB payload to 20 KB might reduce the number of required TCP round trips from 10 down to just 2 or 3, which dramatically improves the perceived speed for the end user, regardless of their raw connection speed.
Storage and infrastructure costs are the silent killers of a cloud budget. When you've uncompressed data, it bloats your S3 buckets and database disks. The mechanism is simple. Every byte stored has a monthly cost, and every byte moved between regions adds an egress fee. The consequence of this bloat is higher cold storage fees and significantly increased cost for cross-region replication, which is vital for disaster recovery. Consider a scenario where you're replicating petabytes of logs for compliance. Without compression, you might be paying $10,000 a month for bandwidth that could be reduced to $1,000 with a simple ZStat or gzip implementation. The failure behavior manifests when your monthly cloud bill exceeds your revenue growth because your data footprint is expanding faster than your user base. Highlighting this fiscal impact in an interview shows that you're an engineer who thinks about the business reality, not just the technical code. Efficient storage is just as much about cost saving as it's about technical capacity. To tackle these issues, we'll look into the compression toolbox, which contains 4 main approaches: gzip, broadly, lossless mechanisms, and lossy mechanisms. Gzip is the long-standing universal standard for compatibility, while broadly is a newer alternative that often provides better compression ratios for text-based assets. The mechanism of lossless compression ensures that every single bit of the original data can be perfectly reconstructed, which is absolutely critical for things like code, JSON, or database records. On the flip side, lossy compression discards non-essential data to achieve massive savings, which is standard for media like images and video. The consequence of picking the wrong tool is either poor compression or data corruption. For example, using lossy compression on a configuration file would be a catastrophic failure because the file would become unreadable. In an interview, you should be ready to categorize these tools and explain that your choice depends entirely on the type of data and the required fidelity of the output. When comparing web standards, it's usually gzip versus broadly. Gzip is the universal standard. It's fast and supported by almost every browser and server since the 90s. Its mechanism relies on the deflate algorithm, which is great for general purpose use. However, broadly, developed by Google, offers superior compression ratios, especially for static text like HTML, CSS, and JavaScript. It uses a predefined dictionary of common web terms, which allows it to shrink files even further than gzip. The consequence of sticking only with gzip is that you're leaving about 15 to 20% of potential bandwidth savings on the table. The failure behavior for broadly, though, is its high CPU usage during the initial compression phase. If you try to compress large dynamic responses with broadly at its highest setting in real time, your server's latency might actually increase. In an interview, the winning move is to suggest using broadly for static assets that are compressed once and gzip for dynamic on-the-fly responses where speed is more important than the absolute smallest size. The distinction between lossless and lossy mechanisms is fundamental to data integrity. Lossless compression preserves every single bit, which is non-negotiable for JSON APIs, source code, and database backups. If you lose one character in a JSON string, the whole thing fails to pass. The mechanism here involves finding patterns and replacing them with shorter codes.
Lossy compression, however, is a different beast. It discards information that human senses won't miss, like subtle color variations in a JPEG or high frequencies in an MP3. The consequence of using lossy is a massive reduction in size, sometimes up to 90%. But the failure behavior is artifacting or blurriness if the compression is too aggressive. Imagine a product photo on an e-commerce site becoming so pixelated that customers can't see the detail. In an interview, make sure you emphasize that the choice isn't just about size, it's about the meaning of the data. You'd never use lossy for a bank transaction log, but you'd almost always use it for a user's profile picture. Identifying high ROI targets is where you actually save money. There are 5 primary areas where compression wins big: APIs, static assets, file downloads, media delivery, and storage. For APIs, compressing JSON responses can reduce payload size by 80%. For static assets like JS and CSS, it speeds up the initial page load. File downloads and media delivery are obvious candidates for reducing egress. Finally, database storage compression saves on disk I/O and cost. The mechanism is to target the data that moves the most or stays the longest. The consequence of ignoring these targets is lazy infrastructure that requires more hardware to do the same job. A failure behavior might be a mobile app that feels sluggish because it's downloading 2 MB of uncompressed JSON every time the user refreshes a feed. In an interview, if you're asked how to optimize a system, start by identifying these 5 targets. It shows you have a methodical approach to finding the biggest performance gains with the least amount of architectural change. When we focus on optimizing APIs and static assets, the goal is to reduce the time it takes for a user to see the first pixel. Compressing JSON responses and CSS or JavaScript files directly reduces initial page load times and significantly improves the mobile user experience. The mechanism here is usually middleware or edge-level compression. For example, if your API returns a huge list of products, gzip can turn that 500 KB text file into a 60 KB compressed stream. The consequence is a much faster time to interactive. The failure behavior to watch for is double compression, or trying to compress things that are already tiny, which can actually add overhead. If you're building a system for a high-traffic event, like a flash sale, ensuring your static assets are pre-compressed and served from a CDN is a basic requirement. In an interview, highlight that for static files, you should always pre-compress them during the build step, rather than doing it at runtime, which saves your server from doing redundant work over and over again. Media delivery and database storage require a different lens. For media, you're usually using optimized lossy compression through an image or video CDN. This maximizes throughput by serving the smallest possible file that still looks good on the user screen. For database storage, the mechanism is often built into the storage engine itself, like Snappy or Zstat in RocksDB or WireTiger. The consequence of these optimizations is a much smaller physical footprint, which means your backups are faster and your hardware lasts longer. A failure behavior here would be a database that runs out of disk space because it's storing raw, uncompressed logs that could have been reduced by 10x. Imagine a system that generates 1 TB of logs a day. Without compression, that's 30 TB a month. With it, it's 3 TB. That's a massive difference in cost and management effort. In an interview, explain that for media, the focus is on the user's visual perception, whereas for storage, the focus is on the physical disk throughput and the cost per gigabyte. It's important to remember that compression is not a silver bullet. It can actually hurt performance when applied to the wrong files or under high CPU pressure. There are 3 main danger zones here: already compressed files, tiny payloads, and high-throughput systems where CPU is the bottleneck. The mechanism of compression requires CPU cycles, and if those cycles are more expensive or more scarce than your bandwidth, you're making a bad trade. The consequence is increased latency, even though your files are smaller. A failure behavior is when a server's response time doubles because it's spending 50 ms zipping a file just to save 10 ms of network time. This is a common mistake in systems that are already CPU-bound. If your interviewer asks about the risks of compression, you should talk about this net negative effect. You need to monitor the CPU cost of the compression step itself. If the time saved on the wire is less than the time spent compressing, you're actually degrading the system's overall performance. The CPU overhead penalty is a real architectural constraint. Every algorithm has a computational cost. Compression requires cycles to scan for patterns and build dictionaries. High-throughput systems may experience CPU bottlenecks if they spend too much time zipping data. This is why we've levels of compression, usually 1 through 9. A level 9 gzip will get you a tiny file but will crush your CPU. Level 1 is much faster but gives a larger file. The consequence of a poor choice is a system that can't scale horizontally because the CPU is too busy with compression tasks. A failure behavior looks like a sudden spike in latency across all services during a traffic surge because the shared proxy is pegged at 100% CPU. In a system design interview, you should mention that you choose a middle-of-the-road compression level for dynamic content. You are looking for that Goldilocks zone where you get most of the bandwidth savings without creating a CPU-driven bottleneck that brings down the entire application. Another failure mode involves already compressed or tiny payloads. If you try to compress a JPEG, which is already a highly compressed format, or a tiny 1 KB JSON payload, you'll often find the resulting file is actually larger. This happens because the compression mechanism adds its own headers and metadata. The consequence is wasted CPU cycles and a larger file on the wire, which is the exact opposite of what we want. There are two scenarios where you should skip compression. First, for formats that are already compressed like zip, PNG or MP4, and second, for any payload smaller than about 1 KB or 2 KB. The failure behavior here is negative compression, where the overhead outweighs the savings. In an interview, a smart engineer will mention setting a min-length threshold in their nginx or server config. This ensures that the system doesn't even try to compress small files, saving those precious CPU cycles for the larger responses where the impact will actually be felt. Choosing the right strategy is about finding the optimal equilibrium between three factors: network bandwidth, CPU consumption, and storage savings. This is a constant cycle of balance. If bandwidth is expensive and CPU is cheap, you compress aggressively. If you're on an internal high-speed network where bandwidth is effectively infinite, you might skip compression entirely to save on CPU and reduce latency. The mechanism is a three-way trade-off. The consequence of a well-balanced system is that it's cost-effective and fast. A failure behavior is a one-size-fits-all approach, where the same compression is applied to every single microservice regardless of its specific constraints. For example, a high-frequency internal cache might skip compression to maximize speed, while a public-facing API for mobile users would use broadly for maximum savings. When you're in an interview, don't just pick an algorithm. Describe how you'd measure the bottleneck in that specific architecture and then select the compression strategy that alleviates that specific pressure point. When evaluating the total cost of ownership, you've got to ask a fundamental question. Is the storage or bandwidth saved worth the latency added during the compression step? This is the core signal an interviewer looks for. You're weighing the fiscal savings of smaller cloud bills against the performance cost of increased compute and latency. There are 3 points to consider here: the cost of egress, the cost of CPU instances, and the target latency SLA. If your egress is costing you $50,000, but adding compression only adds $5,000 in CPU cost and stays within your 200 MSA latency target, it's a massive win. However, if your users are hypersensitive to every millisecond and your bandwidth is cheap, the trade-off might flip. The failure behavior is an optimization that saves money but loses users because the site feels slow. A strong interview answer doesn't just say compression is good. It explains the formula for deciding when the savings justify the overhead, showing that you understand the business impact of your engineering choices. Let's look at real technologies and implementation. Modern systems typically use three main tools for this: Nginx for edge-level compression, standard HTTP-level compression for APIs, and the high-performance Z-standard or ZSTAD. Nginx is the workhorse here, often handling gzip or broadly at the reverse proxy level, before the request even hits your application code. Z-standard is a newer entrant that's becoming the gold standard for high-performance systems. The mechanism is to offload this work to dedicated layers, so your application logic doesn't have to worry about it. The consequence is a cleaner architecture with centralized control over compression settings. A failure behavior would be every microservice implementing its own compression logic, leading to inconsistent configurations and a maintenance nightmare. In an interview, discussing these tools shows you're familiar with real-world stacks. You should be able to explain how these tools fit into a request lifecycle, from the server-side configuration to the client-side headers that negotiate which algorithm to use for that specific connection. Implementation often starts with NGINX and the HTTP protocol's native support. By enabling the gzip on directive in NGINX, you automate the process of compressing responses. The mechanism relies on content encoding headers. There are 3 steps in this negotiation. The client sends an accept encoding header listing what it supports. The server chooses the best one and compresses the data, and then it sends back a content encoding header to tell the client how to decompress it. The consequence is a seamless automated reduction in payload size. A common failure behavior is forgetting to set the very accept encoding header, which can cause CDNs to serve compressed content to clients that don't support it, resulting in garbage text on the screen. In an interview, mentioning these headers and the NGINX configuration shows you understand the plumbing of the web. It's not only about the algorithm, it's about the protocol handshake that makes it work reliably across millions of different browser and server combinations. Z-Standard or Z-Stead is the modern gold standard. Developed by engineers at Facebook, it was designed to bridge the gap between fast, low-ratio compression and slow, high-ratio compression. The mechanism is unique because it offers a huge range of compression levels with incredible real-time speed, outperforming traditional gzip in almost every metric. The consequence of switching to Z-Standard for internal data transfer or log storage is often a significant drop in both CPU usage and storage size simultaneously. A failure behavior for Z-Standard used to be browser support, but that's rapidly changing. However, it's still most commonly used for backend-to-backend communication or massive data lakes. If you're designing a high-performance logging system or a large-scale data pipeline, Z-Standard is the tool you should recommend in an interview. It shows you're current with modern standards and understand that the industry has moved beyond the simple gzip-only world. It's the go-to choice when you need the best possible balance of speed and density for massive data sets. So, we've broken down how compression is a massive lever for cutting egress costs and slashing latency. We saw that the bandwidth problem isn't just about speed, it's about the literal price of moving data. You've now got 4 primary strategies in your toolbox, using gzip or broadly for web standards, and choosing between lossless or lossy approaches, depending on whether you're handling JSON or media. In an interview, the signal you want to send is that you truly understand the trade-offs. You're weighing the CPU cost against the transfer savings to justify the overhead. Well, there are 3 big pitfalls to avoid: recompressing already zipped files, hitting tiny payloads, or choosing a CPU-heavy algorithm for time-sensitive traffic. Think of that e-commerce platform we discussed. Metadata growth shouldn't double your cloud bill if you're selecting the right algorithm for the job. Ultimately, you've got to find the point where the reduction in bytes justifies the extra processing. That's how you scale systems without letting the infrastructure bill explode. That wraps up our dive into compression. When you're in a system design interview, remember that compression isn't a free lunch. You've got to weigh 3 main factors: network bandwidth, CPU consumption, and storage savings. So, if you're deploying Z-Standard on Nginx to save on egress, you have to ensure that the extra processing doesn't bottleneck your latency, especially on CPU-bound nodes. Avoid the common mistake of double compressing assets, like JPEGs or encrypted streams, where you'll just waste cycles for zero gain. It's all about proving you can find that equilibrium where the transfer speedup actually justifies the computation cost. Now here's a question for the comments. If you have a system with unlimited bandwidth but very high CPU costs, is there any scenario where you'd still choose to compress your data? Let me know what you think. Happy engineering!
When your dataset jumps from thousands to hundreds of millions, a simple query can easily become a system-killing bottleneck. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 35 of System Engineering series, and today we will explore pagination strategies in a way that helps you prepare for system engineering interviews on this topic. Understanding the 3 main patterns, offset, cursor, and keyset, is vital because interviewers use them to gauge your depth in database internals. Now we look at how to stop queries from breaking your system, so you can justify high-scale design choices with total confidence. This lesson opens with the scaling crisis that hits when a product catalog jumps from a few thousand to hundreds of millions of records. We'll look at how returning massive datasets actually breaks a system, dragging down compute and triggering memory exhaustion. So we'll explore the solution through three architectural pillars: offset, cursor, and keyset pagination. You'll understand why it's easy for traditional offsets to become a bottleneck at scale and how direct pointers allow the database to jump straight to the records you need. Now things get interesting when we add various sorting criteria like price, rating, or popularity. We'll examine the indexing trade-offs required to keep these queries fast and why tiebreakers are essential for stable ordering. We are going deep into the database engine, looking at query plans and composite indexes to ensure our logic holds up under production pressure. We'll wrap up by looking at the API design decisions like page size limits and response structures used by real-world technologies. By the end, you'll be ready to defend your choice of pagination strategy in any high-scale system design scenario. Imagine you're the lead engineer for a massive e-commerce platform during a global sale like Black Friday. Your product catalog has ballooned to over 50 million items and users are performing complex searches, expecting to scroll through results indefinitely. In this situation, the database isn't just a static storage bucket, it's a living system under extreme load. If a single user request triggers a query that tries to load a million records into the application's memory, the consequences are immediate. The app server's garbage collector will go into overdrive, CPU usage will spike to 100%, and eventually the process will crash with an out-of-memory error. Meanwhile, the database is struggling to scan massive indexes, blocking other critical transactions. This isn't just about a slow UI, it's about a total system failure that prevents anyone from making a purchase. Understanding how to slice this data safely is what separates a junior developer from a senior system architect who can maintain stability details. The transition from 1000 records to 100 million records isn't just a change in scale, it's a fundamental change in physics for your database. When you're small, almost any query is fast because the entire dataset might even fit in the database's buffer cache. However, as your product catalog grows, you hit a scaling crisis where users still expect search results to appear in under 200 milliseconds, but the system starts groaning under the weight. Imagine a user searching for a popular category and trying to view the 10,000th page of results. If your system isn't optimized, that single click can trigger a massive disk I/O operation that slows down the database for every other user. The consequence of ignoring this growth is a platform that becomes progressively slower until it's unusable. This is where we see the breakdown of simple sorting and filtering logic, forcing us to rethink how we navigate the dataset to maintain the performance users demand. Returning massive datasets isn't just a performance bottleneck, it's actively destructive to your infrastructure. The real problem is a multi-layered system overload. First, it overwhelms the database compute because the engine has to spend precious CPU cycles gathering and sorting millions of rows. Second, it consumes limited network bandwidth. Sending a 50 megabyte JSON response for a single request is an architectural nightmare that clogs the pipes for everyone else. Third, and perhaps most critically, it leads to application memory exhaustion or OOM errors. Think about a Node.js or Python worker trying to deserialize a million rows into objects. The memory footprint explodes, the operating system kills the process, and you end up with a service restart loop. This failure behavior creates a cascading effect, where one slow query takes down an entire pod, shifting load to other pods and eventually causing a total site outage. Preventing this requires us to stop thinking about data as one big block and start treating it as a controlled stream. The big idea we need to embrace is the infinite slice. In reality, users rarely need to see the entire dataset at once. Whether they are looking at social media posts or bank statements, they are usually only looking for the next 10 or 20 items to make their next decision. The core of engineering efficiency is realizing that by only fetching exactly what is needed for the current view, we can provide the illusion of a massive searchable dataset without the cost of actually loading it. One simple way to picture this is a flashlight in a dark warehouse. You don't need to turn on every light in the building to find one box. You just need enough light to see the path immediately in front of you. By delivering data in these small manageable slices, we preserve memory, reduce latency, and keep the database responsive. This shift in mindset allows us to build systems that feel infinite to the user but remain lean and predictable on the backend, regardless of how many billions of records are stored. To handle millions of records effectively, we utilize three primary architectural patterns: offset pagination, cursor pagination, and keyset pagination. In a system design interview, you should be ready to compare these three approaches and explain when to use each. Offset pagination is the most common because it's built into almost every SQL database, but it has significant performance flaws at scale. Cursor pagination is the gold standard for infinite scrolls, like you see on social media, because it provides constant time performance by pointing directly to the next record. Keyset pagination is a specialized version of this that uses actual sort values like a timestamp to filter the data. Each pattern has a different mechanism for how the database identifies the next set of rows. The consequence of picking the wrong one could mean your system works fine for the first week but crashes as soon as your table hits its first million rows. We'll spend the next few slides digging into the mechanics and trade-offs of each specific pillar. Offset pagination is the entry-level approach most of us start with, typically using the limit and offset keywords in SQL. The mechanism is straightforward. The database skips the first n rows and returns the next m records. While it's easy to implement, performance degrades significantly as n increases because the database engine still has to scan and discard every single skipped row to find the starting point. Imagine you're asking for page 1000 with a page size of 50. The database has to read 50,000 rows just to give you the last 50. This leads to high latency for deep pages, which is a major bottleneck for large datasets. A common failure mode occurs when a user navigates to a very high page number, triggering a query that times out because the scan takes too long. In an interview, make sure to mention that while offset pagination allows for random access, like jumping straight to page 10, the lack of constant time access makes it dangerous for millions of records. Cursor pagination solves the deep page performance issue by using a point and move mechanism. Instead of telling the database how many rows to skip, the client sends a cursor, which is usually an encoded pointer or ID representing the last record they saw. The next query asks the database for records that come strictly after this pointer. This allows the database to leverage an index to jump directly to the correct spot in the table, rather than scanning from the beginning. For example, if your cursor is a unique timestamp, the database just finds that spot in the index and reads the next 20 rows. The consequence is constant time performance, meaning page 100 is just as fast as page 1. However, the trade-off is that you lose the ability to jump to a specific page number, as the system only knows how to find the next set of data. This is why it's the preferred choice for infinite scrolling feeds, where users move sequentially through the data. Keyset pagination is a variation of the cursor approach that involves filtering by actual sort values, such as a created at timestamp or a numeric ID. There are two main reasons this is powerful. It's deterministic and it's stateless. Unlike traditional cursors, which might be opaque strings, keyset pagination uses the data itself to define the boundary. If you're sorting by price, your query might look for items where the price is less than $20 and the ID is greater than the last one seen. This ensures the query leverages existing indexes effectively without the database needing to maintain any special session state. A concrete scenario would be a log viewer where you're scrolling through millions of entries. By using the timestamp as a filter, the database quickly narrows down the search range. The failure behavior here usually stems from improper indexing. If the sort column isn't indexed, the performance benefits disappear. When implemented correctly, it provides a stable and highly performant way to walk through massive datasets while keeping the query logic simple. Pagination doesn't happen in a vacuum. It's almost always tied to how the data is sorted. The sorting challenge is a major hurdle because supporting multiple sort fields like price, rating, date, and popularity fundamentally changes how you design your retrieval logic. In an interview, you should consider 4 main points when discussing this: index coverage, sort stability, cursor complexity, and memory usage. If you allow users to sort by any column, you can't just use a single cursor based on an ID. You have to track the last seen value for that specific sort field. For example, if a user sorts by highest rating, the cursor must include the rating of the last item. This adds a layer of complexity to your API contract. If your database isn't prepared for these dynamic sorts with proper indexes, it will fall back to a slow file sort, which can cause massive latency spikes and potentially crash the query under high load. We have to balance user flexibility with system predictability. When we talk about dynamic sort fields like price, rating, date, and popularity, each one requires a unique pagination strategy. The mechanism involves tracking different types of last seen values. For a price sort, your cursor might be a decimal. For a date sort, it's a timestamp. This means your backend needs to be generic enough to handle different data types for the cursor, while remaining type safe. Consider a scenario where a user switches from sorting by newest to price. The entire pagination state has to be reset because the order of the millions of records has completely shifted. If you don't account for this, the user might see duplicate items or miss records entirely during the transition. The consequence of poor design here is an inconsistent UI where data feels broken. To prevent this, architects often limit the number of sortable fields to those that can be efficiently indexed, ensuring that every possible sort order has a dedicated path for fast retrieval without overwhelming the database engine with unoptimized queries. To avoid the dreaded file sort operation where the database sorts data in memory or on disk because it can't use an index, every paginated sort field needs a corresponding indexing strategy. This often leads to a classic trade-off between read speed and write overhead. While more indexes make your paginated reads incredibly fast, they slow down every insert and update because the database has to maintain those extra data structures. In a high-write system, like a social media platform, adding too many indexes can actually become the bottleneck. Imagine an index for every possible combination of filters and sort orders. The storage costs and write latency would skyrocket. The failure behavior here is a slow crawl during data ingestion. To find the right balance, you have to analyze which sort orders are most frequently used. In an interview, explaining this trade-off shows you understand that optimization isn't free and that every design choice has a measurable impact on the system's overall health and throughput. True engineering involves looking past the SQL syntax to understand how the database engine actually fetches your pages. This is what we call database thinking. When you execute a paginated query, the engine has to decide which index to use, how many pages to read from disk, and how to join that data with other tables. If you're using a cursor-based approach, the engine is essentially performing a range scan on an index, which is very efficient. However, if your query includes complex joins or subqueries, the pagination logic might not be applied until after the expensive work is done. A concrete example is a query that joins 5 tables before applying a limit clause. The database might join 1,000,000 rows only to discard 900,000 of them. The consequence is wasted CPU and I/O. By understanding these internal mechanics, you can write queries that filter early and join late, ensuring the database does the absolute minimum amount of work necessary to return the requested page. Query execution plans are your best friend when debugging pagination performance. They reveal whether you're hitting an index or a slow full table scan. One of the most effective tools in your arsenal is the composite index, which combines the sort field and a unique ID. For example, an index on price and ID allows the database to find the exact starting point for a price sorted page and then use the ID as a tiebreaker. This is crucial for ensuring stable, fast pagination. Without this, the database might find the right price but still have to scan many rows with that same price to find the specific record where the last page ended. The practical impact is a query that stays fast even if there are thousands of items with the same price. In an interview, mentioning composite indexes for pagination signals that you understand how to design for stable ordering and index-only scans, which are key for handling millions of records without hitting the disk more than necessary. Stable ordering is a hidden trap in pagination design. If you're sorting by a non-unique field, like a product's price or a user's rating, you run into the problem of non-deterministic results. Imagine two items both cost exactly $49. Without a secondary sort key, the database might return them in a different order each time the query runs. This causes a frustrating user experience where a record appears on page 1 and then shows up again on page 2, or worse, disappears entirely because it shifted across the page boundary. To fix this, you must always include a unique tiebreaker, such as a primary key ID, in your order by clause. This ensures every record has a fixed, predictable position. In a high concurrency environment where records are being inserted or deleted constantly, failing to enforce this stability leads to data gaps that are incredibly hard for the client to handle, effectively breaking the reliability of your API's navigation and causing user confusion. Beyond the algorithm itself, architects must define the contract between the database and the user through critical engineering decisions. This involves thinking about how the API layer translates database results into something the client can use. You have to decide on the maximum page size to prevent accidental overfetching and how to handle empty results or the end of a dataset. These decisions ripple from the core database out to the front-end components. For example, if you decide to use cursor-based pagination, your API must provide the next cursor in every response. This changes how the client-side code is written, as it can no longer just guess the URL for page 5. The consequence of a poorly defined contract is a brittle system where changes in the backend break the front end. In an interview, focusing on the interface design shows that you're thinking about the whole system, not just the query, and that you value clear communication between different parts of the architecture. Designing the API response is vital for client-side ergonomics and system safety. You should consider three main components in your response: the data list, the page info, and the total count. The page info should include fields like has next page and the end cursor, so the client knows exactly how to request the next batch. Furthermore, defining strict page size limits, such as a maximum of 100 records, is a critical safety mechanism. Without this limit, a malicious or poorly written client could request 1,000,000 rows in a single call, triggering the system overload we discussed earlier. A concrete scenario is a mobile app that needs to know if it should show a load more button. By providing a clean has next page boolean, the app can make that decision without needing to know the total number of records, which is often expensive to calculate. This design ensures the client stays in sync with the server while keeping the individual requests small, fast, and predictable for the infrastructure. Selecting the right pagination strategy depends on your dataset size and expected access patterns. There are two main use cases to consider: random access and sequential scrolling. If your users need to jump to specific pages, like in a search result for a legal database, offset pagination is often necessary despite its flaws. In this case, you might mitigate the performance hit by limiting how deep users can go. However, for sequential scrolling, like a social media feed or a log stream, cursor-based pagination is almost always the better choice because of its constant time performance and stability against data changes. The trade-off is clear. You exchange the flexibility of jumping to any page for the reliability of high-speed, scalable data delivery. In an interview, being able to articulate this choice based on user behavior shows a high level of senior level thinking. You're not just picking a favorite tech, you're matching the technical solution to the specific business constraints and user needs of the platform. Different technologies handle these pagination strategies in unique ways. For instance, relational databases like PostgreSQL and MySQL are the classic environment for limit and offset, while also supporting the composite indexes needed for key set pagination. On the other hand, search engines like Elasticsearch use a search after parameter, which is a built-in implementation of cursor pagination, designed to handle billions of documents across a distributed cluster. Frameworks like GraphQL have even standardized this with the relay cursor connection specification, providing a consistent way to handle edges and node metadata. If you're working with NoSQL databases like DynamoDB, you'll find that they often force you into cursor-based patterns using exclusive start key, because they are built from the ground up for massive scale, where offset is simply not an option. Understanding how these tools implement these patterns allows you to hit the ground running in any production environment and choose the right stack for the specific scale you're expecting to handle. To wrap up, let's look at 5 key questions that often come up in system engineering interviews. First, would you use offset or cursor pagination for an Instagram-style feed where new posts are constantly being added? Second, how would you approach paginating results in a distributed system like Elasticsearch? Third, should every sortable field have its own index, and what are the trade-offs there? Fourth, how do you prevent duplicate records from appearing as a user scrolls while new data is being arriving? Finally, how would you design a pagination system that needs to handle billions of rows where even a simple count query takes several seconds? These questions are designed to test your ability to apply the concepts we've covered to real-world high-pressure scenarios. There isn't always a single right answer, but a strong response will weigh the pros and cons of memory usage, database load, and user experience to justify a specific architectural choice for the given constraints. So, we've tackled the massive challenge of scaling search results from a few thousand items to hundreds of millions without crashing your system. The big takeaway is that returning massive data sets is a recipe for OOM errors and network bottlenecks. We broke down 3 main architectural patterns: offset, cursor, and keyset pagination. While offset is the easiest to implement, it's often a trap at scale because the database has to scan every skipped row, leading to major performance degradation. That's why we focused on cursor and keyset pagination as the professional alternatives. These methods allow the database to jump straight to the data using encoded pointers or sort values. In an interview, you'll need to justify your choice based on these exact trade-offs, like choosing cursors for a high concurrency social feed. Remember, great pagination isn't just a UI feature, it's built on intelligent database design. Well, that wraps up our session on handling massive data sets. When you're in a high-stakes interview, remember that you aren't just choosing an algorithm, you're managing database load. If you suggest cursor pagination for a feed like Instagram, explain how it avoids the skip and duplicate issues that happen when new items arrive during a scroll. We've covered 3 primary approaches: offset, cursor, and keyset pagination, showing you understand why a query plan stalls on page 500 or how a composite index prevents a full table scan is what separates a senior engineer from the rest, right? In the next episode, we'll talk about, does every business problem really need an instant answer? And look at Kabir Anand, the system engineering series, and pagination strategies. How would you design a system to support deep linking to a specific result page if you're using strictly cursor-based pagination? Drop your answer in the comments. Keep building. Is speed actually creating business value, or are you just layering on unneeded engineering complexity? Welcome to Systemic Stack. My name is Kabir Anand. This is episode 36 of System Engineering series. And today we will explore batch versus real-time processing in a way that helps you prepare for system engineering interviews on this topic. Interviewers test if you can balance performance with business reality. We'll examine 4 specific dimensions: latency, throughput, freshness, and cost. So you're ready to justify choosing between these 2 processing models. This lesson opens with a look at the tension between needing answers right now versus being able to wait, using the contrast between fraud detection and monthly statements to frame the problem. We'll dive into the 2 core processing paradigms, batch and real-time, to see how they handle data volume and velocity differently. You will get a solid handle on the 4 key vectors used to evaluate these systems: latency, data freshness, throughput, and operational cost, which are exactly the points an interviewer wants you to hit when justifying a design choice. From there, we move into the actual architectural patterns, comparing asynchronous streaming and queues against the more orchestrated world of jobs and pipelines. We'll also examine the tuning levers like batch size and frequency that dictate your system's efficiency and responsiveness. So we can keep it grounded, we'll map these models to the industry standard stack, including tools like Kafka, Flink, Spark, and Airflow. Finally, we'll address the risks of over-engineering, focusing on why the fastest technology isn't always the right solution. By the end, you'll understand how to select a processing model based on actual business needs. Let's set the stage with a situation you'll likely face in the real world or a design loop. Imagine you're building the data backend for a massive global retailer during a peak event like Black Friday. You're dealing with millions of transactions per minute across thousands of stores. On one hand, you have a security team that needs to block stolen credit cards in milliseconds to prevent massive losses. On the other hand, you have a logistics team that needs an inventory restock report by 6 a.m. the next day. If you try to process that massive inventory report using the same sub-second logic as the fraud detection, you're going to burn through your infrastructure budget and likely crash your streaming cluster. This scale creates a natural tension between what needs to be fast and what needs to be thorough. Understanding these constraints is how you avoid over-engineering systems that are too expensive to maintain. The immediacy versus latency paradox is all about recognizing that value isn't always tied to speed. Think about a global bank. When a suspicious transaction happens in a different country, the fraud detection system has to trigger a block almost instantly. If it takes even 5 minutes to process, the money's already gone and the system has failed. However, that same bank's customers are perfectly happy receiving their monthly statements every 30 days. If the bank spent the engineering effort to generate those statements in real time after every single coffee purchase, they'd be wasting specialized resources for zero extra value to the customer. In an interview, being able to distinguish between these two scenarios shows you're thinking about the business impact. You're acknowledging that some users need results now, while other critical processes can safely wait hours. The paradox is that the slower system is often the more robust and cost-effective choice for the specific problem it solves. When we talk about how data actually moves through a system, we're generally looking at two distinct execution styles. First, there's batch processing. In this paradigm, you're collecting data over a period of time and processing it in one large, efficient chunk. It's like doing laundry. You don't run the machine for a single pair of socks, you wait for a full load. Then we have real-time processing, where data is handled almost the moment it's generated. This is more like a sink with a continuous drain. As soon as the water hits, it's gone. In an architectural discussion, you'll need to explain how these styles handle failure differently. A batch job that fails can usually be restarted from the beginning of the block. A real-time stream that fails might lose data or require complex checkpointing to resume. Each has its place, and choosing between them requires you to weigh the complexity of immediate execution against the delay of scheduled intervals. The batch processing model is the workhorse of the data world, focusing on high-volume data handled at scheduled intervals. Its main strength is efficiency. By processing millions of records at once, you can optimize disk I/O and use heavy-duty compression that wouldn't be possible in a streaming setup. Take a company's payroll system as a concrete example. You don't need to calculate a worker's taxes every time they clock in for an hour. Instead, the system waits until the end of the pay period and processes everyone at once. This ensures that the massive data sets are handled accurately without the primary concern being how many seconds it takes. If a batch job fails halfway through, the consequence is usually just a delayed report, which is manageable. It's the ideal choice for nightly analytics refreshes or any situation where throughput and cost efficiency are more important than how fresh the data is in the moment. Real-time processing operates on individual events or tiny micro batches the very moment they are generated. You'll see this used for low latency needs where every millisecond counts, such as live monitoring dashboards for a server farm or high-speed ad bidding systems. Imagine you're running a notification engine for a ride-sharing app. When a driver arrives, the passenger needs to know right then, not 10 minutes later in a batch update. The consequence of a lag here is a bad user experience or a lost sale. However, because you're processing data continuously, the system is always on, which puts a constant load on your CPU and memory. This model's failure behavior is also trickier. If your real-time consumer falls behind, the data starts to back up, creating a bottleneck that can lead to system instability. It's a powerful tool, but it requires much more sophisticated monitoring and infrastructure to keep it running smoothly 24/7. Deciding between batch and real-time isn't just a coin flip or a matter of preference. As an engineer, you've got to evaluate 4 specific dimensions to make a sound architectural choice. First, look at latency expectations. How long can the user wait? Second, consider throughput requirements or the total volume of data you're moving. Third is data freshness, which is how current that info needs to be to remain useful. Finally, you have to factor in the operational cost of the infrastructure. For instance, a real-time fraud system needs high availability clusters that run 24/7, whereas a batch reporting job might only need a fleet of servers for 1 hour every night. In an interview, explicitly walking through these four vectors shows you're balancing technical performance with fiscal responsibility. If you pick real time when the business only needs data freshness of 24 hours, you're essentially choosing a more expensive, fragile path for no reason. Let's dive deeper into that first factor, latency and data freshness. It's helpful to think of latency as the delay between when data is input and when the output is ready. Data freshness, on the other hand, describes how stale that information is when the user finally sees it. For a stock trading platform, latency needs to be near zero because a price that's even 3 seconds old is useless for a high-frequency trader. Real-time processing minimizes both latency and staleness, but it comes with a significantly higher resource cost. If you're designing a system for daily sales totals, a latency of 12 hours is perfectly fine because the freshness only matters at the start of the next business day. When you're explaining this, highlight that reducing latency usually means increasing complexity. If you can tolerate a bit of lag, you can often build a much more reliable and simpler system using batching. Now let's talk about throughput and operational cost. Throughput is essentially the total volume of data your system can crunch in a specific window of time. Generally speaking, batch systems have much higher total throughput efficiency because they can use optimizations like bulk reads and sequential disk access. Real-time systems, while fast, often have lower overall throughput efficiency because they're handling data bit by bit, which creates more overhead for each record. This leads directly to a higher operational cost. To maintain a real-time system, you're paying for 24/7 high availability infrastructure, whereas bad jobs can often run on cheaper spot instance hardware that only exists while the job is active. Imagine a log processing system for a website. Running a continuous stream might cost 5 times more than just processing those logs once an hour in a batch. If the business doesn't need to see those logs in real time, that extra cost is a major architectural red flag. Building these systems requires choosing the right structural patterns to facilitate the desired processing speed. There are 4 main patterns we see in the industry: event streaming, message queues, scheduled jobs, and data pipelines. Event streaming and message queues are typically the heart of your real-time architectures, acting as the nervous system that carries signals instantly. On the flip side, scheduled jobs and data pipelines are the foundation of batch processing, where you orchestrate heavy-duty movements of data at specific times. For example, you might use a message queue to handle incoming user signups, so they get a welcome email immediately, but then use a scheduled data pipeline to move those signup records into a data warehouse for the marketing team to analyze once a week. Understanding how these 4 patterns interact is key to building a hybrid system that's both responsive and efficient without becoming a maintenance nightmare. When we look at asynchronous patterns like event streaming and message queues, we are talking about the backbone of modern real-time systems. Event streaming, like a continuous log of user clicks, allows you to process data as a never-ending flow. Message queues, however, are great for decoupling your producers from your consumers. This means if your database is momentarily slow, the queue can hold on to the messages so you don't lose any data. It's like a buffer that smooths out spikes in traffic. A classic scenario is a food delivery app. When you place an order, it goes into a queue. The restaurant's tablet picks it up when it's ready, and the payment service processes the charge independently. This decoupling ensures that a failure in the payment service doesn't stop the restaurant from seeing the order. It's high-velocity, event-driven data movement that keeps the system resilient even when individual components are struggling. In contrast to streaming, orchestrated patterns like scheduled jobs and data pipelines are the standard for high-volume batch systems. Scheduled jobs are usually cron-based, meaning they wake up at a specific time, like 2 a.m., to perform a task. Data pipelines, or ETL flows, are more complex sequences that move, transform, and clean data in massive predictable waves. Think about a global retail chain that needs to reconcile its books. Every night, a pipeline pulls data from thousands of point-of-sale systems, converts the currencies, and loads it into a central database. This approach provides a reliable, repeatable way to handle scale that would be incredibly difficult to manage in a real-time stream. Because the execution is orchestrated, you have much better visibility into where a process failed and can easily rerun a specific stage of the pipeline. It's all about consistency and the ability to handle massive scale without needing constant sub-second attention. As you're designing these systems, you'll find there are three primary levers you need to tune to get the behavior you want. These are the batch size, the processing frequency, and the execution trigger, whether it's event-driven or scheduled. Tuning these levers is where the real engineering happens. For example, if you're getting complaints about slow updates in a batch system, your first instinct might be to switch to real-time. But a more efficient move might be to simply increase the processing frequency from once a day to once an hour, or to decrease the batch size so data moves through the pipe faster. In an interview, discussing how you tweak these three levers shows you understand the nuances of system performance. You're not just picking a tool, you're optimizing the configuration to find the most cost-effective way to meet the service level agreement without jumping straight to the most complex technology available. Finding the sweet spot between batch size and frequency is a classic optimization problem. If you go with larger batches, you're going to see much better throughput efficiency because you're amortizing the overhead of starting the job over more records. However, the consequence is higher latency. The first record in that batch has to wait for the last one to arrive before anything happens. On the other side, increasing the frequency, say running a job every minute instead of every hour, reduces that latency, but it significantly increases the overhead on your processing engine. Every time a job starts, it has to connect to the database and initialize resources. If your job takes 30 seconds to start and you run it every 60 seconds, you're spending half your time just on overhead. It's a delicate balance. A real-world example is an image processing service. Batching images together might save money on GPU costs, but if users are waiting for their profile picture to update, you have to increase that frequency. The choice between event-driven and scheduled execution really comes down to how reactive your business needs to be. Event-driven systems react immediately to individual state changes. Think of a smoke detector. It doesn't check for smoke every 10 minutes. It reacts the second it senses a change. This is essential for critical alerts. Scheduled execution, however, waits for a specific time window or a data volume threshold. It's more like a trash pickup service that comes every Tuesday morning, regardless of how much is in the bin. The trade-off here is predictability versus responsiveness. Scheduled systems are much easier to monitor and resource plan because you know exactly when the load is coming. Event-driven systems can be unpredictable, often requiring complex auto-scaling to handle sudden bursts of activity. When deciding, ask yourself, does the business gain anything from reacting to this specific event in real time, or can it wait for the next scheduled window? Once you've decided on your processing model, it's time to choose the tools. The modern data landscape is vast, but we can generally categorize the most common technologies into two ecosystems, the streaming stack and the batch stack. In the real-time or streaming world, you're looking at technologies designed for continuous flow and low latency state management. In the batch and hybrid world, you're looking at tools built for heavy-duty distributed processing and complex workflow orchestration. Knowing which tool belongs in which bucket is vital for any system design interview. You don't want to suggest a batch tool like Airflow for a sub-second messaging problem, and you don't want to use a streaming tool like Flink for a once-a-month financial audit. Let's look at the heavy hitters in each category so you can accurately map the right technology to the right business problem and avoid the common pitfall of tool mismatch. If you're building in the real-time stack, the two names you'll hear most are Apache Kafka and Apache Flink. Think of Kafka as the distributed log and message hub. It's incredibly durable and acts as the central nervous system, holding on to streams of events so other services can read them. Apache Flink then provides the brains, offering powerful stateful stream processing. Together, they are built for sub-second, high reliability event handling. For instance, a ride-sharing company might use Kafka to ingest GPS coordinates from thousands of drivers and use Flink to calculate real-time search pricing based on that data. The consequence of failure here is that your pricing might become inaccurate. So these tools have built-in features like exact once processing to ensure data integrity. They are sophisticated and powerful, but they require a high level of expertise to manage, which is a major point to mention when discussing operational overhead. On the batch and hybrid side, the ecosystem is led by four major players: Apache Spark, Hadoop, Apache Airflow, and AWS Glue. Spark and Hadoop are the workhorses for massive distributed processing, allowing you to run complex queries over petabytes of data by breaking the work across hundreds of servers. Apache Airflow is the gold standard for orchestrating those jobs, letting you schedule complex workflows with clear dependencies. AWS Glue is a managed option that simplifies the ETL process by handling the underlying infrastructure for you. These tools are the backbone of the modern data warehouse. For example, a marketing team might use Airflow to trigger a Spark job every night that joins user behavior data with sales records to generate a recommendation report. It's not about speed here, it's about the sheer volume and reliability of the data being moved. These tools excel at handling the heavy lifting that streaming tools often struggle with. A huge mistake I see in interviews is over-engineering. Systems often break or become liabilities when engineers build expensive, complex real-time systems for workloads that could easily run as a batch job. This usually happens because real-time sounds more impressive, but the reality is that it leads to massive maintenance cost and a very fragile infrastructure. Imagine a startup building a real-time Kafka-based dashboard for the internal HR team to see employee birthdays. It's a total waste of resources. If that Kafka cluster goes down, someone has to get paid at 3 a.m. for something that could have been a simple daily email. This overcomplexity provides zero added business value and actually increases the risk of system-wide failures. In an interview, your ability to push back and say we don't need real time for this is a huge green flag. It shows you're focused on the goal, not just the technology. The ultimate engineering wisdom here is to aim for right-sized processing. Your goal should always be to process data as quickly as the business actually needs it, not as quickly as the technology allows. Don't let the cool factor of streaming distract you from the reliability and simplicity of batch processing. In many cases, a well-tuned batch system is more resilient, easier to debug, and significantly cheaper to run. A great example is a recommendation engine. While you might want to update a user's recommendations based on their last click, often a batch update once an hour is more than enough to keep them engaged. By choosing the simpler path, you're freeing up your engineering team to focus on features that actually drive growth. In your next interview, justify your choice by showing how it aligns with the business's tolerance for delay versus its budget for complexity and uptime. To wrap things up, I want to leave you with 5 key questions that often pop up in system design interviews. First, should invoices be generated in real time? Think about the overhead versus the benefit. Second, should fraud detection always be real time? Consider the consequence of a 5-minute delay. Third, when is streaming actually a bad choice? Look at the maintenance and cost vectors. Fourth, would you batch recommendation generation? Think about how much a user's interests change in a single session. And finally, how would you decide between using Kafka and just setting up a few scheduled jobs? These questions don't have a single correct answer, but your ability to weigh the trade-offs we've discussed today will define the strength of your response. Being able to explain the why behind your choice is what separates a junior developer from a senior system architect. We've broken down the tension between engineering complexity and actual business value. At the core, there are 2 main processing models, batch and real-time. In a high-level design discussion, your value comes from weighing 4 specific factors: latency, throughput, freshness, and operational cost. Think about it. Fraud detection needs immediate real-time action, but generating a monthly invoice is a classic batch job that can wait. I mean, building an expensive, high-availability streaming system with Kafka for a report that people only read once a week is a huge architectural red flag. So you've got to balance tools like Airflow or Spark against event-driven pipelines based on what the user truly needs. Ultimately, the best engineers process data as quickly as the business demands, not just as fast as the hardware allows. That's how you avoid over-engineering. So, we've seen how to balance speed and complexity. In an interview, don't just reach for the shiniest tool. Explain why a simpler batch job might be better for the bottom line than a high-maintenance streaming pipeline. You've essentially got 2 main models to choose from, and deciding between patterns like event streaming or scheduled jobs depends entirely on the business requirement. Next, we'll move into throughput optimization. Now, let's get to the question for today. If you were designing a system system to calculate a user's total lifetime loyalty points, would you update that in real time on every purchase or run it as a nightly batch? Let me know your reasoning in the comments. Catch you later. Throwing more hardware at a performance problem is an expensive gamble that rarely pays off as expected. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 37 of System Engineering series. And today, we will explore throughput optimization in a way that helps you prepare for system engineering interviews on this topic. It's vital to grasp why adding servers often fails to provide linear gains. So we'll discuss how pinpointing the slowest stage from CPU limits to network latency allows you to confidently justify architectural trade-offs during an interview. We begin with the scaling paradox, where throwing more hardware at a problem fails to deliver those expected linear gains. This lesson opens with the reality that every distributed system is only as fast as its slowest stage. So we'll look at how to find those bottlenecks hiding in CPU cycles, database indexing, or even backed up queues. Once the friction is identified, we'll dive into a toolbox of 6 key techniques, ranging from parallelism and batching to data strategies like caching and connection pooling. It is not only about the code though. You'll understand the high-level trade-offs between refactoring existing software and moving towards event-driven architectures when a monolith hits its limit. We'll also walk through a repeatable cycle of measuring and validating results using real-world tools like Redis, Kafka, and NGIX. By the end, you'll possess the reasoning needed to avoid the trap of blind optimization and understand exactly how to justify infrastructure decisions in a high-pressure engineering interview. Imagine you're managing the backend for a massive global event like the 2026 World Cup. You've got millions of fans trying to book tickets or check scores at the exact same moment. The mechanism here is a massive surge in concurrent connections hitting your load balancers. If your system is designed poorly, the consequence is a total lockout where the database cannot handle the right volume for seat reservations, causing every single request to time out. Even if you have the world's most powerful CPU, if your application is stuck waiting for a single-threaded lock on a database row, that extra power goes to waste. The failure behavior usually looks like a cascading collapse, where the front-end servers fill up their connection pools and then start rejecting everyone. This situation is exactly why we need to look past hardware. You can't just buy your way out of a synchronization bottleneck in the code. We have to understand how data moves through every pipe, from the user's browser down to the physical disk, to ensure the system stays upright when the world is watching. The scaling paradox is a frustrating reality where you double your hardware budget but only see a 10% increase in performance. The mechanism behind this is often contention or synchronization overhead. Think about a scenario where you have 100 workers trying to write to the same single file. Adding another 100 workers doesn't make the writing faster, it just increases the time everyone spends waiting in line. The consequence of this paradox is a massive waste of capital and engineering effort on vertical scaling that doesn't solve the core issue. When a system hits this wall, the failure behavior is often a plateau where throughput stops increasing regardless of how many cores you add. In an interview setting, you'll want to point out that linear scaling is the goal but rarely the default. You have to explain that as you add more nodes, the communication overhead between those nodes starts to consume the very resources you just added. If you don't design for horizontal growth from the start, you'll eventually hit a point where adding hardware actually makes the system slower because of the increased complexity of coordination. Every distributed system is fundamentally governed by its slowest stage, which we often call the weakest link. The mechanism here is simple. If your web server can process 10,000 requests per second, but your database can only handle 500, your total system throughput is 500. No amount of optimization on the web server will change that final number. The consequence of ignoring this reality is that you spend time fixing parts of the system that aren't actually the problem. Imagine a high-speed assembly line where one person is manually signing papers. That one person dictates the speed of the entire factory. The failure behavior when this happens is a massive buildup of requests in the buffers right before the slow stage. This leads to memory exhaustion and eventually causes the service to crash or drop connections. In an interview, being able to identify that slowest stage is a major green flag. It shows you understand that performance isn't about making everything fast, it's about making the right thing fast. If you optimize a stage that is in the bottleneck, you haven't actually improved the system's capacity at all. You've just made a fast part faster. Before you can fix anything, you have to find where the friction is hiding. Friction typically lives in one of three places: the hardware resources, the data layer, or the communication path. The mechanism for finding it involves deep monitoring and profiling under load. For example, if you see high disk wait times but low CPU usage, you know your bottleneck is the storage I/O, not the computation. The consequence of a misdiagnosis is that you might spend weeks refactoring code for speed when the real issue was just a slow network switch or a misconfigured database pool. The failure behavior of a system with hidden friction is often jitter, where performance is fine for a while and then suddenly tanks for no obvious reason. In an interview, you should talk about using tools like distributed tracing to follow a request and see exactly where it spends its time. Is it waiting for a lock? Is it waiting for a packet? By visualizing the request lifecycle, you can pinpoint the friction and apply the specific fix needed for that subsystem. This targeted approach is much more effective than just guessing and checking different configurations. When we look at resource bottlenecks, we're usually dealing with 5 specific components: CPU cycles, memory limits, storage I/O, database locking, and indexing issues. Let's say you're running a high-frequency trading platform or a social media feed. If your CPU is pinned at 90% because of heavy serialization, adding more RAM won't solve the latency issue. Similarly, if your database doesn't have the right indexes, a single search query might force a full table scan on millions of rows. This causes the database to lock up, meaning every other incoming request starts queuing up. This is a classic failure mode, where the system feels slow, but the actual work being done is just the disk head spinning or the CPU waiting for data. In an interview, you should be able to explain how these hardware constraints interact. For instance, high memory usage might trigger constant garbage collection, which then spikes the CPU and kills your throughput. Identifying which of these 5 resource points is the true constraint is the first step towards a fix that actually moves the needle and prevents the system from stalling under heavy traffic. Transmission bottlenecks focus on how data moves between services, and there are 3 main culprits: backed up queues, network latency, and slow external dependencies. The mechanism here is a chain reaction. If an external payment API starts taking 2 seconds instead of 200 milliseconds, every request in your system starts taking longer. The consequence is that your internal threads stay occupied for longer, which eventually exhausts your thread pool and prevents new users from even connecting. Think of a highway where one lane is closed. The traffic doesn't just slow down at the closure, it backs up for miles. The failure behavior is often a death spiral, where the increased latency causes more retries, which adds even more load to the already struggling network, eventually crashing the whole stack. In an interview, you should discuss how to mitigate this using patterns like circuit breakers. If a dependency is slow, you stop calling it temporarily to save your own system. By managing these 3 transmission factors, you ensure that a single slow component doesn't take down the entire distributed architecture through a ripple effect of delays and resource exhaustion. Now that we know where the problems hide, we need an optimization toolbox to solve them. This isn't about buying more gear. It's about mastering techniques to squeeze every bit of efficiency out of what you already have. The mechanism involves looking at how tasks are executed and how data is managed. For instance, instead of making 100 separate database calls, you might use batching to send them all at once. The consequence of using these tools correctly is a massive jump in throughput with 0 additional hardware costs. However, the failure behavior of an incorrectly applied optimization can be subtle. If you implement aggressive caching without a good invalidation strategy, users might see stale, incorrect data, which is often worse than a slow system. In a system design interview, your goal is to show that you have a library of these strategies ready to go. You don't just suggest caching because it sounds good. You suggest it because you've identified that the database read volume is the primary bottleneck. This slide sets the stage for the specific execution and data efficiency techniques we are about to dive into. To master execution efficiency, we focus on 3 main approaches: parallelism, asynchronous processing, and batching. Parallelism is about doing multiple things at once using multiple cores, like processing 10 separate images simultaneously. Asynchronous processing is different. It's about not waiting around. When a request hits a database, the thread shouldn't sit idle. It should go handle another user while the database does its work. Then we have batching, which reduces the overhead of constant communication. Imagine you're a waiter. Instead of taking one drink to a table and coming back, you take a whole tray. The consequence of ignoring these patterns is a system that spends most of its time context switching or waiting on I/O, which kills throughput. If you overdo parallelism, the failure behavior is resource contention, where threads fight for the same CPU cache, actually slowing things down. In an interview, explain that you choose async for I/O-bound tasks and parallelism for CPU-bound tasks. This shows a deep understanding of how to manage execution flow to keep the system moving as fast as possible, without hitting a bottleneck of its own making. Data efficiency is another massive lever, and it relies on three key strategies: caching, connection pooling, and efficient algorithms. Caching allows you to serve frequent requests from memory rather than hitting the slower disk or database. For example, if millions of people are checking the same World Cup score, you cache that result for 30 seconds. Connection pooling is the mechanism of keeping a set of database links open, so you don't waste time creating a new one for every single query. If you don't use pooling, the consequence is a massive spike in latency, as the database spends more time handshaking than actually returning data. Finally, using efficient algorithms ensures the raw computational cost of every request is as low as possible. The failure behavior for poor data efficiency is often a cache stampede, where the cache expires and thousands of requests hit the database at once, knocking it offline. In an interview, highlight how you'd manage these tiers. Reusing connections and serving from memory are the low-hanging fruit that can provide a tenfold increase in throughput before you even consider changing a single line of business logic. When you hit a scaling wall, you're faced with four high-level quadrants of decisions: fixing the code, changing the structure, expanding the foundation, or rethinking the product. The mechanism here is a trade-off analysis. Fixing code is often the cheapest, but has limits. Changing the structure, like moving to a distributed architecture, is high impact, but also high risk and expensive. The consequence of making the wrong choice is engineering debt, where you spend months on a rewrite that doesn't actually solve the scalability issue. Imagine a scenario where the product requires real-time updates for every user. Maybe the best scaling decision is to change that requirement to every 5 seconds. The failure behavior of a poor decision here is often a product that never launches because it became too complex. In an interview, you want to show that you're a coder, and more specifically a decision maker. You evaluate the cost of engineering time versus the cost of cloud infrastructure. Sometimes buying a bigger server is the right short-term move to save developer hours for a more meaningful architectural shift later. Being able to explain this logic is what separates senior engineers from juniors. The choice between software optimization and infrastructure expansion is a classic debate. Optimizing software involves refactoring code to be more efficient, which saves money in the long run but takes significant time. Adding infrastructure, like scaling vertically with a bigger instance or horizontally with more nodes, is faster to implement but increases your monthly cloud bill forever. The mechanism for deciding between them is usually a cost-benefit analysis. If a developer costs $15,000 a month and can save you $10,000 a month in server cost, the math is clear. The consequence of always choosing hardware is that you eventually hit a hard ceiling where no larger server exists. On the other hand, the failure behavior of over-optimizing code too early is premature optimization, where you waste weeks making a function faster that only runs once a day. In an interview, emphasize that you start with measurement. If the code is genuinely inefficient, refactor it. If the code is fine but the volume is just too high, scale the infrastructure. This balanced view shows you understand both the technical and business side of the scaling equation. Sometimes small tweaks aren't enough, and you have to redesign the entire architecture. This usually means moving from a monolith to microservices or an event-driven pattern. The mechanism here is decoupling. By breaking a big system into smaller pieces, you can scale the parts that are actually busy. For instance, in an e-commerce app, the search service might need 50 nodes, while the checkout service only needs 2. The consequence of staying in a monolith too long is that the entire app becomes slow because one small feature is hogging all the resources. However, the failure behavior of microservices is distributed system complexity, where you now have to deal with network failures between services that didn't exist before. In an interview, you'd explain that you don't just jump to microservices for fun. You do it when the team size or the scaling requirements of specific components make the monolith unmanageable. You have to be ready to discuss the trade-offs, like the added latency of network calls versus the benefit of independent scaling. It's a high-level architectural move that requires a very clear justification based on the bottlenecks you've observed. To stay ahead of scaling issues, you need a performance mindset built on a repeatable 4-step cycle. Measure the current state, identify the bottleneck, optimize that specific part, and then validate the results. The mechanism of this cycle ensures you aren't just guessing at what's slow. For example, you might use a tool like Prometheus to see that your request queue length is growing. The consequence of skipping the validate step is that you might think you fixed a problem but actually just moved the bottleneck somewhere else. One simple way to picture this is fixing a leak in a pipe. If you plug one hole, the pressure might just burst the pipe further down the line. The failure behavior of a team without this mindset is chaos engineering in the bad sense, where they keep changing things without knowing what works. In an interview, describe this as an iterative process. You optimize, then you remeasure immediately. If the throughput didn't go up, you revert and try again. This disciplined approach prevents you from bloating the code base with optimizations that don't actually provide any measurable benefit to the end user. In the real world, we don't build everything from scratch. We use industry-standard tools to implement these strategies. The mechanism of these tools is to handle the heavy lifting of concurrency, caching, and distribution so you can focus on business logic. The consequence of choosing the right stack is a system that can handle millions of requests with relatively simple code. For example, using a proven load balancer like NGINX is much more efficient than trying to write your own traffic distributor. However, the failure behavior of a poorly chosen toolset is vendor lock-in or operational complexity that your team can't handle. If you pick a complex tool like Kafka for a simple task, you might spend more time managing the tool than the actual application. In an interview, you should mention specific tools and why they fit the problem. Don't just list names, explain that you'd use Redis for low latency caching because of its in-memory data structures, or Kubernetes for orchestration because of its auto-scaling capabilities. This shows that you understand the practical application of the concepts we've been discussing throughout this series. When it comes to messaging and memory, there are 3 heavy hitters you'll see in almost every high-scale system: Redis, Kafka, and RabbitMQ. Redis is the mechanism for high-speed caching. It lives in RAM, so it's incredibly fast for things like user sessions or leaderboard data. Kafka and RabbitMQ are used for decoupling and handling asynchronous message throughput. The consequence of using these is that your frontend doesn't have to wait for slow backend processes to finish. Imagine a user uploading a video. You give them an immediate success message and then use Kafka to process the video in the background. The failure behavior if these tools go down is often a total system stall, as they are central to the data flow. If Redis is your only source of truth for sessions and it crashes, everyone gets logged out. In an interview, be sure to distinguish between them. Redis is for state and speed, while Kafka is for high-volume data streams and persistence. Knowing which one to pick for a specific bottleneck, like moving slow writes out of the main request path, is a key architectural skill. For control and operations, we rely on 3 essential components: Kubernetes, NGIX, and thread pools. Kubernetes acts as the mechanism for orchestrating your instances, automatically spinning up new containers when traffic spikes so you don't have to do it manually. NGIX serves as a high-performance load balancer and reverse proxy, sitting at the edge to handle thousands of SSL handshakes efficiently. Then, inside your application, you have thread pools, like those in Java or Go, which manage local concurrency. The consequence of well-tuned thread pools is that your server doesn't crash when it gets a sudden burst of requests. It just queues them up. The failure behavior for misconfigured operations is often resource starvation. If NGIX isn't tuned to handle enough open files, or if your thread pool is too small, your high-end servers will start rejecting traffic even if they have plenty of CPU left. In an interview, explain how these 3 layers work together. Kubernetes scales the nodes, NGIX distributes the load, and thread pools manage the execution. Getting all 3 right is how you achieve true system-wide throughput without the system falling apart under its own weight. Even the best engineers can fall into traps where systems break in unexpected ways. The mechanism of failure is often a lack of visibility or a misunderstanding of how components interact at scale. For example, you might optimize a service to be lightning fast, but that speed just overwhelms a downstream database that wasn't ready for the increased load. The consequence is a self-inflicted denial of service attack. Another common trap is ignoring tail latency. If 99% of your requests are fast, but 1% take 10 seconds, those slow requests can eventually clog up your entire system by holding onto resources. The failure behavior here is a slow hang, where the system appears to be working, but users are experiencing massive delays. In an interview, it's vital to talk about these edge cases, mentioning how you'd use timeouts and retries to prevent a single failing component from dragging down the rest of the stack shows you've thought about graceful degradation. You want to show the interviewer that you aren't just designing for the happy path, but for the messy reality of production environments. Two of the biggest traps in engineering are premature scaling and blind optimization. Premature scaling is the mechanism of building for 1 billion users when you only have 1,000. The consequence is a massively complex system that is impossible to maintain and expensive to run, all for no actual benefit. Blind optimization is even more common. It's the act of making code faster without measuring first to see if that code was actually the bottleneck. Imagine spending 2 weeks optimizing a sorting algorithm that only accounts for 0.1% of the total request time. The failure behavior is wasted engineering cycles and a system that is faster on paper but exactly the same speed in reality. In an interview, the strongest signal you can give is to say, "I would measure first." Explain that you'd use a profiler to identify the hot path before changing a single line of code. This measurement-first approach is the mark of a truly experienced engineer who values their time and the company's resources. It's about being surgical with your fixes rather than just guessing where the friction lies. As we wrap up, let's look at 5 key questions that often come up in senior-level interviews. First, why didn't doubling the servers double the throughput? This tests your knowledge of Amdahl's law and synchronization overhead. Second, which bottleneck should you optimize first? The answer is always the one currently limiting the system's total capacity. Third, when does batching hurt performance? This happens when the batch size is too large, causing high latency for the very first item in the batch. Fourth, how do queues improve throughput? They act as a buffer to smooth out traffic spikes, allowing the system to process work at a steady, sustainable rate. Finally, would you optimize software before buying more hardware? This is a trade-off question about engineering cost versus infrastructure cost. Being able to talk through these scenarios shows you have a holistic view of system design. You're not just looking at the code, you're looking at the flow of data, the cost of resources, and the reality of how distributed systems fail when pushed to their limits. These questions cover the mechanism, consequence, and failure modes we've discussed throughout the module. So, we've broken down why simply throwing more hardware at a scaling problem often fails. It's because your system's throughput is only as fast as its slowest component, regardless of how much RAM you add. To fix this, we identified 3 main categories of bottlenecks: hardware limits like CPU and RAM, data layer issues like database locking, and transmission hurdles like network latency or backed up queues. You've got a toolbox now, including parallelism, batching, and async processing to clear those hurdles. For example, if your database is choking on thousands of small writes, batching those updates into one larger operation can drastically reduce the I/O overhead. In an interview, you've got to show you can identify the root cause before requesting more servers. The smartest engineers don't just scale out, they eliminate unnecessary work first. That wraps up our look at throughput. In a system design interview, don't just suggest adding servers. You've got to show you can pinpoint which of the 7 key bottlenecks, CPU, memory, storage, databases, queues, network, or external APIs, is the real culprit. Interviewers want to see you justify choices like using Kafka for detuppling or NJINX for load balancing based on where the system actually breaks. Well, if you optimize a stage that isn't the bottleneck, you won't see any gain. Now, here's a challenge for the comments. When you push throughput to the limit using aggressive batching, what's the trade-off for individual request latency? Looking forward to your thoughts. Keep building. What happens when your servers are perfectly healthy but they've stopped talking to each other? This silent failure is often the toughest part of distributed design. Welcome to Systemic Stack. My name is Kabir Anand. This is episode 38 of System Engineering series, and today we will explore network partitions in a way that helps you prepare for system engineering interviews on this topic. Mastering these invisible breaks across switches or cloud regions proves to an interviewer that you understand the high-stakes trade-offs between consistency and availability. This lesson opens with an analysis of the split brain crisis, exploring what happens when two healthy data centers lose their fiber link and must function in total silence. We look at why this is such a dangerous, invisible failure compared to a simple server crash. So we'll begin by examining two primary categories of partition scenarios, ranging from environmental isolation in cloud regions to physical hardware failures like severed submarine cables. The core of our discussion then focuses on the three strategic choices engineers face: whether to pause and wait, continue independently, or halt operations to protect data. This part's vital for your interview reasoning because it forces you to weigh availability against consistency under pressure. We'll see how these strategies play out across four major technologies, including infrastructure layers like AWS and Kubernetes, and data-heavy systems like Cassandra and Zookeeper. Finally, we'll cover two main failure modes, split brain and stale data, so you can recognize where systems actually break. By the end, you'll understand how to justify specific architectural decisions when a network link inevitably fails. Let's set the scene with a real engineering situation you might find yourself in. Imagine you're managing a global payment processor that operates across two massive data centers for redundancy. Everything is running smoothly until a construction crew accidentally digs up a primary fiber line. Suddenly, the two sides are alive and healthy, but they can't see each other. This isn't just a hypothetical, it's a high-stakes constraint that forces a system to decide who's in charge. If both sides keep accepting payments, you risk double spending or corrupted account balances. If they both stop, you lose millions in revenue every minute. In an interview, you'll often be asked how to handle this exact scale. The mechanism of the failure is a network break, but the consequence is a fundamental loss of coordination. You're operating in a state of high uncertainty where your system must rely on its pre-configured partition logic rather than real-time consensus. Understanding how to navigate this tension is what separates a senior engineer from a mid-level developer. The split brain business crisis occurs when the network link between two data centers fails, but the servers on both sides remain fully operational. This is a nightmare scenario because each side might assume the other side has died and try to take over as the master. For instance, in a primary replica database setup, if the replica loses its connection to the primary, it might promote itself to primary. If the original primary is still up and accepting writes, you now have two sources of truth writing different data to their local disks. The consequence of this behavior is a diverged state that is incredibly difficult to reconcile later. In an interview, you should highlight that this isn't just a technical glitch, it's a business risk where customers might see inconsistent account balances or lose their data entirely. The failure behavior here is a lack of global agreement, leading to a fragmented system where the right hand doesn't know what the left hand is doing, creating a split in the system's consciousness. One of the most dangerous things about a partition is its invisible nature. When a server crashes, it's loud and final. The connection drops and the system knows it's gone. But a partition is a silent failure. From the perspective of a single node, it just looks like the other side is being slow or unresponsive. You can't tell if the remote server is down, if the network is congested, or if there's a hard break in the cable. This ambiguity makes detection significantly harder than a standard hardware failure. If you assume the other side is dead and start reallocating resources, you might cause a massive conflict if they're actually still running. Well, this uncertainty is why we use heartbeats and timeouts, but even those can be fooled by a flaky network. In a system design interview, explaining this distinction shows you understand that up and down are not the only two states a system can be in, and that the unknown state is actually the most dangerous one to manage. In a distributed system, silence is definitely not golden. Why partitions change everything is because they force every node to make a choice without having all the facts. In a healthy state, nodes use consensus protocols to stay in sync. But when that network link snaps, the source of truth on the other side becomes unreachable. Now, the system is forced into a corner. Does it continue to process requests, potentially serving old or wrong data, or does it stop entirely and wait? This is where the CAP theorem comes into play, which you'll definitely want to reference. The trade-off is between being available for your users or being consistent with your data. For example, a social media site might allow you to keep posting even if the global timeline is out of sync, preferring availability. However, a stock trading platform might freeze all trades to prevent illegal moves, prioritizing consistency. The local node has to become autonomous, and how you program that autonomy determines the system's overall reliability during a crisis. Network partitions aren't just theoretical puzzles, they are triggered by real-world events across the stack. There are two main ways these occur, through logical isolation or physical destruction. Logical isolation happens when software-defined networking rules, like a misconfigured firewall or a buggy routing table update, block traffic between specific segments of your network. On the other hand, physical destruction involves the actual hardware failing. Think about a backhoe cutting through a fiber optic cable buried in the ground, or a power surge frying a core router in a data center. Both scenarios lead to the same result, a system that is split into isolated islands. You'll want to explain to an interviewer that while we try to build redundant paths, there are always single points of failure, like a shared cable duct or a top-of-rack switch. The consequence is always a loss of communication, but the recovery steps might differ depending on whether the issue is a software configuration that can be rolled back or a physical cable that needs a repair crew. Environmental isolation typically happens at two levels, data centers and cloud regions. When a whole facility loses external connectivity, we call it data center isolation. This might happen due to a massive utility failure or a localized natural disaster. On the cloud side, region failures are rarer but more complex. They occur when regional APIs or the internal backplanes that connect different availability zones fail, leaving your local instances stranded even if they're technically running. For example, if you have an application in AWS US East 1 trying to talk to a database in US West 2, a failure in the cross-region network will cause a partition. The instances in the East will keep running, but they can't reach the source of truth in the West. This forces your architecture to have local failover logic or a way to gracefully degrade. If you haven't designed for this, your application might just hang indefinitely, waiting for a response that will never come, which is a classic failure mode to avoid in global system designs. Hardware failures, like switches and cables, are the physical root causes of partitions. There are two scales to consider here. First, localized switch failures can isolate a single rack. If the top-of-rack switch dies, every server in that rack can talk to each other, but they're cut off from the rest of the data center. Second, we have macro failures like submarine cable outages. These are the massive undersea lines that connect continents. If one of these is severed by a ship's anchor, entire countries can experience massive latency or complete disconnection from global services. This proves that physics still dictates system availability. Even the most sophisticated software can't bypass a physical break in the medium. In an interview, you should mention that we mitigate this by using multiple network providers and physically diverse routing paths. If you rely on two cables that happen to run through the same tunnel, a single accident can still take down both, leading to a total partition. This level of physical awareness shows a deep understanding of infrastructure reliability. When a partition is detected, engineers face what we call a trilemma. You have to choose between three specific paths. You can wait for the network to come back, you can keep working alone, or you can stop everything to protect your data. This is a critical decision point in any system design. If you choose to wait, your system becomes unresponsive, which might be okay for a background batch job, but terrible for a customer-facing website. If you keep working alone, you're prioritizing availability, which is great for user experience, but risks creating conflicting data. Finally, stopping everything is the safest way to ensure data integrity, but it results in a total service outage. In an interview, you should justify your choice based on the business use case. There is no correct answer, only trade-offs. A banking app will almost always choose to stop or wait to prevent errors, while a streaming service will keep working to ensure the video doesn't stop playing, even if the likes count is slightly out of sync. Some systems are designed to just pause and wait for the network link to return. This strategy is all about preserving consistency at the expense of availability. When a node detects it can't reach the rest of the cluster, it simply stops processing new requests and enters a waiting state. The mechanism here is a complete halt of the application logic. The consequence is that your system effectively goes offline during the partition, which looks like a total failure to the end user. However, the benefit is that once the network is restored, there are no data conflicts to resolve because nothing changed while the link was down. A classic example would be a distributed lock manager. If it loses the network, it can't grant new locks because it doesn't know if another node has already granted them. If it kept working, you'd end up with two different processes thinking they have the same exclusive lock. So the system fails safe by doing nothing, which is a vital pattern for high-integrity financial or coordination systems. When deciding whether to continue or halt during a partition, you're essentially choosing between two different philosophies of failure. There are two main approaches: prioritizing availability or prioritizing consistency. If you continue independently, you're building an AP system under the CAP theorem. This is common in shopping carts. If the network breaks, we'd rather let you add items to your cart locally and sync later than prevent you from shopping. The risk, of course, is a data conflict when the network heals. On the other side, halting means building a CP system. This is used in systems like distributed databases where every write must be verified by a majority. If the partition makes a majority impossible, the system stops accepting writes entirely. This prevents stale or dirty data from being recorded. In an interview, explain that the continue approach requires a robust conflict resolution strategy like CRDTs, while the halt approach requires high availability in your networking layer to minimize the impact of these intentional shutdowns. Modern technology stacks don't just leave partition handling to chance. They have built-in mechanisms to detect and survive these events. These tools range from global cloud infrastructure to specialized distributed databases. When you're discussing this in an interview, it's helpful to categorize them into infrastructure and data layers. The infra layer, like your load balancers and orchestrators, handles how traffic is routed around the break. The data layer, like your databases and caches, handles how the actual information is stored and protected. For instance, global load balancers can detect when a whole region is unreachable and shift traffic to a healthy one. Meanwhile, databases use quorum logic to decide if they have enough nodes to safely continue. By using these established patterns, you're not reinventing the wheel. You're leveraging proven strategies to keep the system as stable as possible. We are going to look at specific examples like AWS, Kubernetes, and Cassandra to see how these theories are applied in real-world production environments. Looking at the infrastructure layer, let's look at how AWS and Kubernetes handle these breaks. AWS multi-region architectures often use Route 53 health checks to manage partitions. If a region becomes isolated, Route 53 detects the failure to respond and automatically shifts DNS traffic to a different healthy region. This is a high-level way to maintain availability by routing around the partition. In the world of container orchestration, Kubernetes uses a system of taints and tolerations. When a node loses its network connection, Kubernetes marks it as unknown. If the node stays in that state for too long, the controller will evict the pods from that node and restart them elsewhere in the cluster where the network is working. This failure behavior ensures that your application doesn't stay stuck on a standard island. However, the trade-off is that if the partition is brief, you might have moved your pods unnecessarily, which causes its own kind of churn. It's a balance between reacting quickly and avoiding flapping or unstable system behavior. In the data layer, we see the CAP theorem in action with technologies like Apache Cassandra and Zookeeper. Cassandra is designed for high availability, so it allows for something called local quorum writes. During a partition, a node can accept a write if it can reach enough other nodes in its local data center, even if it can't see the rest of the global cluster. This keeps the app running, though data might be slightly inconsistent across regions for a while. Zookeeper takes the opposite approach. It's built for strict consistency and uses a leader-based system. If a partition occurs and the current leader is on the minority side of the split, Zookeeper will immediately stop serving rights and force a new leader election on the majority side. If no majority can be formed, the whole service stops. This mechanism ensures that you never have two leaders giving out different instructions. In an interview, this is a perfect way to show you understand that different tools are chosen for their specific partition handling behaviors. If partitions are handled poorly, the resulting failures can be catastrophic. When a system isn't designed to expect a network break, it often fails in unpredictable ways. One major area where systems break is in resource management. For example, if a node is waiting for a response from a partition peer, it might keep its connection threads open indefinitely. Eventually, it runs out of threads and crashes, causing a cascading failure that takes down even the healthy parts of the system. Another risk is the storm effect, where nodes constantly try to reconnect and overwhelm the network once the link is restored. This is why we use circuit breakers and exponential backoff. Without these, a temporary partition can turn into a permanent outage. In an interview, emphasize that a well-designed system doesn't just survive a partition. It manages its own resources so it can recover cleanly. You need to consider how the state of the system radiates outward and impacts everything from your database logs to your end-user latency. State errors during a partition usually fall into two main categories: split brain and stale data. Split brain is the most dangerous, occurring when two different nodes both think they are the leader because they can't see each other. Imagine two different servers both thinking they have the exclusive right to update a user's bank balance. They'll both accept changes, and you'll end up with two conflicting versions of history. Stale data happens on the read side. A client might connect to a partition node that is still up but hasn't received the last 10 updates from the rest of the cluster. The user sees an old version of their profile or an incorrect stock price. Both of these are consequences of prioritizing availability over consistency. To fix this, there are two common techniques: version vectors to detect conflicts and quorum reads to ensure we are seeing the latest data. Explaining these two specific failure modes shows an interviewer that you can visualize exactly how data becomes corrupted when the network fails. To wrap up, let's look at 5 key questions that often come up in interviews. First, what exactly is a network partition? It's a communication break between nodes that are otherwise healthy. Second, how is it different from a server failure? A server failure is binary, while a partition creates islands of operational but isolated nodes. Third, should both sides continue processing requests? That depends on your consistency requirements. There's no one-size-fits-all answer. Fourth, can partitions be completely avoided? In a distributed system, the answer is no. Physics and hardware will eventually fail. This leads to our fifth point. Why is partition tolerance considered unavoidable? Because if you can't handle a network break, you don't have a distributed system. You have a giant single point of failure. In an interview, being able to walk through these 5 points clearly shows you've moved beyond just knowing the definitions and actually understand the design pressures that force us to build systems that can withstand the network literally disappearing under our feet. So, we just broken down one of the most dangerous failures in any distributed environment, the network partition. Unlike a loud server crash, these are silent because both sides of your architecture stay alive. We looked at 4 primary ways this happens, from localized rack switch failures to literal submarine cable outages. In a high-level design interview, you'll need to justify how your system reacts when the link drops. You essentially have 3 strategic paths: pause everything to keep data consistent, continue independently and face a potential split brain, or just stop entirely. Whether you're configuring Kubernetes or choosing between Cassandra and Zookeeper, you're always weighing availability against data integrity. The big takeaway here? Well, systems don't just fail when hardware dies. They fail when perfectly healthy servers can't talk to each other anymore. That wraps up our look at network partitions. In a high-stakes interview, you'll need to explain how to navigate the three main strategies: stopping requests, waiting, or continuing independently. It's not enough to say you'll use Zookeeper or Cassandra. You've got to justify why you trade availability for data safety in a split-brain scenario. Interviewers want to see that you can predict those invisible failure modes where healthy servers simply stop talking. In the next episode, we'll explore the split brain problem and work through how to keep your cluster synchronized. Quick question for the comments. If a partition creates two isolated groups of equal size, which side should win? Stay sharp and happy building. Imagine two healthy servers making conflicting decisions at the same time. It's the fastest way to corrupt a database. Welcome to System Stack. My name is Kabir Anand. This is episode 39 of System Engineering series, and today we will explore split brain problem in a way that helps you prepare for system engineering interviews on this topic. Understanding how network partitions trigger these independent promotions is vital. We'll see how to use mechanisms like quorum and fencing tokens so you can confidently explain how to maintain a single source of truth during a crisis. It starts by breaking down a classic distributed systems nightmare, the split brain problem. We'll walk through a scenario where a network partition makes two healthy servers believe they're both the primary boss. You'll see how lost heartbeat signals and independent promotion logic trigger this mess, proving that perfectly healthy nodes can actually be more dangerous than a crashed one. We then look at the fallout, specifically how duplicate writes, like two clients writing to two different nodes simultaneously, create divergent timelines of reality that lead to irreversible data corruption. Well, this is a critical failure mode to understand because it tests your ability to reason about consistency versus availability during a partition. To prevent this disaster, we'll explore three specific engineering safeguards: quorum and consensus logic, fencing tokens, and the use of witness nodes as neutral tiebreakers. Finally, we'll look at the coordination stack, covering how industry tools like Zookeeper, HCD, Console, and Pacemaker manage state when things go sideways. By the end, you'll understand how to implement the guardrails necessary to keep a distributed system from tearing its own data apart. To really grasp the stakes here, let's look at a massive real-world scenario like the infrastructure surrounding the FIFA World Cup 2026. Imagine you're managing a global ticketing system across multiple data centers. You have a primary database in North America and a standby node in Europe. Now suppose a transatlantic fiber optic cable gets cut, or a major router misconfiguration creates a total network partition. The North American server can't see the European one, and vice versa. If your system isn't designed correctly, both sides might assume the other has crashed. The North American node continues processing ticket sales, while the European node promotes itself to primary and starts accepting new requests for the same seats. You now have two bosses selling the same seat to two different fans simultaneously. This operating context makes the cost of a split brain event absolutely massive, leading to overbooked stadiums and a logistical nightmare that's incredibly difficult to untangle after the network heals. Managing distributed conflict is really the heart of modern high-availability architecture. In this lesson, we're looking at how to maintain a single source of truth when the underlying hardware starts to fail. Interviewers love this topic because it reveals whether you understand that distributed systems are inherently unreliable. When you have multiple nodes, you're constantly fighting the possibility that they lose touch with each other. If that happens, the system faces a choice. Should it stay available and risk conflict, or should it shut down and maintain consistency? This isn't just a theoretical debate. It's a design pressure that dictates how every database and orchestration tool you use actually behaves in the wild. We're going to break down why the simple "if I can't see him, he's dead" logic is the most dangerous assumption you can make in a distributed environment, and how that assumption leads to the dual primary conflict we're discussing today. Let's look at the business story of how we end up with two primaries. In a healthy state, you have a clear hierarchy where node A is the boss and node B is the backup. They are constantly talking over a network heartbeat. But then a partition occurs. This could be a top-of-rack switch failing, or even just a heavy spike in network congestion that drops the heartbeat packets. Suddenly, the link is severed. From node A's perspective, everything seems fine locally, but it can't see node B. More importantly, from Node B's perspective, Node A has disappeared. Node B's monitoring logic says, the boss is gone, I must take over to keep the business running. So Node B promotes itself. Now you have two servers, both believing they are the primary. They are both ready to accept writes from users, but they have no way to sync those writes with each other. The system has effectively bifurcated into two independent conflicting realities. There's a strange paradox here that we call the hidden danger of health. Usually, as engineers, we are worried about servers crashing or hard drives failing. But in a split brain scenario, the crash isn't the problem. The health of the servers is the problem. Both servers are functioning perfectly. They are processing CPU cycles, they are writing to their local disks, and they are responding to local network requests. Because they are healthy, they are capable of making decisions. If Node B had actually crashed, there would be no problem. Node A would just keep working. But because Node B is healthy and just isolated, it starts making conflicting decisions. It's like having two pilots in a cockpit who can't see or hear each other, and both start cramping the controls to steer the plane in different directions. This duality is far more dangerous than a total system outage because it actively creates bad data while you think everything is fine. To understand the logic chain of how this happens, we have to look at three distinct mechanical failures. First, there's the lost communication, where the heartbeat signal between nodes is interrupted. Second, we have the failure of detection mechanisms. The system fails to realize that the other node is still alive but just unreachable. Third, we have the independent promotion trigger. This is the code that says if heartbeat is missing for 5 seconds, become primary. When these three things happen in sequence, you're in the split brain zone. Think about a load balancer that starts sending traffic to both nodes because it sees both as healthy from its own vantage point. The nodes don't know about each other's status, so they both proceed as if they have exclusive rights to the data. This sequence is exactly what you want to walk an interviewer through to show you understand the technical triggers of the conflict. The root cause is almost always lost communication, and it's often more subtle than a clean break. Sometimes we deal with a flapping network where the connection drops and reconnects every few milliseconds. This creates an isolation zone where heartbeat signals can't cross the wire reliably. Imagine a database cluster where the primary and secondary are in different racks. If the switch connecting those racks starts dropping packets, the secondary might miss enough heartbeats to trigger a failover. However, the clients on the primary side can still see the primary. You now have a situation where the network is split but not entirely down. This creates a ghost-like state where the nodes are essentially blind to each other's existence while remaining visible to different segments of the user base. This physical isolation is the catalyst for the entire logical failure that follows, and it's why network stability is so critical for cluster health. When a node stops hearing from its peer, it has a decision to make. In most basic configurations, silence is interpreted as death. This is the failure of detection. Without a global truth or a third party to verify the status, each node relies on its own local observation. So, node B assumes node A is dead. To ensure the system stays available for users, which is usually a key business requirement, node B promotes itself to primary status. This is the independent promotion phase. There's no coordination, no handshake, and no consensus. It's a unilateral move. Well, in a distributed system, unilateral moves are incredibly risky. If you're building a simple failover script that just checks a ping and then runs a promote command, you've just built a split brain generator. It's a common mistake in early stage architectures that don't account for the fact that I can't hear you is not the same as you are dead. Now, why is this duality so dangerous for the business? There are three main consequences you will see in a system-wide failure. First, you get duplicate writes to different disks. Since both nodes think they're the boss, they both accept new data. Second, this leads to conflicting data states. One node might update a user's balance to $50, while the other updates it to $70 based on a different transaction. Third, and most importantly, this results in irreversible data corruption. When the network eventually heals and the two nodes try to talk again, they realize they have divergent histories. There is no easy way to merge these timelines. If you're an engineer at a bank and this happens, you can't just pick one version of the truth without losing actual money or legal records. The system has branched, and the longer it stays in split brain, the more the data drifts apart. Let's look at a concrete example of duplicate writes and conflicting data. Suppose client A connects to node 1 and tries to buy the last remaining item in an inventory. At the same time, client B connects to node 2 and tries to buy that same last item. Because of the split brain, node 1 thinks it has the item and confirms the sale. Node 2 also thinks it has the item and confirms the sale to client B. Both nodes are acting as the source of truth, creating two divergent timelines of reality. Now you've sold one physical item to two different people. This isn't just a software bug, it's a violation of the fundamental rules of your business logic. When you are explaining this in an interview, emphasize that the bottleneck isn't the speed of the writes, but the lack of a shared state that should have prevented that second sale from ever being authorized. The most painful part of this whole ordeal happens when the network finally heals. That's when you face irreversible corruption. You now have two different database files that have been modified independently for minutes or even hours. Merging these two divergent histories is often impossible without manual intervention or significant data loss. There's no automatic way for the system to know which write should win if they happened at the same time on different nodes. You might have to resort to last write wins, but that ignores the business context of the operations. In many high-stakes environments, the only solution is to take the system offline and have DBAs manually reconstruct the timeline, which can take days. This is the ultimate failure point. It proves that a system being up and accepting writes isn't always a good thing if those writes are happening in a vacuum without consensus. To prevent this kind of disaster, we use three specific engineering safeguards. First, we implement quorum and consensus protocols which force nodes to get a majority vote before making any big moves. Second, we use fencing tokens to physically or logically block a stale leader from writing to storage. Third, we can introduce witness nodes, which act as neutral third parties to break ties. These safeguards change the system's behavior during a partition. Instead of both nodes becoming primary, these rules might force one node to shut itself down or stop accepting writes until it can prove it has the majority support. It's a trade-off. You're sacrificing a bit of availability in exchange for absolute data consistency. In an interview, being able to explain these three layers of defense shows that you prioritize the integrity of the data over the simple uptime of a single server. Quorum and consensus are the most robust ways to handle this. The rule is simple. You need a majority, or n divided by 2 plus 1, to make a decision. If you have a 3-node cluster and one node gets isolated, it can't reach a majority. It only sees itself, which is 1 out of 3. Because 1 is not a majority, it refuses to promote itself to primary. Meanwhile, the other two nodes can still see each other. 2 out of 3 is a majority, so they can safely elect a new leader. This ensures that only one side of a partition can ever claim leadership status. Well, this is why you'll almost always see clusters deployed with an odd number of nodes, like 3, 5, or 7. If you only have 2 nodes, you can't have a majority if they lose touch. Each one is only 50%. Quorum effectively kills the split brain before it can even start. Fencing and witness nodes provide two different styles of protection. Fencing is an active defense. If node A is the old leader and we want to promote node B, we use a fencing token to tell the storage layer, only listen to the node with the newest token. When node A tries to write with its old expired token, the storage rejects it. We sometimes call this STNite, or shoot the other node in the head, where the cluster actually cuts the power to the old node to make sure it's dead. On the other hand, a witness is an observational defense. It's a lightweight node that doesn't hold data but participates in voting. If two main nodes lose contact, they both turn to the witness. Whoever the witness can see gets to be the boss. This breaks the tie and prevents both nodes from independently assuming they're in charge, effectively acting as a neutral referee in a distributed dispute. In the real world, we use industry-standard technologies that are specifically designed to manage state and coordination. These tools have the consensus logic baked into them, so you don't have to write your own "is the other guy dead" scripts. They are built to handle network partitions, flapping connections, and slow nodes gracefully. When you're designing a system for the 2026 World Cup or any high-traffic event, you rely on these pieces of software to act as the single source of truth for the entire infrastructure. They ensure that even if the network is chaotic, the system's brain remains unified. Interviewers will expect you to know which tool fits which scenario, as each one has different trade-offs regarding performance and complexity. The core idea is that you're outsourcing the difficult problem of distributed consensus to a specialized coordination layer that is battle-tested and proven to prevent the split-brain scenarios we've been discussing. There are 4 key tools in the coordination stack you should be familiar with. First, Zookeeper is the veteran, used in Kafka and Hadoop for leader election and strong consistency. Second, etcd is the modern choice, serving as the distributed key value store for Kubernetes state. Third, Consul is great for service discovery and comes with built-in health checks that help manage cluster membership. Finally, Pacemaker is a resource manager, often used in Linux clusters to move IP addresses and storage mounts between nodes. If a network partition occurs, these tools use the consensus logic we've discussed to ensure only one node remains active. Using these specialized tools instead of building your own heartbeat logic is a best practice that prevents the fragile guesswork that leads to split brain. In an interview, mentioning these by name and explaining how they enforce a single leader demonstrates that you know how to apply these abstract concepts to actual production environments. As we wrap up, let's think about this from an interviewer's perspective. They might ask why split brain occurs, and you can now explain it as a breakdown in communication combined with a lack of global consensus. If they ask how quorum prevents it, you'll point to the majority rules logic that stops an isolated node from going rogue. We've talked about the witness node as a tiebreaker and whether active-active systems can suffer from this too. The answer is yes, if they don't have a way to reconcile conflicting updates. Finally, consider how fencing tokens solve the stale leadership problem by effectively locking out the old boss from the shared resources. Being able to answer these questions shows you don't just see a cluster as a group of servers, but as a coordinated system that must constantly fight against the chaos of a failing network to protect the data it holds. We've seen today how a simple network partition can turn a high availability setup into a data nightmare. Split brain occurs when lost heartbeats trigger independent promotions, leaving you with 2 healthy leaders acting as a source of truth simultaneously. In a design interview, you've got to be able to explain why this health is actually the danger. 2 nodes writing to different disks creates divergent timelines that are often impossible to merge. We covered 3 main ways to stay safe: using a witness node to break ties, implementing quorum-based consensus with tools like etcd or Zookeeper, and using fencing tokens to lock out stale leaders. It's a classic case where having no leader is actually safer than having 2. Articulating that trade-off between availability and consistency shows you truly understand the risks of distributed state. That wraps up our look at the split brain problem. In a design interview, you'll need to explain why 2 active leaders are often more dangerous than a total failure. It's all about that risk of irreversible data corruption. We explored 3 primary safeguards: quorum, fencing tokens, and witness nodes. Highlighting the trade-offs between these shows you're thinking about consistency over availability. In the next episode, we'll explore clock synchronization, specifically NTP and logical clocks, as we continue the system engineering series and dive into distributed timing. Now, if a network partition splits a 5-node cluster into groups of 2 and 3, which group remains functional in a quorum-based system? Drop your answer in the comments. Keep building. By the end of this combined journey, the important win is not that you have heard many buzzwords. The real win is that you can connect these topics into one mental model. You should be able to understand why certain systems prefer replication over coordination, why some architectures optimize for availability while others optimize for correctness, why traffic protection patterns matter under stress, and why time, partitions, and synchronization become unavoidable design constraints at scale. Use this masterclass as a reference path, a revision guide, and a framework for thinking through distributed architecture decisions with more precision and confidence.